Hello everyone. Welcome to the first lesson for computational methods for applied statistics. In this set of lessons, it's going to be a lot of slideshow before I jump into like coding and all the kind of stuff that this course is going to involve. But I really wanted to start by introducing the data landscape. So this is going to start with talking about data in general, different technologies and things like that, programming languages, then moving on to careers in that deal with data. So this course focuses on applications of computational methods in applied statistics using R and Python. I'm predominantly going to be focused on R, though I do plan on having some supplementary topics in Python and Julia, maybe some SAS, SQL, things like that. While historically this course used to be taught using SAS, modern statistical learning and industry standards tend to favor open source ecosystems. Now, there are exceptions to this in certain industries where they want to have closed systems where it's owned by a company. So therefore, if anything goes wrong, they have somebody that they can go to. Because right now, the problem with open source would be if you want something done in a system, either you have to change it, find someone who will, or wait for the community to make the change. But with systems like SAS, if you're a big enough company, you can basically put pressure on them and say, I want this implemented, and they can have their developers work on it. Or some industries will actually have requirements like pharmaceuticals, things like that, where they have to use certain systems because of the regulation around it. So note, I will discuss supplementary technologies about a wider context of technology and other tools such as Julia, SQL, and cloud technology. So let's first look at the course topics we're going to be looking at as I build out all these videos for these courses. So first, we're going to start with computational foundations. That's what we're looking at right now. We're going to look at the modern stack, which is an introduction to data technologies, things like Git, Markdown, things we'll be using in the course, and some things that'll be outside the course, but I wanted to kind of bring to your attention for things to dive into deeper or at a later date. Then we're going to be looking at programming logic. So this will be an introduction to R, data types, variable naming, things like that. Then we also look at control flow. These will be things like sequences, if-else logic, loops, things like for loops, while loops, and then of course vectorization. And then of course we'll look at functional programming, which will be writing and debugging custom functions. We're going to look at data engineering and visualization topics, for example, data structures. We're going to look at how to understand vectors, matrices, lists, and data frames. We will learn about tidyverse. So this will be things like on modern data wrangling, importing, and cleaning data. We're then going to also talk about the grammar of graphics. This will be looking at topics like exploratory data analysis, specifically using ggplot2 to do just that. We'll have topics, things like applied computational statistics. This could be things like stochastic simulation, which means generating data and simulating different distributions, like using the central limit theorem or binomial or Poisson, things like that. We'll learn about inference via code. So those will be computational approaches for things like confidence intervals and hypothesis testing. And then we'll also do linear modeling. We'll look at linear regression, so both simple linear regression, regular linear regression, and possibly multiple linear regression, and ANOVA in R. And then some advanced topics we may cover towards the end of the course or in the future will be statistical learning. This will be things like introducing model validation, overfitting, and learning principles. We can also finish off with some AI and optimization, which have things like dimensional reduction and LLMs in coding. So these are all topics that we either will cover or will cover in the future or touch on depending on how deep we want to go into them. For example, my background is in statistical and machine learning, so I could actually create an entire course devoted just to this. So while we may touch on it briefly here, we're likely not going to go as in depth as if I were having an entire course on this. So let's talk about data. Data is tremendously valuable, now more than ever. And it's not always going to be something that's straightforward. You may have a lot of data, but it might not be the right data, right? In statistical learning and machine learning, we always say garbage in, garbage out. Just because you have data doesn't mean that it's good data or it's useful data. So how do you gather that data to make sure that it's the data you want? How do you find the data that will actually answer the question you want to ask or can give you the insights that you're looking for? Once you have that data, where do you store it? And these are the kind of things you have to kind of think about when you're working in the data space, is not only how to get your data, but how to store it, How do you access it? How do you explore and analyze this data once you have it? What models should you use to do this analysis? And once you've done this analysis, how are you going to disseminate your findings, right? Are you a researcher and you're going to write a paper, go to do presentations at academic conferences? Are you in industry and you're creating some sort of slide deck that you're going to show to management or even possibly your boss? Are you working in the public sector? Maybe you want to get this out to regular people. These are all things that need to be considered whenever you're working on projects and data. So first, let's talk about our analytic methodology. So this methodology clarifies the purpose and implementation of analytics. So first, you want to start by defining or refining your business objective. So if you're starting out from the beginning, you want to define what the business objective is. Once you have that objective, that's where you need to figure out how to get your data. So you need to select the data that you're going to use. Is this a repository that already exists? Are you going to have to go out and gather data? And if you are doing that, think about to your statistics courses. How do you go out and sample that data based on how much bias you're willing to accept, but also balancing things like cost and manpower, right? So we talk about an introduction to stats, all these different statistical ways that you can properly sample data because you want a representative sample. But sometimes it's not just about getting the best sample. Sometimes it's about getting the best sample based on the means you have available. Once you've gathered that data or grabbed it online, if you're using, again, public repository, something like that, then you want to explore that input data. Now, you'll notice that there's arrows connecting each of these parts. So once you've selected data and you go to explore input data, you may have to, at this point, if you find out the data is not quite what you're looking for, you may have to go back to select new data or gather new data. Maybe it's not enough to get what you want. Maybe based on what you're interested in, you just didn't get what you were looking for. If you did, then you need to look at preparing and repairing your data. So this would be things like if you have missing values. Based on what kind of analysis you're doing, you might want to delete those, or you may want to use some sort of imputation method, something like EM algorithm or something like that, in order to kind of fill in the gaps. So what you're doing at this point is you're getting it sort of into the form that you can actually do some analysis on, right? You're looking for any issues you have, NAs, missing data, data that doesn't make any sense, like outliers, things like that. Once you've finished preparing the data, then you need to transform your input data. This is getting it into the form that you're actually going to be able to use and do analysis on. And I know these boxes make it seem like these are pretty, easy steps and things like that, but honestly, there are entire careers that are focused on the ETL pipeline, which is extract, transform, and load. This is all just getting data into the place and form that it is needed. So each of these steps can be a whole process that you're doing. In fact, I will tell you that whenever you're doing data projects, you are going to spend more time on the collecting, evaluating, fixing data, data wrangling really is what we call it. You're going to be doing all of that far more than you are the analysis. The analysis is actually the easy part, which actually leads us to our next part. Once you are in the transform input data part, this may be where while you're trying to transform your data, you're finding small things that need to be fixed. You could send this back into the prepare and repair data if you need to. Or once it's ready in the form that you can do your analysis, then it's time to apply your analysis. This is where you're doing the modeling. This is the part that everybody studies and spends a lot of time focusing on, but you'll notice how far down the chain it actually is. You have to get it to the form where you can actually do this analysis. So then you figure out what analysis you're doing, you deploy your models, and again, each of these steps you can always go back and apply new analysis depending on what your model's finding, things like that. And then once you've deployed your models, you want to assess the results. And based on those results, you can either start to implement them, whether it be disseminating the information, getting out anything you need to from that, using it in business or in practice, or possibly going back to the beginning and refining your objective based on those results you got. Now, this is sort of focused on a business analytics kind of point of view. So let's focus more on our reproducible method, research methodology. This is more how we're going to focus as people with a strong statistical background. So it's a structured workflow that ensures that our statistical analysis is consistent, verifiable, and scalable. So first thing we have is our data ingestion, followed by data wrangling, followed by exploratory data analysis, modeling and validation, and then reproducibility and communication. So data ingestion or extraction, this is the bridge where we programmatically are going to import data from either a SQL database, an API, or flat files into our environment that we're going to use. This would be things like R or Python. Once we have our data in the system, what we need to do is what's called data wrangling. So this is an iterative process where we're going to be tidying up the data, we're going to be repairing it, we're going to be transforming that raw input data into a structured format that's going to be suitable for what we're actually trying to do, our analysis. Once the data is in the form we can use, we're going to be doing exploratory data analysis, or EDA. And this will use things like visualization, making graphs, histograms, box plots, things like that, and descriptive statistics to explore patterns and refine our research objective before we actually do our formal modeling. In fact, a lot of times when I'm working in research with other teams, this is one of the first things that I do is when they give me some data, I look at it, for example, if I pull this up in Excel, I'm just going to see a bunch of numbers. It doesn't mean anything to me. No matter how many years you've done this, you don't see the math like they show in movies. All you see is a table full of numbers. This is the step where you start to get a feel for what the data actually looks like, right? Is it normally distributed? Is it skewed? Does it have kurtosis? Is it, does the mean and median diverge? There's all sorts of stuff you can find out about it. Is there a correlation between different variables? And these are all things that can actually affect the next step, which is when we get to modeling and validation. Going back to correlation. If I get a bunch of data and I find that there's multicollinearity, that'll cause a real problem when I'm doing modeling, because most models do not do well with multicollinearity. So this would be something I would look for in my data exploration phase. So model and validation, this is where we're implementing statistical theory via code and using simulation to assess model stability and check for things like overfitting. This is where we're trying to create our model and then double check whether it's working. So like, for example, if I'm doing classification algorithms, then I would use a confusion matrix, find things like precision, accuracy, F1 score, ROC curves, and these are all ways to evaluate how well did my classification algorithm do. And then once you've done this analysis, now it's time to actually do some form of communication. A lot of times I'm going to be focusing on reproducibility. So this would be like disseminating findings through automated reports, things like Quarto or Markdown. And we're going to be using Markdown in this whenever I'm giving out assignments to my students. In this class, I use Markdown so that not only can they put in their code, it will run the code, it will knit it all together in a document, and we can easily evaluate whether it's working or not. Because evaluating code can be a lot more difficult than evaluating a normal statistical assignment, because sometimes you might have different ways that work. Maybe somebody uses an if-else-then or if-then statement, somebody uses an if-else, or someone uses a where statement, and somehow they're all able to get the function to do the same thing in some roundabout way. So what we're looking for is it reproducible? So this will ensure that basically give us an audit trail that we can verify. And there are other steps to this. For example, for reproducibility, you oftentimes are going to want to have version control systems set in. For communication or sharing of these systems, you might want to use some sort of containerization so that when you share this, they have the exact same environment you do, things like that. So looking at this image down here that I created using R actually, this course is mostly going to be focusing on the data wrangling through validation steps. Now, there will be a little bit from each. Like, we'll be looking at data ingestion, how to bring in data, import it, things like that. There will be a little bit on reproducibility, using these systems, things like that. But really, it's mostly going to focus on the programming parts of this, of once you have this data, how do you, do the data wrangling, find out about it, transform it, visualize it, model it, and then validate that you have a good model. After you have your objective, now we need to focus on gathering our data, and this will be our first important step. So first we need to select our data based on our objective and our goals. We're not just grabbing data for the sake of grabbing it. So some common approaches are gathering all data possible, because you might find data that is possibly useful later. You might find unexpected insights from it, or some companies will do this using data as an asset. And this is where a lot of times data analysis in the business world versus from the academic side differ wildly. This is because when we're teaching statistics, for example, take hypothesis testing. We start with the fact that you have a hypothesis, you gather your data, you do your hypothesis test, and at that point, you test your hypothesis, whether it passes or fails at some level of significance. The thing is, if it does fail, let's say it's very close though, oftentimes we will say in statistics, well, you need to now get a new hypothesis, go gather new data, run a new hypothesis test, and test this hypothesis. But realistically, what most people will do in the business world is they're going to gather the data. They're then going to see what hypotheses would be true doing this. In fact, whenever we're doing stuff in R, you're going to see that whatever model we make, it's going to give us a p-value. It's going to automatically hypothesis test for us. So then most of the time, people are going to take more of the other side of things where they will just say, well, it has a p-value of 0.03, so therefore we know that we can reject the null hypothesis up to a level of 0.03. And this is where I was kind of talking about the fact that it is very different, because a lot of times in statistics, we're seeking out very specific data to answer our question. We're not just throwing things at the wall to see what sticks. But oftentimes, if you look at business practices, this is exactly what they're doing. They are pulling in every bit of information they can. Like if you're on a website, they're looking at what type of device are you on? Are you on a cell phone? Are you on a TV? Are you on a tablet? Are you on a computer? They're going to look at things like your geolocation. They're going to find your clicks per minute. They're going to look at your click-through rate. They're going to look at where your mouse is hovering, which is a measure of focus. They're gathering anything and everything they can, because those insights might give them some unexpected insights and possibly be useful later for something that they need to do. An example of this was, for a while I was working with this one company, and as we built in new products, I told them that I would like to get this kind of data so that we can do analysis on this. But the problem was anything that we had sold in the prior years, because we didn't have this being gathered by the system, we couldn't use that for our analysis. All the prior years of information for this sort of analysis weren't available to us because we didn't have the information that I needed based on the test I wanted to do. So some companies, what they'll do is, just to err on the side of caution, they'll grab anything and everything because it might be useful later. And then, of course, this leads us to our last part, the data as an asset. This is something that is very common nowadays. They always have a saying, if you don't know what the product is, it's you. There are many companies out there now that are gathering anything and everything they can, and they're selling it. In fact, especially now with large language models, these companies need massive amounts of data to build their models, meaning they're going to these data brokers, gathering anything and everything they can. And they're actually, a lot of times, able to get a lot of really good insights from this. An example of this is I was doing some consulting for a company a couple months ago, and we were creating a propensity scoring system in order to use people's information that we could get from these data brokers to help automotive sales places find customers that would be primed to be buying a car and things like that would be in the market, which would be likely to come in and make purchases based on advertising, things like that. And again, this data was all easily purchasable, right? Because these companies exist just by gathering as much data as they can, creating these huge databases, and then selling it to other companies. So we talked a little bit about gathering the data. Now let's talk some more about tools, right? Once you have this data, where should it be stored? How will the data be accessed? And what sort of things matter? Speed, cost, scale, things like that. And this is where it's immensely important. And a personal example I have of this is I had a friend, he used to work in data sales for, I think it was Dell EMC, back when they were just EMC. And his issue was a lot of times when they would be doing bidding contracts, a lot of times companies would ask for, we want to be able to store this amount of data. So you'd have these companies come in and they would give them an offer, like we could do it for this cheap, but the problem is they weren't asking the follow-up questions. Well, how fast do you need to access that data? Because think about when you have large amounts of data. Would you want to use a system like Google if it took 20 minutes for a search? No, because even though Google has vast amounts of data, speed is also a big factor. If I have to wait more than 3 seconds before I start getting my results, I'm already lost interest. This is the kind of stuff you have to think about. Not only what do you do with the data, you need to know how are you going to access it? How fast does it need to be? How much do you need to scale? These are all things that you need to be thinking about when you're working with data. After defining your research objective, sourcing the right data is going to be our first computational hurdle we need to look at. So, as I mentioned before, objective-driven selection, right? We don't just want to gather data, we want to select data that specifically satisfies our model's assumptions and our research goals. This is the statistician in me coming out, because this I always think should be key. You want a representative sample to what you're actually looking for. The data as a scalable asset. In modern statistics, data isn't just in a spreadsheet. A lot of times, this is going to be things that are beyond the tools that we use, especially, for example, in the education field. When we're teaching about this, we're going to be giving you small, what I call toy data sets, which are things you could pull up in Excel. But anything that goes beyond like 16,000 rows in Excel basically becomes unusable. So then you have to start looking at how can we scale as our data gets much bigger than this. And you'd be surprised when you start working in data how quickly that actually can happen. Right? When you're learning how to do all this stuff, we're giving you data sets with a couple hundred data points, and we're using it to train you on the specific methods. But as you scale it, a lot of these tools stop working. A lot of these methods stop being able to function because they're not built for that kind of scale. And you also have to look at modern access methods. So things like programmatic extraction. This will be moving on beyond manually grabbing things in R or Python for things like SQL queries. You might be using things like API calls or web scraping, right? So a lot of times nowadays, when you build a system, you don't want to have to go in every time, manually tell it to import this data. You want to have an API call where it goes out, gathers it automatically, or a lot of systems now will use web scraping, which is an gray area where there's a lot of back and forth about the legality of it, the ethics of it. But in the end, it is something that's done all the time, and people will go out and scrape the web. And this is a part of these systems you might have to consider. Now, one thing I actually want to talk about briefly about that before we move on is this is also a big issue for people who have systems online, because every time somebody visits, like let's say of a website, they have some minor charge based on that. So when it scales up, you expect to pay more. So major sites cost more money. Well, as web scraping has become more and more of a thing, especially with the advent of large language models and generative AI, this has actually been increasing costs to a lot of these small users or companies, and it's causing a lot of issues, which is why you'll find more and more companies and websites are adding do not crawl functionality into their sites, which of course then leads to issues with things like Google and stuff like that. And this is the reason why. This is, like I said, it's one of those ethical gray areas because, yeah, you want the data and you have access to it and it's technically not illegal, but you are putting a lot of the cost onto somebody else. And these are things you might have to consider. So next we have storage infrastructure. This would be deciding where the data lives. For example, we might want to have it locally at our university cluster, something here like we have Circ, or you may want to store it in the cloud. And this is a big thing you have to consider because this last year we've had a couple of cloud outages with things like CrowdStrike and things like that. So when you have your data on the cloud, you don't have control of that data. But it does offset a lot of the cost because you don't have to maintain a bunch of servers and data storage capability. On the flip side, when you have this online, it also allows you to have scalability. If I have a server that can hold a certain amount of data and I start to get to the edge of that, I would have to expand that server or build another one in parallel, something like that. Maybe I use cluster computing. But if I have cloud computing, I can always scale basically with almost no limit. So these are the kind of things that, again, when you're thinking about data, you have to think about and you have to kind of decide. Now, what your role is in the future, what you're doing with it, this may not be something you have to decide yourself. This may be something that someone else decides based on what you're using it for, things like that. But I just want to give an overall kind of view of the data space in general. Now we talk about the unexpected insights. Well, while an objective-driven approach I think is better, maintaining raw data in its natural format, for example, in a data lake, can allow us to use it for discovery later on. And a lot of times this has been used tremendously in the past, where people gathered data, it basically sits there in some repository, and maybe some other researcher has a question on this, and your data actually fits the bill. So even though it wasn't part of your analysis, maybe it becomes useful to somebody else in the future. So this leads us into data lakes, data bricks, and data warehouses. So once an objective is established and our data acquisition begins, we need to consider storage architecture to determine how effectively the data can be processed for our statistical analysis. So a data lake is a system or repository of data that's stored in its natural or raw form. So it's usually things that are blobs or files, they're unstructured, and it can store data indefinitely. Now, of course, the problem with this is it's not right now in its current form in an immediately usable form that you can use. I know I'm basically repeating myself. It's not a form. What I mean is it is not currently in a form that you could take into R, Python, something like that. You have to do some sort of pre-processing with it first. It's in its raw form. But the nice thing about this is because it's in its raw form, any manipulation or changes that have been made downstream are not in this data, meaning you can go back to the original source and make the changes based on what you need. So this is often where the initial extraction from an API or web scraping will reside before processing. This leads us to a data warehouse. So this is structured data that's been cleaned and processed. This is optimized for analysis, and it's ready data and SQL-based retrieval. So basically, this data now, instead of being in its raw form, has been transformed into a structured form that you can now pull ready for analysis. So these environments facilitate reproducible workflows by providing consistent, high-integrity data source for model training. And then we have Databricks and modern integration. So this serves as a unified platform that can bridge the gap between raw lakes and our structured warehouses. It can facilitate collaborative computational environments where things like R and Python code can run directly against large-scale distributed data. So this is where we're going to end this lesson. When we come back, we're going to look at database management systems and start diving a little bit deeper into specifics, not to the level we will later, but we're going to start with this overarching view, things like data lakes, data warehouses, and then start distilling it down into actual database management systems, and then from there into actual systems we're using, things like that. So we're kind of funneling it down in this section. So I hope this is useful. Again, follow along. I guarantee you that we will not be just focusing on slides in the future, just for this first couple sections while we're setting the stage and getting all the definitions out there. Hello everyone. In our last lesson, we were introducing all sorts of definitions about data and talking about the data career space field in general. Now we're going to focus on specifically the systems we use to actually store and access data. We'll begin by talking about data management systems. So a database management system, or DBMS, handles the storage, retrieval, and updating of data within a computer system. And while many types exist, we're going to focus on the most relevant for our statistical data structures that we're going to be using, generally focusing on statistical analysis. So the main one that's used, and this is the most commonly used one for most things, are relational databases, or RDBMS. So this is the most common type of database for structured data, utilizing tables and specifically SQL, which is structured query language. Then you have NoSQL, which is optimized for specific requirements like flexible schemas and what's called horizontal scaling. And we'll talk more about all of this later. You also have hierarchical and network, which are older models that use tree-like or interconnected graph structures. You've got object-oriented management systems, which store data as objects. This is similar to the structures that are used in R and Python when you're using those systems for programming. And then one of the newer databases, not really the database type itself is not new, but it's more commonly used nowadays, are vector databases. These are designed to store and query high-dimensional embeddings. So in context of statistics, these are essential for modern AI applications where data is represented as a vector in high-dimensional space. And then from that, you can go out and gather what you need based on what you're trying to do. We're going to start first by focusing on hierarchical database structures. So this model organizes data into tree-like structures with a single parent node for each record. So the structure is that the data is stored as records connected by links and then moving from a root node down to the leaf nodes. So for example, let's say we have here a university system. So the university is that root node. And then from that, there are two child nodes to it, department and administration. The administration is one of our leaf nodes where it ends. That's part of the structure. In department, though, this is now a node that branches off into three other nodes: students, faculty, and resources. So, for example, in the department, you will have certain faculty that are part of that department. That department is part of the university. So your university might be ours, and let's say the department is mathematics and statistics. Then the faculty would be people like me who are part of that department, which is a part of our university. Another department, let's say social sciences, would have a different group of faculty in their child node of that part of the database. So the constraint, though, with these is that they are very rigid, and a child node cannot be more than one parent, or part of more than one parent. So let's say that you had a dual enrollment. You are a student who is a dual major between math and philosophy. Well, in this structure, you have to be placed in one or the other. You are either a math student, part of the math department, or you are a philosophy student, part of the philosophy department. This actually can be expanded then into a network database structure. So it's an evolution of the hierarchical model that allows for more complex relationships. So it's a graph-based model where child nodes can have multiple parents. It allows more flexibility, so it better represents many-to-many relationships, such as a student being part of both departments and a club. So now looking at our example here, we have our university, which again breaks into department and administration. This department still has nodes of student, faculty, and resources, but now you also have this club node. And the people in this club could be part of the students, part of the faculty, and also part of the resources that the university or the department specifically has. So in this case, that student could be a part of this department and also a part of a club. And of course, you could have this as different departments as well. You could have a student who branches off from multiple departments, things like that. So this is useful in representing complex relational networks or social data where simple trees will fail. Next, we have object-oriented structure. So this model will store data in objects rather than tables. This will closely match the way we handle data, again, in R or Python. So we have classes and we have attributes. So data is grouped into classes, for example, person, with specific attributes like name and address. And then each specific class, let's say in this case, student or professor, inherit attributes from general parent class. So looking at this sort of table we have here on the side, we've got person. That person has a name, phone number, and address associated with them. If we look to the left, this is of type, which means what type of person are they? They're a student. If they're a student, it has their roll number, their average grades, and are they eligible to enroll in a course. If the type of to the right is a professor, this database might have information on their salary and or their qualifications. Do they have a PhD or not? And then if we look below, lives at, this would be the address. So you have this person, which could represent both students and faculty. Every one of those people have an associated address with street, city, state, postal code, and country. But then you also will have this branching off logic based on the object of if they're a student, you have this information. If they're a professor, they have this information. And this is kind of how we store things when we're using R. It is an object-based language. When you create objects, you have certain attributes and data that you associate with them that can be called on and actually part of bigger objects, sub-objects, things like that. So this maps directly again to how R handles list objects or how Python manages classes, making the bridge between database and the code very short. And this is why I mentioned previously that oftentimes when you're like learning SQL, once you have a little bit of background in data, it's pretty easy to pick up because it's going to be very similar to what you're already using. In fact, it translates very closely when you're using R to access, for example, a SQL database. Next, we have relational databases. So relational databases are basically the industry standard for structured data. They're structured to recognize relationships between stored items of information through what are called linked tables. So it has a tabular structure where data is organized into tables with predefined schemas, which consist of rows, which are the records, and columns, which are the attributes. So this means that for every event, there will be a row, which is, again, the record of that event. This could be a sale in a system. And then you're going to have your columns. These are the attributes. Could be things like date of purchase, how much was spent, what items, things like that. Then there'll be a key-based relationship. So the tables are connected using primary and foreign keys to ensure data integrity and reduce redundancy. So this is called normalization. This is something that's used a lot of times because, again, when you're storing data, you have to consider that if you are gathering every little thing, you have a lot of redundancy, you're going to be using up a lot of space. A lot of times you're going to want to have something that is both reliable and also efficient. So this is using, specifically focusing on something called structured query language, which is SQL. This is the universal interface for data definition, manipulation, and retrieval. Most companies use SQL. I know people who work at, for example, like Raymond James, and they use SQL. I know people who work in all sorts of industries. Almost every industry will use SQL, so you'll probably want to know this. So some popular systems will include open source objects like PostgreSQL, MySQL, or SQLite, as well as enterprise solutions, things like Oracle or Microsoft SQL Server. In fact, my experience personally with SQL is I originally learned using SQLite, which every one of these systems are SQL, but they're going to have differences in them. For example, SQLite does not have, I believe it's right joins, whereas in SQL Server does. It has left and right joins and things like that. Currently, for my systems that I've been using PostgreSQL for almost all of my operations. And which one you use will be partially based on what your company or whatever you have access to uses, what you feel most comfortable with, and sometimes which one will work best for whatever it is you're trying to do. Now, some benefits of this kind of system is that it has high accuracy, it's easy to collaborate because again, it's the industry standard, so more people know how to use it than other systems generally, and it doesn't have a very high bar of entry comparatively, and it has strong data integrity. But there are some limitations. So you can face physical storage constraints and decreased performance in datasets as they scale to massive volumes. So the problem with, for example, SQL is that it has a horizontal structure. So the more data you get, the bigger and bigger the structure gets, the longer it takes to access that data because it has to go through all the rows. It doesn't have what's called a horizontal structure, which means that it allows it to expand or scale quickly. So this is, of course, its limitation. It's used by many companies, but oftentimes when you get to a certain point, it actually can become a bottleneck. And then here's some more examples of different ones. We've got Oracle database, MySQL. These are just emblems you can see here. The benefits for simplicity, ease of use, accuracy, data integrity, normalization, and again, collaboration. Limitations, maintenance difficulty. It can be difficult to maintain, especially as the system gets older, it continues to grow. It can become costly, again, as it continues to grow. You might run into issues with physical storage. It has a lack of scalability. It does not scale well, depending on how much data you're getting. Complexity and structure. This can actually grow out of hand very quickly. An example of this, I worked for a company and we were working on building out a system. And as we built out the system, the schema for it got more and more and more and more complex to the point where it actually became very difficult for our backend developers to maintain. And of course, it can have decreased performance over time. Now let's talk about vector database structure. So a vector database differs from traditional systems by storing data in mathematical coordinates or embeddings rather than rows and columns. So these embeddings are the raw data, things like text, images, or even SQL outputs, and it's transformed into a high-dimensional vector via an embedding model. So this model has a way that it embeds them, giving them sort of coordinates on this vector space. And then with that, data can be plotted in a high-dimensional space where the distance represents statistical or semantic similarity. Notice that I have distance in quotes. This is actually on purpose, and this is because how do you measure distance? Some might use what's called Euclidean distance, which is just, think of rise over run. You have 2 points, you know what the distance is between them, you do the change in y over the change in x. But you could also have things like Manhattan distance, Mahalanobis distance. There's different types of distance that you might want to use based on whatever it is you're actually looking at and how you were defining it. For example, if I'm looking at a mapping company and I'm trying to figure out how to, set up routes from point A to point B, it doesn't matter to me if the destination is 13 miles away because that's not the distance I'm going to drive, right? If I have a grid view of streets, how far would it actually be for me to actually take those streets to get where I'm going, not just as the crow flies, as it were. So instead of exact keyword match, the system will find what's called the nearest neighbor using distance function like cosine similarity. And this is something I have a lot of experience with as well, is how do you describe what's similar? Specifically when you're doing a lot with natural language processing. Oftentimes you're looking for similarity between things, and it might be word overlap, it might be things like that. And what you're doing is you're using these word vectors to try to determine how close they are to a match. So this is crucial for dynamic modeling, model validation, and detecting overfitting in complex data sets through simulation. The next thing we're going to look at is NoSQL. Now, based on the name, you might think that it's not SQL, but it actually means not only SQL. So it has all the functionality of SQL, but more. So it does not use a tabular schema of rows or columns. It will use storage model. It's a storage model optimized for the specific requirements of the data being stored. So it might be, for example, key value, could be wide column, could be graph, could be document based. So this is why it's not only SQL. It can, in fact, replicate exactly what SQL does or is, but it also can have other schema or storage methods that SQL does not have. It allows you to have flexible schemas. It will allow for horizontal scaling, which means that it's actually a lot better for scaling up than SQL is. And these would be things like Cassandra, MongoDB, HBase, Redis, and plenty of others. I've mentioned schema quite a few times, so let's talk about what a database schema is. So a schema is just a formal structure of a database described in a language supported by one of our database management systems. It serves as a blueprint for how the database is constructed and organized. So what it does is it refers to the organization of the data. So think of it like a blueprint where it's going to tell you how the data is actually connected, constructed, and where data goes. So the types of schema you might encounter are a logical schema, which defines the logical constraints and data organization, such as an organization of data into tables in SQL. You could have a physical schema, which describes how the data is actually stored in a storage medium. Or you could have something like a view schema, which defines how the data is viewed at the application or user level. An example of this would be SQL. SQL uses a logical schema. Specifically, we describe them using what is called an ER diagram. So let's actually talk about that then. An ER diagram, or an entity relationship diagram, is used to visualize this logical schema. So what we're doing is we're using entity relationship between our different entities and how they're related to each other. And I'll talk more about these little arrows in a second. These are crucial for people like statisticians to understand what's called the chain of custody and connection of the data before we start merging tables in either R or Python. So each of these will include the entity. This is an object or concept about which data is being stored. So in this case, on the right, we have apparel size, we have product categories, product color, and categories. You've got attributes. These are specific property or characteristic of an entity. So this would, of course, in this case, the product is our entity. You've got these different attributes. And then the relationship, how entities interact or connect with one another. For this interaction, we have different cardinalities which describe the nature of that connection. We have one-to-one, we have one-to-many, many-to-one, and other ones like that. So looking at our table over here, whenever you see a line touching one of the entities, that would be one. Where you see it split into three, that is many. So looking from product to apparel size, this would be a one-to-many because there's one product, but it can have many different sizes. So let's say we have a shirt. That shirt could be small, medium, large, extra large, 2X, things like that. So this is a one-to-many relationship. This style of shirt has many different sizes. This style of shirt has many different colors. These colors can have many different IDs, stuff like that. Many to one would be the relationship in the other way. If I'm looking at what shirts do I have that are yellow, then I could have many different, many different things associated with just that one shirt, right? So this one shirt has many different colors. If we're looking the other direction, if I have one product, it could be part of many other things that are connected to some attribute or entity. You could also have many to many. This would be something like if I have a whole variety of products that are associated with a whole variety of colors. This would be something like if I sell like water bottles and I've got different sizes, 16 ounces, 32 ounces, and I've got a variety of colors, but every size bottle can be any color. So I can say, okay, well, I want the 32 ounce in pink, I want the 32 ounce in gray, I want the 16 ounce in pink, I want the 16 ounce in gray. So this would be a many to many connection because for each of the many options of bottles, they have each of the many connections in color. So again, looking at this image here, this is what an ER diagram would look like. This describes the relationship of that data. So from this is how you would determine how to make the SQL queries that you're interested in, right? So you might look up and you want to do a search on product based on apparel size or based on colors or based on apparel size and color. And then from that, you could pull the data specific to what you're looking for using the commands you would learn while doing SQL. So that's it for our discussion on database management systems. In our next lesson, we're going to then look into what happens when you get into the scale of big data. Everybody loves to talk about big data. Now it's time to look at some of the considerations you have to have when you get to that scale. Hello everyone. In this lesson, we're going to continue where we left off and going from learning about data, database management systems, and now taking it one step further to other tools you might be using in your data career. So let's first talk about big data and specifically the 5 V's. So when data sets reach a scale that goes beyond what traditional software can handle. For example, things like Excel, and it won't be able to manage this amount of data anymore. This is where you start to enter the realm of big data. And this will require a fundamental shift in how we handle data, things like velocity and variety. So first I want to define what is called the data deluge. This is a situation where the volume of new data being generated is overwhelming the capacity of institutions to manage it or researchers to make use of it. So again, we talked about this a little bit when I was describing the syllabus for the course, but whenever you are given data, when you're learning about stuff like this, you're learning programming, these are usually small contained data sets where you're learning more about the methods. But once you get beyond a certain point, things become a lot different. It becomes very difficult to deal with different data situations using the traditional tools that you might use for day-to-day projects or homework assignments, things like that. And this is actually one of the biggest transitions that people make, especially when they go from like academia into industry. Unless you're into like some bigger, deeper research, oftentimes you're dealing with much smaller data. So there's the 5 V's you have to consider with big data. The first is volume. So the initial size or amount of the data being generated or stored. When you have large amounts of data, this is something that can actually lead you to have issues whenever you get to the big data stage. If you look at companies like Google, Amazon, IBM, they deal with massive amounts of data beyond anything that you probably have ever encountered in an outside situation. Take YouTube, for example. They have how many thousands of hours of video being uploaded every single minute. This is beyond anything that you've been taught in any of your classes on how to manage. And all the systems that you've worked with or know how to use likely are not in the realm of being useful for this kind of situation, right? We talked about the fact that when you are getting data, not only do you have to know how much you need to store, you also need to consider things like how quickly do you need to access it. So this leads us to the velocity. The velocity is the speed at which data is generated and the rate at which it moves through the system. So again, looking at something like YouTube, they have a large amount of data available, right? You go on anytime right now, you can find millions of videos. But the velocity is also very high because, again, thousands of hours of video every minute or second are being uploaded to YouTube at any given moment. So they not only have to deal with volume, they have to deal with velocity. Then there's variety. Variety is the diversity of data types ranging from structured tables to unstructured text, video, and sensor data. So not only might you have a lot of data and a lot of data coming in, you might also have to be dealing with variety of data, right? So if you're some big company and you're bringing in sensor data, sales data, web traffic, video data, these are all things that you would have to learn and figure out how to handle. Then there's veracity. This is the quality, accuracy, or trustworthiness of the data. And then there's value, the actual utility and insights a researcher or company can derive from the data. Because just because you have data does not mean that it's necessarily useful, right? We talked about a little bit about this. So in machine learning and statistical learning, we have a term which is garbage in, garbage out. Just because you have data, if you do some analysis, you will get an answer. The question is it a good answer? And a lot of times it depends on 2 major factors. How good is your data and what analysis did you do to actually make your assessment? But the thing is, even if you have the best analysis method, if you have bad data, you're going to get bad answers from it. And this is where the value of the data comes from. And it's twofold. Trying to answer the question you're interested in, but also from a company's perspective of what is its value worth in the sense of monetary value. Again, going back to YouTube as an example, they make money by having people maintain attention. They sell advertisements. They are basically a giant advertising company. And the more videos that people are watching for longer means they can serve more ads. So if you post a video and you get 1,000 people that watch it for 20 minutes, that is a certain amount of value. If somebody else makes a video and 100,000 people watch it for 30 minutes, that is a more valuable value of data for them because that data, the video, is bringing in more actual value in the sense of more ad revenue, meaning they make more money. So here's an image they have. This one's a little out of date, but this one only has the 4 V's. But you'll see here that we have got volume, variety, velocity, and veracity. So it doesn't have value, which we include now as one of our V's. But you can kind of see if you look here, pause the video, you can look at some of the stuff from here. Now, like I said, this is drastically out of date. So when it's talking about 6 billion people have cell phones, that was, I don't know, probably 15 plus years ago. You can see that as of 2011, the global size of data in healthcare was estimated at 150 exabytes of data. That was over 10 years ago. So imagine what it is now, right? You got 30 billion pieces of content shared on Facebook every month. I feel like that's probably out of date as well. So this is just sort of an example, though. I left it in here because it still kind of shows that this was already an issue, right? Who here has ever worked with exabytes of data? And this was in 2011. Imagine what it is now in 2026. So these are things where you have to consider. If you get to this scale of data, this is where I talked about things like SQL not scaling well. If you're getting up to this level of scale, even those tools that many companies use would become basically unusable. Now, most companies nowadays get around this by using cloud technology. So modern computational statistics relies heavily on cloud services to implement the database types and big data strategies that we've discussed previously. So these platforms allow for scalability that local hardware generally cannot match. Now, I won't say they never can match, because some companies will have their own in-house services and servers and stuff, but they're paying to maintain that because for them, it might be more valuable to have control over their data, because there's always trade-offs for anything. If you use cloud services, then if you're not a big fish, if anything happens to it, you're at the bottom of the queue, right? So if their system gets attacked and they only can get certain parts of the system online at a time, they're going to be focusing on big companies that pay them millions or billions of dollars, not your small website that has 1,000 viewers a month. This is the problem with cloud technology, is that you don't control the data. You have access to it, and of course, if you're a bigger company, you probably have more control over it, but it's a trade-off that you are trading control for ease and scalability. So the major providers for cloud technologies are Amazon with the AWS system. You've got Google with the Google Cloud Computing, or Cloud Platform, GCP. You've got Microsoft with their Azure system. You've got IBM with I don't remember what their system is called for this, but I know their AI system is called Watson. And then you've also got specialized platforms like Databricks. And there's many others. For example, when I build my systems for my statistical projects that I have my students do, and I need to run analysis on a whole bunch of projects every semester, I use Render to create a PostgreSQL database. So I'm offloading the database management to a cloud system. It is not stored on my computer. It is not being processed on my computer. I have it outsourced using cloud technologies. So some key advantages though, parallelism. This allows you to be capable of implementing parallel or distributed databases for faster processing. So instead of having a single database, and you can do this in a company as well, you can have multiple databases where instead of trying to find one piece of information in one database, you can actually split the process into mini databases where it's looking for that information in all of them at the same time, allowing you to have faster retrieval. You also have scalability, the ability to scale resources up or down based on the computational load of the analysis. This is where cloud technology really does take off, is that if you have some analysis and you're on a local system, you are completely constrained by the capabilities of your system. But with cloud technology, you can always expand as you reach the edge of whatever constraints you temporarily have. Now, you can set hard restraints on it to limit cost, but if you need more, you can expand it. And this is oftentimes how companies will use it. In fact, I've had to do this before in the past, where I was doing a random forest one time, and I was trying to do 1,000 trees based on some bigger amount of data that I had. And when it was trying to store all those trees, it actually filled up my random access memory, my RAM on my computer, and my computer froze. And it ran into this problem where every time I tried to load R, it tried to reload all those trees back in, and it would freeze R again. So I had to basically kill the process, and I had to offload to a system. I think I used Google Colab or something like that to use a system with more RAM, which allowed me to then do the analysis. So this is the nice thing about it. It adds that scalability. If you reach some threshold, you can always expand it further from there. Then there's also accessibility. Its centralized storage allows for better collaboration and consistent data accessed across teams. This is again where it's really useful, because if you're just doing some analysis for yourself or a small company, generally having it locally stored is fine. But the nice thing about cloud storage and cloud based systems for analysis is that if I put something on the cloud, I can send a connection, someone else can connect from somewhere else, and we can collaborate on it. And this is not something easily done with your local system. It can be done. You could definitely set up where someone could remote access in, things like that. But again, it's simpler. Now, one thing I do want to point out, though, is with that simplicity, though, does come the downside of that is more vectors of attack or weaknesses. Because if something is stored on my system, as long as my system is sort of air-gapped from everything else, it means that no one can generally attack it unless they can get access to my system or I connect to somewhere where someone can. On a cloud system, on the other hand, if somebody can get your security key, your passwords, whatever it is, they can, of course, access it from anywhere, because that collaboration of anyone can access from anywhere means that if somebody has your information, it can be a vulnerability. Just like anything, strong password, store it, don't write it down, all the general security measures. Okay, so now let's talk a little bit about the ETL pipeline, or extract, transform, and load. And I mentioned previously that there are entire careers that are built just around this. In fact, data engineers, this is a big part of what they do. And if you look at data jobs, data engineers generally are one of the higher paid jobs. Over data scientists, data analysts, oftentimes they are highly paid. And it's because this is so vitally important to these big data companies. They need the data extracted, they need it transformed, and they need it loaded into form that can be used, that then can make money or make products or whatever it is that they are using to what their company is based on. So ETL is a three-phase process used to move data from various sources into a centralized container for analysis. So you have the extraction phase. So the sourcing data from various origins, such as relational databases, SQL servers, or even flat files like CSV or text documents. Then you want to do the transformation phase. This is the most critical phase for a statistician, where the data is cleaned, sanitized, scrubbed, and then reshaped to meet the analytical requirements. This is getting it to the form where you can actually do analysis. And then you have the loading phase, which is moving the process data into an output container, such as a data warehouse where it's ready for modeling. So again, this is oftentimes handled by a data engineer, and their job is to take in all these sources of data and then get it in the form and the place where then the data analyst, the data scientist, the actuaries, whoever it is, can access that data. And this is immensely valuable. And it does overlap quite a bit, but also diverges a decent amount from your other data careers. Another useful technology that we use in data is called containerization. So the number one thing that everybody in programming hates is the response when something goes wrong of, well, it worked on my computer. And this is a problem because when you build a program, let's say on your computer, and you send it to me, it doesn't work. Why? Well, it could be because maybe I'm using a different version of the software. Maybe I have a different operating system. Maybe the packages that I have are more updated or less updated than yours. This is where containerization comes in. So to ensure that code that we write in R or Python runs consistently across different environments, we use containerization. It allows us to have consistency. Packages that software code with only the specific operating system libraries and dependencies required to run. So if you think about what a container is it is a container with whatever it is that you're trying to send, let's say your code or your program, but it also will have all of the system libraries and dependencies that that code needs to run. And the nice thing is when you create these containers, you can set the exact environment you want it to run in. So if you wrote your code in Ubuntu 16 point something or other, but I'm running it on Windows, my container though that it's in could be for Ubuntu 16 something or other, or vice versa. If I wrote it in Windows and you're using Mac OS or OS X, whatever they call it, same thing. I could have the dependencies and libraries that you would need to run this Windows program in a not Windows system. This allows us to have portability. Containers run identical on any infrastructure from, for example, this MSI laptop that I'm using to a university supercomputer. And this is actually a relevant example because, again, when I'm doing my research, I'm working right now in front of me. I have an MSI laptop. You can probably see it right here if I, nope, okay. But I have an MSI laptop and that I'm on right now. But whenever I'm putting out code onto the university's access to a supercomputer, again, if I run it in a container, I can actually bring all the dependencies with me that I need for it to run properly. It's also very resource efficient. It's more lightweight than traditional virtual machines. So popular systems for this are Docker, which is the industry standard for creating and sharing containers, or Kubernetes, which is sort of Google's version of it, which is used for managing and scaling large numbers of containers. Now, one thing I want to point out real quick, because I used to have a slide on virtual machines, but I kind of got rid of it, but I'll just briefly talk about it here. So virtual machine is where you basically were running another version of that operating system or whatever it is that you are using within your computer. So for example, if I have a Windows computer, I could run a virtual machine that had OS X on it or something like that. Like let's say I wanted to do app development. I'm using Swift because I want to make an Apple app. Well, I could then use a virtual machine. But the problem is that loads everything that I would need in order to run that operating system. All the parts you need, but also all the parts you don't need, which is why it's very resource intensive compared to containerization, which only brings the needed environment data or pieces that you need. For example, your dependencies and your libraries. Next, we're going to look at the real meat of this course, which is programming and software. So the choice of which programming language you use is going to depend on the statistical task that you are actually interested in doing, the scale of the data, and how computationally efficient you need it to be. These are all important. Now, I will say, before any of this, is which programming language you use generally doesn't matter. Which one you prefer will usually work. For example, there are advantages to using R versus Python or Python versus R. But if you know how to use R very well, that would be probably better to use than using Python badly. Similarly, if you know Python really well, you can do anything you need to do that R can do probably about just as well. They are very similar in capability. There are, again, some advantages between them, and of course, that's ever-changing. It used to be that R was the king of graphical representation using ggplot2, but then you've got Seaborn for Python, which is, catching up rapidly. Python used to be the de facto language if you wanted to do large language model like AI type systems. R has access to pretty much all the same stuff. Now, there is also things like scale of data and efficiency. R and Python are not overly efficient programming languages. And I'll talk more about these whenever I actually get to them specifically, but it's because a few things. One, they're high-level languages, which means that they're not close to the computer language that is actually directly touching the hardware. So basically what it is, you're at a high level of abstraction, and then of course it has to be translated to get down to the computer level. That adds a lot of inefficiency. Also, the systems are older, which means a lot of the stuff that's on them has kind of been tacked on as it was built out over years, because both of them were originally started in the 80s. So some programming languages and software, R, obviously, SAS, Python, Julia, this one, again, I haven't really added this in yet, but I do really want to start implementing this a little bit more. There's also Java, not to be confused with JavaScript, which also can be used, but it's generally more towards web development. Scala, C, C++, and many others. Now, we talked again a little bit about efficiency. If you want to have highly efficient, fast code, and you're dealing with a lot of data, C, C++, even Julia can be your way to go. If you're just doing a quick analysis, you just need to do a quick multivariate adaptive regression spline or a support vector machine, R and Python work just fine. In fact, there was actually this comic, I'll share it with my students, stuff like that, where it showed C walking up to Python. It says, "Hi, I'm C," and then Python just stands there. C kind of walks away, and then after it's gone out of the frame, it's like, "I'm Python," and the joke is that it's so slow that C already left. Now, of course, when you're doing this programming, generally you are going to want to use either some notebook system or an IDE, which is an integrated development environment. I will be covering using this. In this course, I'll be using RStudio, which now is called Posit, but if you look up RStudio, it still shows up as RStudio. There's also, for example, Jupyter Notebook. This is a popular web notebook that can be used as your IDE. Visual Studio, specifically Visual Studio Code. I just want to specify those are technically different things, just like they're different. You got Notepad Plus, or Notepad++, and you've got Vim or NeoVim, Sublime Text. These are all different integrated development environments. They all have their advantages and disadvantages. I will say that if you want to be able to lord over how superior you are to everybody, get NeoVim or Sublime or Emacs. You can tell everyone about how you're amazing. You use Arch Linux and you're better than everybody else. But for most people, VS Code, Jupyter Notebook, PyTorch, those will be the ones that most people will focus on. Okay, so now let's talk about the main language of this course, R. It's most often used by mathematicians, statisticians, and data miners for developing statistical software, graphing, and data analysis. It's an array-oriented syntax, which makes it easy to translate from math to code. It has the world's largest repository of statistical knowledge with more than, and by the way, this again is also out of date, but it says more than 15,000 released packages. Technically true, but also it's a much higher number now. It integrates well with other programming languages, specifically Python, and it is stronger object-oriented than most statistical computing languages. Now, a couple of things I want to focus on here is the array-oriented syntax. This is why I prefer R over Python. You'll have some people who say that Python is easier to understand or learn. And I don't think that's a true statement. I think that is a statement based on where your background is. If you have a computer science background, Python is probably easier to understand and learn because it is made for computer science oriented people. An example of this would be it indexes starting at 0 because computer memory starts at 0. R is built for statisticians, which means when it, for example, when it indexes starting at 1 because when we write a summation, we say I equals 1 to n. So it is built like math, meaning that if you have a strong background in algorithms, mathematical algorithms, and things like that, and functions, then R is very easy to translate to. If I write down a mathematical function, it is easy for me to then translate that into R code. Python is not as straightforward for that. It's not difficult, it's just a matter of, and if you can learn one, you can learn both of them. But I do want to point that out. When some people say that Python is easier to learn, based on your background, that might be true. But because most of the people who are my students have a math or statistical background, I would argue that R is probably the easier language to jump straight into. Now that leads us into Python. So this is the most popular language for data science in the world. It is not the most commonly used programming language in the world. That would be JavaScript, but that is mostly used for web services and things like that. Though you can do some analysis in JavaScript, not Java. They are different. But Python is the go-to. And I will say that part of this is because Python is the go-to. Like one of the best comments I ever saw online is Python is, every problem has a best tool. And the second best one is Python. Python is not the best at anything, at all, ever. But it's always really good at everything. So where R might be the best at this one thing, Python is right behind it. But when you want to do like, anything else, Python is right behind those programming languages as well for those different tasks. This is where Python's strength is. And because everybody uses Python, that means most systems that are built in Python. So most companies have people who built out a system in Python. So guess what? Now they're looking for Python developers, and they learned Python because Python's the most commonly used language. Now they're building onto the system using Python. It is not the best system for most tasks, but it works really well for most tasks and most people use it. So if you had to pick one language to learn that is most useful in a data career, it is likely Python. It has a vast amount of resources available. It's a general purpose, high-level programming language. Remember I mentioned it's a high-level language, and it does have a large standard library. And there's many of these different libraries have specific focuses. For example, if you're doing scientific computer libraries, these would be things like Pandas, NumPy, SciPy, and Matplotlib. For AI, you have things like PyTorch, TensorFlow, Keras, and scikit-learn. And then for natural language processing, you have the Natural Language Toolkit, or NLTK. Now, this is one thing also that's different between Python and R. In R, it has a lot more base functionality. I could jump into R right now with no packages loaded and do some basic analysis. Python, can't do it generally. Python, you have to load in, so they're not called packages, they're called libraries. And the difference is in R, when I load a package, I can just use it. I don't have to reference it. Python, you're going to have to reference which package you're using for this specific command you're doing. Both of them have their advantages. R, quick and dirty analysis, a lot faster. But if I have two different packages that have the same exact function, it's just which one does it choose? It's just going to randomly pick whatever one it thinks is best based on whatever I'm trying to do, and the syntax may be different, so I can specify, but I don't have to. In Python, you have to explicitly state that, which does make it a little bit more robust, if a little bit more work. So next we have SAS. This is a command-driven statistical software suite that's widely used for statistical data analysis and visualization. It was originally developed in 1970 and it is commercial software, so it is not open source like R or Python is. Now, again, I mentioned this previously, but some companies or industries, this is actually kind of the point, because having this SAS corporation that you can go to if you run into a problem for help, support, or even getting new functionality added is something that can be very beneficial to large companies that don't want to rely on the open source nature of, if I need something built, I either have to build it myself, get someone to build it, or just wait for somebody to build it. Again, also some industries though have strict regulations, meaning that they have to use these sort of proprietary closed systems, because basically if something goes wrong, there's somebody that can get in trouble for it. It does have an easy syntax to learn. It has ability to handle large databases, and this company actually has other tools you can integrate with it, which can be very useful. For example, Jump. Jump is a graphical interface for data analysis. It's very useful, and whenever you're making these models using its GUI system, you can actually output anything you do into SAS, which then can make it easy to manipulate, change, share, things like that. Now we move on to the system that I told you I'm most interested in diving more into, which is Julia. This was developed at MIT for high-performance numerical analysis. It's speedy development like R and Python, but it can run fast like C or Fortran. And this is where its real advantage comes in, because R and Python were originally created in the 80s, meaning they did not have parallel processing, they didn't have multi-core usability, stuff like that. Julia is built from the ground up with that functionality in mind. So it takes the ease of syntax of R or Python, but the speed of these more low-level programming languages like C or C++, and it's actually a really cool system. There's a lot going on with it. If you ever look up, I think it's JuliaCon or something like that, you can look it up and they have a lot of stuff on it. It's growing pretty rapidly, but it's also very niche right now because, again, if you're going into data, most people are going to use Python, so it's hard to get that foothold in. It is compiled, it can call on things like C, Go, Java, MATLAB, R, Fortran, and Python libraries, and again, it has defined parallelism. Now, this doesn't even begin to scratch the surface of the tools you could use. For example, a lot of people will use SPSS, MATLAB, Excel, Minitab, Stata, GraphPad, Prism, C, C++, Java. There's so many you can choose from. And like I said, if you're just looking to do analysis, most of these can do most of the things you want. I prefer, the open source systems like Python and R, because anything that I need to do, there's probably a package for it. For example, if I'm doing, again, I mentioned multivariate adaptive regression splines, I would use the Earth package in R. And this just makes it where I have a lot more control over it. It's a lot more programmatic. SPSS is a graphical system where you're going to click drop-down menus. You have a lot less control over it. But if you just need to do a quick analysis and it's got the functionality, it works just fine. Similarly, just like Jump from SAS. So now let's talk a little bit about those IDEs, or integrated development environments. So an IDE provides an interface between the programmer and the raw code. This will offer tools for debugging, visualization, and project management. You can do programming in a basic notepad and start from there. You could literally do it from there. In fact, when I learned how to do web design way back in like 2001, that's what we did. We used a basic notepad, put all the headers, everything in there to create our code, and then you could create a web page. But an IDE adds a lot more functionality. So first what I'm going to focus on, which is what I'm going to be using, is RStudio. It's a standard environment for R development, specifically optimized for statistical workflows, package development, and R Markdown or Quarto. And it also supports Python. So in RStudio, I can do Python code directly there. I can create Markdown files directly there. Now, Posit, the company and or name of RStudio now, also has a new system they brought out, a new IDE called Positron. So this is a next generation extensible IDE built by Posit. It focuses on high performance R and Python development using a modern fast editor foundation. It's basically they took VS Code and created RStudio version of VS Code, which adds a lot of functionality to it, because VS Code, which I'll talk about in a second, is basically the king of IDEs for most people. But before we get there, let's talk about Jupyter Notebook. This is commonly the first starting point for anyone who's learning Python. It's a web-based interactive environment that combines live code, equations, and visualizations. It's preferred for exploratory data analysis and sharing computational narratives across R, Python, and it can even do Julia. So that's the thing. RStudio does not have Julia capabilities. But Jupyter Notebook, you can download a Julia kernel and use it there. But really the king, as I said, is VS Code. So VS Code is a versatile professional editor used by multi-language projects and version control. It's a primary environment for Julia development through specialized extensions. Pretty much if you ever jump online and you see someone programming who's not a NeoVim user or something like that, this is most likely the one you will see. It is the sort of default that most developers use. It's the most commonly used, and it's because it has access to basically be able to do almost any type of programming. If you want to do R programming, it's got that. If you want to do Python, it's got that. You want to use AI code editors to assist you with your coding, it's got that. You want to do Julia, it has that. Go, it has that. It's very functional for almost anything you need to do because it's based on the kernels that you download for it to be able to do whatever it is you want to do. Now, sometimes you'll want to expand on these program environments using what's called distributed computing. So when a data set exceeds the memory or RAM of a single machine, we utilize what are called distributed frameworks to split the computational load across a network of nodes. So this will help with the bottleneck problem. So standard R and Python operates often within some memory bounds, like I mentioned. So large-scale statistical models will require distributed data across a cluster to prevent system failure. Remember I mentioned that random forest that I ran into an issue with. This is an alternative you could do, is you send parts of it to different systems and basically distribute the load, and therefore it gives you a robust system where you can compute faster and also have more access to resources. So an example of this would be Apache Spark. It's a unified analytics engine designed for large-scale parallel data processing. In R, you could access this functionality using Sparkly R or PySpark. These are high-level interfaces that allow us to write R and Python code to Spark and translates into distributed tasks. You also have frameworks like Hadoop and HDFS. So it's a framework for distributed storage and processing. This will utilize Hadoop Distributed File System, or HDFS, to ensure that data redundancy and reliability across multiple hardware nodes. And if you look at the picture here on the right, you can see that this Apache Spark can connect to all these things. I mean, I could go into Apache Spark and I could access, my database management systems. I could pull data from a data lake using Delta Lake. I could do Elasticsearch, or program in R or Python. It has a lot of functionality. So the role of the cluster is it wants to utilize resources like high performance computing or HPC cluster to run simulations or train models that would be impossible on a single workstation. And again, this is also where it kind of relates to cloud infrastructure. So for example, if you have these systems, let's say we're at the university and I have access to a whole classroom of computers, I could do distributed computing by sending parts of it to every single computer. Generally, what I'm realistically going to do is I'm going to jump on a system like Google Colab and I'm going to use their cloud system to distribute it automatically for me. Makes things simple. But this is an option that a lot of companies will use, and you may interact with this based on what you're doing and what the company's resources are. So this is something to kind of be important to at least know exists and maybe take a look at. So another thing that's really important is version control. So we talked about things like containerization and all this kind of stuff, but a lot of times you're going to want to focus and use version control as well. So version control is a mechanical necessity for reproducible research. It allows us to track every change made to our code, mathematical formulas, and documentation. Now there's three types of version control. There's local version control, centralized version control, and distributed version control. You can cancel changes or even look at impending changes. You can revert to a previous version of a file, and you can compare versions. This is especially useful if you are working in a team, because let's say you have your basic code base. What will happen is multiple developers may be working on something, and then they do what's called a push. They push the code to the version control system. Then you'll have somebody who oversees the system, and they can look at what changes you're making, what changes this person's making. It can look for any conflicts, and then they can actually decide whether to submit the actual push or deny it or push it back. There's all sorts of different functionality you can do. So this can be great when you're working on teams, so you don't end up having multiple people pushing code that's going to counteract or conflict with each other. Another place you might have seen this is if you use something like Box and you have a Microsoft Word document in there. It actually has version control built into it, meaning that if I make changes, I can go back and look at all the different versions that I had and see what changes were made from the original creation of the document to its current form. The most common type of version control is Git. It's a distributed version of version control system that maintains complete history of the project across multiple machines. You've got your repository or repo. This is the centralized directory where the project history, code, and documentation are stored. You've got, so a commit. A commit is a recorded snapshot of the current state of the project that creates a verifiable audit trail for statistical results. Then you've got branching and merging. Branching allows for experimental modeling or feature testing without disrupting the main code. Oftentimes, big companies will also have sort of a sandbox where the code is put in, implemented, tested, and then pushed to the actual code. Merging integrates those validated changes back into the primary workflow once they've been verified. And then, of course, like I said, collaboration is a big part of this. So you have platforms like GitHub or GitLab, which facilitate team research allowing multiple authors to contribute to the same code base simultaneously without conflict. As we talked about, this course will end in a major project, which should be the beginning of your research project portfolio. I would also highly suggest that everybody who's following and doing this focuses on project-based learning, but specifically also does make, for example, like a GitHub account and start building up your project portfolio there. And there's a lot of functionality. Definitely would look more into it. It's going to be a little bit beyond what we're teaching in this course, but it is vastly useful, especially for showing what you've done and things like that. So as we're actually covering all the coding we're doing and everything we're going to do, there's going to be a lot of times you're going to need to look up help. I am a big proponent of going to the original documentation. I'm going to cover that. I always like to go to the actual source, and you have things like this. If you go for R, you have rdocumentation.org, or you've got www.r-project.org and docs. For Python, you've got docs.python.org and then /3 for Python 3. Or for Julia, you have docs.julialang.org. If you're doing SAS, support.sas.com. These are all places you can go for actual original documentation on the programming, things like that. In fact, with R, when you're looking up projects, and I'm going to be doing this in a lot of my video stuff, we're going to be using what's called CRAN, which is the Comprehensive R Archival Network, which has all the documentation for anything and everything R package you're going to want. Not every R package is on there. There's some where you can do like a direct download, stuff like that, but most of them are. You can also use resources like Stack Overflow if you have a stomach for people being kind of pedantic and very aggressive. They tend to overreact quite a bit if people ask questions without first doing their homework. They'll tell you to instead of answering a question that'd be very simple for them, they'll be like, oh, if you've read through, you'll be able to find it here, like stuff like that. They tend to be very kind of passive aggressive, stuff like that. But it is a really good resource. Generally, you can find something that's similar to what you were curious about. You could find something, usually you'll Google it. It'll pull up a Stack Overflow question. Follow along, try to figure out what's wrong. Reddit also has a lot of really good programming groups that have a lot of things that you could find useful for finding help. And then, of course, I didn't add the slide here because I do want you to be very careful with this one. There's also AI systems. They can be very useful in programming. They're pretty sophisticated for basic stuff, but the more you get into the more obscure, they're good at what things have already been done. But the reason I want to caution you about focusing on that too much right now is remember that you're in the learning phase, which means you should be focusing on how to find the answers yourself, have that little bit of friction, which will help you learn programming better than just getting the answer given to you, right? Because if it's doing the thinking, you're not learning. But speaking of AI tools, I am not saying you should not use them and avoid them at all cost, right? So AI tools are increasingly being employed to enhance and augment the process of software development, significantly improving productivity, quality, and speed. I'll caveat that with high-level developers. There's been a lot of stuff actually showing that the quality is not better, the speed is not better because people are spending more time debugging than actually putting out code, stuff like that. But for low-level learners, stuff like that, it can quickly put out code comparable, maybe a little bit better than what you probably would have. So it can speed things up. But again, if you're always relying on it, you're not getting better. But I will say there's a quote that always kind of stuck with me, which is AI will not replace you. A person using AI will. And that's where AI kind of comes into play, is that once you have a certain amount of expertise, specifically domain expertise, then you can use it to augment. But don't ever let it replace. Again, if it's doing the thinking, you're not using it right. You need to use it to augment, and you should verify everything, which is why you should be very cautious about using it before you have a certain amount of domain expertise to double check what it gives you. And even if you do have domain expertise, check it anyway. A week ago, I saw an article where a bunch of fake citations are making it into research. These people pulled up, citations from AI systems, didn't even put in the effort or time to verify that they're real. They just put it into a research paper. They didn't grab the paper. They didn't check to make sure it's real. They didn't check to make sure that it actually supports what they believe. They just put it in. And that's what I was kind of talking about, is even if you have expertise, these researchers probably do, and they're looking for something to just support their argument, but verify, always. Let's talk briefly about AI systems though. Artificial intelligence is no longer just a research topic. It's an integrated part of professional software and data development lifecycle. So rather than replacing developers, these tools augment productivity, again, quality and speed. Maybe. I will say that there are a couple different types of ways and systems you can use. So the main one that most people have interacted with are large language models, or LLMs. These would be things like ChatGPT, Gemini, Claude, and these are kind of like generative chatbots that you have question answer interface, and they can interpret complex requests, generate code bases, and automate repetitive tasks. So for example, if I need to make a program that takes every number from 1 to 1,000, adds it together, doubles it, and then puts it under the square root, something like that, it could do that. I give it the complex, instructions, it gives me the code for it. But oftentimes with programming, there are more advanced systems that people are using. So you have AI first IDEs and code agents. So for example, you have Cursor and Windsurf. These are AI native editors that understand your entire local code base, not just the file you're looking at. Then you've got things like GitHub's Copilot or Claude Code. These go beyond simple autocomplete, and these are agents that can refactor large code blocks, run tests, and debug issues autonomously. So these systems are built into the actual fabric of programming. So instead of giving it a piece of code saying, help me make this more efficient, help me test this, it's actually integrated into the environment. And of course, with R and RStudio and Python, you can actually integrate these code agents in as well. But there are actual environments that are built specifically for this. For example, Gemini now has their own, I can't remember what it's called, if you look it up though, Google has their own to work with Gemini as well. There are also autonomous data agents. These are tools built on frameworks like LangGraph or Crew AI that can execute multi-step research tasks. So an example of this would be that an agent can ingest the raw data, can perform exploratory data analysis, can generate a report, and it can flag outliers with minimal human intervention. So if you go online, agents are the big thing that everybody's raving about. Again, cautiously, I would look at it, but wait and see. I generally, AI systems are not putting out the work that people act like it is, but again, still it can be useful depending on what you're doing. And then for research and analysis, we've got some specialized tools. A big one is Notebook LM. It's a research-specific tool for grounding AI responses in your own PDFs, notes, and data. So unlike other AI systems where it's going out and gathering anything, it's going to focus specifically on the files that you give it. And then you have stuff like Perplexity, which is a real-time search engine AI system that will help using fact-based citations, which is essential for example, if you're in academia and you're looking for actual information. So these two specialized tools, I actually do really like those two because they kind of bring AI with sort of this academic verification. I'm only going to use the resources you're finding, things like that. So they actually can both be very useful for research and learning. For example, if you are learning a programming language, grab a bunch of documentation about Python. Create a Notebook LM for it. So that's going to be it for this. Next lesson, we're going to look at data careers, and then after that, we'll finally jump into some real programming. Hello, everyone. Up until now, we've looked at all sorts of things around data, from planning to tools you might use, to then programming languages or environments that you might end up implementing your analysis on. We're going to finish off this first arc of the course by looking at data careers. And we want to look at understanding the different roles in data and software fields. So in this lesson, we're going to explore 6 of the roles in the field of data and software. We're going to look at data analysts, data scientists, data engineers, actuaries, statisticians, and software developers. We're going to look at what each role involves. We're going to look at the technologies and skills that they require or are constantly looking for, how these roles are similar and different, and of course, by the end of this, hopefully you'll have a clear understanding of these different roles and be better equipped to pursue whichever one aligns with your interest the most. Now, I do want to point out before we begin, this is not an exhaustive list, and oftentimes there's a lot of overlap in job titles. So you might see some jobs saying that they're looking for a data scientist, but the actual position generally lines up more with a data analyst. So just be aware. But this is the general idea of each of these careers. Most of these graphs that we're going to have in this section are out of date. These predate the AI systems that have come out. So it's focusing more on the core technologies. But I still think these are relevant because other than the AI systems that have come out and implementing those with the different technologies you'll use, you're still going to be using a lot of the underlying technologies that you did before. So looking at 3 searches here, we have data analyst, data scientist, and data engineer. And you'll see that the first one on the graph, SQL, is highly used in job searches for all 3 of them, with data engineer being the highest. And this is because data engineers deal a lot with the actual data pipeline, which SQL typically falls within. Now, data analysts and data scientists do still use SQL quite a bit, but oftentimes it's on the pulling data to use and implement kind of side of things. If we look at Excel, you'll see that data analysts use this pretty regularly, but for data scientist and data engineer, it's not an overly used skill. It sometimes does come up, but not very often. Then you've got Tableau. This is used more by data analysts than anything else. Again, the data scientist part, I would argue, is still some of those positions probably that would be more, better classified as a data analyst, and some with data engineer. So this is just a system for creating dashboards that allow you to visualize data, stuff like that. Then if we look at this 4th category, Python, you'll see suddenly how it skyrockets up for data scientist. Now, it's still used, but not as much for data analyst, and it is also oftentimes used for data engineer. This is like what I talked about previously, is that Python is the go-to de facto gold star language in data careers. So when you were looking at these different careers, not as much analyst, because analyst typically is more on the data visualization side, stuff like that. Hence the using Tableau, where the other 2 don't use it as much. But for data engineering and data science, any part of programming, oftentimes they're going to be using Python. Now, after Python, you'll see R pop in here. Again, not very used very often for data analyst and data engineer, but is still pretty heavily used by data scientists. Not quite as high as Python, but still pretty high. In fact, a lot of jobs have overlap where they'll want skills in Python and R, or Python or R, or related language, things like that. Notice how SAS is not as requested in job searches, right? So these jobs, companies posting jobs, don't list SAS as much. It is still listed. Like I said, there are companies and industries where it is used, but not as much as R or Python. Then you've got PowerPoint, SQL Server, Oracle, Power BI. Power BI is another system kind of like Tableau for data visualization, creating decks and dashboards and stuff. Oracle, SQL Server, SQL, these are all versions of SQL. Just some companies will be asking for particular systems, right? Oracle versus just SQL. So these all kind of fall under SQL skills. But this should give you a brief idea of kind of like what jobs are looking for these 3 careers. So if you really wanted to kind of zero in on like the best skills to learn, even with AI systems being a thing, SQL and Python are still king, followed by R. So the first job we're going to look at are data analysts. So data analyst is a professional who collects, cleans, analyzes, and presents data. They use their skills to find trends and patterns in data and to make recommendations based on their findings. Data analysts typically have a background in statistics, mathematics, or computer science, and they use a variety of tools and technologies to analyze data, including statistical software, data visualization tools, and programming languages. If we look at the programming languages that are oftentimes cited in jobs, for a data analyst, the number one request is Python, even though they don't have as heavy of a programming load as the other two positions we talked about so far. It is still Python most of all when they do need it, followed by R, followed by SAS, and then followed by Java, which is still pretty low and probably falls more into like those niche roles. And then here's two more graphs, kind of similar idea. So the first one is technologies and data analyst job listings from 2020. And again, you'll see the number one thing people are looking for, SQL. And this followed by Excel, followed by Tableau, then followed by Python and R and SAS. Because the data analyst oftentimes is going to be doing analysis that they need to present with, and it's going to be doing things like grabbing data from it through, using SQL, doing stuff with it in Excel, cleaning it, getting into the form it needs, stuff like that, and then bringing it into Tableau to actually create these data dashboards that they're going to then display the results in and share with people. They also will add request skills, like I said previously, in PowerPoint, SQL Server, Oracle, and Power BI. Looking at the second graph we have, this one is data analyst skills required by employers. This is a different search of scraping data from this. Again, top one though, still SQL. But this one, it changed up a little bit. Instead of having Tableau as a skill that it wants right away, it actually has BI tools, which are business intelligence tools. This is what Tableau and Power BI both kind of fall into. Then it's followed again by Excel, then Python, then R, then some will ask for skill in ETL, extract, transform, load, followed by statistics, SAS, Git, and NoSQL. So the first one is focusing more on technologies. The second one is just more overarching terms that are used in a lot of job searches. So going back to the skills that they need then, the most common skill they're looking for is SQL, followed by Excel, then Python or R, then Tableau or Power BI. And then with this, they also expect you to have some statistical analysis. So if you're planning on going to data analysis, I would start by learning SQL and Excel for your data manipulation. This is how you'll get your data. This is how you'll get it in the form you want. Then once you've done that, I would either move into Python or R for more complex analysis. Which one you choose isn't really a big deal. They're both kind of requested roughly about the same, with Python, being a bit more popular and common than R. And then once you've done that, I would then look at learning data visualization tools like Tableau or Power BI. Some portfolio projects you could consider doing are trend analysis, sales forecasting, customer segmentation, or performance metric analysis. Again, these are some general, like boilerplate kind of projects. I would then suggest you focus on something relevant that you're interested in that you could actually dive into and do an interesting problem on. But these are the kind of things they're going to be looking for. Things that show that you can find trends, forecast, simulations, stuff like that. Our next job is data scientist. And this is the most popular one generally among my students. So a data scientist is a professional who uses data to solve problems and make predictions. They use their skills to collect, clean, analyze, and model data. Data scientists typically have a background in statistics, mathematics, computer science, or machine learning. They use a variety of tools and technologies to analyze data, including statistical software, data visualization tools, and machine learning libraries. So if you look at this job description, it almost is word for word the same as data analysis. The key divergence here is that in data analysis, oftentimes they will focus more on visualization, right? Those Tableau, Power BI, dashboards that you're getting out this information, where data scientists veer a little bit more often into machine learning. So looking at the top 20 technology skills for data scientist job listings, first and foremost, Python. So Python takes the seat as the highest sought after skill for data scientists, followed by R, then followed by SQL. So SQL is still a vitally important skill for a data scientist to have, but it's put after programming languages in how often companies are looking for it. And it's because that's really where it diverges. Data analyst, it's getting the data, doing something with it, visualization. Data scientist, you still need to get the data, but the big focus is on the analysis part, which is where you'll usually be integrating slightly more advanced methods like machine learning methods. This is followed by Hadoop and Spark, which was discussed when we were talking about distributed computing. Then we have Java. So Java is more heavily weighted for data scientists. And this often would be probably based on the companies that are looking for data scientists, the systems they already have, what kind of problems you're doing. Then we have SAS. Now we have Tableau. So it is in there, but not as highly relevant. Hive, Scala, AWS, and now we bring in some cloud technologies, C++, MATLAB, TensorFlow, C, Excel, NoSQL, Linux, Azure, and scikit-learn. So looking at this, again, if we focus just on the main core skills, just like before, Python or R, SQL, and then your distributed computing systems. But you'll see in some of these, like for example, Excel. I told you that some of these jobs are going to have some overlap. I've seen it when I've looked at jobs where you'll have companies saying they're looking for a data scientist, but if you actually read it, it's really a data analyst position. And it's because a lot of times companies aren't really sure what the title should be, so a lot of times you're going to have some overlap. Oftentimes, most data science positions, you're not going to be using Tableau or Excel, but you could. Also, some of these are very specific, like for example, companies asking for scikit-learn. This overlaps quite a bit with Python. Oftentimes it'll be something like experience in Python, specifically pandas, scikit-learn, stuff like that. This is basically saying machine learning using Python. So the key skills and technologies that data scientists will use is Python or R, SQL, followed by Apache, Hadoop, or Spark, and then machine learning libraries like scikit-learn or TensorFlow. And then following that, then you get to data visualization. So again, data scientists tend to focus more on the analysis side of things. So the learning path I would suggest for a data science, if you're interested in getting into data science, is a strong foundation in mathematics and statistics. And then from there, you want to jump into learning R or Python. You also are going to want to learn SQL for data manipulation. And then based on that, you will dive probably into machine learning and some visualization tools. So that's sort of your priority, right? You want to be a really strong programmer. Then you definitely need to learn SQL. And then it would be good if you could learn some machine learning techniques, things like that. I will say oftentimes the thing with data scientists is that they have so many skills they're expected to have between computing, statistics, machine learning, deep learning, all that kind of stuff, that oftentimes you're not going to be an expert at all of them. So if you're a strong programmer, you probably would be really good at making these systems. You can run anything and everything, but maybe you don't have as much foundational knowledge in the mathematics to understand its strengths, weaknesses, shortcomings, distributions, stuff like that. If you're coming from a more statistical side, you probably have a stronger basis there, but you might not be as strong at programming. And this is oftentimes the trade-off between the two. And it's really a good idea sometimes when you'll have teams made up of a little bit of both. For example, I've worked with teams like that before where I was the statistician side of things. So I was the one looking at models, making determinations, kind of overseeing everything. But then I had these computer science-based data science people working with me who were much stronger programmers than I am. They could build the systems faster, more efficient, and better than I could. But I was the one who could tell us which system would be most appropriate, things like that. So some portfolio projects you might want to look at if you're looking at doing data science are predictive modeling projects, natural language processing, image recognition, or recommendation systems. And these are all very interesting ones, I think so, because most of them are focused on machine learning. So specifically natural language processing, even though we've pushed more and more into large language models, a lot of the foundational stuff is still using natural language processing techniques or at least ideas. It is different because now the generative AI are usually using recursive augmented generation or something like that, RAG. And it's different than natural language processing, but there is a lot of overlap in it. Whereas in the embeddings are different, the attention mechanism is different, but a lot of this natural language processing stuff can still be very relevant. In fact, a lot of projects I've ended up working with, I seem to need these more often than not, even if that's not really what I'm interested in doing at that moment. Image recognition, this one is kind of a go-to for a lot of machine learning, stuff like that. So you'll find a lot of projects, you can look at that. But the key thing to remember is if you're doing these projects, it's fine to follow tutorials to kind of figure out how to do them, but you need to do something different. You can't just do the digit recognition problem that every aspiring machine learning practitioner uses and does, because everyone does it. It doesn't stand out. So take these ideas, look at tutorials, but you need to do something different. You need to find your own project. And then, of course, recommendation systems. This one is actually tremendously interesting to me, and you actually interact with them all the time. Anytime you jump onto a system like Netflix or YouTube and you're getting recommendations, these are recommendation systems. And there's some really interesting ideas behind this mathematically, things like market basket analysis and stuff like that. So there's some really cool projects you can do if you're interested in getting into data science. Now let's talk about data engineer. So data engineer is a professional who builds and maintains the infrastructure that stores and processes data. They use their skills to design, develop, and implement data pipelines, data warehouses, and data lakes. Data engineers typically have a background in computer science, engineering, or information technology. They use a variety of tools and technologies to build and maintain data infrastructure, including programming languages, databases, and cloud computing platforms. Of the 3 jobs we've talked about so far, generally, data engineers are the highest paid of all the positions. Now, I say generally because some data scientists who specifically are machine learning engineers do oftentimes get paid higher salaries than your average data scientist, which has a lot of overlap with a data analyst. But data engineers are the people who make sure the data gets from point A to point B, gets stored properly, gets indexed, gets in the right form, transform, right? That's the ETL pipeline, extract, transform, load. And this is why they get paid so much, because there's a lot of value in this data. Companies want this data, they want it accessible, they want it where it's supposed to be, and they want it in the form that it can be used. And this is why data engineers make a lot of money. So they're not as related to the analysis side of things that we're going to be focusing on, but it is still part of the data ecosystem. So looking at these 2 graphs here, these are the top 20 technologies. Again, remember, these are all from pre-AI systems, large language model, generative AI. First one, Python, just like data scientist, followed by SQL, and then it jumps into Spark and Hadoop, then Java, then AWS, Scala, Kafka, Linux, Redshift, then R. And this is something I kind of wanted to kind of focus on here versus like data science. In data science, Python is the most commonly used program language, but R is a close second. In data engineering, R is not oftentimes the main language to use. Python is a more general purpose programming language. It's better for a lot of these tasks that you're going to be doing as a data engineer versus R. R is excellent for data analysis. It's great for all sorts of stuff that I use it for, but if you're interested in getting data engineering, you need to focus more on a general purpose language. This is why Java is one of the bigger languages here, because as I mentioned, data engineering is pulled away from somewhat of the analysis side. Yes, everyone doing analysis is using it, but it's being used by anything. Web-based companies with websites and sales and all that need data engineers. Big cloud companies need data engineers. Recommendation systems need data engineers. Data engineers have a more overarching job in the data industries. And you'll see a lot of things on here. For example, 2 of the top 4 are Spark and Hadoop. They use a lot more of the distributed computing that we've talked about previously, because again, it's useful for the kind of stuff that they're doing. And then following R, we've got Oracle, HBase, another databasing thing, Cassandra, so a bunch of database stuff here, Azure, MySQL, MapReduce, S3, which is part of AWS, EMR, and Git. So you'll see that a lot of their things they're looking for data engineer are database related, right? It's distributed computing and databasing. Looking at the technologies for job listings, okay, this one, SQL actually slightly eked out Python. Python is second, again, followed by Spark, and this one had AWS as number 4. One thing I want to point out is the technologies for data engineering from 2020, there is always going to be some variability to this based on the jobs that were posted at any given time, when this was scraped, source, stuff like that. So Python and SQL, though, regardless, they seem to be the 2 most commonly used ones. If you're really interested in getting data engineering, those are the 2 things you need to know very well, followed by some sort of distributed computing and cloud technology. So Spark, AWS, Hadoop, things like that. If you're interested in becoming a data engineer, the key skills and technologies you're going to want are going to be SQL and NoSQL databases. ETL tools, remember, extract, transform, load. I've mentioned it multiple times. There's a reason for that. Data warehousing solutions, Apache Hadoop or Spark, and then your programming languages. Python, and a fairly close second is going to be Java. R is not going to be the language of choice for you if you're interested in getting into data engineering. Now, your learning path is you want to have strong programming skills, particularly in the languages that are being used. That'd be Java, Python, or Scala. Then you want to learn about SQL and NoSQL databases. So you want to go beyond SQL. For most data analysts and data scientists, SQL is enough. For a data engineer, SQL is not enough. You have to expand into NoSQL and learn about schema and types of logic paths that are different than what's available in SQL. You also need to understand and learn ETL processes, and it's oftentimes required that you have some background in big data technologies, right? So you're going to have to pick up some cloud computing because that's really where your key skills come in, right? It's where you need to be able to work with the kind of data that companies need experts in. So some portfolio projects you might be looking at would be designing a data pipeline, creating a data warehouse, or implementing a real-time data processing system. These are things that can kind of show you have some strengths in what they're looking for. Of course, obviously, probably not the scale that you would have for the companies you end up working for, but it shows that you have those fundamental skills that you can then learn more as you get to these companies with more resources, data, things like that. So the next skill that next job I want to talk about is actuary. Now, this one might seem a little bit weird. I put this one in here because a lot of people who take statistics are interested in becoming actuaries, and they do have a lot of overlap with data jobs. Two of the common things people get into for statistics are actuarial science or becoming a quant for Wall Street. And there are a lot of advantages to becoming an actuary. In fact, I'm actually going to be teaching an actuarial mathematics course this upcoming semester because it's something that we're going to be allowing students to specialize in. So before I talk about what an actuary actually is, let me tell you why it has one of the highest job satisfactions in the world. It's because it's a fairly high paid job that has a lot of satisfaction involved in it, but it also has a very high floor of entry. And it's because to become an actuary, you have to pass a certain number of actuarial exams to be able to work in the industry. So one of the disadvantages of data science and data analysis is that anyone can become one, which is also an advantage depending on how you look at it. But if you are interested in becoming a data scientist, that means you are going to be competing with many people who are also interested in becoming data scientists. And you're going to have a variety of ways that people learn. Some people will be self-taught, some will have taken boot camps, some will have a degree. But regardless, that is a large pool of applicants that you have to compete with, meaning that this is why the portfolios are so important. How do you stand out by showing your skills when looking at CVs or resumes doesn't really give a whole picture, and a lot of them start to kind of look the same? How do you stand out? You do it by having really strong projects. But becoming an actuary, you have to have passed these exams, meaning that it doesn't matter if you know the topic inside and out. You know everything about actuarial math. If you don't have the exams done, you can't be an actuary. So for example, I will be teaching actuarial math this upcoming semester, and yet I can't be an actuary because I've never taken the exams. So this actually leads to a certain amount of job security because the industries where actuaries work have to have actuaries. This isn't we need people because we need to get the job done. This is a requirement. This is by law, they have to have these people doing this stuff. They have a certain floor to entry because of those exams, and it actually pays fairly well and has a lot of job satisfaction. Now, personally, I have no interest in being an actuary, but it is an amazing job that a lot of people never consider because honestly, it probably sounds pretty boring to most people. But if you look it up, you will see that it has one of the highest job satisfactions of any career that somebody could get. And it's safe from AI because, as I mentioned, by regulation, you can't just get rid of those jobs. So let's actually talk about what an actuary is. An actuary is a professional who uses mathematics, statistics, and probability to assess risk. They use their skills to calculate insurance premiums, determine the financial impact of risk, and develop risk management strategies. Actuaries typically have a bachelor's degree in actuarial science or related field, like statistics, and they must pass a series of exams to become a certified actuary. And whenever you talk about this stuff, there is, just like with data science, there's some overlap with data analysis. There are another position in these insurance companies, which is related but not quite the same, which are called underwriters. So oftentimes some of these tasks that you look at, for example, determining financial impact of risk, developing management strategies, you will be kind of setting the groundwork that these underwriters will then use in pricing premiums and things like that. So you work as part of a bigger team where you're creating the systems that they're going to be implementing. So you're Key skills in technology. You need to have strong mathematical and statistical skills, knowledge of calculus, probability, statistical theory, expertise in risk management, and proficiency with statistical software in things like R, SAS, or Excel. Your learning path, generally you want to have a degree in mathematics or statistics. Some places will have, like I said, a actuarial science degree itself, but oftentimes if they don't, you'll get a statistics or an economics degree. You'll need to gain knowledge in finance and economics and learn statistical software. Now this one, the projects are a little bit different because actuary, it could be helpful to have a project portfolio, but it's, again, you're passing the actuarial exams is your first hurdle. That is more important than these portfolio projects. But again, they still could be something that is useful to have because it gives you something to point to that you have some expertise that you've done, and also it gives you a talking point whenever you're asked about your skills and why they should hire you. So some examples of portfolios projects you might want to do are risk assessment models, financial forecasting, or pension planning. These are all things that could kind of show you have some of the skills needed by actuaries. Next, we're going to move into statistician. That's what I am. So a statistician is a professional who collects, analyzes, and interprets data. They use their skills to find patterns and trends in data and to make predictions based on their findings. Statisticians typically have a background in statistics, mathematics, or computer science. They use a variety of tools and technologies to analyze data, including statistical software, data visualization tools, and programming languages. Now, the thing I will mention about a statistician, because this is actually what I do, so I have some input on it, is what you end up doing kind of depends on what kind of statistician you are. In fact, statistics oftentimes will branch into specializations. For example, you have biostatisticians, or for example, in medical schools, oftentimes you'll have bioinformatics, which is closely related, even though it's separated enough that they've dropped the statistics part. There's actually a saying that I love in statistics, which is the beauty of statistics is that you get to play in everybody else's backyard. And that's true. Statistics does all the things. You can do analysis. You can do data science. You could be part of a team that is helping do some of the data pipeline. Probably not to the extent of a data engineer, but for a small research team, sometimes your skills in that will be helpful. You can do machine learning. You can do AI. We do a little bit of all of these things because our main thing is that underlying statistical foundation. And this is where, if you decide to become a statistician, your strengths kind of lie. I am not as good of a programmer as a data scientist generally is. I'm not as strong of a programmer as somebody who came up through computer science, things like that. But I can program fairly well. And that allows me to work with people in different departments: behavioral health, communication sciences, social work, psychiatry. And I've done this because the thing is, as a statistician, we oftentimes have a lot of tools and other people have some really interesting problems. So rather than focusing on always working with who most statisticians do, engineers, medical, things like that, I decided to branch out into more of the social sciences because, again, they have some really interesting problems and I have these tools that can help them do better analysis while solving these real world and very interesting problems. So of course, your skills and technologies. First, a deep understanding of statistical theory and methods. As a statistician, we're theory first, then followed by application. This is why we teach this course in applied methods for computational statistics, is because oftentimes most stats programs are very theory heavy. We learn the theory, we learn how to calculate, we learn about distributions, and now we have to make that transition into actually implementing it using technology. You want to have proficiency in statistical software like R, SAS, or SPSS, and knowledge of programming languages like Python. And usually we will use a little bit of all of these things. For example, I use R, but I also use Python. When I need to do certain deep learning type things, I will fall to Python. Can R do it? Yes, but there's some things where just Python is more robust in. So learning path, if you want to get into statistics, is you need to get a degree in statistics or mathematics typically. You can do statistical work. It's not saying you can't, but to be an actual statistician, you do have to get a degree, generally actually a higher degree. You'll want to learn statistical software, and of course you'll have to learn programming languages like Python or R. And again, R is our kind of go-to as statisticians. It's built more like the mathematics that we use, so therefore a lot of us err that direction. But there's literally no reason you wouldn't pick Python over R or vice versa. They're honestly, at that level, they're kind of comparable. So some portfolio projects you might want to use are designing and analyzing a survey, right? Survey design is big in statistics, performing an experimental analysis, or predictive modeling. And honestly, any of the portfolio projects from the other parts would be useful for any of these. They're not saying these are the only things you can do. Though some of the portfolio projects like risk analysis that you do for actuary can still be useful as a data scientist, can still be useful as a statistician. And then finally, I added software developer in here. This one might seem a little weird, and it's because oftentimes when you're working in data, you're working as part of a bigger team. So a software developer is not someone who necessarily works in data. They could be doing anything. They could be programming websites, they could be building apps, games, or doing a data analysis. That software developer is such an expansive field that I added it because it can end up doing this. In fact, a lot of people who fall into this, that is how they get there. They are a software developer, and then they join a company who's working on this project, and as they're doing it, they're starting to pick up more of the skills that they need to be able to do this. They might not be doing the specific analysis, but they might be helping build out the pipeline. They might be building the systems that the people are using. They might do some of the analysis depending on the type of company it is. If you're a small startup, you oftentimes have to wear many hats. So a software developer is a professional who designs, develops, and tests software applications. They use their skills to create software that meets the needs of the users. Software developers typically have a background in computer science, engineering, or information technology. They use a variety of tools and technologies to develop software, including programming language, software development methodologies, and version control systems. This sounds generic because it kind of is. You can be a software developer that does game programming. You could be a software developer that's creating real estate websites. So it's not as focused as some of the other jobs, but again, it can completely overlap with them, which is why I included it. So the key skills you're going to need is proficiency in one or more programming languages. Now, depending on which tasks you're going to be doing, this may be things like Java, C++, Python, or JavaScript. Understanding of data structures and algorithms, this becomes a lot more important. Now, these are things that data scientists, data analysts, statisticians should all understand as well. But as a software developer or programmer, this could be even more important. In fact, most software developer jobs, you're going to have these sort of leak code problems where they're going to say things like, use this sort of sorting algorithm to do this, or explaining different sorting algorithms, or, what is bubble sort, or random things like that. They're going to test you on these things. Even if you're not necessarily doing it in your day-to-day tasks, you still have to have a strong understanding of it. You're going to want to have knowledge in web development toolkits or technologies for web developers, and familiarity with version control with systems like Git. In fact, a lot of software development positions, they will specifically ask you for your GitHub or whatever version control system you use, and they're going to be gauging a lot of it based on that. So to become a software developer, first you want to begin with programming languages, things like Python, Java, C++, depending on what type of developer you want to be generally. Then you want to learn about data structures, algorithms, and of course, optionally, depending on what you want to do, maybe web technologies, things like HTML, CSS, JavaScript, any of those kind of web-based focused things. And then you want to, of course, familiarize yourself with version control systems like Git. In fact, it's going to be even more important than the others because the other positions, you need to use these things, right? Data scientists, they're going to ask you to see your portfolio. They're going to want a GitHub profile. But as a software developer, they're going to have a higher bar where they're going to expect more from you. They're going to expect you to have a much better understanding of the actual underlying technologies that, again, data scientists have to know so many things that they're expected to know fairly well, but a software developer, oftentimes when it comes to the actual technology, you're going to have to know it even better. So some portfolio projects you might have, developing a web or mobile application, creating a game, building an API. Again, it kind of depends on what you get into and what sort of programming or software development you're interested in. So let's talk a little bit about similarities and differences. Now you might notice all of these roles deal with data, but they deal with it in different ways and to different extents. Data analysts, data scientists, and actuaries often work on the analysis side of data, while engineers will focus on the infrastructure side. Statisticians will emphasize the theoretical aspects of data analysis, while software developers may not work directly with data analysis, but they often need to understand and use data and algorithms in their work. Data analysts, data scientists, data engineers, actuaries, statisticians, and software developers all use data to solve problems and make predictions. They just do it for different types of problems and for different reasons. Now, there are different roles and responsibilities. Data analysts typically focus on collecting, cleaning, and analyzing. Data scientists focus on building and training machine learning models. Data engineers typically focus on building and maintaining infrastructure to store and process data. Actuaries typically focus on assessing risk, which means they're only using a certain aspect of the data. Statisticians typically focus on finding patterns and trends. And software developers typically focus on designing, developing, and testing software applications. So again, they all overlap together. And depending on what company you're working for, you may have a singular focus or you may be wearing many hats. If you end up getting a job at some small startup, you may be their software developer, their data scientist, and their analyst at the same time. So looking at the slide here, you can see this sort of table that I created or that was created. So you have data analysts, again, talks about their similarities, but also difference, right? May not have the skills or experience to build machine learning models. Data scientists may not have the skills or experience to design and build data infrastructure. Data engineer may not have the skills or experience to collect, clean, and analyze data. Actuaries may not have the skills or experience to build machine learning models, design, or build the infrastructure, right? Because again, they're very specialized in their focus. Statistician may not have skills or experience to build machine learning models or design or build data infrastructure. And software developers may not have the skills in any of these things, or might have skills in any of them or all of them. And again, this is why all of them start with may not, because I'm a statistician and I definitely can build and train machine learning models. I can build them from scratch. I can implement all sorts of things with them. But building data infrastructure is one of my weaknesses. I have been practicing it to some degree, but it's not my expertise. There are other statisticians who barely know how to program. They barely touch a computer. So that's why all of these are may not. I do a lot of research. Again, my focus is machine learning and statistical learning, but I do a lot of research with AI systems, which means I am more on the computational applied side of statistics, but some statisticians aren't. You might have a statistician where they use SAS and they just do their analysis. They work with medical, they do analysis with them, and that's all they need, right? So don't take any of these may not have these skills to mean that if you become a data analyst, you can't do this. You can, because a lot of them are going to have some overlap where if you're interested in being a data scientist, there's nothing stopping you from being able to get a data analyst position. Similarly, if you're a data analyst, there's a lot of data science jobs that you could probably get. Again, data engineer typically is different enough that most people don't, just fall into it. But there are some times where you will, depending on what skills you have and how much overlap there is, and how much you go above and beyond what the skills expectations are. So I just want to give you a brief overview of these different careers that you might be able to pursue using the stuff we're going to be learning in this class. And a lot of it's going to be focused on what you're interested in doing. And from that, you're going to be doing some, hopefully this class will be a good springboard to help you jump into that next level, right? We're not going to talk about version control, but you'll notice it's pretty important for any of them. So once you have this stronger basis in programming, analysis, algorithms, stuff like that, hopefully you can use that, start learning about version control, and then start creating your portfolio. So a couple things I would focus on for professional resources. First, project-based learning. The most effective way to master R, Python, or SQL is to build something. Following tutorials is fine. Reading on things is fine. But you are not going to actually learn until you start building something. That's where you're going to start stretching your skills. That's where you're going to run into roadblocks, and you're going to have to go seek out how to fix it, how to change it, what do I need to do to implement this. You want to focus on end-to-end projects. That is from raw data ingestion all the way to cleaning and your final report. Try to think of it like you're creating a project where you're a one-man show where you need to go from all the way to starting with getting the data all the way to then presenting it to somebody, in this case, possibly somebody looking to hire an employee. You want to use a personal GitHub repository to showcase your work as a living portfolio for potential employees. Next, I would focus on documentation over tutorials. While video tutorials are a good starting point, you want to prioritize official documentation, things like R, the CRAN, so Comprehensive R Archive Network, Python, you got PI, PL letters, and Quarto. These are all things that can be really useful resources. Focus on the documentation over the quick tutorial, because a lot of times tutorials will make you feel like you're learning, but you're not actually learning. Project-based learning, dive into the documentation. Learning to read technical documentation is a vital professional skill that will outlast any specific version. And the reason this is so important is because where others tend to struggle is when you get to that next level, that edge, Right now, you might have somebody who's an expert at creating websites using HTML, but then CSS comes out. And now they have to learn this. Well, what do you do when there's not a ton of tutorials that are out for it? Which, by the way, this is an example that was, a long time ago. But what's the next thing? A new language comes out. You're interested in doing it. Well, guess what? You're going to have to dive into official documentation. You're not going to have the resources like you do for a tried and true language like Python if you're trying to get into those edge cases, right? The first people to jump on and start doing generative AI didn't have a roadmap and a framework to work with. So this is where understanding how to use official documentation is so important. Next, you want to be able to use community knowledge. Utilize things like Stack Overflow and GitHub issues to find solutions for community-identified bugs, implementation errors, stuff like that. Like I said, if you're going to use Stack Overflow, it's great as a resource, as a passive user. If you're going to go in and ask actual questions, either do your homework or have a really thick skin because it can sometimes be a little toxic. Use things like Perplexity and Google Search for real-time technical news and fact-check citations. This one's big, right? Remember, always double-check everything. Don't trust it. Even Googling stuff, make sure it's coming from a reputable source. If you're using code stuff, try it out, try to understand it, things like that. If you're looking at looking into the research from like cutting-edge stuff, you have things like Archive and Research Journal, which yes, that R is if that's a chi, so it's archive. And research journals. This is a good way to stay up to date on these new statistical methodologies or even technologies that are kind of cutting edge. And this is something I keep up with quite a bit. I'm always keeping up with the newest things coming out, dealing with generative AI, new methods to implement, do this, help with memory, help with stuff like that. And then, of course, another one, this is a newer one, which is AI augmented research. You can leverage large language models and agents like Claude, Cursor, and ChatGPT to explain complex error logs, refactor code for efficiency, and brainstorm alternative statistical approaches. So this might be something like if you run into an issue with your code and you get an error, guess what? You could copy that into Claude or Gemini or ChatGPT, and oftentimes it will be able to help pinpoint what the error is. It's not always going to give you the right solution. Sometimes you're going to have to do it, iterate multiple times, stuff like that. But a lot of times it can help because otherwise, what are you going to do? Well, oftentimes what we would do is we would copy the error code, we would put it into Google, we would find a Stack Overflow question about it, try to find one that's kind of like what we're doing, and then, error correct from there. This just kind of knocks out a little bit of that legroom. But again, as I mentioned before, if you're using AI systems, don't let them do the thinking, but use it like a tool like anything else, right? If you could find the answer on Stack Overflow, you can kind of think of it the same way. But again, verify everything. Next, last part, just like I said, verify everything. Do not let AI systems do the thinking for you. Hello, everyone. In this lesson, we're actually going to begin by diving into R and introducing R, how to install it, how to grab it, RStudio, and then how to look up help and some basic functionality about it. So first things first, let's look at how we're going to get R. So if you go to our first slide, you can see here that we can get R at www.r-project.org. Or you could just try, Googling it. For example, if I go into Google here, I can just type download R, and you can see here that it will pull up either r-project.org like I did, like I said, or you can go to download Windows, which of course I have, but you could also go back if you wanted to get for other versions. So I'm going to go back and I'm going to go to the main R page. And you'll see that there's a bunch of stuff here. It's pretty bare bones, but at the top, getting started, you can get R here. Just go to download R, and you're going to see that there's a ton of different places where you can do this because open source, so it's sourced all over the place. So just find the closest place to you. For example, I'm in the United States, so I'm going to just pick one of these. I'll pick, let's do Indiana University. I'll click on here, and then it's going to bring you to a different download page. And at the top, you can see that you can download R for Linux, for example, Debian, Fedora/Red Hat, or Ubuntu. If you're a Linux user, you could also probably use like a git command, things like that. You can just Google how to get it. For example, Linux git R, and someone probably has, or AI could tell you exactly how to do it. For example, here you can just put install r-base, and it can do it automatically for you. If you're a Mac user, you would just go to download R for Mac OS. And if you are a Windows user like myself, you would click on download R for Windows. Now you're gonna see a couple options here. What you probably want to do is click on this install R for the first time. This will bring you to installing R from scratch. It will also have a README that you can follow, things like that. If you want more functionality, we can do it within R in RStudio, or you can download some of the stuff that's here. So I'm going to click on download R for Windows, and then I'm going to let it install or download. Now, one thing I want to point out is I already have R on this. So I'm going to go through the steps and then I'll show you what you need to do. Now, the reason I haven't talked about RStudio yet is you need to get this stage completed before you worry about RStudio. Because if you run RStudio before you have R actually installed and run, it's not going to be able to find your version of R you have. Okay. And of course, if you ever want to update R, you just follow the same steps. And then in RStudio, you can change which version you're using. So I'm going to go to my downloads, I'm going to click it, and then I should get a pop-up for installing it. So I'm going to tell it that yes, I want to give a control. I'm doing it in English. I'm going to agree to its EULA, and then of course you select where the file is going to go. I would highly suggest you keep track of where this is installing, right? So if you're on Linux or Mac OS, it's going to be /home, somewhere like that. Windows, the default is // program files /r / and then whatever version of R you're downloading. So I'll hit next. And then of course, just leave this. You want to download all these, and then I'm just going to leave it as defaults. And this will be what is called in your start menu if you're on Windows. It might be a good idea to change this, and I'll show you in a minute why, because it's kind of a pain to figure out where this is, but we'll hit next. And then do we want to create a desktop shortcut? I'm going to say no. And I'm going to leave it where save version number in registry, associate R with .r data files, and then I'm not going to do a quick launch icon. Okay, so then I just install R, and once this is done installing, we actually need to run it before we start RStudio. Okay, the install for R 4.6.0 is complete. I hit finish. Now here's why I told you to kind of keep track of where the file is actually located. Because one of the issues with R is that R comes up in so many things. For example, let's say that I wanted to Google R and I wanted to do analysis using MARS, which is multivariate adaptive regression splines. If I do R MARS, what's going to happen is I'm going to get a subreddit specifically for MARS because Reddit uses /r for their subreddits, and of course MARS being a package here. Now you can see that this is there is a Mars package that shows up for our project underneath, and then underneath that, Mars Society, you got Wikipedia Mars, NASA. So most of the stuff that's going to come up is not R related. There was one, and this one is mostly because it knows that I'm an R user, so it's going to give me that as a priority for my searches. So what you could do, if you want to make sure, this is usually what I do when I'm trying to look up a specific package, is I would do RStudio Mars, and that way it kind of tells Google that I'm not looking at subreddits and things like that. It's not Mars, the planet I'm interested in, it's the analysis method, right? And so we have here Mars multivariate adaptive regression splines, and this is, I believe, the one I want. Oh no, this is the one I want right here. Earth multivariate adaptive regression splines from CRAN. And we'll talk more about getting packages and stuff like that later, but this is the one that I would use in order to do Mars. The reason I wanted to bring this up is because when you go to install R, or rather to run R the first time, if you try to go into like your search bar and type R, it's not going to pull up R, right? It's going to pull up RStudio, again, because I already have it installed. It's going to pull up things that start with R, Remote Desktop, RetroArch, Razor Synapse, DaVinci Resolve. It's going to give me some options possibly at the store, some web searches that it thinks I might want, like RuneLite and RuneScape for some reason, even though I've never played those. You could go into your start menu, and if you look at all the programs that are pinned, I don't have it there because once you set up RStudio, you're never really going to use R. This recommendation does have R because I just installed it, but normally that would not show up here either. I can go down here though, and it is in my developer tools. So like I said, what I would suggest you do though is remember where it's located and then just go to that file. So for example, mine is in C. Program files, I'll scroll down to R, and then I had R 4.5.1 before this. I just downloaded R 4.6.0, and then I need to go to bin. This is where you're going to find the r.exe file. So you're going to run this, and this is what R looks like, which they have changed it recently because used to be it would be light mode. Apparently it starts in dark mode. And from here, I can actually use R. For example, if I wanted to run mtcars, it's right there. It's already ready to go. This is R. But the problem with this is that the functionality is not really what we're looking for. So this is where we're going to now install RStudio. So as before, if you go to posit.co, this is where you can find RStudio, or you can just Google RStudio. And then of course, this will bring you to Posit. And this is not the homepage for Posit. If you were to click on that, it would go to the generic page for Posit, which has RStudio, but it also has a link here for downloading Positron. But we want to specifically download RStudio. So what we're going to do is we're going to go RStudio Desktop, and then it first tells you, install R. You need to have at least a version of R that's greater than 3.6.0, which if you're downloading it now, it definitely will be. And then you want to download the RStudio Desktop for Windows. Now this will take a little while. Same process though, it'll download, you'll run it, you'll go through the options, things like that. So now let's talk about, now RStudio is a little bit easier because when you go to my search menu, I can just put RStudio and it will actually find it because it's a name that's more specific than just R. Let's talk about what RStudio looks like. So I already have RStudio up. When you first open up RStudio, this is what you're going to see. So the first thing I would do is up here, just click on this little sub window here, and it will expand it to the view that you're actually going to be using. So let's talk about what we actually see in RStudio. So this is where we can actually type in our code if we want to save it. Like if we're trying to create a script or a program. For example, if I wanted to say, I'm going to label X as 1, 2, 3, and when I hit enter, nothing happens, okay? So all this did is I put this here, it's saved here, but it hasn't done anything. I haven't run anything. Down here at the bottom left, this is the console. Now, if I did the same thing in the console, let's say this one I'm gonna label Y as 2, 4, 6. If I hit enter here, it will actually run this command. Okay, so it says graphics interversions is not supported in this studio. That's fine, I'm not trying to use graphics. So if I run Y, it's gonna give me back the numbers 2, 4, 6. So this console window, if you type something in, just runs the command. At the top, this is going to show you, so you got your environment, history, connections, and tutorial. So if you go to history, this is going to be the history of the commands that you've run. Notice I did not run that X labeling earlier. All I did is I set it up here. This is where, again, you would actually write out fully fleshed out functions, programs, things like that. In your environment, this is going to show you what you currently have loaded in the system. So I don't have to reference and say, go and run this and grab it. It has Y automatically in the system. So if I were to go back down to my console, type Y, hit enter, you'll see that it just runs it because it's in the memory. Connections, this one we can talk more about later. This would be, for example, if you're using something like Shiny apps or things like that and you're connecting to some other service, this would be where you can have things like that, and then you can push your code actually to whatever service you're using. And then of course you have tutorial, which is a way that you can kind of get used to using R in the R environment by giving you some practice to work through. So generally I leave environment open just so I can see what I have available. Then at the bottom left or bottom right, you're gonna see plots. Anytime you create a plot, whether in generic R, ggplot2, anything like that, this is where it's gonna show. And once you have that plot, if you want to do anything with it, for example, you want to put it in a paper or anything like that, you can go to export, and then you can save as image, save as PDF, or copy to clipboard. I will warn you, I've never really had good luck with the copy to clipboard. It usually gives weird borders. It just never seems to work right. So I usually will save as an image, and we'll talk more about that when we get into the graphical implementation in R. So next we have files. This would be if you wanted to grab files. I'm going to always pretty much be grabbing files using command line. The reason is I find this to be better for when you are sharing code or coming back to code, because then it's within the code. So I'm not having to remember, wait, I went in and I had to, grab this and this and this, right? So if you could just, click on something here. So for example, let's say I wanted to load up Baldur's Gate Enhanced Edition. I could just click check there and it loads it up, but I'm not gonna do that. Like I said, I'll use command line for everything. Next, we have packages. Like I mentioned, R has many thousands, tens of thousands of packages that you can use, which add to the functionality of the base program. So this will show the packages that you currently have installed, and then the ones with the check marks are the ones that you currently have loaded. So for example, by default, I have base loaded, I have datasets loaded, and I have some other ones, graphics, GR devices, things like that. If I wanted to, for example, load up mass, which again, I will be doing this in command line for the entire course, but I could just click on this and you'll see at the bottom left that it ran the command, see, right? It runs the command line for me to load up mass. And if I uncheck it, you'll see that it's going to detach it from R, meaning it's no longer available unless I reload it. Next, we have help, which we will talk about in this lesson a little bit. But there's a lot of functionality here. It's actually really great. For example, if you wanted to learn R online, you could just click this and it will take you to Posit's website where they have a bunch of information for beginners, for teachers, for learners, things like that. You could also go to CRAN Task View. You could look at R on Stack Overflow. Like I mentioned, it's integrated in with the programmer environment. It's still pretty deeply embedded. You can look at getting help with R. You've got some specific RStudio things. And then we've got manuals here, and these are vitally important. Remember I mentioned previously about the different manuals that I would look at and things like that. One of them is this right here, an introduction to R. And you can actually pull this up on your browser, for example, so it's a little bit easier to read, but it's got a ton of information. You can see that it's got this table of contents. You can click on any of these. So for example, if I wanted to look at objects, their modes and attributes, I just click on this. And it gives me all sorts of information about this. It gives me examples. It gives all sorts of stuff. It gives links to other places. So this is actually a very useful resource to use. And then finally, for my students, you actually don't need to install R on your computer at all. I would suggest using R on your computer because you'll have more control, because on the school system, you're going to have some limitations because you don't have super user access like you would on your own computer. Also, you have to change the method you use to download files, where you place them, because the way the system works is that you will be on a virtual machine on a server that the school controls. Meaning that if you have a file on your computer, you can't do like you normally would and say, okay, go to program files, download whatever downloads, grab this file. You would have to actually put it onto your user files on the server. Then from there, you would have to go to it. And you also have to change how you actually run the command because instead of using single slashes, you use double slashes. And we'll talk more about that when we talk about uploading data into R. Okay, but let me show you exactly how you would do that. So if I go back to my web browser, I'm just gonna go to our main school site. Okay, go to Learning and Teaching Tools, and you can click on Application Gateway. This will take you to the application gateway where you as students have access to a ton of resources through the university. So I'm going to sign in real quick. This does take a little bit to load. So, okay, not now. And now this is going to pull up a ton of programs that you as students would have access to. So you can see you got HP Calculator, you got eDraw, you got Blender, almost anything and everything you could want, right? For example, if you want to do Python, we got Python here. We have VS Code further down, but what we're looking for is RStudio. So you'll click on that and it's going to open a new window. Now this part will take a little bit to load. You'll say connect, and then it's going to go full screen, and it wants me to sign in, which I can't do right now because I'm on my phone. I need my phone for that, and I'm recording on my phone currently. Actually, it looks like it might let me sign in. I thought it was going to make me do two-factor authentication. So like I said, it's going to take a little bit to load. It's kind of slow, but it runs perfectly fine when you're actually using it. It's just that initial starting up of the instance for the virtual machine. And now we wait. We wait for it to load. Okay, and now what it's going to do is it's going to pop up. It's going to say, I'm going to say use 64-bit version, hit OK, and you're going to see that it's going to load up the exact same view that we had on RStudio. I'm just going to make this bigger. Same thing as before. Remind me later. Say no to this. Okay, and just like before, it's going to give me that initial view that we had, and I'm just going to click on this, and guess what? You are in R on the computer. Just like before, I could do X. I can label it. I'm going to do 1, 2, 3, 4, and of course, I'm going to hit Control Enter to actually run this. you'll see that it goes to the bottom left console and it ran it. But notice it didn't show anything, right? Well, now if I just want to type X, I can run this and it shows, just like we did when we were using it on our actual computer. So this is a resource, again, that our students have available. Students at other universities might have something similar, but through a different system, things like that. So this is why I was kind of saying when I did my syllabus video that you all don't have to download R or RStudio. If you don't want to, you can do everything for the course through this. If when you're taking the exam on the computer, if you use the computer lab computers, this is how you would do it. You're going to do it through the application gateway. Otherwise, if you just bring your laptop, you'll be good to go. You can use whatever your operating system of choice is, Linux, Mac, Windows, whatever you want. Okay, so I already kind of covered this, but to get started, first thing you do is you're going to run R. So as I said, this is what R looked like previously. It would pop up this light mode version of the basic command line interface. And like I said, you can run R right from there. Some people do, but most don't. Generally, we like to use an integrated development environment because it makes what we're doing a lot easier. It allows us to keep track of variables. It allows us to have a place to run commands, but also to keep commands. It allows us to use a graphical interface. Even though I don't use that very much, I still like having some of the functionality that comes with having an integrated development environment. R is an integrated suite of software facilities for data manipulation, calculation, and graphical display. So as I mentioned previously, this is one of the things that R has that's different from some other programming languages like Python. R has all of this kind of built in. The packages will expand what it can do. But for example, if I wanted to do some basic calculations, like just say I wanted to do x plus 4, I'll put a space just to make it look nicer. What it did is it added 4 to each of those values that were in x. It has this functionality. If I wanted to plot x, it's not a very beautiful plot, but you can see here that it pulled up the plot, just like I said, and it has this base functionality. I don't have to call in a graphical library or anything like that. It just has this functionality. Now, again, it is limited. If you want to do more advanced things, you will have to pull up other packages, install them, load them, things like that. And we'll talk more about that throughout the course. Among other things, it has an effective data handling and storage facility. It has a suite of operators, integrated collection of intermediate tools for analysis. It has graphical facilities for data analysis. And we developed simple and effective programming languages. So for example, R is actually based on a simpler language called S. So S was originally created and R was built on top of it in order to use the base functionality of S, but adding those functions I talked about. The graphical things, the basic operators, all that stuff is included in base R, which is sort of an extension. So R is really just sort of S, but then built out further, so it's a bigger system. So we'll have things like conditionals, loops, and then of course recursive functions and input and output facilities. So again, this is where the base R is actually really useful, because if you just need to do a really quick analysis, a lot of times it's already there. For example, if I just want to know what the mean of these values are, I can quickly just type mean x, run it within base R, and I've got the mean. I don't have to download a package. I don't have to get anything like that. If I just want to know what the mode is, mode of x, it's okay, so many numeric, it's fine. If I want to know what the median is, median of x, 2.5, and again, this is all built into base R. No packages needed, no downloads needed, so just quick dirty analysis, base R works just fine a lot of the times. Okay, so now we talked about the fact that we're going to be using RStudio, which is an integrated development environment. So there's a software application that provides comprehensive facilities for development. This thing has things such as a source code editor. It's got building automation tools. It's got a debugger. It's got information panel. It's got variable browser, and it has other things. So one of the stuff I didn't kind of show you is at the bottom here, we have console. There's also terminal if you need to run certain commands, specifically on the computer. For example, if you wanted to change your R environment, things like that. You've also got background jobs. You can see things that are going on in the background, stuff like that. For most general cases, you won't need these. When I started working in Shiny apps and was pushing programs to Shiny apps, I started having to use these more often when I was debugging, but for most general analysis, you don't really need these that often. Okay, so now in R, you're gonna see this little sideways caret. This is what's called a prompt. This is where you're gonna put commands into R to run them. Okay, and then below this in the console window is where the output of those commands will run. And if the command is too long to fit, you can use a plus for continuing a prompt. So going back to RStudio, specifically down here at the bottom left, you see our console window, you see this little caret. This is the prompt. It's saying, okay, this is where this console window represents just base R, what you're actually seeing when you pull up R without any sort of integrated development environment. When I am here, what I can do, like I said, just like before, I put it into the source window and I actually ran it from there, but you could type it directly in here. So I could do mean of X, and you'll see that it does have autocomplete functionality. So if I hit, so again, I only have to hit enter, one hand, hit enter, and it's going to run it. Directly below that prompt where I put my command, it will give me the output for it. If there's multiple lines, it will give it to me there. An example of this might be, let's say I wanted to do a linear model of MT cars where miles per gallon is modeled by everything else. Hit enter. Oops, what am I missing? Okay. Data equals MT cars. Try that. And you'll see that my output for this gives me multiple lines. This is my output from running this. The thing is, though, is when I close R, this all goes away that's in the console. But this up here at the source editor, this will stay. So if I save this, you'll see right now I have it as untitled. So you can hit Control S and you can save your script, whatever you'd like to call it, and that way you can pull it up. So now going back to our R that we have on the computer, everything is exactly the same that I was just explaining. But the reason I wanted to show you this is because you'll notice up here, untitled 1. This is the script name that I'm working in. So if I wanted to save this, I could just go up here to File. I could do things like save, save as, save with encoding, all that kind of stuff. If I hit Control S, it'll save. And then what I can do is I can actually save this wherever I want to. So what I'm going to do is I'm going to go into C. I'm going to go into a folder that I have. We'll just do temp. This is where my video editing stuff is. And I'll just label this as basic R code. And then you'll see that it changes the script name here. And that way, when I close this, this will be saved. This will not. So when I start back up, this is going to be blank. And I got rid of that, by the way, by hitting Control L. When you close R, or RStudio, it's going to ask you if you want to save everything. It's not talking about this. This will be saved, but you have to still actually save it. So if you run it, it'll have everything there. What it's talking about is your entire environment, meaning that when you close out R, if you hit save, it's going to save any environmental variables that you have in R. So let me just run this X real quick, and you'll see that I have these two variables. If I close it and save it, when I open RStudio back up, it will be on this script that I have here. It will have these variables set, and it will have any packages that I have loaded in also automatically loaded. So I don't have to reset up everything each time I want to. Okay, so now let's talk about getting help. When you're working in R, a lot of times you're going to want to get help. Now, of course, generally you can just Google it. This is the most simple way, but you could also use the help command. For example, we have here help and then in parentheses solve. So by the way, anything with these parentheses, this is called a function. So if I wanted to use the help function, for example, I do help, and if I just do open parentheses, close parentheses, if I run this, what's going to happen is it's going to pull up basic documentation. But if I put a particular function in there, for example, like the slide has, solve, what it's going to do is it is going to pull up the documentation page for solve. And I will go more into detail on this later, but basically it's going to be the same format for any package that you're looking at or any function. So what it's going to do is it's going to give you a very brief description of what it is. It's going to show you how it's used. So in this case, it's solve A, comma, B, comma, dot, dot, dot. And it'll give you kind of an example of what this might look like at the end. And then it's going to tell you what each of these are. A is a square, numeric, or complex matrix containing the coefficients of the linear system. Logical matrices are coerced to numeric. So that means that if I use solve and I have logical matrices, they will be converted into numeric matrices. B, it's also a numeric or complex vector, blah, blah, blah. Tolerance is detecting for detecting linear dependencies in a column on A. You have other things like this. And then of course, there's more information, details here. You got source. If you click on this, this will take you to the actual documentation page online for this. And also you got references. This has to do with who created it, things like that, where it came from. And like I said, it has examples. So here, for example, if we were to just, copy this and run it. And then you can see it in action. So a lot of times this can be really helpful because this will help you kind of figure out what you can just change on it. So actually I'm going to show you an example of this, because another way that we can get help is you can put a question mark before a function. So what I'm going to do is I'm going to do question mark and I'm going to do rnorm. And then this is going to pull up the help for the D, P, Q, and R norm functions. So you'll notice rnorm, it's rnorm parentheses n mean equals 0, SD equals 1. And I'll talk more about what this all means later, because these actually have specific meanings in their placement and also their default values. So then I can look here and say, okay, n is the number of observations. Mean, this would be the mean that I want for my data. SD would be the standard deviation. And so what this function does is it actually is going to pull from a normal distribution with the mean and standard deviation that I set, and it'll randomly generate n number of those values. So then trying that out, we would do rnorm. Let's say we want to get 5 values. We want a mean of, let's say, 22, and we want a standard deviation of, let's say, 3. So if I run this, go down to my console, you'll see that I got 5 numbers which were randomly generated from a normal distribution with a mean of 22 and a standard deviation of 3. And I could figure this out by going to the documentation. Sometimes you might have to put quotes within help if it's something where it really, basically if it's something that conflicts with like the naming convention. So for example, if I did help square bracket, oops, can't spell, parentheses, square bracket. If I were to run this, notice it says unexpected square brackets in help. Because what it's trying to do is it's trying to figure out what it is that I'm trying to help on, and it's looking for, oh wait, I don't want these. Anyway, same outcome though. But what happens now is if I were to select these, put it in quotes, now when I run this, it understands that I'm looking for help specifically on the square bracket, not trying to use square brackets within my help function, right? And this will make more sense when we start getting into using different things to grab subsets of data, stuff like that. We'll do square brackets and all that kind of stuff. You can also use help.start, and this will give you a place where, again, like before, where it has a lot of stuff about basic R functionality, right? You got your introduction to R, writing R extensions, things like that, references, and this is just a place where you can get general help instead of help for a specific function or thing about R. You can also use double question mark. So for example, here we have double question mark solve. And if we run this, what it's going to do is it's going to pull up anything in the R documentation that has solve in it. So this is a search function. So if we look, for example, these are all help pages that have solve as part of the description. Doesn't mean that they're all necessarily related to solve. It could be, for example, like when we did that solve example, it used function. And therefore, we weren't, it wasn't about a function, though. It was just using it in the example, stuff like that. So this is just searching. It's doing a search on anything and everything that has solve. For example, if I wanted to use the mass package and look up cement, then this has solve in it somewhere. And then the next thing is that you could do example and then topic. So let's, keeping it on theme of solve, let's do example solve. And if we run this, what it's going to do in your console window is you're going to see that it's giving me an example just like we did when we copied it over from the help file. It gave me a function called Hilbert, and then it got some data from that. And then from there, what it did is it did a solve function just like we were looking at. So this would be an example of that. Another one, let's say I want to do example rnorm. I don't know why it was doing this. Oh, okay, it's giving me an example with graphs and stuff. I don't know why it popped up the graph though. But again, you can go through the console window and you can see what it did and the outcome, output and all that kind of stuff. Okay, so these are some useful commands to keep track of. The most common one that I would use, I actually use all the time still, is the question mark solve. Generally, that's what you need most of the time. You just want to do a quick search. And it's mostly because, like I mentioned previously, when we're looking at something like rnorm, it's going to tell me the placement of the different variables and also any defaults. This is why oftentimes I'll look it up. Not because I don't know how to use the command, just sometimes I'll need to double check. Is mean first or standard deviation, or is it standard deviation then mean, stuff like that. The help function or question operator in R for documentation, datasets, and other objects can look up standard packages. It can also be used for contributed packages, though a lot of times those contributed packages do have to be installed on R and sometimes have to actually be loaded into R. Okay? So to access help for a function from a package, let's say you wanted to get help on something from the mass package, then what you would do is you would do help, the parentheses, then you would put what it is you want help on. In this case, RLM, and then comma, package equals, and then in quotes, put the actual package name. Now these package names are case sensitive. So let's do that and see what it looks like. So if I were to just do help RLM, notice what's going to happen. It says no documentation for RLM. So then what I'm going to do is I'm going to put, you'll see that it's package. This will matter later because whenever we're installing, we need to install .packages. Just want to clarify. So we want to do package equals parentheses, and then mass is all caps. Now what it's going to do is I've told R, I want help on this specific function from this specific package. As I mentioned kind of in my previous videos, this is where one of R's possible weaknesses comes from, is that if I have a ton of packages loaded, you might have another package that has RLM as a function in it. So you can either specify which one it's using, you can unload one of the packages, or you just run it and you're not going to be sure which one it's pulling from. And again, same thing here. If I wanted to do help for RLM and I have multiple packages with it, I can now specify which package specifically do I want to know about that function. There is no need for quotes for standard names, including uppercase and lowercase letters. So what you can include are uppercase and lowercase letters, numeric values 0 to 9, underscores, and periods. And as I said, non-standard names will need to be within quotes, right? So as I talked about, if I tried to do something like, I want to get help on help, if I do question mark, it's not going to work. See, it's going to say, okay, what is it you need help with? It did this plus here in my console, which, by the way, remember I mentioned this plus means I'm continuing the command. If you want to get out of this, you just hit escape and it goes away. To specify that I want help with question mark, which is help, I'm going to put my quotes. And now when I run it, it knows, oh, okay, you want help on help. So it's talking about documentation shortcuts. So we're going to stop here in this video. This was just your starter to get started I'm assuming that anyone in this class likely has very little to no programming background or knowledge. If you do, then this might just be a little refresher. You might have seen one or two little things you don't really think about, like how to do different help commands, stuff like that. But realistically, I understand that a lot of times I feel like whenever I'm looking up something on like programming, people jump straight into, here's how you do this. And no one talks about, well, okay, how do I get Python? How do I start VS Code? And it actually is surprisingly complex sometimes. For example, if you decide you want to use Python in VS Code, you would download VS Code. You then need to go into VS Code and grab the extensions. You need to search for Python. You would grab the base Python extension. And these are things that like anyone who's done any amount of programming will figure out pretty quickly. But for someone who's never touched programming in their life, this can be kind of foreign to them, which is why I wanted to have this sort of very basic start as we build into our understanding of programming, specifically statistical programming using R. So in the next lesson, we'll start looking at some syntax. And I've been showing some examples like that, but we'll continue on with that and get more into detail about what we're actually doing. Hello, everyone. In this lesson, we're going to be looking at some simple operations in R, continuing our introduction to R. So R is a language with a very simple syntax, especially if you have a math or statistics background, because like I said previously, it's written like math. So R is case sensitive. For example, capital A and lowercase a will be seen as different symbols. So this would refer to different variables. So you can see here we have a couple commands. We have A equals, so capital A equals C 1, 2, 3, 4, and lowercase a equals C parentheses 4, 3, 2, 1. So if we go into R, we can start by putting these commands. So I'm going to have A equals C 1, 2, 3, 4, and I'm going to run this. Now watch what happens when I actually run this. If you look at the console, you will see that it shows that something ran, but there's no output. And the reason is when you're using R, what this is doing, and we'll talk more about assignment operators in a second, but this is assigning so this A is called an object. And this is assigning the values 1, 2, 3, and 4 to that object. So if I actually wanted to run that, I would need to put capital A and tell it to run the command. And as a reminder, when I'm in the actual source window, anytime I'm running a command, I'm using Control Enter to tell it to run. If you're in the console, which is at the bottom, you just hit Enter and it runs it automatically. I hit A and you'll see that it outputs the numbers 1, 2, 3, 4. Now what we're gonna do is we are going to assign lowercase a. So lowercase a equals C 4, 3, 2, 1. So I'm gonna run this one and you'll see that when I run this, I get 4, 3, 2, 1. So if I were to run A again, which I could just again type A and I could run it, or I can go to the line that it's on, again hit Control Enter, and it will run it. Capital A is 1, 2, 3, 4. Go to lowercase a, so you could do that, or if I wanted to run just a specific part of what's on a line, I could highlight it, hit Control A, so I'm gonna run A, and lowercase a is 4, 3, 2, 1. So even though they're both objects that are labeled A, capital A is seen as a different object than lowercase a. So R is a case-sensitive language. Your name for your objects must begin either with a period or a letter, meaning if I tried to do an object like 1A and do 1, 2, 3, 4, it's not going to work. So I'm going to go to the next line, put 1A equals 1, 2, 3, 4. I'm going to run it and you'll see I get an unexpected symbol in 1A. So this gives me an error. But I could start with a period if I wanted to. For example, I could write this as point A or period A, and it runs just fine. And now going over to the top right, if we look at our environment, you will see that I have an assignment for lowercase a, for capital A, for X, and for Y. And then also, if I were to put dot A, actually, let's mix this up a little bit just to try something. Let's add a 5 to it. So if I run dot A, I get 1, 2, 3, 4, 5. And if I do lowercase a, you'll see that I still have 4, 3, 2, 1, because dot A is a different variable than A is. I'm not sure why this one is not showing up in my values, but you can see clearly that it is labeled by the numbers that I put because when I ran it, it worked. If you start with a period, the second character cannot be a digit, meaning that period 1, again, will not work, but period A will. Now you can have numbers in your variable names, that's perfectly fine, right? But for example, if I did dot 1 equals, and I'm just gonna make it a number, 4. Again, you'll see that error in dot 4, point 1 equals 4, invalid, do set left-hand side to an assignment. And this is because what it's doing is it's trying to assign point 1, the value, to 4. But if I did point B equals 4, that's perfectly fine. Point B is a perfectly fine name. Now, as I mentioned, you can have numbers in your names. For example, I could do a 1 and I could assign it as 5, and you'll see that that's perfectly fine. So you can have numbers, but you can't start with a number and you can't have a period followed by a number. It's case sensitive, and otherwise this is how you can label objects in R. And this is actually how R is going to work. And this is one of those differences with R and Python, is in R, when you assign an object, it is permanent. It is called immutable, meaning that when I do any sort of operation on it, let's say I multiply every value by 4, it will give me the output of what that equals to, but it will not change the original object. So for example, if I take my original capital A, and I want to just do multiplication, so I'm going to do *4. If I were to run this, you will see that it took the numbers 1, 2, 3, and 4, and it multiplied each of them by 4, giving me 4, 16, 12, and, 4, 8, 12, and 16. But if I were to go back and run A again, just run basic A, not the labeling, I still have the values 1, 2, 3, or 4. It did not change the original object. That object A is 1, 2, 3, 4. The only way that it will ever change the original object is if I go back to where I actually assigned it, A equals, and I change it there. So if I did A equals 1, 2, 3, 4, 5, 6, now A is 1, 2, 3, 4, 5, 6. And again, if I go and multiply everything in A by 4, I will now get all of those values multiplied by 4. Python is a mutable language, meaning that the objects are not permanent in the sense that if I do any manipulations to them, it can change the actual original object. They both have their advantages and disadvantages. I actually prefer the immutable aspect of R because I like having control of exactly when I assign a variable or an object specific things. But there are examples of when mutable might be a better option, right? There's a reason why they choose these. It's not just arbitrary. In R, you can also separate commands using a semicolon. So for example, here we have mx equals the mean of .a. So we have .a is assigned the values 1, 2, 3, 4, 5. So if I did mx equals mean .a, you'll notice it didn't run anything, and I ran it, but it didn't output anything. If I do mx, I can now see that the mean of all these values within .a is 3. Now, what I could do instead, though, is I could put a semicolon, and this will tell it mx equals mean.a, semicolon ends that command. The next thing after it is the next command. So it's saying mx equals mean.a, run mx. So if I do that, you'll see that it's just going to run, it's going to assign this, and it's going to run it. So let's change a little bit to test it out. Instead of doing .a, we're going to do capital A. So I'm going to get the mean of capital A, and so I'm going to assign mx, the object, I'm going to reassign it to something new. Now, instead of being the mean of .a, it's going to be the mean of capital A. And then I'm going to run mx to see what the mean is for capital A. And you'll see that it's 3.5. So a semicolon can be used to separate commands, and you can have as many as you want. So if you want to have 6 things in one line, you can do that. That's perfectly fine. Also, occasionally, I want to point out in my slides, you might see something like this where there's a capital when it shouldn't be. This is because when I set this up in PowerPoint, it loves to auto-capitalize whatever's at the beginning of a sentence or a bullet point, and some of them I might have missed. So this was just supposed to be lowercase mx equals mean.a, semicolon mx. For elementary commands, can be grouped together in one compound expression using curly brackets. So for example, here, this should be a lowercase I, again, PowerPoint. For I in 1 to 10, this is telling it that I'm going to do what's called a for loop, which we'll talk more about later. It's saying I'm going to do I equals 1 to 10, just like we would with a mathematical expression, let's say like a summation. And then within those curly brackets, I can give it a complex or compound command. I can tell it for I from 1 to 10, take every value I, multiply it by 2, and then sum them together. And I could put this in this curly bracket. So what this is going to do is it's going to tell it that these run together. They're treated as, a sequence of commands that are all lumped together. And we'll talk more about this when we get to functions, for loops, while loops, all that kind of stuff. Comments can be put anywhere in your code by putting a pound or a hashtag. After that, anything that you put will be a comment. So for example, going back to our previous command where we labeled mx and then we ran it, if I were to do a pound, I would say this is the mean of A. And if I were to run it now, what's going to happen is it's going to run the assignment of mx, it's going to run mx to give us the output, and it's going to give us this comment here. but the comment's not part of the output, it's just part of the code. This is for the people actually looking at your program. One thing I want to talk about comments is a lot of times when people start coding, the first thing they want to do is they want to comment on every little thing, what each function does. So you might say something like a equals 4.6.3 or 4.653, and then you're going to say a is this, and you're going to say like mean of a. It's like this finds the mean of a, and that's not really useful comments. When you're commenting your code, what you really want to do is you want to explain sort of the reasoning or process that you're using. The reason is because when you're coming back to your code years later, or you're sharing it with somebody else, you want your comments to be helpful for somebody to follow along with what's being done. So if you were assigning some object, you might want to put a comment if they don't know what this is, right? A equals blah, blah, blah. This, is sensor data from sensor station, whatever. Okay, great. That could be a useful comment because now if somebody is running this, or you share it with a colleague or a friend, or you come back to it 3 years later when you're trying to remember what you were doing, those kind of comments can really help. So a lot of times you'll see later on as we get deeper into this, I will start having more commented code when we get past sort of just the very generic, here's how to do X, Y, or Z basic functionality. An example of this would be for our original command, mx equals mean of dot A, and then you could put # mean of dot A. And it's just showing that what this is. Anything that is after the # is a comment, including other #. For example, if I were to go to, let's go back to our capital A, and I would put a #, I could write out some message for whoever's looking at this code later. But I could also put multiple #, and I could just say something like, this is A, and it will have that comment within the code. Now, you might wonder why it would matter that I could put more than one #. Well, a lot of times because when I'm doing stuff like this, what I like to do, if you want to do some separation in your code, is just put a bunch of #. And that way, I now know that this is sort of a break, right? So now I have my intro code, and now if you look at this below, I've been pushing this down as we've been typing these things out. For the preceding slides for part 2 of this course, I actually put all the code in ahead of time so you didn't have to watch me type out every single thing, because otherwise I'd be back and forth between the slides trying to remember what my values were, stuff like that, what I might have labeled something. And again, we will also talk later about good labeling for your objects. Right now, I'm using really bad practices as we learn about them. I'm trying to use something simple, A, B, C, X, Y, Z. Later on, when you're actually doing real coding, you would want to use labels that make sense. So if you were to read the code, you could figure out what it does without having to put a ton of comments, right? So instead of putting A equals and then putting a comment, this is sensor data, you could put sensor1 output and then assign that object. Now someone will know, oh, those values that you put in, those are from sensor1, something like that. You can also use vertical arrow keys on the keyboard to scroll forward and backward through your command history. Now this is specifically for the console command, in RStudio, or if you're using base R, the actual R. So if we go back to R and we go down to our console, you'll see that there's nothing there. If I hit up, what's gonna happen is it's gonna pull up the last thing I did, which was when I labeled A as capital A as 1, 2, 3, 4, 5, 6, and I added the comment. If I push up again, it will go to when I labeled MX and I added the comment. If I go above that, it'll just be the example from X, and you can see that I can scroll through these by hitting up, and it will go to each previous command. Or I could hit down and start going forward through the commands. That way I can go through my history. So if you're using base R, for example, or you're doing something in the console and you just want to change, you're trying to figure something out, a lot of times this is a good way to do it. An example of this might be, let's say I'm doing a linear model, we'll say like, okay, LM, and again, I'm gonna do MT cars because it's something that is built into R. I'll use it quite a bit for examples. And I'll say MT cars, money sign, MPG, follows dot data equals MT cars. And so I run this, okay, I get my linear model. And you say, well, what if later on you say, actually, you know what? I only wanted to focus on how the miles per gallon is modeled using a linear model using the weight of the car. So instead of having to go and type all this back in, I could just go hit up, come back to the command I just did, and I can change it. So I'm gonna change it to a WT, And now I have a linear model where I'm looking at how the weight of these cars affects the miles per gallon of these different cars. And I'll talk more about the MT cars data set later in the course when we're doing more actual data manipulation. But I just wanted to show you now that you can, if you're in the console, use the up and down commands, or if you are in base R, you can hit up and down to go back through your commands or forward and find previous commands. A lot of times it's great if you just want to do some quick edits if you're not really interested in like adding it to your source at the moment. Now in R, there are some elementary arithmetic operators and they can be very useful for basic math manipulation and calculations. So you have plus, this does addition, right? So if I do 4 plus 6, I will get the outcome of what 4 plus 6 is. So for example, 4 plus 6, run it, you get 10. You also can use a minus sign for subtraction. So 6 minus 4, run that, I get 2. I could also use a star for multiplication. 6 star 4 is going to give me 24. Or I can do division. Let's say I do 6 slash 4, which by the way, everyone online always calls this a backslash. This is a forward slash. Backslash is this one. But anyway, so 6 slash 4 will give me 1.5. So this is division. You can also use the caret for power. So if I wanted to do 4 to the 6th power, then I would just do 4 caret 6, run that, and I will get 4,096. So this is your basic mathematical operations that you would have on like a 4-function calculator with power, stuff like that. That also does have other operators. For example, I can take log using log parentheses. I can get the exponential using exp parentheses. I can get sine and cosine tangent using sine parentheses, cosine or cos parentheses, or tan parentheses. I could do square root with sqrt parentheses. So for example, if I wanted the square root of 36, I just put sqrt parentheses and it will give me the square root of whatever is inside of this. So let's say we did 16. So you'll see that we got square root of 16 is 4. Now here's where I always like to say, whenever you're learning this stuff, try different things out. So what if I wanted to get 2 different square roots? Let's say I wanted to get 16 and I wanted to get the square root of 81. So I add 81. Notice I got an error. And you might wonder why. I'm trying to get the square root for 2 things. Can I not do 2 square roots at once? And you can. And this is where, when you're learning how to use R, it's going to take some practice as you kind of build up the different skills. And you might have actually seen me use this in the previous video, but what I'm going to do is I'm going to put C, and then I'm going to put parentheses, and then I'm going to close parentheses. And now what it's going to do is it's going to give me the square root for both 16 and 81, giving me an outcome of 4 and 9. And we'll talk more about this later, but the C is how you put multiple objects together. It's called concatenate. So what we did is we concatenated these 2 values. So we're treating it as one object for this. We're saying take the square root of all the values that are lumped together in this these parentheses that are concatenated together. We also can use colon. This will give us a sequence. So if I did x equals 1 colon 5, what it's going to do is it is going to list out the values 1, 2, 3, 4, 5. So we have x equals 1 colon 5. And then what I'm going to do is I'm going to do semicolon, and I'm going to put an x, meaning it's going to assign x as 1, 2, 3, 4, 5, and then it's going to run it. So the colon will give you a sequence, okay? And we'll talk more about this actually, because literally right when we finish this, we're jumping straight into sequences. Again, you can use mean of x. So now that I've assigned what x is, I could do mean of x, and you'll see that I get a 3, right? Because if I take the values 1, 2, 3, 4, 5, if I take all of them added together, divide by the 5 numbers I have, I get an outcome of 3. I could also do a command like this. X square bracket 1 plus x square bracket 2 plus x square bracket 3 plus x square bracket 4 plus x square bracket 5 divided by length of x. Now, you might wonder, why do I want to do this? Well, let's look at what actually happens when I do this. So I have x square bracket 1 plus x square bracket 2 plus x square bracket 3 plus x square bracket 4 plus x square bracket 5. And let's see what happens when we run this. We get 15. So what it's doing is these square brackets are an index. So when I put x square bracket 1, it's saying take the first value from x. right? Remember, x is 1, 2, 3, 4, 5. So the first value is 1. X square bracket 2 is saying grab the second indexed value. So the index is just where they're located. The first value, second value, third value, fourth value. This is like when we're doing mathematical operations and we have I equals 1 to n. I is the index. X1 is the first value. X2 is the second value. X3 is the third value. X4 is the fourth value. If we do length of x, this is going to give us how many numbers are in this object x. In this case, it is 5. So if I were to go and we put this in parentheses, because you got to think order of operations, just like when you're on a calculator and stuff like that, and you're doing your math classes. I'm going to put this in parentheses. I'm going to take those values, 1, 2, 3, 4, and 5 from my x. I'm going to divide by the number of values in x, and I'm going to get 3. So what I did is I just, instead of using mean of x, I actually created the mean by taking each indexed value and dividing by the length of the values. Now, later on, when we talk about for loops and things like that, there's ways you can go through every, I equals 1 to n. You don't have to type in I equals 1, I equals 2, I equals 3 for every n values. But I'm just doing this to kind of show you that with these basic operations, you can do a lot of this stuff automatically in R without any packages, anything like that. So even though there is a function that does it, if you want to create another function, you can. For example, let's say that I wanted to do some function, or I wanted to create some calculation where I took the mean of x plus 1. Maybe I want to have a length plus 1. Maybe I have some, somewhere I'm doing degrees of freedom. Let's say minus 1, right? Because that's pretty common. So we're going to take the length of x and we're going to subtract 1 from it. So I'm going to put parentheses. I'm going to hit -1, close parentheses. So now what I did is I took the sum of all the x values, and then instead of dividing by a length of x, which was 5, I divided by 4. This is how we would create stuff like this, right? If I'm creating the standard deviation or variance when I'm dividing by n-1, this is how I can do it. Now you might wonder why would I want to do length of x -1 instead of just putting 4? Well, because a lot of times when you're creating code, especially later on when you're doing functions and loops and stuff like that, anything that you can sort of put in these generic terms, where no matter what length your data is, this makes it a lot more robust. Because let's say that my x, instead of being 1 through 5, was 1 through 6. Well, what I wrote here is only going to give me the first 5 numbers added together. And then divided by, in this case, I would do length of x, which would be 6, and then I have -1. But if I wanted it to be actually the mean, I would have to take into account that no matter what x values I put in, I need to add up all those numbers. I need to sum up whatever is in x. I just want to do that. Like, let's say that I'm going to change x. So let's do y instead. So y is going to be equal to 1 through 12. Okay, so no problem. Let's run it, and you'll see that y is the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If I wanted to find the mean, I could use something like sum of y divided by length of y. I run that, and I get 6.5. Now, let's say that you get more data in. Now, instead of y being 1 through 12, let's say it's 1 through 20. So we run this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9 through 20. Now, when I run this, guess what? It still works. I don't have to go and change it because none of it was hard-coded. It took whatever the value y was and it added those up. It took whatever the length of y was and it divided those sum of values by that. So this is why a lot of times you don't want to hard-code things if you don't have to. Now, if it's something that literally never changes, it's fine, but generally we're going to be using commands like this in order to create more robust systems that we can bring any amount of data into, right? So whenever I'm doing an analysis on something, if I have 100 data points, I'm not going to put n equals 100 and I'm going to run it. I'm going to do n equals length of this column. And that way, if I bring in more data, maybe it's 1,000 this time. Guess what? It still works. I don't have to change all the n values and all that kind of stuff. Next, we're going to talk about vector arithmetic, or specifically element by element recycling. So mathematical operations in R are vectorized by default. And this means that they operate in an element by element basis rather than a vector as a single object. So what does that actually mean? So that means when you're adding 2 vectors of equal length, What R is going to do is it's going to pair them up. The first value and the first value are going to get added. The second value and the second value are going to be added. Third value and third value are going to be added. The recycling rule in R is that if I add two vectors that are unequal length, R will automatically start repeating the smaller vector until everything has been added together. So if I have a 4 length vector adding to a 2 length vector, what's going to do is it's going to take 1 and 1 and add those together. It's going to take 2 and 2 and add those together. And then it's going to take 3, because there's no 3 on this one, it's going to recycle back to 1, add that together, and then it's going to do 4, and it's going to go to the next one. So 4 and 2. So it's going to be 1, 1, 2, 2, 3, 1, 4, 2. If it does not evenly go in when you have a smaller vector, you will go to warning, but it still will do the calculation. So if the length of the longer vector is not perfect multiple of the shorter vector's length, R will still perform the addition, but will issue a warning message. So, for example, let's say that we did this calculation here. C 1, 2, 3. So I have a vector 1, 2, 3. And I'm going to add this to 10, 20, 30. So if we did this, C 1, 2, 3 plus C 10, 20, 30, you'll see that it adds them up. 1 plus 10 gave me 11. 2 plus 20 gave me 22. 3 plus 30 gave me 33. If I have differing lengths, let's say in this case now we have 1, 2, 3, 4 as a vector and 10 and 20 as a vector. So C 1, 2, 3, 4 plus C 10 and 20. Now what happened is it added the first element from each vector. So 1 and 10 gave me 11. Then it added the second element from each vector. 2 and 20 gave me 22. Then when I got to 3, the third element on the first vector, it had to recycle back to 10. So 3 plus 10 gave me 13. And then the last one, 4 plus 20 gave me 24. But what if they are different lengths? So if we go here, we see we have 1, 2, 3, and 10, 20. So we have C 1, 2, 3 plus C 10 and 20. So what's going to happen when we run this is it's going to do 1 plus 10 is 11. It's going to do 2 plus 20 is 22. And then it's going to recycle back to the 10. So it's going to be 3 plus 10 gives us 13. But it is going to give us a warning. Warning, longer object length is not a multiple of the shorter object length. But if we look at our output, it did still give us 11, 22, and 13. So it will still run this, but you have to kind of think of this when you're dealing with vectors, which R automatically likes to vectorize things, is that it does element by element addition, things like that. What about if we wanted to look at element-wise multiplication? So vector operations in R are vectorized, again, by default, meaning multiplication is performed vector by vector, or element by element, meaning the first element will multiply by the first element. Second element will multiply by the second element. And this works exactly the same as when we did our vector addition. So for example, if I have 3 times C 1, 2, 3, what we're going to get is we're going to get 3 times 1, 3 times 2, and 3 times 3, which is going to give us 3 values, 3, 6, and 9. If we have 2 vectors that we're multiplying by each other, so C 1, 2, 3 times C 10, 20, 30, what's going to happen is that it is going to multiply the first element times the second element times the third element. By the way, you can see sometimes I'm putting spaces in my code. This is just because I'm trying to, this is my habits coming in where I'm trying to write a specific way to create clean, readable code. But a lot of times I kind of try not to focus on that too much when I'm creating or focusing on intro level type stuff. But a lot of times with spacing, it makes it easier to read, follow, things like that. And you'll see that it did 1 times 10, 2 times 20, 3 times 30. It did element-wise multiplication. And of course, just like our addition, if we have 2 different size vectors, right? So C 1, 2, 3, 4 and C 10, 20. I'm just gonna cheat on this one. I'm just gonna delete what we already had for the 30. It's going to give us the outcomes, right? 1 times 10 gives us 10. 2 times 20 gives us 40. 3 times 10 gives us 30. But it's going to give us a warning, just like before, that you have unequal length vectors. Now, we're not going to go in too much detail about this right now, but I am going to, so I'm not going to run the example, but you can see it here. I even have the outputs and everything like that. But when you were doing matrix multiplication, so it does element-wise multiplication, that is what the star means. If you want to do matrix multiplication, you have to explicitly tell it to do matrix multiplication, but using the percent sign, then star, then the percent sign. So if you want to perform standard linear algebra row by column multiplication, that is A dot B, you must use that percent dot star percent, and that will tell it to do normal matrix multiplication. So for formal matrix multiplication, the number of columns in the first row must be strictly equal to the number of rows in the second matrix. This is not like when we're doing element-wise. If it is not the same, then it just won't run. It'll give you an error and you'll have to figure out what you did wrong, right? Either you have the wrong size matrix, maybe you missed a number, something like that. And if we look at the example here, you can see that I created two matrices. A is a matrix 1, 2, 3, 4, and it's a 2 by 2 matrix. B is 10, 20, 30, 40, and it also is a 2 by 2 matrix. So if I do A star B, what's going to happen is it's going to multiply for the first element 1 times 10. For the second element, 2, 1, it's going to give us 2 times 20, which is 40. For the element 1, 3, it's going to give us 3 times 30, which is 90. And for element 4, 4, it's going to give us 4 times 40, which is 160. So notice what it did is it multiplied the first, so the top left with top left, top right with top right, bottom left, bottom right with bottom right. If I wanted to do actual matrix multiplication, where you do multiplication of the row by the column, then I need to do A percent star percent B, and this will tell it to multiply using matrix multiplication. Now let's talk about data permanency and removing objects. So the entities that R creates and manipulates are called objects. I've already talked about this. These would be things like variables, arrays of numbers, character strings, functions, and more general structures built from these components. So if I were to type objects parentheses, this is going to list off whatever objects we currently have loaded in R. So you can see that we have the objects A, capital A, A1, IRF, these are from when we did that prior example with solve last time. MX, X, and Y, right? And by the way, we'll talk about this in a minute. This will list all the objects you have. Now you might wonder, why would I need to do that? I can literally see it in my global environment. I can see all the variables I have loaded. Well, remember, this is functionality that's built into R because you can do all of this in base R. But a lot of times the reason this will be really useful is because sometimes you're going to want to know about objects within a certain function or something like that. You might create a function that has many objects. You just want to list off what are the functions. Or you might, for later on, you're probably going to use names a lot of times, which will give you the columns and stuff like that. You can also use the command ls, and this will list off the objects that you currently have loaded in R. If I want to remove an object, I can use rm parentheses and then put the object name within it. So for example, I'm going to remove .a. So then to do this, I can just do rm.a, and now when I removed it, let's go back and see what objects are currently loaded in R. And you'll see what happened is .a, actually let's not do a .a, because remember that one wasn't showing up properly. Let's do lowercase a. So if I remove lowercase a, now when I run my list of objects, you'll notice that I no longer have a there, right? So before it started with lowercase a, now it starts with uppercase a because lowercase a has been removed. So I removed this specific element from my loaded objects, meaning a is no longer loaded into my environment. And a lot of times you are going to want to do this to keep it kind of clean. When you're done with something, you remove those objects. That way you're not cluttering up, because the whole thing is those objects in your environment are loaded into your RAM on your computer. So if you're building fairly large data sets or objects and you're getting a lot of them, it will eat up your memory of your computer. In fact, it could do it to the point where it crashes. I've had an example where I did this. I was creating random forest. I created too many for my computer's capabilities, and it literally crashed my computer because it was trying to put all of the trees in my memory, and each of them take up just a little bit, but when you add up enough of them, it becomes a huge problem. Unlike previously where I showed you where we had to concatenate to do different parts or different objects, for the remove function, rm, you can just do rm and then each object you want to get rid of. So you could do rm a, comma b, comma c, and it will remove the objects a, B, and C all at the same time. Before we move on to the next part, the vector assignments, stuff like that, which is where the code actually begins that I had typed in already, I do want to show you also that up here, if you go to your environment, you'll see this little broom. If you click on the broom, what's going to happen is it's going to say, are you sure to remove all objects from the environment? This operation cannot be undone. And I can also check include hidden objects. So when I hit yes, now my environment is completely clean. So that means I've gotten rid of all of the things that I had loaded in my environment. So if I were to go and list off my objects, you'll see that I get character 0. There's nothing there. If I were to run objects, same thing, character 0. If I were to try to run one of my things, for example, let's say we're just going to run lowercase a, it's going to say object A not found because nothing is now loaded into R. I have no objects or variables or arrays or vectors or anything in R. This will actually work the same way with plots. If we go back to plots, there's a little broom right here. You can get rid of all your plots as well. You can delete a specific plot or you can delete all of the plots. So now let's talk more about vector assignment. So to set up a vector named x, which consists of 5 numbers, 10.4, 5.6, 3.1, 6.4, and 21.7. This is actually how I'm going to be writing them from now on. I do not use the equal sign because equals has a very specific meaning, specifically at lower levels of our coding, for example, like more in functions and stuff. So what I'm going to be doing is using an arrow. So we would use x, and then you create an arrow with your little bracket, and then dash. So x arrow, so I'm telling it, these objects that I've concatenated together, 10.4, 5.6, 3.1, 6.4, 21.7, they're concatenated together, and I'm assigning them to x. So when I do this, what's going to happen is you're going to see now that I have x is these 5 numbers, right? So we're going to be using this arrow operator from now on to assign our variables or objects. Notice that the assignment operator, that arrow, which consists of 2 characters, the less than symbol and the minus symbol, occur strictly side by side. And it creates an arrow that points to the object receiving whatever you're putting in there, right? So whatever you're assigning to that x, that's what the arrow points to. It points to that x. In most contexts, equals can be used as an alternative, but again, I told you I prefer not to use the equal sign. There's reasons for it, but for now, it's not really a huge deal. When you get deeper into it, it actually does have some effect, but for right now, it's not a huge deal. Now, we also could use the assign function. So this one, if you want to explicitly assign something specific to an object, you could use this function we have here. So it is assign, and then you have to say, what is the object you want to assign? Notice that it is in parentheses. This is because we're assigning it to this character x, so we put it within parentheses. And if you look here, I don't have this. It works either way, right? So for example, if I had this and then concatenated those numbers, let's do it a little different. Let's change it to y. You'll see now that y is assigned. So if I wanted to, like I said, if I just want to run y, I can go within the code, highlight y, hit Control Enter, and it will just run y. If I did not have the parentheses, it's going to give me an error, invalid first argument, because it's trying to assign y, and we'll talk more about this later with different types of object or different types of variables, but this is called a character, where I put it within the quotes. I'm telling R that it's character y, not some sort of value or object, things like that. You also could do the arrow in the other direction. So you have concatenated, got those same numbers, arrow pointing the other direction. For example, I'm going to change this to z. And then, of course, when I run this, you'll see that also assigned z the same values. So it's treating it like an arrow. You can actually take these assigned objects, in this case, these are vectors, which you can actually check this with type of. So for example, if I do type of x, you will see that it's what's called a double. We'll talk more about that later whenever we talk about, again, different variable types, stuff like that, or different data types. But you could take these objects we've created, and I can do like 1 over x. So 1/x, just remember the slash means divide. So I'm going to take 1 and I'm going to divide it by x. But remember, it's going to be piecewise with the recycling. So it's going to be 10.4, it's going to be 1 divided by 10.4, 5.6 divided by 10.4, 3.1 divided by 10.4, and so on through all the numbers. And this will give me what those values are for 1 divided by each element within my vector. You can also assign an object with elements from other objects. So if we look here, we have y is assigned as, we're going to concatenate x, 0, x. So what this is going to do, I'm just going to put semicolon y, so it just runs y. What it's going to do is it's going to assign the first elements as what are in x. So 10.4, 5.6, 3.1, 6.4, 21.7. Then it's going to assign a 0, and then it's going to assign the elements from x again. So we have 10.4, 5.6, 3.1, 6.4, 21.7, 0, 10.4, 5.6, 3.1, 6.4, 21.7. So you can actually take objects and assign other objects as part of that object. You can think of it like a subgroup, things like that. We're creating subsets. You also can do operations within those assignments. So for this one, v, what we're doing is we're assigning 2 times x plus y plus 1. So whenever we run that, let's see what happens. Even though we are adding vectors, and as I showed you, this does work. For example, if I do this part, y plus 1, you'll notice that all it did is add 1 to each value. But when I try to run this entire thing, it's going to say that the object length is not a multiple of the shorter object length. But it's not giving me the output. Oh, actually, I got to run it. Okay, so it did work. I was seeing the warning message because the warning message came up when I assigned it, but it wasn't doing the output, and that's because I wasn't actually running that. And so what we did here is we took v and we assigned 2 times x. So whatever is in x, that 10.4, 5.6, 3.1, we multiplied each of those values by 2. Then we added y, which remember these are different length vectors, so it's going to cycle through. And then it's going to add 1 to each of those. So now looking at v, we now have a new object which is made up of different objects, which are vectors, with different operations run on them. And this is where, again, you can get into more complex programming ideas because you can take your objects, create more advanced objects from them, but the initial object still has not changed, right? Because if I still go to x, it is still those same initial values that we put there because x is immutable. Unless I reassign x, it will not change what those values are. In R, equals and the arrow are both assignment operators. The R community, again, generally prefers to use the arrow as the assignment operator. I'm one of those people as well. So the operator arrow can be used anywhere, whereas the equals operator can only be used at the top level. That's what I was kind of mentioning earlier. So in the complete expression typed at the command prompt. So if you want to look up more documentation on this, you can go to rdocumentation.org, packages, base versions 3.6.2/topics /assign ops. This probably has an equivalent for our current version, which was, we downloaded 4.6.0 today, but when I originally created the slide, it was 3.6.2. R does not process spaces. So spaces can make commands more understandable. This is what I was talking about earlier. I add spaces to make them more understandable. For example, you could do R less than -3, and it's going to see this as I'm assigning 3 to the object X. But it's also it makes it harder to understand because am I saying that X is assigned 3 or am I saying X is less than -3? So let's actually look at those different operations. So if I did X less than -3, what's happening is that it is assigning 3. But if I wanted to be more explicit, which makes it more understandable for someone reading the code, if I did X arrow 3, this is explicit that I am assigning 3 to X. But if instead I did X less than -3, this is doing a logic statement of, is X less than -3? And the answer is no, because we assigned +3 to X, and 3 is not less than -3. But see how by just adding the space, you can see the difference between these two statements. This one is saying that 3 is assigned to X. This one is the logical statement of, is X less than -3? If it's together like this, you don't necessarily know which one it is. It will do the assignment operator by default, but if I had wanted to make it less than -3, then this wouldn't work. So to kind of fix this, what we do is we just put spaces to make it more clear. It also makes it more readable, so you're just not seeing a bunch of mashed, dense numbers together. It helps spread it out a little bit. It helps make it more readable. but this is one of the big reasons why. The note, as I mentioned before, with your arrow, you can assign in either direction. So you could also do 3 arrow to x, and that will assign x to 3 as well. For some basic statistical functions that are built in R, if you wanted to get the variance of a value, we could do var of x. So this would be var of x. If we do var of x, you'll notice I got NA. This is because what I did here is I reassigned x, right? If I look at x, go to my console, type x, it's just the value 3. There's no variation to 3. It's variance at 0. If I reassign x as 10.4, 5.6, all that kind of stuff, now if I use var of x, I will get the variance. If I want the standard deviation, I can use the SD function. So SD parentheses x, this will give me the standard deviation. Right now, of course, we all know that standard deviation is just the square root of variance. So just like before, I could do square root, so SQRT, parentheses, and within this function, I can put another function. I'm going to put var of x. So I'm going to take the square root of the variance of x, and you will see that I get the exact same thing as when I did standard deviation. Try some of these things out. Try different commands, see like things like that. So for example, this isn't in the slides, but maybe you want to go the opposite direction. Maybe you're going to say, well, I know that the variance is the standard deviation squared. Let's try it. SD parentheses x, and we know if we want to do a square, I'm just going to use a caret function too. I'm going to run this, and look at that. I got my variance. And this is what I was kind of talking about previously. Is whatever we're doing in the lessons, the class, you should be following along, trying things out. Don't just follow the example of what I did. Try different numbers. Try changing things around. Try different operators and see what works, what breaks. And then when you do run into an issue, this is where you can start troubleshooting. Why did I get this issue? Maybe you just had a small typo, like you missed a comma or something like that. Or it might be something bigger where you want to take those, whatever that error is you're going to get. You can go into Google, search for it, things like that. Or even possibly, this would be where you might want to use like an AI system if that's what you prefer. You type in this error, you could just put your code, put the error, and from there it could tell you, oh, here's where you made a mistake, most likely. But I would suggest first trying to solve it yourself, because that's what's going to help you be a stronger programmer. So we're going to finish off this lesson by focusing on sequences. So R has the capability of a lot of different ways of creating sequences. So for example, let's say I wanted to create a sequence of the integers 1 to 1000. Well, I already talked about one of them. I could use 1:1000. What that's going to do is going to give me a sequence of the numbers 1, 2, 3, 4, all the way up to 1000. So if I wanted to do that, what I could do is just do x. I'm going to assign 1:1000, and then I'm going to put semicolon x. We can see what happens. I'm going to run that, and you're going to see that what it's going to do is it's going to just list off the values at integers of 1, 2, 3, 4, 5, 6, all the way up to 1000. Now, one thing I actually want to point out while we're doing this, let's say we had a bigger number. Let's say it was, I don't know, 100,000. So if I were to do 100,000, it's going to do the same thing. This x is the integers from 1 to 100,000. But notice what's going to happen in the output is that it's going to go up to 1,000, and then it's going to stop. It's going to say reached max, get option, max.print, omitted 990,000 of my... 99,000 entries. The entries are there. X is the values 1 to 100,000. But the global options I have set in R by default will stop at 1,000 values. You can change this. You can also explicitly tell it to do more entries if you want to see what they are. But generally, when you get to that point, you just know that they are there, and you can do other things to look at, like the shape of the data, stuff like that. But this is just sort of a default limit of what it's going to output. Because after a while, like if you have so many numbers, it really doesn't mean anything to look at it. In this case, it's easy because it's a sequence. But if it wasn't, if it was like different numbers from, like I said earlier, like a sensor or something like that, seeing 1,000,000 or 1,000 of them, it all kind of, you just get an idea of like, okay, here's what it looks like. The data looks good. And then you can do other inspection type methods to look at the, mean, median, mode, skew, all that kind of stuff. If we did 10:15 minus 1, what do you think is going to happen? Let's try it out. So 10:15, this is going to give us the sequence starting from 10. So 10, 11, 12, 13, 14, 15. If I were to put a minus 1 at the end, notice what happened is it took that sequence 10, 11, 12, 13, 14, 15, and it subtracted 1 from each of them. So there's an order of operations that is done in R. And one of the early order of operations is this colon operator, this sequencing, meaning that it is going to take priority creating the sequence 10 to 15 over the subtraction. So what it did is it created the sequence 10, 11, 12, 13, 14, 15, and then it subtracted 1 using our element-wise subtraction. So it subtracted 10 minus 1, got 9, 11 minus 1, 12 minus 1, 13 minus 1, 14 minus 1, 15 minus 1. Okay, so first now I'm going to assign this. So we're going to do, oops. Now what I'm going to do is I'm going to assign x1 as this sequence here. So this 10 to 15, right? And we'll see that just like before, when we assign it, we have 10, 11, 12, 13, 14, 15 as the object x1. So now if I take x1 and I subtract 1 from it, it's going to do the same thing, right? Because that's what it's doing, is even though I hadn't assigned it to an object, it still was creating that array, that vector of 5 numbers and then subtracting 1 from it. If I wanted to subtract 1 from each of them, I would have to do it differently. I would have to use parentheses, things like that to get the order of operations that I want. I could also change the actual sequence. So in this case, I did 10 colon, and then by using parentheses, I changed the order of operations, so 15 minus 1. Now this minus 1 is within parentheses, which takes priority. So it's going to be 10 colon 15 minus 1, or 14. So let's do that. 10 colon parentheses 15 minus 1, and you will see that we get 10, 11, 12, 13, 14. So what happened in this case is now those parentheses gave us order of operations, so instead it was 10 to 14 instead of 10 to 15 minus 1 from each element. You also can create sequences in descending order, and you do it the exact same way. You just start with your ending number. In this case, we do 5 to 0. It's going to list the numbers from 5 to 0 with jumps of 1. So 5, 4, 3, 2, 1, 0. So let's try that real quick. 5 colon 0. We run that. You'll see our output is 5, 4, 3, 2, 1. Let's say you wanted to have a specific sequence. You don't just want to have sequences jumping by integers of 1, and you don't necessarily want to start at a nice round easy number, something like that. You can use the seq command function to create sequences that whatever you want. So for example, if we did sequence -4, 1.5, let's see what happens. So we're going to type this in real quick. Seq -4, 1.5. So what happened is it started at the value -4, and then it went up by an amount of 0.5. So it went from -4 to -3.5, -3.5 to -3, -3 to -2.5. And it did this until it got to our stopping point, 1. So now let's go back for a minute and talk about our help. So I'm going to do question mark seq, or sequence. Oops, I put a 9 on there instead of parentheses. Okay, looking at our sequence, it is seq parentheses from equals 1, 2, or comma, 2 equals 1, comma, by equals, and then whatever is here. What this means whenever you're looking at a function like this is the value, the position, will tell you what it is. So the first position is where we are starting. Where are you starting from? And of course, we can look this up by scrolling down here, and you will see from the starting and to and maximal values of the sequence. So it's telling us the start and end point. So it starts from 1 to 1. So what this means is when it has this equals, this means that this is a default value. If I do not put this in, it will automatically fill in the blank for it, right? So an example of this, let me show you. I'm going to go back to our R norm. So question mark, R norm, parentheses. Now, if I look at this now, R norm, remember the idea of R norm is that in this case, it's in numbers. That's how many it's going to randomly generate from a normal distribution. Mean equals 0, SD equals 1. So what this is telling me is that when I'm using R norm, if I put a number in the first position, that will represent how many numbers in that I want it to output. Mean, that's the second value, I can change by putting some number there. But if I don't put a number in the second position, then it will default to 0. The third position is standard deviation of that normal distribution. If I do not put a value in there, it will default to 1, meaning it's going to default to the standard normal with a mean of 0 and a standard deviation of 1. The other thing is, it's not just positional. I can also use the names that it's showing here, right? So for example, going back to our sequence, we have that it's from equals 1 to equals 1 by. So what I could actually do is I could say something like sequence, I'm going to go up to 10, so 2 equals 10, comma, from, and I'm going to set this one equal to, I don't know, let's do 6. And you know what, let's actually switch it up even more. I'm going to do the second command is by 0.3. So now what this is going to do is this is going to create a sequence from 6, meaning it's going to start at 6, it's going to go up to 10, and it's going to make jumps of 0.3. So this is what I was talking about looking at your documentation, how you'll sometimes want to do it even if you know how to use the function. And it's because you can look this up quickly to see what is the ordering. So if I want to do an R norm, I don't have to always worry about, okay, do I want to put mean and SD? I can just do, okay, well, the first one's in, second position is mean, third position is standard deviation. But if I wanted to have a specific order, I could do that. And again, if you look at your documentation on it, it will also tell you if there are any defaults. So for example, if I just did sequence, it's just going to be 1. Because again, if you look at our sequence, it says that it's going to go from 1 to 1, right? It's giving us a sequence from 1 to 1. There's only one value, it's 1. Another thing I want to point out quickly is for the sequence I just did a second ago, where I went from 6 to 10 with jumps of 3, notice that it stopped at 9.9. Because what's happening here is that I am giving it the boundaries of the sequence. You were starting at 6, you were going up by jumps of 0.3, but you will not go beyond 10. So it lands on 10, it would put 10. But because I can't add 0.3 to 9.9, it's going to stop there. Because it's basically what's going to do is it's going to have to prioritize where's the stopping point. It can either be what your end point is, or if you have some set jump width, then it will end on the last one it can do before it would jump outside the boundaries you've set. Our sequence can use the arguments, that's what they're called, by the way, within a function. These are arguments. By equals some value, how big of a jump you want to do, and length equals value. So you could also tell it how long of a sequence you want. So for example, I could say something like sequence from equals 12 by equals 0.2, and I'm going to do length equals, I don't know, 36. So what I'm telling it now is starting at the value of 12, I want to do jumps of 0.2, and I want to list out 36 numbers. So doing that, you can see I have 12, 12.2, 12.4, 12.6, all the way up to 19.0. If I change this, instead of doing 36, let's do 37. What's going to happen is it's going to do one more jump because I changed the length by 1. And this is what I was talking about. You can actually do a lot of different really cool sequences by understanding how these functions work. And you might wonder, why would I need to do this? Well, a lot of times it's because, remember, think mathematically, right? I equals 1 to n. Well, guess what? When I'm doing a function and I do that I, in 1:10, I'm giving it a sequence. I equals 1, I equals 2, I equals 3, I equals 4, things like that, right? You can use these sequences within functions and other things like that. So now here's just some other examples I have in my slides. So sequence from 1 equals 1, 2 equals 5, and length of 4. What this is going to do is this is instead, because I didn't tell it by how big, I told it how many to have. It is going to figure out what jump size it would need. So let's try it. So we do sequence from equals 1 to equals 5 and length equals 4. So what it's going to do is instead it's going to start at 1 and then it's going to make 4 jumps to get to 5. So that means that it figured out that it needed to do jumps of 0.33 or 1.333333 repeating. So it did 1 to 2.333 repeating, 2.33 repeating to 3.666 repeating, 3.666 repeating, up to 5. So in this case, instead of telling it how big of a jump I wanted, I let R figure it out, and I did this by telling it the starting point, the ending point, and how many jumps I want to be between those 2 points. If I did the same thing, but I changed the length equals to 2, all it's gonna do is it's gonna do the 2 jumps to get from 1 to 5. So it's just gonna say, okay, I'm gonna do 1, and then the second in the sequence would be 5. And then of course the last one, like I mentioned before, you can change on the order. So this one, it has a length of 10, meaning it's gonna do 10 jumps. It's gonna start at -2, and it's gonna end at +2. So again, because we have the length, it is gonna figure out what width of each jump should be in this sequence. So now what I'm gonna do is I'm gonna create some sequences and I'm gonna assign them. So first thing was we have a sequence from -5 to 5 with jumps of 0.2, and I'm gonna assign that to S3. So we have a sequence from -5 to +5 with jumps of 0.2. And notice that I'm putting by equals 0.2 so it knows it's not length. And then I'm going to assign that to S3. Okay, so again, if I were to run S3, you will see that it is -5, -4.8, -4.6, all the way until it gets up to 5. Next thing I'm going to do is I'm going to create this sequence S4, where it is a sequence of length 51 from -5 by 0.2. So S4 is a sequence with a length equal to 51 from -5, and then it's by 0.2. And again, I'm just gonna put a semicolon S4, and this will give me the exact same sequence. Okay, and then last one, I'm gonna do S5, and this one is going to be a sequence where what I'm gonna do in this case, I'm gonna have a length of 10 from the same values. So length equals 10 from equals -5 by equals 0.2. And then if I were to do S5, you will see that the sequence is shorter because now I told it start from -5, make jumps of 0.2, and only give me a length of 10. Now you might have wondered, why am I doing this? Well, because now that I have these sequences, remember I talked about the fact that I could create objects from other objects. Well, I can also create sequences from other objects. First things first, let's look at the rep command. Rep means to replicate. So let's look at S6, which is going to be assigned as rep. And then what am I repeating? I am repeating the values of X 5 times. Now, if we remember, originally I had X as this 1 to 100,000 from our last example. When I originally wrote this code, this was supposed to be for this. This X is 10.4, 5.6, 3.1, stuff like that. So what we're gonna do is we're gonna rep X times equals 10. So what it's gonna do is it is going to take X and it's going to list it out. 10.6, 5, or 10.4, 5.6, 3.1, 6.4, 21.7. And then it is gonna repeat it 5 times. 10.4, 5.6, 3.1, 6.4, 21.7. 10.4, so on and so forth. So with the rep command, you can actually repeat whatever it is we put in there. So for example, if I wanted to, I could just say rep for 26 times. I'm gonna do times just to make sure, because I haven't double checked the, what it's gonna do is it's going to repeat for 26 times. So as always, anytime we have a new function, what I always suggest you do, question mark, and then what we're gonna do is we're gonna do rep, we're gonna run that, and you can see that we have rep, X, comma, stuff. In this case, X is a vector, so it can be a number, or it can be a sequence of numbers, it could be a series, it could be just a vector of numbers. And then we have a couple different arguments we could make. We could do times, which is an integer valued vector giving the non-negative number of times you want to repeat this, Or let's say you didn't want to repeat x 5 times. What you wanted to do is you wanted to repeat each value 5 times. You could do that with the each command. So let's do it. Let's see what happens when we do that. If I did the same thing as S6, I'm going to call this one, I think I already have an S7 in my example. Oh, actually, that's literally the next example I have. So S7 is going to be, we're going to repeat x, but what we're going to do now is we're going to repeat it each equals 5 times. So now what's going to happen when I look at S7 is it is telling it the first value in x, write that 5 times. Second value in x, write that 5 times. And that will be the sequence that makes up S7. So you'll see that it's 10.4, 10.4, 10.4, 10.4, 10.4, 5.6, 5.6, 5.6, 5.6. And it's going to do this for each value in the sequence. But what it's going to do is it's going to repeat that value 5 times before it moves on to the next element in that vector. Sorry, not sequence. So this is where we're going to end this lesson today, but I want to leave you off with a problem to try, and I will actually create a very mini video on how to do this. I want you to use the sequence and rep commands to try to create an object which is a deck of cards. In a deck of cards, you have 4 suits: diamonds, hearts, spades, and clubs. You also have the cards 2 through 10, Jack, Queen, King, and Ace. So what I want you to do is think about if you were to create this sequence of values, so 2 through 10, with the addition of Jack, Queen, King, and Ace, which you can just use the letters J, Q, K, and A. And then you have all of the cards for a suit. But what I want you to do is I want you to combine these together. And the way we're going to do it is you're going to use the paste command. So I want you to do question mark, paste, and I want you to figure out, if you can, how to create a deck of cards as an object using the paste command, rep command, and sequence command. Or if you want, you could just use colon to represent your sequence command. So that's going to be it for today, and then we continue on. We'll jump more into introducing all the fun things you can do with R as we build up our basic foundational knowledge. Hello, everyone. In this lesson, we're going to be going over logical vectors and indexing in R. So first, the logical operators are less than or equal to, greater than or equal to. You have the double equal sign, which means setting equal to for exact equalities, or exclamation point equals, which means is not equal to, right? Because there is no not equal to way you can type it in easily with a computer. So in computing, we use exclamation point equals to mean not equal to. So we're going to start with this example of x greater than 13. So going to R, I'm first going to create just some x values. I'm just going to make x a sequence of numbers from -10 to 30. Okay, so then what I'll do is I will run that and I'll put the semicolon x so we can see this as our output. And you can see here that we have -10, -9, -8, and so on up to 30 with increases of 1. So now what we're going to do is we're going to set our temporary object, so temp, and we're going to set this to x greater than 13. So if we do this now and we run, so I'm going to semicolon so we can actually see what the output is. Oops. Put term instead of temp. You're going to see that it's going to give us the output false, 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 a bunch of falses until it finally reaches true. So what this is actually doing is when we do this logic vector, it is testing whether this is true or not. So when I set the x values as -10 to 30, for the first value, -10, it's saying, is it greater than 13? No, it's false. -9 is greater than 13, false. -8 is greater than 13, false. And then once it reaches 13, it'll still have false. But when it goes to the next number, 14, now suddenly it is true. So you can see that it would be true for the values 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. This is what our logic vectors will do, is it will determine which ones the statement is true or false for. Now, this can be very useful later on when we look at indexing, because a lot of times you can index based on something being true. So for example, if I only wanted to grab the positive numbers, I might index it as x greater than 0, and it would only include those that are positive. In addition to this, we also have the logical statements of an intersection and a union. If you remember from Intro to Stats, an intersection is when we have two groups, A and B, where they intersect with each other. So it's whatever is within A and also within B, or in this case, I did C1 and C2. A union or an or statement is anything in A or anything in B. So it could be anything that's in both of them, it could be anything in one, or it could be anything in the other. As long as it's included in one of these sets, it would be included. I'll give some examples of this when we get into indexing, but before we do, I first wanted to get into how do you look for missing values. So there's two types of missing values that you might encounter in R. There's NA, or not applicable, which means that there's nothing there, and then there's NaN, which is not a number. And they're different because while not a number is also NA, NA does not necessarily mean that it's NaN, because NA just means that there's something not available that you could use. It could be a blank, it could be the NA value, it could be something that's not a number. For example, if you're trying to do some sort of modeling and you have a character string, right, instead of having a number. NaN, not a number, means exactly that. There is some data in that cell, but it is not a number. In some cases, the components of a vector may not be completely known. When an element of a value is not available, or it's a missing value, in a statistical sense, it's a place within a vector that may be reserved by assigning it this value NA. So the reason that R does this is rather than just ignore that positioning within a vector or a list or anything like that, what it does is it saves that space by putting that NA there as a placeholder. Now, this can be an issue sometimes because some models, if you have NAs, it will not work properly. So you have a couple ways you can deal with this. Some people will just delete the NAs. Some will impute the values to try to figure out what it could be. Some models actually deal with NAs fine. So this is something you have to consider when you're actually doing your modeling. But in general, any operation on an NA just becomes NA. So if I take all my values in a vector and I multiply it by 3, then NA times 3 is still NA. So the motivation for this is simply that if the specification of an operation is incomplete, the result cannot be known, so therefore is also not available. You can look for these NA values by using the command is.na, and then of course with whatever vector you're looking at. So this will give us the logical vector of the same size as our x value. So in this case, is.na x would give us a vector of the same size, and it would put a true if and only if its corresponding element within x is also NA. So let's look exactly at that. So here we're going to set the vector z as the values 1, 2, 3, and NA. So let's do that real quick. We have z, we're going to assign it as 1 through 3 and NA. And then, of course, as always, I'm going to do semicolon z so we can actually see our handiwork once I've run the command. So you can see here now at the bottom that it is 1, 2, 3, NA. So now what we're going to do is we're going to use the is.na command on our z vector. And if we run that, you will see that we get the output false, 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 true, because the first three numbers, 1, 2, and 3, are not NA. They're not missing. There's no held spot with nothing in it. But the fourth spot is an NA, so therefore it gets a logical outcome of true. So now what we're going to do is we're going to create an index. So we'll do end, and this is just going to be my is.na z. And now what I've done is I've actually created an object where I have this outcome. Now, again, you might wonder why I'm doing this. This might be because if I wanted to index something where I only wanted to grab values that have outcomes in them, I could use this as the index, basically where it is equal to true. So what it would do whenever I do this, it would go through and it would take the first value, the second value, the third value, the ones that are true. But then when it sees that NA, where it is false, that there is rather vice versa. It's false that it's NA. So the first three, 1, 2, and 3, have a number in them. The fourth one is true for is.na, so it would ignore that fourth position and therefore would only use the first three. But before we jump into more on vectors, I did want to take a quick aside to talk a little bit about character strings, because we're going to be encountering this more. And you might wonder, why am I putting this in now before we jump deeper into indexing if I'm already kind of getting started on this? And it's because it all is kind of intertwined. And some of the examples I'm going to be using, I'm going to be interweaving indexing with NAs with strings. So character strings are entered either using double quotes or single quotes, but they're printed using double quotes or sometimes without quotes. So this actually can cause a huge issue. And I will give everyone a warning right now. I have been known to do this on assignments where I will give students a bunch of data. I will give them some task to do with it, and it fails miserably. And it's because while they're seeing the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that, what's actually in the computer is the character 1, the character 2, the character 3. So the problem with whenever you're dealing with strings, oftentimes we think of as words or letters, right? So A is a string. The word about is a string. But numbers can also be strings because they can just be a label. For example, if I'm looking at watching some sporting event or something like that, and the players have numbers on them, that number does not have some sort of numeric meaning. It is a label. Player 1, player 3. So you could think of that sort of similarly to what a string is. If I put a 1 within quotes, R is going to see it as the label 1, the string 1, not the number 1. So for example, let's just do one of these off the top of our head real quick. If I take 1 within quotes and then I add it to 2, what's going to happen is it's going to say we have a non-numeric argument in the binary operator. This is because it does not see that 1 as the number 1. It sees it as the label 1, which is, again, a character string. So this is why I kind of want to talk about this, because when we're doing indexing, I have some examples where we're going to be using character strings. We can also sometimes run into issues with character strings, though, where you might have characters that you can't use within a character string. They use a C-style escape sequence using backslash as the escape character. So double backslash is entered and printed as double backslash. And inside double quotes, the quote is entered as backslash quote. These escape sequences are ways that you can actually add formatting and special things into a character string that would be illegal otherwise. For example, if I wanted to put quotes within my string, that's going to throw off R, because if I have my outer quotes and I put my inner quotes, what R is going to see is it's going to see the first 2 quotes and think that's a string. It's going to see the second 2 quotes and think that's a string, not one whole string with a quote inside of it. For example, if I was quoting something within a sentence string. So what we could do is you could use an escape character to specify that this character is not actually part of, this illegal character, whatever it is not actually part of, the string. It's not like the actual quote, so therefore it won't end the string. So some other useful escape sequences are backslash in if you want to have a new line, backslash T if you want to add a space or a tab, and backslash B for a backspace. And you can check this out using question mark quotes or help quotes, and this can give you more information on that. Now, I will tell you, realistically, the most common place where I'm going to use this in R is whenever I'm doing graphing. And it's because, let's say that I wanted to title my graph something, and it's a little bit long. Well, R is just going to list it off on the top of your graph. So what I would do is I would use this escape character of backslash in to create a new line, therefore creating multiple lines for my title rather than just having a long string title that's cutting off on the graph, things like that. Let's say that we have this str for string, and in quotes it says, here's an example of a string in R. And you'll notice that we have a quote within the character quote string. So I'm actually going to change it up a little bit because I actually tested this earlier and it looks like they've made R a bit smarter since when I created this slide, and it actually was able to recognize that. So what I'm going to do now instead is I'm going to actually change this to, I want this to have double quotes. So notice what's happening now. If you look at the coloration, character strings show up in R with this light green color. So by adding this string within quotes, what it's seeing is this part is one string, this part is another string, and string is just in the middle, which R is not going to have any idea what to do with this. But our next line, you can see I have the backslash there. I always have to play with these because I'll be honest, again, I don't use these very often. You'd have to play with the formatting a little bit. But either way, if I leave this one as single quote, it's still going to work, but it would work without it for this example. But the next example is what I actually really want to kind of show you. This is where I actually would use it. So notice we have the string now written as long \t lines can be \n broken with new lines. So remember, the B is going to backspace it, and the N is going to create a new line. So if I run this, what's going to happen now is I've created this string, and I'm going to use write lines string to actually write it. And this is why the first example would have failed if you just tried to run it, is you need to actually write it or print the command. And notice what happened is that it created this spacing, and then it broke it into a new line. So like I said, this is oftentimes where I'll actually use it when I have some title in a graph where it's too long, and then I just use \n. Realistically, that's the only thing I really use for this, but you may encounter situations where you do need to implement this. And like I said earlier, is you can always do question mark, I think it's capital quotes. Yeah, and this will give you a readout of all the different ones you can use, right? So you got new line, carriage return, tab, backspace, from read, vertical tab, \, things like that. Now, oftentimes when you're trying to create a string, it can be kind of annoying to work with. For example, like my students, when I give them these slides, they're in PowerPoint, and if you try to copy the code over, it does not copy over the quotes properly, meaning you have to unquote everything that's quoted in a character string, and then you have to requote it, which means I actually already did this, which is why you see all the lines of code afterwards, so I don't have to do this while I'm recording. I actually want to look now at the paste function. So the paste function takes on an arbitrary number of arguments and concatenates them one by one into character strings. Any number given among the arguments are coerced into character strings in a way that would be if they were printed. And this is what I was talking about, because a lot of times when we're creating these sequences, combining things, you could use something like the paste command. And if I were to take these numbers and paste them into something, it is going to coerce them or change them into a character string. And then later on, if I were to try to do analysis on this, it's not going to work because it's going to see it as characters, not as numbers. So the arguments by default are separated in the result by a single blank space. And then you can change this with the paste command using sep equals, and then within quotes, you put what you want the separator to be. This can be changed by a name parameter, right? So sep equals string. You could put dash if you want to be like first thing dash second thing. You could actually just put the quotes together where there's no space. That'll get rid of the space. You could put a period, and this would tell you how are you separating the two things that you were pasting together. Again, it will change it into a string, and it is possible to have empty outcomes when you paste things together. Okay, because when you paste them, you're going to tell it exactly how you want it to be pasted together. Now we're going to look at an example. We have labs, the object is being set as paste, and then we're going to concatenate the strings x and y with the numbers 1 through 10. And we're going to separate it by nothing, right? So there's nothing between those quotes, meaning that we're not going to have any separation between them. When I mentioned the default is one space, that means if I didn't include that separate or sep attribute, then it would put the first thing pasted with the second thing with a space between them. But instead, because I specified I want separation of, and I put nothing between the single quotes, that means that it's not going to have any space between them. So what this is going to do is this is going to paste, and remember we talked about this, when you're bringing two vectors together, it's going to do one by one. So it's going to go x, and it's going to paste it to 1. And then it's going to take y, and it's going to paste it to the next value in the sequence 2. And then the next value in that sequence is 3, but there's nothing left in x and y. So it's going to recycle, go back to x. So it's going to be x3, y4, x5, y6. So let's try it out. So we have labs. We're going to paste this together. Like I said, I already typed this in, so I don't have to undo and undo the quotes again. And you'll see that we got the outcomes x1, y2, x3, y4, x5, y6, x7, y8, x9, y10. But notice that each of these are within quotes. That means that they are character strings. For example, if I wanted to change this, let's say that I wanted to, instead of doing x and y, I'm going to do, I'm just going to take 3 and 4. So I'm going to paste 3 and 4 into 1 through 10. But notice what we get. we got them coerced into character strings. If you look at the bottom, all of these 3-1, 4-2, 3-3, these are all character strings. These are not numbers. This is the thing you have to be careful about. Remember, I talked about the fact that you might look at, is.na, things like this. You might be looking for, is it a number? No, this is a character string. So what about, let's actually do some examples messing with this separation. If I were to put actually, let me just do this real quick. If I were to get rid of this separation, what's going to happen? By default, they're going to have a space between them. So now the first one is 3-1, 4-2 instead of 31-42. But similarly, I could also change this and I could put, for example, like a period between them. And now it's going to be 3.1, 4.2, 3.3. I could put a dash between them. So this separator is just how you're going to separate them. In the last video, I mentioned when we were looking at repeating the rep command, how you could use this to create different sets of data based on whatever it is you're trying to do. And I asked everyone to try to create a deck of cards using the rep command, and I mentioned that you would have to use paste. So I've actually done that. In fact, if you look below this in the code, I've actually done it 2 different ways. So let's look at what I did. I have cards, this is the object, and what I'm doing is I'm pasting. So what I'm going to do is I'm going to repeat the numbers. So I'm going to concatenate the numbers 2 through 10, Jack, Queen, King, and Ace. And you'll notice for each of these letters, I had to put them in quotes, because if they weren't in quotes, what's going to happen is that it's not going to know what to do with this, because J is not a thing. So if I were to try to run this, it's going to say this object J is not found. But by putting it into quotes, it will recognize that this is the character J, the letter. So what I've done then is this first part, this rep 2 through 10, Jack, Queen, King, and Ace, this is the type of card within a suit. And what I've told it to do is I've told it to repeat that 4 times. So if I were to just look at this repeat statement, what this is going to do is it's going to give me 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace, and then it's going to go back and it's going to do the whole thing. Actually, no, sorry, it's each. Each is going to do 2, 2, 2, 2, 3, 3, 3, 3, 3. It's going to do each of them 4 times. So if I were to do this, you'll see that I have 2, 2, 2, 2, 3, 3, 3, 3, and it's going to do this for every single thing within this repeat statement. Then I have the next repeat statement. So for this one, I did times 13, which means it's going to go through the entire cycle 13 times, meaning it's going to go heart, diamond, club, spade, and then it's going to recycle back. It's going to do a second time, heart, diamond, club, spade. It's going to recycle, do it a 3rd time, 4th time, until it does 13 times. Then once I've got these 2, actually, let's run it real quick. So you'll see here, heart, diamond, club, spade, heart, diamond, club, spade. It's going to repeat that 13 times. Then I'm going to take these 2 repeated sequences and I'm going to paste them together, and I put no separation between them, but you could if you wanted to. Let's see what happens when we run this. So I'm going to unselect this code. I'm going to run it, and then I'm going to run cards. And you will see that we have 2 of hearts, 2 of diamonds, 2 of clubs, 2 of spades, 3 of hearts, 3 of diamonds, 3 of clubs, 3 of spades. And it follows this sequence all the way through. But you may actually want to do it a little bit differently. Let's say instead of it being the 2s and then the 3s and then the 4s, you want to put them together by suit. Okay, you could do that as well. So what I've done now is, for cards 2, I've changed it so we've got repeat 2 through 10, Jack, Queen, King, Ace 4 times, meaning that it's going to cycle through. So it's going to go 2 through Ace, it's going to go back 2 through Ace, and do it 4 times. For my second repeat, I've got hearts, diamonds, club, spade, where now it's going to repeat each individual one 13 times. So it's going to be heart, heart, heart 13 times, diamond 13 times, club 13 times, spade 13 times. Now I'm going to bring these together using my paste command, and I'm going to see what I got. And I got 2 of hearts, 3 of hearts, 4 of hearts, 5 of hearts, all the way through Ace of hearts. And then it's going to go to 2 of diamonds, 3 of diamonds, 4 of diamonds. So with this, I've now, with a lot shorter method than typing out every possible card, I was able to create a deck of cards using the paste and the rep command or function in R. But one thing I do want to warn you about is, again, remember, whenever you do any sort of paste in R, it is going to coerce it into a character string, even if it's numeric. I will talk a little bit at the end of this lesson, how can you actually coerce it into being numeric. So looking at our slide, this paste that we did with our labs previously, before I start talking about cards, would be equivalent to typing out C parentheses quote x1 comma quote y2 comma I don't want to type this out, right? Because what if this sequence was much longer? This is where, again, your paste command can be really useful. If you have some repeating pattern that you want to create, but you don't want to type out a ton of these character strings. So now that we understand character strings a little bit better, let's talk about index vectors, specifically selecting and modifying subsets of our data set. So first things first, remember we set our z as 1, 2, 3, and NA. So now what we're going to do is we're going to create a new object called y, where I'm going to select z, and the square brackets are saying, okay, now within z, I want to select something specific, and I'm going to put is.na. So it's only going to select what is.na. So let's do that. So we have y is going to be z is.na z. And then if I look at y, what I'm going to get is my one outcome that is NA. But notice, remember I talked about the fact that when I run this, right, because I could do it without actually labeling it to some object y, it's going to give me this NA. But I didn't actually change z. All I did is I selected the elements within z that are NA, and I didn't change z. So if I were to run z, notice that it's still 1, 2, 3, NA. So you might wonder, why would we want to specifically determine which value is NA? When it gives us the output, it just tells us NA. There's one single NA. It doesn't tell us which one is indexed, but it's actually there. So where this is really useful is, what if you wanted to select the values that are not NA? Well, remember when we were talking about our logical operators, I mentioned that exclamation point is the way in computer programming to say not. So let's change this up a little bit, and we're going to say y is the object where we're going to select z, right? So that's how whenever we're indexing, we do this. What vector are we looking at? Z. Square bracket. Within that vector, or list, or matrix, whatever z represents, what are we selecting? And we're selecting currently the values that are NA. So what we're going to do is we're going to change that to exclamation point is.na z. So that's going to say, from the vector z, which is 1, 2, 3, NA, I want you to select everything that's not NA. And now if we run this, what do we get? We only get 1, 2, 3. So by doing this, I actually eliminated the NA from the data. Now I didn't eliminate it from the z, right? Because remember, R is immutable. I didn't change z. I created y to be this value. And this can be really useful, because if I have tens of thousands of numbers and there's a couple NAs sprinkled in there, rather than going through and manually finding where the NAs are, I could just say, give me the data without any of the NAs, right? So for example, let's say that we wanted to take the mean of z. It's going to say NA. Why is that? Well, it's because I can't take the mean if there's an NA in there, because it's trying to add up all the numbers. And how do you add up a not a number, right? We talked about the fact that if you do an operation on an NA value, that you're going to get NA back. So what we're going to do, same idea. We're just going to say, okay, well, what I want to do is from z, I want to select within it not is.na for z. And now, oops, I did a tilde instead of an exclamation point. And now I got the mean of the values within z that are not NA, so 1, 2, 3, and I got a mean of 2. So this is where this can be very useful, because these square brackets allow you to select within your vector, again, or matrix, or list, or data frame. And this is.na can allow us to use a logic statement to only select some of the values. We can also use these square brackets to create other vectors. For example, let's say that we have x is going to be whatever is within x, 1 through 10, right? So let's actually create some sort of x. What I'm going to do here is I'm going to use this x that's down below it. So we have x is 1 to 20, right? So I'll just run my x just so you can kind of see it. So it's 1 through 20. Then if I were to put the command that I had on that slide, where x is going to be x with square bracket 1 through 10, now what I'm saying is this. I'm saying from x, which I just said was 1 to 20, I want you to go in there and only select the values for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Because 1:10 is a sequence of numbers 1 to 10. So if I were to just run that, it would be the numbers 1 through 10. So then again, by setting this object x to this, I now have reset x because I use this arrow operator, which means I have now actually changed x, and my x is going to be 1 through 10. So we're looking at this next example I had. This is where we're using the sub part to say within this x and y, what I want you to do is repeat it 1, 2, 2, 1, where these are going to act as labels, first position index, second index. So what this is going to give us is x, y, y, x, and then we're telling it to repeat 4 times. So when we run that, we get x, y, y, x, x, y, y, x, x, y, y, x, x, y, y, x. There's a lot you can do with indexing and selecting subsets from your data. In fact, you're going to be doing that a lot when you're programming with R, especially when you start dealing with data frames and matrices, which I'll briefly talk about, but for now we're going to focus on vectors just for kind of explaining all these different parts. What about if we have a vector of a negative integral quantity? So here we have y, the object, is x, but it's going to be negative, and then we have the sequence 1 to 5. So let's try it. So first things first, before we do that, let's actually look at what is currently assigned to y. So I'm going to run it. Okay, I have the values 1, 2, 3. So actually, I'm going to reset this. I'm going to set x as 1 through 20. So y is going to be x, but notice I have negative the sequence 1 to 5, y. So what do you think this is going to do? Well, what it's going to do is this is telling it my y is going to be everything that's in x, but then I'm going to subset it and say not including. That's what this minus within the parentheses is doing, is it's saying not including the index 1, 2, 3, 4, 5, or the first 5 numbers. Similarly, I could do the same sort of thing. Y1 is, again, from my vector x. I'm going to not include the numbers 1, 2, or 3, and therefore it'll just be everything else. So if I run this, I'll get 4, 5, 6 through 20. Now, one thing I want to point out, because a lot of times when I do these examples, I'll just do like 1 to 20, and it might throw off some confusion. It's not getting rid of the numbers 1, 2, 3, 4, 5, or 1, 2, 3. It's getting rid of the first index. So what I'm going to do is I'm going to change one more thing. I'm going to change my original x from 1 to 20 to 3 to 20. So now when I run y, not including the first 5, notice it does not include 3, 4, 5, 6, or 7. It starts at 8. Similarly, if I don't include for y1, 1, 2, or 3 from my x, it will not include 3, 4, 5. It'll start at 6, so 6, 7, 8, 9 to up to 20. When you have that not include 1 through 5, it's not omitting the numbers 1 through 5, it's omitting index 1, the first number, index 2, the second number, index 3, the third number, and so on. We can also make a character of vector strings, and this can be really useful if you want to create something with labels. So it's possible, only applies where an object has a name attribute to identify its components. In this case, a subvector of the names vector may be used in the same way as positive integral labels an item 2 further above. So what this means is first we're going to start with fruit, and we're going to concatenate the numbers 5, 10, 1, and 20. So this is going to represent some sort of quantity for fruit. Next, what we're going to do is we're going to use the names command. So names for fruit is going to be, we're going to concatenate the words orange, banana, apple, and peach. So what it's going to do is for those 4 numbers that we originally set to fruits, it is going to assign each of those names that we just said. So orange will be assigned to 5, banana will be assigned to 10, apple will be assigned to 1, and peach will be assigned to 20. So let's do exactly that. But before we do that, let's actually label our fruits. What happens if I just put the names command? So I put names fruit. And notice it's going to say no. There are no names associated with this vector fruit, which if I look at the vector fruit, you will see that it is those 4 numbers, 5, 10, 1, and 20. So now what we're going to do is we're going to use the names function, telling it specifically the names for fruit, and we're going to assign something. So that's what we're doing here. Is we're saying, okay, we're not assigning something to fruit now. We're assigning something to names, which is an attribute within fruit, or a subvector, and we're going to assign specific values to that. So we're assigning orange, banana, apple, and peach. So let's do that. And now if I just run names fruit, what's going to happen is it's going to tell me what names there are for fruit, which is orange, banana, apple, and peach. Just like before, we can then create some sort of subset from this. So right now we have fruit, which if I were to just run fruit, you are going to see that it is going to have two different values. It is going to have the name of a category, and it's also going to have the number. So for orange, we have 5 oranges, we got 10 bananas, we got 1 apple, we got 1 peach. What we can do is we can create a small lunch, so we're going to call this object lunch, where we're going to pull from our fruit, and we are going to specifically choose banana. So that's going to be our lunch. So if we do that, you'll see that our lunch is made up of 10 bananas. I know the example doesn't really make sense, but just go with it. Or instead, we could, again, within this subindex, we could use our concatenate to select more than one object. So we have lunch, in this case, is being assigned as fruit, which remember, it's immutable. We didn't change fruit. And this is going to be made up of the concatenated values for apple and orange. So what we're doing is we are indexing within this vector, which now has names, by using the name instead of the number. Instead of selecting index 1, 2, 3, or 4, because oftentimes you're not going, if you have a lot of data, a lot of columns of data, for example, in a matrix, you are not going to want to go and try to figure out which index it is numerically. So let me show you a more specific example. Again, this is where I'm going to go back to MT cars. If I pull up MT cars, this is, oops, added an A. If I go to MT cars, it is data for some cars where we have things like miles per gallon, cylinders, displacement, horsepower, things like that, quarter second time. So if I want to grab something, some specific variable from this, let's say I wanted to grab miles per gallon, I can do that. Now, the way you can do this whenever you are using names for something that has these names already attributed to it is you could do MT cars, put a money sign, and then you just put what the name is. So for miles per gallon, it would be MPG. And this will list out all the data from MT cars associated with miles per gallon. So basically just those numbers that were in the column, you just listed them out now. But a lot of times when I get new data, the first thing I want to do is I want to know what are the labels to this. Now, most people, when they send it to me, it's like X1, Y1, things like that. But the way you can do this using that names command is names, and then we're going to do MT cars, and notice what it does. It tells me exactly what the names are. Miles per gallon, or MPG, cylinders, displacement, horsepower. Now I have the names, so I don't have to guess what's available to me. And I can refer to these specifically by their name in the vector rather than going through and trying to say like index column 1 or 4, things like that. I could index by column, right? Because let's say that I do this command. If I use dim MT cars, it's going to give me the dimensions. This is a 32 by 11 matrix. Well, specifically, it's a data frame because there's text in there as well. So what I'm going to do is I'm going to index from this. So MT cars, right? So I want to get a subset of the data. Well, now for a matrix or a data frame, you have to have two pieces of information, your rows and your columns. So what I'm going to do is I'm going to not put anything for my row. So I'm going to just put blank, put a comma, and then I'm going to specifically select the second index or second column for indexing MT cars. Okay, and then what I got from that is I got cylinders. So 66468, blah, blah, blah. Notice down here, 66468, blah, blah, blah. So what I did in this case is I indexed a particular column instead of using its name. Where you might want to do this is oftentimes when someone is going to send you data, you are going to have labels for your X, but that's going to be part of the data. Your Y, your columns will be labeled with some name, but generally you're not going to have some X names. So what you might want to do is you might want to index specific X value. So if I go back to MT cars, I'm not going to select a column, but what I'm going to do is I'm going to tell it I want to select the first 5 rows. So in my first part before the comma, I'm going to put 1:5 for the sequence 1, 2, 3, 4, 5, and you will see that it grabs the first 5 rows of my data. And it doesn't have to be the first 5. I could do instead, I could say I want 6 through 9. And and this will give me the 6th, 7th, 8th, and 9th rows of my data. Similarly, I could make it more complex. I could concatenate this and say I want 6 through 9 and 13. And what it did now is now I have the rows 6, 7, 8, 9, and 13. So you can do a lot with this. As you get really comfortable with using this subsetting, it actually opens up a lot of functionality. And again, it really helps to manipulate your data, to change your data. Remember, we talked previously about the transforming your data, getting into the right form, all this kind of stuff. This is going to be a big part of it. Your exploratory data analysis, your data cleaning. And I will tell you right now that whenever you're doing a project, your data cleaning and data wrangling will be more of it than you predict, and your analysis will be a lot less than you predict. So now let's talk about modifying these subsets. So if you look at this code here, we have X is going to be the numbers 1 through 5, NA, NA, NA. And then what we're going to do is we're going to use X in the subset is.nax. So we're going to take X, we're going to specifically select the NA values, and then we're going to set that equal to 0. Let's see what happens. So if we set up our X, you can see it's 1, 2, 3, 4, 5, NA, NA, NA. So what this is going to do is it's going to take X, again, the subset, the ones that are NA, and it's going to replace it with 0. So now if I look at X, it is 1, 2, 3, 4, 5, 0, 0, 0. And oftentimes this would be something you might want to do depending on what you're trying to attempt to do. For example, when I'm doing grades using Canvas, some things will not automatically populate with a 0, right? So for example, I use Gradescope for exams. When I transfer the grades from Gradescope to Canvas, any student who has a grade gets a grade. Any student who does not have a grade in Gradescope, it leaves it blank. It does not automatically put a 0. So what I can do is when I pull up, I can export this in Excel, and I can pull it up in R, and I could do exactly this command. For the column, which I'll use my subscript, where I can determine which column it is, let's say column like 32, I could use is.na, which means there's nothing there, and I can set it equal to 0, and it will automatically populate those blank spaces, or NAs, with zeros, right? So this is really powerful, especially if you're trying to do a lot of manipulation on a lot of data at one time. You don't want to manually go in and have to add all these zeros, especially because our classes can be hundreds of students. It would take all day to do these kind of things. Another example of changing or modifying our subvector is the third line, which is y, and we're going to select all the values of y which are less than 0, and we're just going to change them. We're going to replace them with negative y where y is less than 0. So we're going to take all the values that are negative, and we're going to replace them with the negative of that. So before we do that, first things first, let's figure out what our y is. So I actually set a new y here because when I'm doing this in class, I have a certain order I'm doing it in, and sometimes it will line up where I'm like, I already have a y set up and we've been talking about it, but just to be safe, I'm going to set a new y. So I'm going to set y as -5 through 10. So you can see here, -5, 4, -3, -2, -1, 0, up to 10. So if I do this, I'm going to select the values that are less than 0, right? So if I just did this, y less than 0, you're going to see the first few are true. So true, 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 true. Those first 5 are negative. So now what I'm going to do is if I select y where they're negative, it's going to be those first 5, -5, -4, -3, -2, -1. The second one, what it's going to do is I'm going to take those values, -5, -4, -3, -2, -1, and I'm just going to take the negative of it. So looking at this, this would make it positive 5, 4, 3, 2, 1. So by doing this, by setting it equal, what I'm doing is I'm now taking those specific negative numbers, -5 through -1, and I'm replacing them with the inverse of them, or positives, and I'm going to get a new y, which is 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, 7, 8, 9, 10. Now, another way I could have done this even easier is sometimes using the functions within R, right? Instead of having to go and manually say, okay, grab all the values that are less than 0, now make them negative of the negative, which makes it positive. I could just use the function apps for absolute value. So ABS, absolute value of y, and I will get the same outcome. So before I do that, let me reset my y. So you see again, my y now includes the negatives again. If I run absolute value, I get the exact same thing. Okay, so now we've already seen some examples where how we're going to get one element of a vector by indicating its position between square brackets, but it also can allow us to use vectors within those brackets. And there's several type of index vectors we can use. So for example, we could use logical vectors. We've already looked at an example like that, where I took all my y values where it was less than 0. I was using a logical vector to give me a vector within my vector. Another example though, let's say we have this. X is going to be 0, -3, 4, -1, so on and so forth. So in that case, now we have this X, and what we're going to do is we're going to take all the X values that are greater than 0. So X greater than 0, you get false, false, true, false, true, true, false. So now what I'm going to do is I'm going to set Y, where it's going to be all the X, it's going to be X greater than 0. So if I look at my Y, it's just going to be that vector, right? This is a vector of true or false logical statements. Now I'm going to subset my X by taking the values of Y. This is where they are true. That means that these are values where X is greater than 0. And this will then give me 4, 45, and 90. It's only selecting the values of X that are greater than 0. So in truth, this would be the same as basically selecting the 3rd, 5th, or 6th element. And so I could do exactly that. Instead of saying, okay, well, I'm going to create a vector and all that kind of stuff, I could have said X square bracket concatenate, and I said, what was it, 3, 5th, and 6th? There'll be 3, 5, 6. And you'd see that we get the exact same thing. But instead of doing it manually, where I have to figure out which elements within my vector are positive, what I can do instead is I could just say, grab all the ones that are positive, output that only. Incidentally, you also could have done this just by saying X and then square bracket, select any X that is greater than 0. That would also work as well. Now, remember we mentioned the intersection and union statements. So the way you can do this is you can use your logical operators, which are available in R. So the vertical line is your OR statement, meaning that if I have this first statement here, within X, I'm going to index X, which is less than or equal to -2, or X is greater than 5. This means that it will take any value that is less than or equal to, or also it will take any value that is greater than 5. So if I have the value -3, it'll take it. If I have the value 7, it'll take it. If I have a value that is not true for either of these, for example, let's say it's 0. 0 is not less than or equal to -2. 0 is not greater than 5. It would not be included. The AND symbol is how you would do an AND statement. So for the second one, we have X, where X is greater than 40, and X is less than 100, meaning it is going to select values that are greater than 40, but also less than 100. So only between those two, not inclusive, because notice there's no equals here. So if we were to do this, you'll see that from our X's, right, just a reminder, X is -0, -3, 4, -1, 45, 90, -5. When we took the X values that are less than or equal to -2, or greater than 5, it gave us -3, because that's less than -2, 45, because that's greater than 5, 90, because it's greater than 5, and -5, because it's less than -2. Our next one, we have our AND statement, where it has to be greater than 40 and also less than 100. So if we look at these values here, 0, no, -3, no, 4, no, -1, no, -1, no, 45, yes, 45 is between 40 and 100, 90 between 40 and 100, and -5, no. So if we run this, you'll see that we only get 45 and 90. So as you may have guessed, again, the vertical line is our logical disjunction, or specifically it is our OR statement, union, while the AND symbol is used for conjunction or our intersection. This means that the first instruction shows us the elements of X that are either less than or equal to -2 or greater than 5. The second example presents elements of X that are both greater than 40 and also less than 100. R also will allow us to use a vector of integers to extract elements from a vector. So, for example, alternatively, you may use a vector with negative indices to indicate which negative integer elements are to be excluded from the selection. So if we did X and then square bracket -1, we're telling it do not include that first element, right? So just a reminder, X is 0, -3, so on and so forth. If I do this -1, notice it drops the first indexed item. I told it do not include index 1, which in this case was 0. I could also concatenate to not include multiple elements. So in this case, we have X do not include, so negative, C, 4, and 6, meaning it is going to exclude the 4th and the 6th elements. So we got 0, -3, 4, 45, -5. You also could do something like this, where first things first, I'm going to set this new object pH as 4.5, 7, 7.3, 8.2, 6.3. I'm going to then label them with names, area 1, area 2, mud, dam, or middle. This is pH level at these locations. So now if I look at pH, you will see that we have these names or labels for the different amount of whatever this data represents, the pH level. I can index specifically by using the name, but notice that I have to put it in a quote, because if I don't have this quote, remember, it's not going to know what mud is. But by having this quote, I am telling it the character string of the name mud, and so therefore, I actually needed it in double quotes. That was my fault. And so what I did here is I actually was able to select it by its name. And just like before, even if I am using the names within to select my subvector, what I can actually do is I could use concatenate to select more than one at a time. So what this means is that I could take pH and I could select area 1 and dam, and I would get both of their pH levels at the same time. So for our last example here, let's talk now about how can we purposely coerce our data into a different form. So first thing we're gonna do is we're gonna set our object Z as the numbers 0 through 9. And then I'm going to create a new object, digits, and I'm going to use the as.character Z. So I'm going to specifically take the values 0 through 9 in Z, and I'm going to tell it to treat it as a character. So let's do exactly that. So we look at Z. Z is the numbers, right? And look, I can even do this. Type of Z, and it will tell me that these are integer values. But now what I'm going to do is I'm going to use digits, which is as characters, so it's going to be the same values from Z, but now they are characters. These are character strings. So now if I do type of digits, you will see that it tells me that it is character. So again, this is where it can be really useful to double check whenever you get some data. If you're trying to do something and you're getting some sort of error about, not being able to distinguish the number or something like that, this may be why, because maybe while you, as the human, see these numbers, the computer doesn't see 0 through 9, it sees the label 0, or the character 0, the character 1, the character 2, through the character 9. And one thing I also want to show is that if you run this as.character Z, it will give us these strings for 0 through 9. But notice it didn't actually change Z, because again, R is immutable. We didn't change Z, all we did was in that instance manipulate it, but then as soon as you're done with that command, it still is whatever it was. We could also use as.integer, which will take those character string if they are numeric, and it will convert it to numbers, right? So this character string, and it took 0, it said, okay, 0 is equivalent to a number, I can make that a number. 1, that's also a number, I can make that a number. And so now we did is we set this new object as D, which is the values of digits, which were the character 0, the character 1, the character 2, and it changed it to numeric. One last thing I'll do, and then we'll be done with this section, or this video, is what if, I'm just gonna, I'm gonna call this one like XZ, because that's not a variable I've used. What if I have something that's kind of mixed? So let's say that I'm gonna concatenate, and I'm gonna get A, I'm gonna get B, and then I'm going to get the values, 3 through 5. So XZ is A, B, 3, 4, 5. But look what it did. I didn't set 3, 4, and 5 as character strings, and yet they are character strings. I'll talk more about this later, but what it did is it automatically coerced them into being character strings because this is a vector, and vectors have to have the same type of character. So what would happen if I did as.numeric on my object xz? So if I were to run that, notice that it says it's NA 3, 4, 5, and it warns me, warning message, NA is introduced by coercion, because what I did is I manually forced it, turn these into numbers, and it did its best. It said A, That's not a number. I don't know what to do. NA. It's just not a number. Or not a number. It doesn't exist. B. Can't turn that into a number, so it gives me an NA. 3, 4, and 5, though, those can be changed and coerced into numbers. So this is one place where, again, you might get NAs when you're trying to manually convert things. So this is something we'll talk more about later in the course, but I wanted to kind of introduce it now so you could get an idea of, one, how to index, but also some of the ways that you might be able to coerce your data into a different form, but also places where you might get NAs. But thankfully, as we've talked about in this lesson, you now know how to handle and find NAs by indexing within your vectors. Hello everyone, we're going to go back to sequences now. So R has a number of facilities for generating commonly used sequences of numbers. For example, we've looked previously at using our colon function, for example, 1:30, which would then give us the sequence of numbers 1 to 30, which again would just be a vector you could write out as C parentheses and then list out the numbers 1, 2, 3, 4, 5, up to 30. But we don't really want to do that. Now, one thing I did mention previously is that our colon operator does have high priority within an expression. So for example, if we had 2 times 1:30, so that means that you're gonna have 2 times the sequence 1 to 15. What it's gonna do is it is first going to create the sequence 1, 2, 3, 4, 5, 6 up to 15. Then it is gonna multiply by 2. So this would give us 2. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So what it's going to do is it is going to first create the sequence and then it is going to multiply by 2 because the colon operator will get priority over the multiplication operation. And as we mentioned previously, if you were to switch the values, instead of 1:30, you did 30:1, it would give us a sequence in descending order. We also talked previously that you could use the seq or seq function to create sequences where we could set starting point from, you could set your end point, which would be 2. You could set by how big of jumps you wanted to do, or length, how many jumps you want to do. Now we're going to look at some functions that are built into R to create sequences or some sort of series of numbers randomly generated using different probability distributions within R. R has several functions that can be used to generate random sequences according to a random sequence large set of probability density functions. Functions have a generic structure, for example, R and then the function based on what kind of distribution you're looking at. And then generally it'll have N, how many values do you want to create? And then it'll have some parameter or attribute. So par1, par2, these represent the different attributes. So func in this case would be whatever the density function is that you're looking at. So for example, you might have a normal distribution, a binomial, a Poisson, a Weibull distribution, things like that. And there are a lot of these built into R. Now, there are other distributions you might want to use that aren't built into R, which have packages likely that you can pull to create sequences from those distributions as well. For example, if I wanted to randomly pull from a normal distribution and create 10 random numbers, let's say from a standard normal, so mean of 0 and a standard deviation of 1, I could just use R norm for normal distribution. An example of this would be R norm 10. As always, before we actually do any of these functions, let's first start by getting some help. So we're going to do question R norm, and I'm going to run this. And if we look here at R norm, we are going to see that its attributes are N, mean equals 0, and SD equals 1. This means that the first attribute by position is N. How many numbers do we want to create? The second attribute, mean, tells us what the mean is going to be. When it has equals to 0, means that by default, if we do not define it, it will be a mean of 0. The third attribute, SD equals 1, means that the third attribute is the standard deviation. And if we don't include a standard deviation, it will default to 1. So this is a standard normal. This means that if I were to put the code just like it was in the slide, R norm 10, and you see that it kind of helped autocomplete there if I wanted it to. What it's going to do is it's going to randomly generate, so pseudo-randomly generate 10 numbers from a standard normal distribution. So R norm 10, and it creates 10 numbers. If I wanted to create 100 numbers, I could change this to 100, and it will randomly generate 100 numbers from a standard normal. If I wanted to change this, let's say I wanted to have a mean of 36, so mean equals 36, and I want a standard deviation of, let's say, 4. So I'd put SD equals 4. So now it's going to create 100 numbers from a normal distribution, which now has a mean of 36 and a standard deviation of 4. Do that. Again, I've got 100 numbers pulled from this normal distribution. Now, because I'm using, I could use the names or I could use the position. So this means that I actually don't need to specify, if they're in the correct order, that SD is 4 and mean is 36. I could just put rnorm 100, 36, 4, and it would also generate 100 values from a normal distribution with a mean of 36 and a standard deviation of 4. If I wanted to put them in a different order, this is where I would specifically have to label them. So for example, I could change this. If I want to do the same thing, I could put SD equals 4, comma, mean equals, I don't know, whatever it was, 36. And if I run this, it would do the same thing. And you can see in the slide, we have an example just like this. If you prefer a mean of 10 and a standard deviation of 3, you would just change it to rnorm 10, and you could put comma 10, comma 3. Or you could specify mean equals 10, SD equals 3, which is sometimes kind of nice. I a lot of times will do this, so when I'm looking back at the code, I don't have to go back and remember what order they're in. Even though you don't have to put the labels for the attributes if they're in the proper order, it's still a lot of times useful for making your code a lot more readable. If I wanted to do a student t distribution, the student t distribution function is t. So for example, if I wanted this, I would have to specify my degrees of freedom. So you might see something like RT and then 5 and then degrees of freedom is equal to 10, which there's a typo there on my slides. But if we just do, as before, a quick question mark, and then I want to do RT for creating random numbers from a t distribution, you will see that the attributes are n, the number of values you want to create, df, that would be the degrees of freedom, and then of course ncp would be non-centrality parameter, but we're not going to focus on that for now. So this means that if I wanted to create 5 numbers from a student t distribution with 10 degrees of freedom, so I could put df equals 10, then what will happen is I'm going to get 5 numbers from a student t distribution with degrees of freedom 10. If I wanted to change this instead to degrees of freedom 22, just change df equals 22 and run that, and now I've got 5 numbers from a student t distribution with degrees of freedom 22. And as before, the position means that if I didn't include the label df, it would still work just by putting 5, comma 22. It means I'm drawing 5 from a degrees of freedom of 22 based on position. Now there are a bunch of other ones. For example, if we wanted to do a binomial, it would be rbinom. So let's do question mark rbinom. And you will see that for our binomial, we need 3 factors. Notice that none of these are set by default. This means that if I only tried to do rbinom, and let's say I want to get 10 numbers, what's going to happen is it's not going to work. Because in order to get numbers from a binomial distribution, you have to specify the parameters. And the parameters are p, the probability of success, and n, the number of trials. So not to be confused with n from rbinom, that's the number of values we want. So it uses the attribute size. So if I wanted to, for example, say that I am getting 10 numbers where my binomial distribution is going to be that I'm going to flip 10 coins and I have a probability of success of 0.5. So just a generic, flipping 10 coins, and then I'm going to see how many heads I get, and I'm going to do that 10 times. This is going to tell me how many heads I got from each of these binomial trials. So I got 4 heads on the first one, 6 heads on the second, 4 on the third, 3 on the fourth, 6 on the fifth, so on and so forth. If I wanted to have a weighted coin, I could then change the third attribute, which again is my probability. Let's say I want to have a weighted coin, and it's got a probability of success of 7. Well, in that case, I could just change that to 0.7, and now I'm using a weighted coin with a probability of getting heads of 0.7. So now when I got my 10 binomial trials, the first one had 8 heads, second one had 6 heads, third one had 8 heads, fourth one had 7 heads, and so on. Similarly, you can do it for Poisson. You can do question mark r poise for Poisson, and in this one, It's again, R poise will give you random numbers generated from a Poisson distribution. N is how many of them you are going to generate. And then the second attribute is lambda, which we do have to specify. We have to specify what our lambda is. So remember, a Poisson distribution is for discrete things that happen periodically, not very often, and your lambda is the rate at which they occur. So in this case, you could pull from Poisson distribution, and there's a lot of different distributions that are built automatically into R. And this is what I was talking about previously about R has a lot of this basic statistical functionality built in. This is all base R. We have not loaded any packages because I'm actually on a fresh install of RStudio because I ran into an error while preparing for these videos. So I have nothing loaded in that's not base R currently. And yet all of this is built in. I can do this from right in this moment without adding anything to it. If there are distributions that are more rare, let's say I wanted to like inverse binomial and maybe it's not included in base R, that's when I could look at packages for doing just that. Now you might have noticed when I was doing those help functions on each of these distributions that I was getting multiple arguments at the same time. It wasn't just R poise, it was D, P, Q, and R poise, or norm, or binom. And this is because every continuous and discrete probability distribution in R utilizes a standard 4-letter prefix ecosystem. That is to say that these letters will actually give me a different thing. So these prefixes modify the root name of the distribution, so norm for normal, binom for binomial, poise for Poisson. D, so D norm, would give me a density or probability mass function, depending on if it is continuous or discrete. P norm would give me cumulative distribution function of, again, either discrete or continuous distribution. Q would give me the quantile function or the inverse CDF. And R is the one where it uses stochastic simulation to generate those numbers pseudo-randomly. So let's talk about each of these individually. I'm going to start at the bottom with R because that's the one we've already been talking about. So the R prefix uses pseudo-random number generation algorithms to simulate n independent and identically distributed, or IID, observations drawn from a specified parametric distribution. That is to say, whatever distribution we're using, it is going to randomly generate some number n observations, right? So if I say 10, it's going to generate 10 values. If I do 100, it's going to generate 100 values. If I do 10,000, it's going to generate 10,000 values. This actually we use quite a bit when we're doing simulation. When we want to simulate data, what we will do is we will a lot of times if we believe it's going to follow some distribution, like a normal distribution or student t, we can actually simulate by pulling these random numbers to simulate different outcomes that might occur based on whatever conditions we've set. Now, its core computational use, for example, would be things like conducting Monte Carlo simulations, empirical power analysis, bootstrap resampling methods, and evaluating stochastic statistical learning models. These are all things where you would need some random data. When you're doing Monte Carlo simulations, you're having different starting points, which you are doing by randomly generating based on some initial condition, usually a normal distribution. For power analysis, same thing. A lot of times we have certain assumptions, and we're going to assume things like normality. And from there, we would say, okay, based on this, if we were to run this test, what is the power of the test? Which, if you remember from Intro to Stats, the power is the probability that you would reject a false null hypothesis. So we can do this by saying, if it follows a normal distribution based on this center, what is the probability that that would actually occur? How strong is my test at rejecting false null hypotheses? Bootstrapping, this is just a sampling method to increase sample size. We'll talk a little bit about this in this course. And a lot of times, a lot of these statistical learning methods will rely on bootstrapping to begin with. For example, if you ever get into statistical learning and you're doing random forest, what it's going to do is it's going to bootstrap samples as it creates its random forest. It also does variable selection, and then from there you create your forests, your trees, and then you can aggregate a response. So the syntax for this would just be R function, so in this case R norm, and you'd put n, the number that you want to draw. In this case, your parameter 1, which for a normal distribution is mean, set what it's equal to. Your second parameter, if there is one. Not everything has more than one parameter. For example, the Poisson distribution that we looked at only had one parameter that you needed to include, which was lambda. And then I've got an example here, what we're going to do is we're going to create simulated data by taking a normal distribution with a mean of 0 and a standard deviation of 1, so it's standard normal. We're going to generate 1,000 values. And then what we're going to do is we're going to find the mean, and we're going to create a histogram based on that. And I will talk more about histograms when we get to the graphing portion of the course. So first thing we're going to do, we're going to create our simulated data. Looking down at the console below, remember I didn't actually tell it to show me the simulated data, but it is there. And if we look at our global environment on the right, you can see that simulated data is now there. So I can run mean on simulated data, and this is going to give me a mean of negative 0.01199,351. And now I can create a histogram where I'm going to have 30 breaks in this, and it's going to be a probability histogram, which just means that it's going to be using relative frequency. And now you can see the histogram from that randomly generated data, and you can get an idea of what the distribution looks like for those 1,000 data points that were generated using this simulation. Next, we have the D prefix, which will return the height of a probability density function curve, that is to say, f of x, at a specified value of x for a continuous variable. For discrete distributions, it will calculate the exact probability mass function, or PMF, at some value x. So basically, this can be used for things like plotting theoretical distribution curves or calculating the likelihood of observations in parametric estimation. That is things like maximum likelihood estimation. By the way, if you're interested in maximum likelihood estimation, I actually am currently also working on videos for mathematical statistics where I go more into detail on this, though it'll be a bit delayed from these. So the syntax for this would be something like, again, if I'm using normal distribution, it would be dnorm. So D, that's the prefix, norm, which distribution, and then x, which is going to be that x value that I want to find this for. Mean equals 0. That means that, again, I'm using a standard normal because I have a standard deviation of 1. So if we did this, we would say dnorm, for the example, 0, mean equals 0, SD equals 1. So from a standard normal, what is the probability that I would get 0? Now, one thing to remember is that for continuous, it is looking at the probability to the left of this. So let's look at this. And we get a probability of 0.3989423. Now, what I'm going to do is I'm going to run this again just to show you that this probability is not changing. It's because unlike the previous part where we were randomly generating numbers, this is going to be based on the probability distribution itself. So now what we're going to do is we're going to actually use this and to create a plot. So first things first, we're going to set our x values, which is going to be a sequence of -3 to 3 by 0.1. So right, that'll be -3, -2.9, -2.8, all the way till we get up to 3. We're then going to set our y values using dnorm based on our x values. We're going to be finding the probability density function based on each of these values. And this is going to be from a normal distribution with a mean of 0 and a standard deviation of 1. And then we are going to plot this. And you can see that this looks like a normal distribution. By the way, I think I misspoke earlier. I think I said that the probability to the left of 0 would be whatever it was. That's incorrect. That would be when we're doing the CDF, not the PDF. So ignore that. Speaking of, the P prefix, which is our cumulative distribution function, or CDF. So this means we're going to calculate the cumulative area under the probability curve up to a specific point. That is to say that if I'm going from, let's say, a normal distribution, we know that it goes from -infinity up to +infinity. If I put some value in there, it is going to tell me the probability to the left of this, for I guess for you all, this direction. So it's going to tell us the probability to the left of this value. So that is, say, f of q, which is our CDF at some value q, is just equal to the probability that our random variable x will be less than or equal to that value q. So this can be used for directly computing statistical p-values, can be used for critical tail regions, and for evaluating cumulative risk models. So the syntax for this is going to be p function, so in this case norm, and q. Q is going to be that value where you are looking to the left of. So it's saying, okay, the one with the probability to the left of this. Mean equals to 0 in this case again, because we're using standard normal. SD equals 1. And then there's one more attribute that we're adding on this time, which is lower tail equals true. This is saying that I want the probability to the left. If I were to change this to lower dot tail equals false, notice, by the way, true is capitalized. You can either do capital TRUE, or you can just do a capital T instead of putting the rest of the true. Similarly, if I wanted to change this to its right tail, it would be either capital F, A, L, S, E, or it could just be capital F for false. I typically write them out. I don't know why, it's just a habit I have. So let's actually do an example of this. So what we're saying is this, P norm, we want to know what is the probability to the left of 1.96 on a standard normal distribution. Of course, you all should know what this value is going to be based on our intro to stats material, which is going to be 0.975. And you all should know from our intro to stats class how much this is. Now, you might be kind of confused because when we did intro to stats, we would say that if I was looking at 1.96, right, if we were thinking about confidence intervals, that this should be 95% of the data. But remember, this is giving us a left tail test, which means it's everything to the left, which means it's that 95% that's in our confidence interval, plus that half of 0.05 or 0.025, which is why we get that 0.975. It's 97.5% of the data is to the left of the value 1.96. If I were to change this to lower tail equals false, right? Because notice the first one, I didn't include the lower dot tail equals true, because by default, it is going to be true, right? So if we did, again, if we, as always, question mark P norm, you will see that for P norm, lower dot tail equals true. That is the default. So you don't have to include it if you want the left side. If you want the right side, though, you do have to specify lower dot tail equals false. Or, again, you could use the positional information, right? This is the third position. You could just put, the fourth position. So you could just put false there. So if we did this, this is going to tell us what is to the right of the value 1.96, which should be 0.025. 0.0249979, or rounding it 0.025. Now, one thing I also want to do is I want to show you, though, that if I were to get rid of false and just leave it as capital F, notice it highlights, by the way, whenever it's ready to go. See, when I'm typing it out, it's kind of this light blue color, but if I add the A, now it goes black. That means that it's not treating it as the logical statement of true or false. So if I just do capital F, it also will work to represent false. So capital T for true, capital F for false. Our last prefix is the Q prefix. This one is the quantile function, or the inverse CDF. In our classes, you probably would have heard me refer to this as our inverse normal probability when we were doing normal distribution. That is because generally when we are looking at distributions, like a normal distribution, we say, what is the probability that X is less than some value? And then we solve it by doing a Z transformation, and then we get a probability by looking at a Z table, or if you're doing calculus methods, by taking the integral. This is doing the opposite. It is saying, if I have some probability, what is that critical value that would make this true based on the direction that I'm looking? So the exact inverse mathematical operator of the cumulative distribution function, which is to say the inverse operator on P, given a probability percent target P, it determines the corresponding variable milestone value X such that the probability of our random variable X is less than or equal to some value X is equal to that probability. And just like before, if we go back to our help here, you can see that when we're doing our Q norm, it also has lower dot tail equals true as a default. If I wanted to look at the probability to the right, then what I would need to do is change that to lower dot tail equals false. Or in the fourth position, put a capital F for false. So some core computational uses, finding critical boundary thresholds for statistical hypothesis testing, constructing parametric confidence intervals, and for identifying percentiles, right? These are things we did in intro to stats, but again, we didn't go as much into detail in them as we could in later courses. But the idea is that a computer can do all of this for you. You just have to know how to tell it to do it. So again, the syntax is Q norm, P for the probability that you were looking at that critical value to the left or to the right, mean, whatever your mean is, right, based on your distribution, in this case, standard normal, standard deviation. So mean is equals 0, SD equals 1, and then again, you can change which distribution. You can use a normal distribution. You can, if you use binomial, same thing. It's just setting the parameters. I'm just doing standard normal for our basic examples for this. So same thing as before. In this case, we are going to say, what is the critical value where 0.975 of the data, so that's 97.5% of the data, is to the left of it on a standard normal distribution. So if we run that, we are going to get the value 1.959964, or if we were to round that, this would give us a critical value of 1.96. Similarly, if I wanted to find the critical value that has 50% of the data to the left of it on a standard normal, this would give us a value of 0, right? Because the standard normal distribution is centered at 0. If I want to know, because remember, it's symmetric and bell-shaped, so if I want to know how much of the data is to the left of it, that would mean that it's half the data, so 0.5, that means it's going to be at 0. There's one thing I kind of want to talk about briefly here, just because I keep saying if we were to round it, but this isn't really rounding it. So what if I wanted to just do that? This is going to be like a little quick side lesson, but if I wanted to round, I could actually put this function within another function, and that function is round. Now, if I were to do round, what this will do is I'm telling it how much to round it to. So I'm going to say round, and I'm going to, within this round function, I'm going to use comma, and I'm going to put 2. And this is going to round it to 2 decimals, 1.96. And anything you see in this class that I mentioned, sometimes I'll talk more in depth about it, sometimes I'll just do a quick aside. But as always, if you're unsure, $round, and it will tell you exactly how this works. You can set the floor, ceiling, truncate it, whatever you want to do. Okay, so that way, instead of having to mentally round it or change the number or anything like that, because anything you can do, you can probably do it within R. An example of this might be if I am doing some sort of distribution of grades for students or something like that. I'm not going to be entering 7, 8, 9 decimal values into Canvas when I'm entering grades. So what I might do is I just might say round to the whole number or round to 1 decimal. And this way it just automatically does this as part of our operation. And you can input these functions within functions for a lot of things. You can create almost like nested functions, sort of like earlier when we were doing, we were grabbing from within vectors. You can kind of do the same thing. You could say some function where within that I have a vector that I'm nesting inside a sub-vector of that, and then I could take that entire function I just created and I could round that, and you could do that all in line as one command. And now I've also created a cheat sheet just so you can kind of keep it all together, right? We've got our D, P, Q, and R prefixes. We've got what the purpose is of each of these prefixes. So density PMF, probability, CDF, you got your quantile, inverse CDF, and you've got your random generation of numbers. And then I've got the mathematical notation. I've got the values that you need to input at a minimum, right? So X, Q, P, and N. But of course, you will also have to input the attributes for the distribution that you're using, depending on how many there are. For example, if you're doing a chi-square distribution, there's 2, alpha and beta. And then finally, just a brief example of the simple kind of things we did here. These are all standard normal, but it would be similar if you're doing binomial, Poisson, anything like that. Chi-square. I think chi-square is CHISQ, I think is what chi-square is. Let's double check that actually. $R chi-square. Yeah, so chi-square is exactly that. And one thing I would like you all to do is try to generate 1,000 random numbers using the following distributions. Weibel, gamma, normal, binomial, and beta distributions. Try doing that in R, and then also don't just leave it in generic form like I did. Every one of the examples I did was using a standard normal. Look up the parameters, see if it has any defaults. If it doesn't, look at what the parameters or attributes in this case, if you're doing it in R, what they represent, and look at possibly some that makes sense, right? For example, if I'm doing a Poisson distribution, it might make sense to have a lambda of 1, 2, or 3, but maybe it's not really that common that I would have something like a lambda of 1,000. Is it possible? Maybe, but look and see based on these distributions, because not only can you use this to practice with R, you can use it to practice with learning about our distributions. And also try with other ones. Look up other distributions, right? Go to Google and Google, RStudio inverse binomial. See if you can figure out how to randomly generate numbers from an inverse binomial probability distribution. And that's going to be it for this lesson. This one wasn't as long as some of the others because really this one is one where you really should try to play with it, to learn. It's not very difficult to do. As you can see, it follows a very specific syntax. And once you kind of have it down, then it's really just a matter of how well do you understand those distributions. But this is one thing that I would always kind of suggest for anyone who's trying to learn computational statistics is start implementing everything you're learning in this class in any other topic you're learning about. So when you're learning about maximum likelihood estimation in math stats, try implementing it in R. Try seeing if you can replicate it or follow along with some examples using R. Try to see if you can do the calculations in R. If you're doing intro to stats, same thing. I've shown you now that you can find these inverse normal probabilities, just like we talk about in that class. If you're taking some other class, let's say you're doing actuarial math, which I'm going to be teaching soon. Let's say you want to randomly generate some data to simulate maybe some risk analysis you want to do. Okay, great. Try doing it in R. Those are the things that are going to help you become a better programmer, not just following along, not just doing exactly what I do, but also trying it on things you're learning in other situations. Hello everyone. In this lesson, we're going to be looking at Markdown in R. Now, the reason this lesson pops up now before we dive deeper into R is this is how I actually implement homework for this class. So pretty much what's going to happen is for the homeworks, I'm going to give a Markdown file, which is going to have different questions, and then you will input your code and you will knit together what is called a Markdown document as a PDF generally, or a Word document, something like that. And that will allow me, or my TA specifically, to go and grade this by seeing your code and also what the output was to see if it worked. Because sometimes it might be the fact that your code is mostly correct, but there's some small issue. So we might be able to look at the code and say, oh, I see there's some small issue, and we can tell by the fact that your output didn't work. Or if the output is correct, maybe you had a different solution than what we were looking for, and that's perfectly fine, right? Because there's not just one way that you can program when you're using R. What is Markdown? So Markdown is a lightweight markup language that you can use to add formatting elements to plain text documents. It was created by John Gruber and Aaron Swartz in 2004 with the goal of enabling people to write using an easy to read and easy to write plain text format, optionally convert it to structurally valid XHTML or HTML. And this is where the strength really kind of lies. It's a way of kind of melding document writing, like an HTML website with headers and all that kind of stuff, and code. And this is why it actually works really well for this, because instead of doing stuff in R and then trying to copy the output and dealing with the formatting of Word or whatever sort of document writer that you're using, this allows us to kind of do it all in one place within R. And RStudio actually has this functionality built in. So the primary purpose of Markdown is to make it as easy to read and write formatted text. Unlike more complex markup languages like HTML or LaTeX, Markdown is simple and intuitive. I would say LaTeX is somewhat intuitive as well, but that's generally geared more towards like formatting for things like mathematical text. Markdown is really good for the kind of stuff we're doing where we want to be able to embed code in these code chunks or code blocks and then have the output, and therefore it kind of puts it all in one nice, easy to read document. So what are some of the benefits of Markdown? Well, first of all, it's its simplicity. Markdown syntax is straightforward and makes it easy to learn and use. It offers a lot of flexibility. You can convert a Markdown file to a variety of formats, including HTML, PDF, or Word documents. So for example, if you were using Markdown, you could directly convert it to HTML and upload it as a web page. You could do it as a PDF, which is what we'll generally be doing, or even a Word document if you wanted to upload in Word and then, even edit it from there. Another big reason for this is for compatibility. Because Markdown files are in plain text, this means that they can be opened and edited in any text editor. This means that if you're a student who is using Mac OS, or you're using Linux, or even if you're using something like Chromium or something like that, and you're writing using Google's Google Docs or something like that, guess what? You can do this. Anyone can do this as long as you have a text editor. Now, of course, we're going to be doing it in RStudio, which has it built in. And then the last reason that this can be really good is because for control. Markdown allows you to control the display of the document. Formatting words as bold or italic, adding images, and creating lists are just a few of the things that Markdown can do. So some common uses you might use Markdown for is writing documentation for software projects. Like I said, they're really good because you can integrate the code directly in and it looks clean. Creating content for static site generators, that is, say, making web pages. Writing scientific reports and presentations. It can be used for this. I would probably, in that case, err towards LaTeX, but and then also for note-taking, because it is still a text editor. You can do it just like anything else. And once you kind of get the feel for it and the general commands you'll use, it's pretty straightforward from there usually. Basically for this class, it's actually gonna be even easier because I'm going to be giving you the Markdown files. You are just gonna be editing them. You don't have to actually create them from scratch. So how do we actually create a Markdown file in RStudio? The first thing you're gonna do is in RStudio, you're going to go to create new file. So you're gonna go to file, and then in the top left corner, and you'll select new file, and you're going to choose R Markdown. And I'm going to show you that in a second, and I'll show you that there are actually a lot of things you can create in RStudio, not just R code scripts. Then you're going to set up your document. It's going to give you a dialog box. It's going to ask you some questions: who the author is of the document. It's going to ask you what format you want to output it in, which, by the way, you can change any of these in the actual document. So these aren't like set in stone. It's just going to set them up for you. And it's also going to ask what's the title of your document. So it's going to automatically put a title for you. So once you've filled in these details, you're going to hit OK. Then you're going to write whatever content using your R Markdown editor and whatever sort of formatting you want to do, like your hashtags for headers and stuff like that. And then you'll save your file. And then next thing you're going to do, though, is you actually need to knit it together in a document. Now, you can look up how to do this using command line, which is usually what I do because I never remember how to actually do it, because I find that it's just it works a little better sometimes. But RStudio actually does have a button you can press to knit it together. And again, I will show all of this to you. So let's look at how we actually would do this in RStudio. So first things first, I'm going to go to the top left and I'm going to click File. I'm going to hit go to New File, and you can see that there are a whole selection of things you can do. So first and foremost is RScript. This is what we've been using so far. This is where we have our code editing, and we've been doing everything in an RScript. Right below this, you can see Quarto document and presentation, and R Markdown and R Notebook. Now, one thing, and I do have a note for this in my slides later on, is that all of the formatting and everything you do in Markdown, you can also do in Quarto. Quarto is basically the newest iteration where it has all the functionality of Markdown and then some. The reason I am not focusing on Quarto for this, even though it's really useful, is twofold. One, I've already got it set up for Markdown for this course, and I'm just going to keep it the same, not add any extra complication. And the other reason is Quarto does have some conflicts depending on your system. For example, most of my actual coding is not done on this computer I'm using. It's done on a Microsoft Surface computer or tablet. And it uses what's called a Snapdragon processor. Quarto has a lot of conflicts with Snapdragon processors, specifically anything with ARM architecture. That is, if you're using a tablet, a phone, or a tablet-style computer like the Surface is. So even though the Surface has full version of Windows on it, because it acts like a computer, inside for the processing, it is much closer to a tablet. And this creates a lot of conflicts with this. You can also do Shiny web apps. This is if you wanted to create applications directly in R. For example, for my projects that I do for my intro to stats classes, this is what I use. You can do C, C++. You can also do HTML directly in RStudio. You can do CSS files, also for web-based things. JavaScript. You got other things. Python. Remember I mentioned how RStudio natively can also do Python? Well, here it is. You can also do shell scripts and SQL. So these are all things that are built into RStudio. But today we're specifically going to be focusing on R Markdown. So we're going to click on that, and it's going to pull this pop-up like we said it would. So first thing, this would be your title. So what is your document called? Then author. This would be your name. And for my students, this is where you need to put your name, because one thing that a lot of students do every semester, they'll send in their homework and it will have the generic name set in there, and then we can't tell who it's from. Like, we can use speed grader in Canvas, but at the same time, put your name on your document. And the next thing is we have the date. When was this put together, specifically when you're creating the document? But what you can also do is use current date when rendering the document, and this will automatically just set to whatever date you render it from the Markdown file into actual document. And then last part, default output format, HTML, PDF, or Word. I'm going to do PDF because, again, people with different computers, not everyone's going to have Word, so we can do it just like this. Okay, so now you're going to see the actual Markdown file. And everything that we just input is up here in this initial chunk. This chunk is going to tell us what the title is, the author, that rsys.date, that's telling it to use whatever date is on your system for the date. If you had set a specific one, like the day you created it, this would have that there. And then output PDF document. And of course, you can change it in here. So if I wanted to change my name, I could put, for your name, I'm just going to change it to Houston, and then there you go. And then whenever you look at this Markdown file, it's going to have some generic things set up for you. So it can kind of be helping you set up. So you have your basic setup. This is going to have some options that we're going to talk about in a minute to kind of tell the document how you want it to work. Which, by the way, you can also put other stuff in here to customize the document and how it works in different ways as well. You see the double pound signs or hashtags. This is telling it that this is a header. So it's going to put this in bold and bigger letters. And then anything you type out types just like a plain text editor. If you want to do a code chunk like this, it is 3 backticks. So 3 backticks, then curly bracket, and then you have to put what is the language that you're using. In this case, we're using R. And then you have to give it a name. This name cannot have spaces in it, so be careful. You can't put something like code space 1. It could be code underscore 1, but it can't be code space 1 because this is spacing dependent. Then you're going to put whatever your code is. In this case, it's just doing the summary of cars. To end your code chunk, you need to put 3 backticks. And then this, another example, it is giving us a plot. So if I were to go up to the top right here to this knit and click on this right now, what this is going to do is it's going to ask me, I'm going to put it in downloads because I already have that up. It's going to ask me to save it as something. So I'm going to call this example doc. And I'm going to hit save because you have to save it in order to knit it together. And you're going to see it doing some stuff at the bottom. This is where it's actually knitting it together into a document. And then it should oh, something went wrong. Okay, so it actually looks like mine failed because I don't have some package that I need to install. So I will worry about doing that later. But for now, what I'm just going to do instead is I'm going to change this to a Word document. See if that works. And I'm going to knit it together. And this will automatically open my document in Word. You can see exactly what it did here. So looking at our code chunk, it gave me a summary of cars and it gave me the output. This is, and this will be some of the options we can talk about, is how to show the code, how to show just the output, things like that. And then for the second code chunk, it had the plot. Notice it does not include the code. And that is because it is using these code chunk options, which are echo equals false. This will hide the source code, but show the output or plots. You have eval equals false. This would show the source code, but does not execute it. Or you have include equals false, which executes the code silently and it hides both the code and the output. This is if you want to run something, but you don't want it to actually show up in your document. So these are 3 of the things you can change within the chunk to change its behavior. Or you could change the behavior for the entire document by putting it in the top part. So if we go back to our document, or rather our Markdown file, you're going to see include equals false. That means that looking at this means that it's going to execute the code and it's going to hide both of them from the actual document. So how are these documents actually formatted? Well, first we have headers. So in Markdown, you can create headers using the pound symbols or the hashtags, which then indicates the level of header. For example, 1 pound will be a header 1. That is your biggest title type header. 2 of them will give you a header 2. 3 of them will give you a header 3. And you can go on so far, for example, down to like header 6. So each of these you could think of like main title, main topic, subtopic, subtopic, something like that. Now, one thing to be careful about here with the formatting of this is that it is after the hashtags or pound sign, there is a space. So it'd be like, you know, hashtag, space, then whatever the header name would be. So for example, if it was like example code, it would be, and you wanted to be a level 2 header, it'd be pound sign, space, example code. If you want to do emphasis in your writing, you can make text bold or italic by either using an asterisk or an underscore. For example, the italic will create italic text, and while bold will create bold text. And you can actually combine these. So for example, we could have, if we wanted to bold and italicize the words bold italic here, we could put the underscores around it. This would make it bold, and also the star, which would make it italicized. I don't really do much with the formatting for this because I'm not usually creating documents for distributing and things like that, but you can, and just like anything, it has a lot of this functionality, and a lot of stuff you'll see online for these technical documents could be written in Markdown, or nowadays a lot of people are switching to Cordo. If you want to make a list, that is to say an unordered list, using asterisks, plus sign or hyphens, or an ordered list you can do by using periods. So for an unordered list, you could use, again, you could use star, plus signs, or hyphens, followed by a space, and that will create a list item. You can do an ordered list by putting a period and then a space, and that will put whatever's after it as a ordered list. You can put links into your Markdown. So you can create links by wrapping the text in square brackets and then wrapping the URL in parentheses. For example, if we're Google, you would create a link to Google, right? So in this case, you would put the square bracket for whatever text you want it to be, and then you put the parentheses and the actual link to it. Images can be inserted by starting with an exclamation point and then followed by alt text in a bracket. So if you wanted to have an image and then as someone highlights it as alt text, you put that into a square bracket. And just like before, if you want a URL that links to something as well, you can do that within parentheses. Now, I mentioned this previously, but I just want to I added this to the slides. But the document structure Markdown formatting syntax you see here is identical between both classic R Markdown, which is .rmd files, and newer Quarto or .qmd documents. In this course, we're going to be focusing again on Markdown, but if you prefer Quarto and it works based on your computer, that's perfectly fine as well. What I'm going to be taking is the output file, so it doesn't matter which one you use, but I'll be giving them to you as a Markdown. But I also do supply them as plain text. So what you could do in that case is you could just copy the text from like a notepad type editor directly in, replace all the stuff that's already there, and you're good to go. If you want to create tables in Markdown, you can do this by assembling a list of words and dividing them by hyphens for the first row, and then separating each column with this pipe operator. And for example, if you look down here, you'll see, pipe operator, and then whatever your first header is, pipe operator, second header, pipe operator, and then the next line, pipe operator, some hyphens. And on the right, you can kind of see what this would look like. It just creates like a little table that you could use. And there's other things you can do to make your tables look fancier as well. Again, I'm not going to go super into detail, but if you wanted to dive more into this, you could look up Markdown and then how-tos, and it could show you how to do all this kind of stuff. There's cheat sheets. I'm just teaching the most basics of it so that people who are learning R could create documents embedding their code into it. There's also advanced Markdown syntax you could use. For example, if you want to do something like put a quote in there, you can do this with a prompt type signal or a symbol or a greater than symbol. And then you can add the text you want. This will then display it as a block quote. So I have two examples. You can kind of see that. Try them here. Block quotes can be used to highlight important quotes from other people or to add emphasis to your own writing. They can also be used to create a pull quote, which is a short quote that will display prominently on the document. So this is, again, something you wanted kind of pulled out. It's a call out. Horizontal rules, you can create a horizontal rule by either doing 3 hyphens, 3 asterisks, or 3 underscores. So you do 3 of them, and then it will create a line or something across. And this can be used to separate sections of your text in a document or to add visual interest to it. You could also do a strike through by using tildes. Again, this is all stuff that you can look up if you wanted to dive deeper into this. This next part is something you might actually be interested in, specifically for our coding experience that we're doing here, which is inline code. So for shorter snippets of code, if you want to include the code like in a sentence, you can use inline code. Inline code uses single backticks around the code. For example, you might write the backtick symbol, the phrase, whatever your code is, and then another backtick symbol. So instead of doing it like backticks, write a bunch of code, then end with backticks, you could do it in line. Backticks, your code, backticks. And this will show your code in line. You probably interacted with this, for example, if you've ever done anything with coding or anything where it needs this sort of formatting in like an AI system. Let's say like you do like Gemini or Claude or ChatGPT. They actually will use this Markdown formatting. You may not see the background, formatting type stuff that we're doing now, but you see the output of it whenever it's writing to you. So if you ever see something like that, like a line, and there's like a little inline, I think it mostly uses LaTeX, but it could use Markdown as well. For code blocks, we already mentioned this, but you can create a code block by wrapping your code in triple backticks. Any code inside these chunks will be displayed as pre-formatted text in a distinct box. For example, you would write 3 backtick symbols, the phrase, whatever your code would be, and then you do 3 more backticks to end it. If you delete those end backticks, it will mess up the entire document because it will not know that the code block is ending. This is the number one issue I see students run into whenever they're doing their assignments. Because I'm going to show you the homework assignment in a minute, I actually have something written into each line of code so that it will run even if there's an error. If you do not include something like that, it also would crash knitting it together if there was a coding error when you ran it. So by default, it would fail if you did this, but again, there's a command you can use to make it not do that. If you want to specify language for syntax highlighting in your code block, you can do so including the language identifier directly after the opening backticks. This is what I was talking about previously about R or Python, something like that. Code blocks and inline code are basically essential if you're doing any sort of technical writing documents in Markdown, which is kind of what we're doing for our homework, just to practice, everything in this class is typically much more technical. And it makes it also easier to read and understand. An example of this might be that if you go into some sort of R documentation online, not like the official documentation, and you might encounter stuff like this, for example, when you're looking up things, especially coding related online. So for this example, I went onto rbloggers.com, so r-bloggers.com, and I just picked a random article. And you can see that they actually have inline code in their articles, right? So in this case, they've got their introduction, they've got a numbered list here, they've got inline code, right? Start graph, all that kind of stuff. Then they've got their code blocks in here, so you can see that it actually is this little cutout of code block, but it doesn't actually run the code, it just shows you the code. This is where you could set like your echo or your include and all that kind of stuff. If I were to pick pretty much any random article on here, let's say that I wanted to look at probabilistic time series cross-validation with R package cross-validation, you will see that it's pretty much going to follow this format. It's going to have their code blocks built in, and you can grab the code directly from there. So like I said, this is something that's commonly used, and the more you dive into programming, looking up stuff online, you're gonna see it everywhere. You're gonna see it when you use AI systems, look a little differently. You're gonna see it on things like our bloggers or even Stack Overflow. These are all places where you'll see stuff like this. I mentioned lists previously. You can also do what's called a nested list. So you can create a nested list by indenting lines by 2 spaces. For example, if you look at the left, we have item 1, and then the next line we have space, and then you have your dash. That dash is telling it that it is part of a list, but the 2 spaces is telling it beforehand is telling it to indent. So that makes it a nested list. It's a list within a list. So you can see here we have item 1 and then subitem 1, subitem 2, item 2, subitem 2, subitem 1, subitem 2 within item 2. Okay, escaping characters. If you want to include a literal character that Markdown usually interprets in another way, for example, star or underscore, you can prefix it by a backslash. So this is where it's coming back in. Remember we talked about your escape characters? This is where one of the places you would likely want to use that. This is known as escaping the character. For example, to include a literal asterisk in your text, you would write \**. If you want automatic linking URLs, you can include the URL in your text and Markdown will automatically turn it into a clickable link. When you are creating a Quarto document, there is going to be an option when you're setting it up, that pop-out that comes up, where it'll ask if you want to use the smart formatting, and it can do stuff like this automatically. It'll also even give you a little sidebar, giving you sort of an index of all the things you've done, stuff like that. Let's talk about where you might actually use this stuff. So a lot of times, instead of hard coding our calculations into some report, this will allow us to have code that actually runs when the report's being created. So that means, let's say you have a daily report based on some data that comes each day. You could do exactly that. You could have the code set up so it ingests the data, it runs it, and then you knit together this document. So that way each day you're not having to deal with hard-coded variables and data and things like that. In Markdown, you could also create a task list using hyphens and square brackets. And then if you leave them, the square brackets with nothing in them, this would be an unchecked box. If you put an X between it, it would treat this as a checked box. And then the last thing we'll talk about for this part is going to be knitting, right? Knitting is a process where you're going to convert your Markdown file into a document or report. And this process can execute any embedded R code chunks, and it will insert the results into your output document. Now, I showed you how you can do this. You can do this by either clicking that knit option at the top of RStudio, or if you wanted to, and again, this is what I always do, I just look up RStudio Markdown knit or inline knit or something like that, and it will give me the code I can just copy in. You don't want to put that actually in your document though. You want to run that in your console at the bottom because that's not part of your document. That is a command you're doing outside your document. So what are some of the benefits of knitting these documents together? Well, one, there's reproducibility. So knitting allows you to create reproducible reports where the text and results of the code are in the same document. So it's not, you're not copying the code in after it's been run, it runs in the actual document when it's being knit. And as I mentioned earlier, this means that you could have constantly updating documents. Every time you knit it, if you have new data coming in, it can automatically update. It allows for versatility. The document that you knit can be in various formats, including HTML for if you want web pages, PDF, which is great for sharing because not everybody has Word, or even Word if you have Word and you want to do some editing on it. I mean, you could edit the PDF as well, but I personally hate editing PDFs. Also, efficiency. It can help you save time or reduce errors by automating process of executing code and compiling results into a report. Again, instead of actually running the code separately and then putting it into a report, it could just be part of your reporting by automatically running the code within your report. Now, there are some common issues that people run into when they're making these Markdown files. The first is a knitting issue. If you're having trouble knitting a document, first you need to check for errors if there's any errors in your R code. Like I said, a lot of times I'll have students who accidentally delete the backticks to close the code or even start the code. Sometimes it'll be something with their R code just doesn't work. Like I said, I've actually included in my homework assignments a command that allows it to run even if the R doesn't work. But if you don't have that, like if you just grab the document we made and put some R code in, you messed it up, it's not going to knit together. Another issue you might run into are formatting issues. This would specifically be things a lot of times like spaces. So if your Markdown formatting isn't appearing correctly, check to make sure you're using the correct syntax. Common issues include not leaving a space after your pound signs in headers, not leaving a blank line before after list or code blocks, and not using the correct number of backticks for code blocks. Also, another one is, like I mentioned, when you were setting up your code chunk, right? R and then the name. If you do not have every one of those code chunks has to have a distinct name, and those names cannot have a space in them. So the number one issue I see is people try to do something like R space code space 1. It'd be like, no, it'd be R space code underscore 1 or just code 1, something like that. You may also have code execution difficulties. If your R code isn't running as expected, check for syntax errors in your code. Also make sure any packages that you're using have been installed and loaded correctly. This is the number one issue I see where it's just everything seems correct. It worked in R, but then you're trying to do it and it's not working properly. And then I included just an example of like what a spacing issue might look like on the next slide. So the first one, you can see that we have a pound sign and then methods, and notice that there's no space there. Also for our item that we're trying to create a list for, we have star item 1 and there is no space there. So this is not going to format correctly. But it'll format, it'll run, it just won't run properly. The one below it, notice that there's a space between the pound sign and methods, and there's also a space between the star and the item. So the last thing I want to do to finish up this section is just show an example of what like a homework assignment might be that I would give to my students in this class. So I have right here my homework1.rmd, and this will automatically pull it up in R because I have RStudio set up to automatically deal with these kind of files. And you'll see that I've got, this is from spring 2025, so I have to update it, but I've got it listed as SA4102, spring 2025, homework 1. I've got your name. This is where you would change it to your name. I've got it set so it would put the date and based on whenever you knit this together. And right now I've got it set to a Word document. And then of course, I didn't really mess with this. And you'll see that I've got the headers and instructions, right? Below you'll find the problems for homework 1, blah, 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 blah. And then problem 1. So see, I've got a header. I've got the perform the following arithmetic operations and include the code and results in your report. And it'd be something like add 2 numbers, subtract 2 numbers, multiply 2 numbers, divide 2 numbers. So each of these, you just put your code in here, right? So right now this is commented so that if it were to run, it would just, problem 2. And notice within this, I have this here, error equals true. This means that even if there's an error, it will still knit the document together. This is because the whole point of creating these homework assignments is that my students are supposed to be trying to learn. And therefore, if you run into an issue, but you're not sure what it is, you can still complete the assignment and get some of the credit, right? We might be able to see like, oh, it's just a simple error. You had a, random comma somewhere that you weren't supposed to have, or vice versa, something like that. And in the beginning, it's not a huge deal, but later on, as we get much into deeper things like functions and stuff like that, this becomes much more critical because I don't want homework assignments that can't be completed because you can't figure out one small code issue on one small problem. Because remember, the whole point of this is you're supposed to be learning. I understand that you could probably just put this directly into AI and it'll give you the answers. But if you do that, you're not learning anything, right? So this is meant to be a learning exercise. You're only hurting yourself if you do stuff like that. Problem 2, create a vector with at least 5 numeric elements and perform the following. Add a number to each element of the vector. Subtract a number from each element of the vector. Find the mean of the vector. Problem 3, assign the following values to a variable and display them, blah, blah, blah. And then basically what would happen is you fill out each of these code chunks with your code to do the operations that I tell you to do. You knit it together as a document, and then you turn in this as your assignment, right? So notice I didn't actually put any code, so that's why it just says your code here, because I have a commented code piece. But other than that, that's all there is to it. I'm gonna, I give this our Markdown file. You don't really have to change any of the writing, anything like that, unless there's one part where I might say something like, explain your reasoning for this, something like that. And there is one assignment where I have something like that. But otherwise, the big focus of this is the programming, it's the coding, and this is just a way for me to give out some practice for you all to do, practice doing it, and then put it into a nice, clean, easy to grade and read document. Hello, everyone. Now that we've finished introducing R and how to look up information and get help, set up basic functions and other things like that, we're going to dive into the actual data in R and how it interprets it, how it sees it, and how you can set it up. R has 5 types of atomic classes of objects. Atomic just means low level or basic. They are character, numeric, which is real numbers. So if you think about a number line with a continuum from -infinity to infinity, you have integer, you have complex, and you have logical, which would be true or false. And you've already seen some of these as we've been going through introducing R. The most basic object in R is a vector. So a vector can only contain objects of the same class. But one of the exceptions is what's called a list, which is represented as a vector, but can contain objects of different classes. And this is usually, again, why we're going to use them. And I'll talk more about that in this upcoming lesson or two. Empty vectors can be created using the vector command. So if you use vector, you can specify how big of a vector you want. It will set spaces in memory for each of them, but it will not actually populate anything into them. So it's sort of an empty vector of some number of spaces. And this can actually lead into errors or NAs and stuff, which we'll talk about as we get there as well. Numbers in R are generally treated as numeric objects, that is to say what are called double precision real numbers. This is why sometimes when you do things like the type of command, it will say double instead of numeric or something like that. And this is because it is specifying that it is a double precision real number. If you want to know more about that, I would Google it. It kind of goes beyond the scope of what we're talking about here. If you explicitly want an integer, then you would want to use the L suffix when you are creating your data. So if you put 10, R is automatically going to see that as the real number 10. But if you want it to be seen as the integer 10, you would write that as 10 with a capital L right after it. So if you enter 1, this will give you a numeric object, but entering 1L explicitly gives you an integer. There's also a special number, which is inf, so INF for infinite, which would be, for example, like 1/0. And this can be used in ordinary calculations. So for example, R will treat 1/infinite or infinity as 0. And you can do this sort of calculation in R. It won't just give you an error or anything like that for it. A value of NaN represents an undefined value. That is to say, not a number. That would be something like if we had 0/0. NaN can also be thought of as a missing value. So it's not to say it's the same as Na, but it can be treated similarly in a lot of cases. Now, these objects that we're putting this numeric information into, or whatever it is we're doing, these objects have attributes. And these attributes would be things like names, dim names, dimensions, this would be for things like matrices or arrays, class, length, and of course there'll be other user-defined attributes or metadata that can be used. Attributes of an object can be accessed using the attributes function. So if you have some data, you can use attributes to check it. For example, let's go to our R here, and what we're going to do is I'm going to pull up mtcars, one of my go-to examples, because it's got a good mix of data, and I'm going to type attributes, and you can see that it's trying to autofill here. So we're going to do attributes, and I'm going to do mtcars, and if I run this, you're going to see that it's going to give me names. This is one of the attributes, which gives mpg, cylinders, displacement, horsepower, stuff like that. It also has row names. These would be the different cars in the data set. And it gives me the class attribute, which is that this is a data frame. So it has data.frame. So this is actually a data frame which has different classes which have different information about it. It's got row names, it's got column names, and it even would have dimensions. For example, we could use the command dim for the dimensions, and this will tell me what are the dimensions of it. This is another attribute that's not really showing when I do attributes, but it is one of the attributes of this data frame. How do we actually create vectors? Well, there's a couple different ways we can do it. I already talked about the fact that we could use the vector function, but another way you can do it is using the C and then parentheses, right? When we do concatenate. So the concatenate function can be used to create vectors of objects. So you can think of this as, again, you're taking some data, you're concatenating together, and if you don't specify otherwise, it is going to treat it as a vector. So let's look at a couple of these and the types that are created, right? We talked about those different data types. So the first one we have is a numeric vector. You can see here we have x, which is the object that is being assigned, and we're concatenating 0.5 and 0.6. So because these are numeric, they're decimals and they have no L after them, this is going to be seen as real numbers. So if I were to run this, you will see that we have 0.5 and 0.6 assigned to x. If I were to use the type of function on x, you will see that we get the output double, right? Because this means that it is a real number. In our next example, we're taking x again, and we're assigning it by concatenating true and false. So this is going to be a logical vector. So of course, if I run this, you'll see that now x is made up of true and then false. If I do type of on x, we're going to get that it is a logical vector. The next example, we have x being assigned, and this one again is concatenating, but instead of using the terms true and false, I changed it to t and f. And this is just to show you that this will have the same result, right? Because we talked previously about you can do capital T-R-U-E for true, or you can just put a capital T. You can put capital F-A-L-S-E for false, or you can put just a capital F. So if we run this, you'll see again we have true or false, and the type of is logical. For my next vector, I'm concatenating the character strings A, B, C, and D together. This is going to make a vector of 4 things in it that are going to be character strings. So we'll do this. You'll see that we have A, B, C, D. Again, notice the parentheses. This means that it is a character string. So even if I were to put a number in here, for example, let's say after D I have parentheses 2, when I would run this, notice that it's got the parentheses. This means that it's not the number 2, it is the character 2. If I do type of, this is going to give me character because this is a character vector. Next, I'm going to create the sequence of from 9 to 29. Of course, I didn't add any other information. I'm using the colon operator, which means that this is going to do jumps of 1. So 9, 10, 11, 12, so on and so forth. If I do this one, you'll see that we have x is 9 to 29 with jumps of 1, and the type of is integer. Now we could also, as I mentioned in the last slide, we could also assign something like this. I'm going to concatenate 1L and 32L. And then I will do semicolon x, which will allow, oops, I got a colon there. And then this will allow me to see exactly what I got. So you'll see the numbers 1 and 32. So it looks like this might be a double. But if I do type of x here, I'm going to get that it's an integer because those capital L's are specifying to R that this is stored as an integer, not a real number. Our next example is for complex numbers. So this can be written as something like this. I'm concatenating 1 plus 0i, comma, 2 plus 4i. By having that I term in there, it is telling R that this is a complex number. So if I run this, you'll see that we have 1 plus 0i and 2 plus 4i. And if I do type of, we will get the outcome complex. I mentioned previously that you could use vector to create this empty vector, or you could fill it if you wanted to, if you have data. Let's look at that. So we have x being assigned, and we're using the vector command. So the first part we're putting is what type of vector is it? And I put numeric. And then I'm going to tell it to create a vector of length 10. So if we run this, you will see that it is going to create a vector with a bunch of zeros, so 10 of them. And if I do type of, you will see that it is double, which means that it is numeric. Now, as always, what I would do is, if you want to know more, question mark, vector. And then when we run this, it's going to pull up our information on vectors. So you can see here that the first attribute of vector is mode. What type of vector is it? Is it a complex number? Is it a double? Is it numeric? Is it integer? Is it logical? And these are all things based on the type of. It says here, allows any type, see type of mode. So let's do that. Let's go back, right? This is the part I talked about playing with it. If you find something, you want to know more information, follow the trail. So let's do type of, and we'll run help on this, and you will see the different types that we have. We have logical, integer, double, complex, character, raw, list, null, closure, so on and so forth. Now we're just focusing on the main data types that we'll be using, so that's why I'm focusing on what your data would actually be. We're not focusing so much on things like special or closure or anything like that. I mentioned earlier in this lesson that vectors all have to be of the same class type. So what do you think is going to happen with these examples? The first one, we're assigning y, and we're concatenating the number 1.7 and the character string a. The second one, we're assigning y, we're concatenating a logical statement of true with the number 2. And for the third example, we have y, which we're concatenating the string a and the logical statement true. So let's run those and see what we actually get. So the first one, we have 1.7 and the character string a. So if I were to actually look at this before I do type of, what do you see? Well, notice that they're both in quotes. This is because I had two different classes. So what it's done is it has coerced it into the most general state. So between a real number and a character string, it is going to coerce everything in it into a character string. If I were to do type of x, you will see that, oops, that should be type of y. If I do type of y, you will see that it is a character. For the next example, we have y is being assigned with true and 2. So again, we are going to just look at y and see what we get, and you will see that it gets 1 or 2. Notice what it did is that it coerced our true statement into a 1. And again, this is because this is the more general case, because with logical statements, there are two outcomes, true or false. And what it can do is it can treat those as numeric values, 0 or 1, right? So let's actually go back. Let's change this true to false and see what happens. Now, when I look at my y, you're going to see that it's 0, 2. So the more general character type for a logical statement or a number is going to be the number, because it'll just treat it as the number, 0 for a false statement, 1 for a positive statement. If we do type of, you're going to see that this is a double. It coerced it into being numeric. For the last example we have here, we're concatenating the character string a and a logic character, which is true. And if we look at this, you will see that it coerces it into a character string. So when I do type of y, it's going to tell us that it's character. This is really important because a lot of times this is where you're going to run into errors where you can't figure out what's going wrong. And it's oftentimes because there might be some missing data or a logic statement, or someone has a character instead of a numeric. And what it's doing is it is automatically coercing the entire vector. So I have another example here, which are going to be some readings, right? We have the values 12.4, 15.1, error, which is character, and 14.8. So this might be something like you have some sort of sensor data that's coming in and you're taking these readings, and in one of the readings you get an error. So the machine spits out that you have an error. So whenever you pull in your data, even though most of it's numeric, and of course it's easy in this toy example where I have 4 outcomes, but what if I had millions of outcomes? This error somewhere in there is going to cause it to coerce it into all character strings. In that case, whenever you try to do some analysis on it, you can't do analysis on a character string using most methods. So this is going to cause you a lot of problems. And this is why it's so important to understand the data. There is actually an ordering to how it coerces the data. You can think of it sort of like tiers. And a lot of times in class, what I'll do is I'll have a whiteboard and I'll draw it sort of like a ladder. I'll talk about that in the next slide. But first, let's talk about how you can explicitly coerce your data into another data type. Objects can be explicitly coerced from one class to another using the as.dot functions. That is to say things like as.numeric, as.character, as.logical. So we're going to now do an example of this. So first thing we're going to do is we're going to create a vector, which is we're assigning to x, which are going to be the numbers 0, 1, 2, 3, 4, 5, 6. And then I'm going to use class instead of type of. This is another way you can check what kind of class it is or type of your data. This says that my x values are integer. So now what I'm going to do is I'm going to do as.numeric on x, and you will see that it gives me the outcomes 0, 1, 2, 3, 4, 5, 6. What happens if I check the class of x now? Well, you're still going to see that it's integer. Okay, that makes sense. 0 through 6, only integer values. What about if I do as.logical? Well, if I do as.logical, notice what it did. It changed the first value 0 into false, and then I have true, 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 true. When you coerce numeric data into logical statements, 0 is false. Anything else numeric is true. That means if you have a 1, it's true. If you have 1,000, it's true. If you have a 16.5, it is considered a true statement. What happens if I do class for x now? You'll see that it still says integer. Now, why do you think that is? Well, the reason is because remember what I told you. In R, objects are immutable. These functions, as.numeric, as.logical, as.character, are not changing x. They are temporarily giving you an outcome as numeric, as character, as logical. So if I did as.character on x, you'll see that it gives me the same outcome, 0, 1, 2, 3, 4, 5, 6, in quotes. That means that they are not numbers now, they are character strings. But if I do class of x, again, you will see that it is integer. Now below this, I have class of as.character a. So now what I'm doing is I'm saying, okay, I get it. I have x, it's not changing. So when I do as.character, it is giving me the output of x as characters. If I were to do class of this, so class parentheses as.character x, you'll see that it is in fact a character. So this, when you use these as.dot functions, it's not changing the object. It is changing the output of the object for that command. This means that if I have, let's say, a bunch of integers that I need them to be real numbers for some analysis, you don't have to change them permanently to real numbers. That means that you can change them within the actual function that you're doing to numeric. And therefore, you would change your integers into real numbers, do the command, whatever it is you're running, whatever function, but the actual main object is not changing. If you wanted to change it, you would need to do like we've done previously and reassign your object x. You could do something like x is as.character x. And then, of course, I'm just going to do a semicolon x so we can see the output. And now when we run x, it is a character vector because I have explicitly reassigned. And I know I keep harping on this about R having objects that are immutable, but this is important to understand because when you were doing these as.dot functions, you are not changing the object. You were just giving an output of that type. Not every type of coercion, though, is going to work out. So let's talk about some nonsensical coercions. So nonsensical coercions, or ones where it tries to coerce the data into a different class, will result in NAs if it's not something that makes sense. Looking at our data here, we have x, which is the values a, b, c, and d. These are character values. So now if I were to look at my x, you will see that it is a, b, c, and d, the character strings. Next, I'm going to do as.numeric on x. Notice that the outcome is NA, 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 and it gives me a warning message. NA is introduced by coercion. I'm going to change one thing up on this, though. I'm going to, again, add a character of 1. You might wonder, why am I doing this? Well, the reason I'm doing this is because when I do my conversion now, look what happened. I got NA, 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 and it changed the character 1 into the numeric value of 1. So you can have something like this where you have specific things that are coerced into NAs because they don't make sense, while other things still convert properly, right? Because if it sees the character that is a number, all it's doing is it's stripping off being a character string and changing it into numeric, works fine. The reason I wanted to bring this up is, again, a lot of times when you're doing stuff like this in R, you're not dealing with small little toy data sets, as we like to call them, like what we're doing in class. I'm teaching you in this very simple level of you have 4 or 5 things in a vector. Easy. You can look at it, easily discern what's going on. But in the real world, you're oftentimes getting larger amounts of data where you could look through and try to find NAs, or you could do like a control F type function, stuff like that. But it's still helpful to understand when this might be a case, right? When you're doing certain things and you get an error within your other function, why? Well, maybe because when you did as.numeric, there was something that coerced into an NA, and that function you were trying to run doesn't allow NAs. So next what we're going to do is we're going to try converting our x value, so a, b, c, d, 1. We're going to convert this into logical. And again, it's going to give us NA, 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 NA. So notice in this case, it did not give us a true statement for 1. And this is because when you were converting to logical, any numeric value that is not 0 would be seen as true. Any numeric value of 0 would be seen as false. But that 1 is not numeric. So just out of curiosity, what would happen if I would to do as.logical, and within that I'm going to have as.numeric. So we know that as.numeric is going to give me an error, but now what's going to happen when I coerce the data into numeric before doing as.logical? Notice the outcome now. NA makes sense, right? You can't convert A, B, C, D into a logical statement. But within the function, by first changing that 1 character into numeric and then changing it into a logical, it now becomes true. And this is what I was kind of talking about previously about you can do this within a function. You can change the data within the function without changing the actual underlying object. And the last one, let's look at as.complex. Same idea. We have a bunch of things that are not complex, but notice that in this one, it was able to change the numeric character string. So we have NA, and then 1 plus 0i, because you can always change a numeric value or an integer into a complex statement by just adding 0i to it. So that's the end of this lesson where we're talking about data and conversion of classes and things like that and assigning classes. Next, we're going to jump into lists, matrices, vectors, things like that. Then we'll follow up more with data frames and how to deal with missing values and all sorts of stuff like that. So go to the next lesson, keep learning about all this stuff, and we're building these building blocks that are going to help you really understand R as you kind of learn to program. Hello, everyone. Now that we've talked about data types and coercing data and creating vectors, let's dive deeper into different ways that we can put our data together on top of just using vectors where all classes have to be the same. The first thing we're going to look at are lists. So lists are special types of vectors that contain elements of different classes. This is the key distinction. A vector is a list, basically, of a set of different values, whatever they are, logical statements, complex variables, whatever, but they must all be the same class. So whenever we introduced this, they were coercing any classes that were different into the most basic class. A list, on the other hand, does not have to have the same class types within that list. Lists are very important data types in R, and you should know them well because we're going to be using it a lot, especially as you get into more complex data states. So we're going to start with our example here, where now we're going to do is we're going to use the list function. And so we have list, which we're assigning to object X, and it's going to be the number 1, followed by the character string A, followed by the logical statement true, and then followed by the complex number 1 plus 4i. So if we were to run this, you will see that we have an output where it has double square brackets 1. This is telling us that is the first part of the list, and we have a 1 in it. We have the square brackets 2. This is telling us that the second part of the list is the character string A. We have square brackets 3, which tells us that this is the logical statement true. And then the 4 within square brackets is giving us 1 plus 4i. Now you might notice underneath those square brackets, the 1, 2, 3, and 4, each of them have a single square bracket instead of double square brackets, which just say 1. And this is saying that within that first part of our list, the square bracket, double square brackets, we have one object, which is 1. You can have more than 1 within a list, meaning that, for example, I could have my first part, I'm going to concatenate 1 and 2. Now if I were to run this, notice that the first part of the list within the double square brackets for 1, I have 1 and 2. And that 1 in single square brackets just signifies that this is starting at element 1. Now the reason it does this is because if we were to get a bunch of data that wraps around, once it reaches a certain point where it's going to recycle to the next line, it will tell you what element you are on. So let's do that real quick. Let's actually change this list real fast. And instead of concatenating 1 to 2, I'm just going to make it the values 1 to 150. So now when I run this, notice that in my first double square bracket, this is the first elements within this list, I have the numbers 1 through 22, And then the second single square bracket, 23, is telling me that the next number is the 23rd element, which you'll see that it does coincide with the numbers we have because I started at 1 and our index is starting at 1. Let's change it up just a little bit. As I said, always play around with it, get a feel for it. Let's say instead of starting at 1, though, we started at 26. So now if I were to run this, you'll see that our 23rd element is 48. Our 45th element is 70. Our 67th element is 92. This tells me then on that line, that first element that I'm seeing, what value it is in my list of values. So the 67th is 92, the 68th is 93, the 69th is 94, and then so on and so forth. You could figure out from there. And then the rest of the stuff, same thing. If I had a bunch of character strings, it would have the exact same behavior. So now let's do a type of on our X that we have here. Looking at this, you'll see that it tells us that this is in fact a list. Similarly, like we did last time, let's say instead we did class of X. You'll see that it also gives us a list. This is because our list is a little bit too complex for type of or class to tell us exactly what is within it. It's just going to tell us in general that it is a list. What we can do is we can use the str function on X, and this is going to give me the structure. This is going to break down the individual parts of the list. So looking at this, you'll see that is a list of 4. The first part is an integer. So this is integers from 1 to 125. That's the elements, not the numbers. The next one is a character string, and it's going to tell me that it's A. It does show, by the way, the numeric, the integers, where it starts at 26. The third one, logical statement, true. And the fourth one, we have complex. So by using the str or structure function, this is going to tell me what the structure is within the list. So type of and class will tell me that I have a list. Str or structure will tell me what is the structure within that list. So again, I just want to reemphasize that when you see those double square brackets, those are telling you what is in individual elements referenced by that list. So the core concept of this is that unlike atomic vectors, which remember, vectors all have to be the same class, and our list is a heterogeneous container. That means that they can be different. It acts as a general purpose umbrella that can store completely different data types, classes, and dimensional shaped objects. Now, why do we use them? Well, most complex statistical operations and modeling, for example, functions like LM for linear modeling, GLM for generalized linear modeling, or ANOVA, cannot return a single vector or matrix. So instead, what they're going to do is they're going to bundle strings, matrices, numeric vectors, and metadata summaries together into a single master list object. So let's do a more complex example. Looking here, what we're doing is we're creating a model, and we're telling it that this is a list. We're going to have our model name, which is ordinary least squares linear regression, or OLS linear regression. We're going to have converged equals. It's going to give us the outcome that it did converge, true. Sample size is going to be 45L. That means that it is an integer, right? Because the L makes it an integer. Our coefficients, we're going to have our intercept is 2.45. Our slope is 1.18. This means that this is numeric or a double. We have residuals, negative 0.12, 0.45, negative 0.32, and 0.08. Again, this is numeric. And then our design matrix, which is going to be a 2D matrix. Now, when I run this, it's going to create this object that we just labeled model output. So I'm going to do our model output, and you are going to see that it is in fact giving us an output like a list. Now it is a little bit different in this one. Instead of doing double brackets, it's using the money sign, which is for atomic vectors. So for now though, same idea, right? So our first one, model name, OLS linear regression. Second one, converge true, sample size 45, coefficients, intercept, and slope. And the reason is these atomic vectors within them, these have names themselves. So within coefficients, we have the names intercept and the name slope. For residuals, and then we have our matrix. So if I were to do str on our model output, you will see that the model name is a character string. The converged is a logic statement. The sample size is an integer. The coefficients are numeric. Notice it also has an extra part here, named numeric. So not only is it numeric, it's also it has a named attribute associated with it. So that means that it's got our intercept and it's got the slope. Residuals is numeric and design matrix is numeric. if we wanted to get the names of different parts of our list, we can use the names command like we did previously. So if I were to do names, you'll see that we have model name, converged, sample size, coefficients, residuals, and design matrix. But I can take this deeper because remember, when we looked at coefficients, these were named entities. So those have a name attribute within them. So what I'm going to do is I'm going to do names, and then I'm going to reference this with model underscore output. And then I'm going to use the money sign to specify which thing within this list that I want to get the names of. So I'm going to do it for coefficients. And when I run this, you'll see that it tells me that the names for the coefficients within the list are intercept and slope. You can reference your different named entities by using that money sign. So if I wanted to, for example, grab the whether it converged or not, I could reference this. And this is actually really useful because a lot of times this is what you're going to want to pull into models. Instead of going in and grabbing all the actual data, you might just want the coefficients. So I'm going to do here, for example, is I'm going to do model output, and I'm going to do money sign, and I can pick whichever one I want, right? I could do sample size, gives me 45. I could do converged, and I'm going to get the outcome true. I can also grab from these different parts of our list using these square brackets, like when we were subsetting data. So if I did model output 4, what this is going to do is this is going to give me the fourth part of our list. So we have model name, converged, sample size, and our fourth is coefficients. It is the same thing as our coefficients, right? So if I were to instead do model output money sign coefficients, you'll see that we get the exact same thing. You can subset your list just like we did previously using square brackets. This will always return a smaller list, right? Because when we have a bunch of different data of different lengths within our list, it's a list of lists. So to extract the raw underlying object inside a container, you must drop the 2 square brackets or $sign operator. Once an internal object is extracted from a list, you can append standard vector or matrix indexing rules to slice further down, kind of like we did where I went within coefficients to then grab names. I could do the same thing where instead of within that, I could just grab the first element, right? So an example of this might be if I did model output, and then I'm going to do money sign coefficients, and then I could grab square bracket. I'm going to grab the second outcome, which is going to be my slope. And you'll see that we get slope of 1.18. If I just wanted to instead grab the intercept, I could do square bracket 1, and it would grab the intercept. So you can subset just like we did previously within a smaller list within our major list. I kind of already touched on this, but let's say we have our model output coefficients. You'll see that it gives us both. If I wanted to grab a specific element, like I said, once you've selected coefficients, which I'm using by using the money sign, the atomic symbol for coefficients, then I just put square brackets to grab within that. So up until this point, we've covered vectors and we've covered lists. Now we're going to dive into matrices. So matrices are special types of vectors in R with an attribute called dimension. I wanted to specify, I specifically said vector. So it has all of the same restrictions of a vector, which means that they must be the same class. The dimension attribute itself is an integer vector of length 2. That is to say, in row, the number of rows in the matrix, and in col, the number of columns in the matrix. All a matrix is in R is a vector where you have a new attribute called dimension, or dim, which tells you the number of rows and number of columns. So let's do that by first creating a very simple matrix. First thing we're going to do is we're just going to create a simple matrix called m, where I'm going to use the matrix command. And then what I'm going to do in this case is I'm going to give it a number of rows equal to 2, and the number of columns equals to 3. When I run this, you'll see that it made this object m. So now what I'm going to do is I'm going to look at m, and you're going to see that we have a 2x3 matrix filled up with NAs, because I didn't fill anything into it. I just made this an empty matrix. So it's sort of like a container. It's got 6 places in it, right? So it's got 2 rows, 3 columns, and nothing actually filled into it. As always, what I would do is question mark matrix, and we can find out more about matrices, right? So you can do, just like before with as.numeric, is. You can do the same thing with matrices. As.matrix attempts to turn an argument into a matrix. Is.matrix tests if this is in fact a matrix. So for example, going back to what we did previously with our model output, I could do is.matrix, and I'll do model output, and you will see that we get false because it is not a matrix, it is a list. This matrix has different arguments, things like the data. This is the data you're putting into it. I didn't put data into my original matrix. We've got the number of rows. This is the desired number of rows. You've got in_col, which is the desired number of columns. And then there's the attribute by row. So this is a logical statement, true or false. If false, the default matrix is filled by columns. If you set it to true, it will fill by row. The default for this is by column. And you can see this here. When you look at matrix, you see by row equals false. This means that it is not going to fill your matrix by row. It is going to fill it up by column. This is actually super important because a lot of times when we're creating matrices ourselves, we will put in some data. And a lot of times people by default think of matrices from, first, second, third, fourth, go to the next row. But what's really going to do is it's going to start at the top left and it's going to go down. So first value, second value, third value, fourth value, go to the next column. So if you want it to fill by row, you would need to do by row equals true. So to kind of show this, what we're going to do now is we're going to expand our previous matrix and we're going to put some data into it. So matrices are constructed, again, column-wise. So you can think of this starting on the top left and then going down and then over to the left from there. So what I'm going to do is I'm going to just go back up to my matrix I created and I'm going to put some data into it. So I'm going to do 1 through 6. So we have the values 1 through 6, and then I'm just going to add semicolon m, so it'll just run it and tell us what it is. And you'll see here that it goes 1, 2, 3, 4, 5, 6. Notice that it is filling our matrix, our 2 by 3 matrix, by column. You also can create a matrix from data you already have. So what we're going to do now is we're going to look at how we can create a matrix directly from a vector. So first, let's create that vector. So our vector is going to be m, because we're just going to replace this, and m is going to just be the numbers 1 through 10. So running this, you'll see now that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And what we're going to do now is we are going to set the dimensions for it. So the way we can do this is if we do dim m, this will tell us the dimensions. You'll notice that it's null. It does not have the dimensions attribute. What we're going to do is we're going to create it by labeling this dimension attribute. So we're going to label the dimensions, and remember it's in row and in column. So it's going to be, we're going to concatenate these, and we're going to have in row, which is going to be 2 rows, and we're going to have in column or in col, which is 5 columns. And now if I were to look at my m, I have now added this attribute to it because a matrix is just a vector with the dimensions attribute. So by doing dim m and then assigning something to it, I have assigned something to the dimensions, in this case 2 by 5, making it a 2 by 5 matrix from an original vector. So in computer science, multidimensional arrays can be stored sequentially in memory, either row by row, right? This is row major, or column by column, or column major. R will natively handle multidimensional arrays using a column major order. You can change this by using by row equals true. When you feed a long flat vector into a matrix function, R will populate the cells starting with column 1, then column 2, then column 3. If your raw data sequence is structured horizontally, that is, say, row by row, you have to explicitly tell it this by using that by row equals true. Now, one thing I also want to point out is that if you don't have enough data, R will impute and actually just put something in there as a place in place of it. So let's start by first creating a new matrix, just like we did before. So we're just going to have our matrix, which is going to be the numbers 1 through 6. And then we're going to give it the number of rows of 2 and the number of columns of 3. Right, so we created this matrix, 1, 2, 3, 4, 5, 6. Notice that if you go across horizontally, it is 1, 3, 5. The second row is 2, 4, 6. We can change this by just adding the by row equals and then true. And now notice that it is 1, 4, 2, 5, 3, 6. Or if you were going across, 1, 2, 3, 4, 5, 6. What would happen if instead, I'm going to do the same thing, but I'm just going to change this to 1 to 5. So notice what's going to do is if you look here, we have a warning message. In matrix 1:5, in row equals 2, in col equals 3, by row equals true. Data length 5 is not a submultiple or multiple of the number of rows, right? Because if it's a submultiple, what it's going to try to do is it's just going to do repeated until it gets to the end. But ours was not a submultiple amount. But if we look at our actual matrix, it is 1, 2, 3, 4, 5, and then it put a 1 in place of it. It was just sort of its filler. It's going to fill this with 1. If I were to go back and change this again, this time I'm going to do 1 to 3. Notice what it does. It does 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3. And this is because this is a submultiple of it, meaning that I am taking 3 values and I'm creating a 2 by 3 matrix, which means I need a total of 6 values. So when it does the first 3, 1, 2, 3, it runs out, but it says, oh, it's the same number in size. I'll just use this again. And this is why, again, it's important to kind of understand how R actually populates this sort of stuff. It's important to keep in mind from a computer memory perspective that R does not actually have a distinct matrix data type. When you are creating a matrix, you are not creating a matrix. It's not a thing in R. A matrix is literally just a standard flat atomic vector with a hidden structural attribute called dim, that is your dimensions, which is attached to its metadata. That's all it is. And you're going to see the same thing later when we get to data frames. Data frames are just lists with an extra attribute attached to them. The dim attribute is a simple integer vector of length 2 for in row and in col. And you can instantly transform a flat vector into your two-dimensional matrix without even using your matrix function, just by assigning the dimension vector directly to it, like we did, where we set dim of m, and we just told it directly what are the dimensions of this vector. So let's do another quick example. In this case, we have x, and we're going to concatenate the objects, the values 10, 20, 30, 40, 50, 60, and we're going to assign that to x. Now, if we look at our attributes of x, you'll see that we get null. It has no attributes. It is literally just a vector of those numbers. Next, what we're going to do is we're going to take dimensions of x, and we're going to assign it a number of rows equals 2, and a number of columns equals 3. So we're going to use dim of x. We're going to assign concatenate 2 and 3. Now, if we were to look at our attributes of x, you'll see that we get 2, 3. That is telling us that this is now a 2 by 3 matrix. And then if I were to print x, by the way, if you ever do print, it'll just print the output of what it is, kind of like when I just run x in this case, because the output is when I run it. Okay, so you'll see that we have the matrix 10, 20, 30, 40, 50, 60. I already mentioned this, but because a matrix is just a vector with spatial parameters, it inherits the strict rules from a vector. That is to say, its homogeneity. So that means every single element inside a matrix must be the same type of atomic class. Mixing a character string or a logical value inside of a numeric matrix will force the implicit coercion of the entire array. If the length of your input does not fit perfectly in your chosen number of rows and column grid, then R will force its recycling engine to fill the missing spaces, but it will throw an explicit warning. It'll give you a warning, but it will still fill in that matrix. And this is kind of important to remember because a lot of times if you're creating a program and you have a lot of lines of code, a lot of times we'll just select everything, run everything, and you may see these warning messages pop up. It's not telling you that it's not going to work, but it is telling you that something is happening. And that could be important because if you have some data, maybe it coerced for some reason or introduced a matrix where it doesn't have the right amount of data, it's going to fill it in for you and put a bunch of ones as you saw if it's not a submultiple. In that case, it'll still run whatever function or command you're doing, but it might not be the output that is what you're looking for because, again, it's using a matrix that's not complete. So let's look at an example of silent coercion. We have matrix and we're concatenating the values 1, 2, character string error, and 4. And we're going to just tell it that the number of rows is 2. You'll notice I didn't put number of columns. This is because when you create a matrix, it has to have these two values: number of rows, number of columns. The fact that I have 4 data points and I'm telling it that there are 2 rows, it is going to automatically infer that there must then be 2 columns. So when I run this, you will see that we get 1, 2, error, and 4. But notice that the data within that matrix is all character strings. And that's because when we got the error from, let's say, our sensing station, because it's character string, it coerced everything else into a character string. And this is because a matrix, just like a vector, has to have the same class. And then we have another example we've already talked about. If we have a matrix with the incorrect amount of data, it is just going to automatically fill in that last data point or whatever number of data points it has, but it will give us an explicit warning about that. So you'll see here that says we don't have the right length, and it just puts a 1 in place of whatever values it's missing. Matrices can also be created by column binding or row binding using the cbind or the rbind functions. So let's say, for example, that we have the object x, which is just the numbers 1, 2, 3. And we have the object y, which is 10, 11, 12. So if we looked at these individually, x is a vector 1, 2, 3. Y is a vector 10, 11, 12. So what I can do is I could use the cbind function, which this is, and then of course tell it which vectors you're doing, in this case x and y. So what it's going to do is it's going to put the x vector as a column, and then it's going to put the y vector as a column, and it's going to combine them together into a matrix. So if we do cbind x, y, you will see that we get, for the column, 1, 2, 3, 10, 11, 12. Or if you were to do it by row, it'd be 1, 10, 2, 11, 3, 12. If I were to do rbind, what it's going to do is it's going to take those x values, 1, 2, 3. It's going to take the y values, 10, 11, 12, and it's going to combine it by row. This would give us the matrix starting at the, if we're doing column, 1, 10, 2, 11, 3, 12, or if we're doing it by row, 1, 2, 3, 10, 11, 12. This means that if you have a set of vectors and they're of equal length, you can use the cbind and the rbind functions to combine them together to create a matrix. So let's say that somebody sends you your x inputs and then they send you your y outputs, but they send them as separate vectors. You could combine them into one matrix with input x and output y to do your analysis. Now, what would happen if we didn't have the same number of objects? So we're gonna do x is 1 to 4, y is 10 to 12. Now, if I try to do cbind, notice what's gonna happen. I'm gonna get a warning. In cbind xy, number of rows of result is not a multiple of the vector length, arg2, but it's still going to give me the matrix. So it's gonna be column-wise, 1, 2, 3, 4, makes sense. And then for the second column, it's gonna be 10, 11, 12, 1. And this is because when it is imputing what it might be for that last data point that it's missing, it is using the base case of that vector. So the base case in this case, because it was 10, 11, 12, is 10. Similarly, if we were to do rbind, we would get the same thing. What about if we changed x to 1 through 5? Well, let's do that. So we have x is 1 to 5, y is 10 to 12 still. Now when we combine it, notice what's happening is on your y column, it's 10, 11, 12, 10, 11. So what it's doing is it's just cycling through, like the slide said. It's just going to cycle through until it gets to having enough data. So it does 10, 11, 12, 10, 11, 12, 10, 11, 12, and then any stopping point you get to, that's where it's going to stop. In this case, because I switched x to having a length of 5, it's going to do 10, 11, 12, and then 2 more, 10, 11. So that's the way that it's going to fill in your matrix. Similarly, if you do rbind, same idea. It's going to add, for the y row, it's going to be 10, 11, 12, 10, 11. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video. First, starting with factors, but then we're going to jump into data frames, which, thinking back to like your SAT comparison type questions, a vector is to a list as a matrix is to a data frame. Or you can think of it as the fact that when you take a vector, you can turn it into a matrix, which is a vector with dimensions. Same thing, a list you can turn into a data frame, which is just a list with new attributes. Hello everyone. In this lesson, we're going to be talking about factors in R. Factors can be used to represent categorical data. Factors can be unordered or ordered, and one can think of a factor as an integer vector where each integer has a label. Factors are treated specially by modeling functions like things like linear models, LM, or generalized linear models, GLM. Using factors with labels is better than using integers because factors are self-describing. Having variables that have values like male or female is better than variables such as 1 or 2. In fact, I've actually taught an entire class on this sort of topic called categorical data analysis. And just by diving into this topic, there are a lot of problems that will end up falling into this sort of thing, but they can actually be very difficult to work with. In fact, in this class, my students will finish with a big overarching project that should be used to start a data science or project portfolio. And I've had a few students in the past who have specifically chosen data that has a lot of categorical variables or factors whenever they import it to R. And it's actually led to a lot of issues because it's actually very difficult to work with. Now, I mentioned previously in this slide that you can have factors that are both unordered or ordered. So unordered factors would be things like I just brought up, male or female. Or if I'm going into the parking deck and I'm looking at the number of different colored cars. So the colors would be unordered factors, green, red, yellow. They are names or nominal data, but they don't have any sort of numeric meaning to like an ordering or anything like that. Ordered, on the other hand, means that while they are still classified by some category or label, they have an order to them. First place, second place, third place, or best, middle, worst, high, medium, low. These are all types of ordered categorical data. And it actually dives a lot deeper than this. And I might bring this up later on in the course, but even when you have these sort of factors, how you implement them in modeling can make a huge difference. For example, if let's say we have 3 categorical variables, A, B, and C. Do I have a single variable, let's call it X, which can be, some value for A, some value for B, or some value for C? Or do I use what's called a dummy variable where I have some A, some B, and some C, and each of them can only be, so 1, 0, 0, 0, 1, 0, or of course, then you'd have the default state, which would be the other one. And this can actually have a big impact on your different types of modeling. So let's actually dive into how we can actually implement factors and everything about them in R now. So our first example, we have our X object, and what we're doing is we are labeling that this is a factor, and we're concatenating the values yes, yes, no, yes, no. So let's do that. And you can see the output of this. We have yes, yes, no, and our levels are no and yes. So if I were to run a table, so I do table, and what it's going to do is it's going to output this as a table where you can see that we have the outcomes no, and we've got 2 of them, and we have the outcomes yes, and we have 3 of those responses. By the way, this table command is great for if you're trying to create a confusion matrix, things like that. If we wanted to strip out the class, we can use the unclass function. So unclass X, this will actually pull out that class attribute, and you will see that our unclassed data is 2, 2, 1, 2, 1. So it's treating it as numerical values, 2 being no, 1 being yes. You'll notice when we did that example though, it had the order as no and yes. The order of your levels can be set using the levels argument within factor. And this can be important in linear modeling because the first level is often used as your base level. I say often because it's not always true. For example, if I have 3 classes, A, B, and C, in R, it will treat A as your base class that everything else is compared to. In something like SAS, the default is that it takes the last class that is your base, and the first 2 would be compared to that. You can change this within R, how you determine which one's base class, but the easiest way to do it is just set them in the order that you want them to be classified in. So if we look now, we have X, which is going to be a factor. We have yes, yes, no, so that hasn't changed. But now we've added the argument levels equals, and we're concatenating yes, no. So we're telling it the 2 levels are yes and no, but specifically in that order. So let's run that and see what happens. Now you'll see that it is giving us yes, no. In fact, I'm going to actually put this into a table again. And you'll see instead of having no, yes, 2, 3, we have yes, which has 3 outcomes, and no, which has 2. So by using the levels attribute, we've set our levels in the order that we want instead of just relying on R to default. to whatever it wants. R's default is that it's going to put it in alphabetical order. So no, N comes before yes, Y. So therefore, by default, if you don't tell what levels to do, it will put N before Y. Let's just do question mark, and we're going to do factor, and we'll see exactly what our documentation tells us. Looking at the documentation, you can see factor. X is equal to character. That is going to be the different data you're actually putting in, things like yes or no. We've got levels, which is what we just talked about. You can also do labels equals to levels, that being the default. You have the command ordered, where you can take your factor and set it as an ordered factor, where there is some meaning or ordering to it, not just label. We can check whether something is a factor using is.factor on whatever that X value is, or whatever the X values are. Is.ordered, you can check whether it's an ordered factored list. You can do as.factor or as.ordered to coerce them into being an unordered factor or an ordered factor. You can also use things like add NA, X. If any equals false, this means that you just won't change it. If it does, things like that. So you'll only add NA level if it's used. So some common misconceptions. Beginners frequently treat factors as a simple character text vector with built-in grouping, right? And you saw when I did table, it didn't put yes, yes, no, yes, no. It did, here are the yeses, here are the nos, here's how many there are. So it grouped them. This can be a dangerous mental model, though, for computational statisticians, because under the hood, the factor is strictly an integer vector. That is 1, 2, 2, 1, 2, something like that. That has a character label attribute that is associated with each of those integers based on levels. So that's really all that R is seeing. R is seeing an integer vector where you have levels that adds a label to each of those values in your vector of integers. Now, why does R do this? This is for memory efficiency. So storing repetitive text strings, things like control or treatment, over millions of rows can be computationally very expensive. So what it does instead is it stores it as ones and twos. So you have 1, 1, 2, 2, 1, 2, stuff like that. And it then just has to map that tiny metadata lookup index to that factored list. And this actually saves a lot of computational resources whenever you're actually using this sort of stuff. The integer underlying structure is how R's design matrix engine actually can automatically handle dummy coding, contrast matrices, or reference levels during regression modeling. So whenever it's doing this sort of stuff, this is actually how it sees it. It sees it as this integer vector, and then they have this metadata, which is much smaller. Instead of having a bunch of different labels, it just actually has, if it's 1, it's this label. If it's 2, it's this label. If it's 3, it's this label. And then instead of having to keep track of all that, it can just do it whenever it's needed for things like linear models, LM, or generalized linear models, GLM. Let's do another example to look at the behavior of these factors. So first thing we're gonna do is we're gonna create an object called vec_char, so character vector, where it's going to be low, high, medium, low. So in this case, just like before, we have some named entries, right? Low, high, medium, whatever this is referring to. Now what we're gonna do is we're gonna turn this into a factor, so factor, by using factor on this original vector. Okay, so now if I were to look at my original vector, you will see that it is just the list of those 4 things, low, high, medium, low. If I were to run or look at my vec factor, now you'll see that it's low, high, medium, low, and it has levels high, low, medium. Notice the ordering that it did, high, low, medium. Again, because this does alphabetical. H comes before L, L comes before M, and I did not specify the levels, so it put it in whatever order it did by alphabetical order of the first letter of each of those levels. If we do unclass, you will see that this would change this factored vector into 2, 1, 3, 2. 2 would be the outcome for low, because that's our second class. You have 1 for the second thing, which is high, because that's our first class. You have 3 for the third place, because that's third class, and then 2, so the second class. When we unclass it, you can see that it's 2, 1, 3, 2, because of the ordering it did by the classes, right? Because remember, it's high, low, medium. If we were to try to do as.numeric on our vector, what would happen is you will see that we will just get a bunch of NAs, and it says NAs introduced by coercion. So even though I've just shown you that this in fact can be viewed as numeric values representing the level 1, level 2, level 3, if you actually wanted to implement something like this on the original character vector, what you would have to do is you'd have to do as.numeric and then do it on the factor, because that's how it can actually figure out what the factors are as parts of those levels. So if you do that, notice that it will in fact give us the integer values 2, 1, 3, 2. And also that there is no warning associated with this, unlike the prior one where it's introduced NAs into our output. Because factors are integer indices, the first level 1 is treated as our baseline or our reference group for our standard regression models. Alphabetical assignment is rarely what you are looking for in analysis. For example, high being the baseline before low or medium because it comes first alphabetically. So what we'll do is we'll use the levels argument or relevel to explicitly establish control groups and prevent garbage dummy variable outputs. Okay, so again, we're going to go back to another example. In this one, we have the object f trapped, and this will be factor concatenate low, high, medium. So just like before, we have created a factor which is made up of low, high, medium, but if we look at it, it's going to reorder it into high, low, medium. So what we're going to do is we're going to use the levels command on that f underscore trapped, and this is going to tell us that our levels are high, low, medium. We don't want that, right? Because that doesn't really make sense. When I'm looking at something and I want a baseline, I generally want it to be low, medium, high. Or if I am using high as my baseline, then I would expect it to be high, medium, low. Wouldn't expect just some random order, because then the comparison really doesn't make any sense whenever I'm actually analyzing using these factors. So what we're going to do is we're going to take our f ordered and we're going to do factored. And this is going to be, again, same data, low, high, medium, except for now what we're going to do is we're going to set our levels to low, medium, high. So now when we do this, we are going to have the order that makes sense for us, low, medium, high. Now if we run our levels, you'll see that it's in the order that we want, low, medium, high. Now one thing I want to note here is when you tell R to run a regression on text data, it silently is going to cast it to a factor first. If you don't control the levels yourself, your summary output will choose your reference baseline group alphabetically. So this can actually lead to a lot of issues. For example, if your groups are placebo or drug, drug will become the baseline purely because D starts with P. But always, a lot of times, we're going to want our other group to be the baseline. So this is something you do need to keep track of when you are working with factors. Next, I want to revisit our missing values. Now that we've looked at all sorts of things with data and putting data into different types of objects, what about missing data? So missing values, again, are denoted by NA, or they can be NaN for not a number. So this would be NA or NaN for unidentified mathematical operations. We can use is.na to test objects if they're NA. You can use is.nan to test whether objects are NaN or not a number. So NA values have a class. Also, you can have integer NA, you can have character NA, things like that. So it can have a class associated with it. You could say that it is a class of character, but we don't know what it is, right? So it's not available, but it is this type of class. And you can have that sort of attribute associated with it. An NaN value is also NA, but the converse is not true. So if you have something that's NaN, not a number, that means that it is NA. But if I have a value that's NA, it does not necessarily mean that it is also NaN. So let's actually prove that by doing an example. So first thing we're going to do is we're going to create this object, which is 1, 2, NA, 10, 3. So we have 1, 2, NA, 10, 3. I'm going to do is.na on this X. And you will see that we get false, false, true, false, false, which makes sense, right? Because 1, 2, 10, and 3 are not NA. NA is NA. If I were to run is.nan, you will see that we get false, 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 because that NA is not NaN. And I know it may seem like a small distinction that doesn't matter, but it does, because NaN is just saying it's not a number. NA is saying not applicable. It could be anything. It could be not be a number. It could be a mathematical operation. It could be something where we don't have that numeric value that we would expect. The next part of the example, we have X, which is going to be assigned as 1, 2, NaN, NA, and 4. Now if we were to do is.na, for is.na, we have false, false, true, true, false. So notice that NA showed up as an NA, sure. NaN also showed up as an Na. But if we were to then run is.it.nan, when we do this, we get false, false, true, false, false. Notice that the Na shows up as true, whereas in the NaN shows up as false because NaN is part of Na, but it is not necessarily Na itself, right? So you can think of it as it's one-way street. Anything that's NaN is also Na. Anything that's Na can be NaN, but it's not necessarily, so it'll always give us a false. So we're gonna stop here for this lesson, and then when we come back, we're gonna jump in to doing data frames and finishing up this section all about data in R. Data frames in R are one of the most useful type of things that you will deal with when you are learning to program in R and doing statistical and computational statistical analysis. Data frames are used to store tabular data. They're represented as a special type of list where every element has the same length. Just like I mentioned previously, if you have a vector of some number of outcomes, this can be converted to a matrix, which is just a vector with some dimensions where they all have the same length. Similarly, a list can have all sorts of different objects with different classes, but if you want to convert it to a data frame, it is a special list where all of the different individual parts of it have the same length. Each element of the list can be thought of as a column and the length of each element as the number of rows. So just like before with our matrix, we have number of rows, number of columns, a data frame also has a number of rows and a number of columns. But unlike matrices, data frames can store different classes of objects in each column. For example, this is just like list, whereas in matrices must have every element be the same class. So if I have a numeric matrix, everything in it has to be numeric. If I have a single character string, it's going to have to coerce it into all characters. In a data frame, if I have a column of characters, let's say that we have a bunch of data and one of the columns is, did you have breakfast this morning? Yes or no? Well, guess what? I can do this in a data frame because while the rest of it might be numeric, what's your body weight, what's your height, what's your age, did you have breakfast this morning? Well, a matrix would have to coerce it all into character strings because of that yes, no part. A data frame does not need to do that because it can have different classes. So one of them being character string, the others being integer or numeric or logical or complex, whatever it is that your data type is for your data. Now, one thing to note is when you use data.frame, which is one way you can create data frames in R, historically this will convert character strings to factors automatically. So it'll be string as factors equals true as the default argument, versus how modern tibbles will preserve your data structure exactly as it's imported. And this is one of the strengths of using things like tibbles. Again, we've talked previously that I might bring in more about other packages, specifically tidyverse, and this is why they are kind of like the industry standard for anyone using R, because they add extra things like this that are just more structurally sound for how people are doing all this stuff. So when you are in base R, like we're learning about right now, if you use data.frame, it will convert character strings to factors automatically, unless you change the argument. Whereas if you were using tibbles within the tidyverse package, which is actually a package of packages, this will just actually import directly to a data frame without making any of those changes. Data frames have a special attribute called row.names. So unlike other things like matrices where we just have the column names, data frames also have row names. In fact, whenever I pulled up MT cars, you've actually been seeing a data frame already, and we'll look at that in a minute. Data frames are usually created by calling read.table or read.csv, depending on where your data is coming from. If you have a table of data, you can do the read.table, or you can use a special case of read.table, which is CSV, which is the comma-separated value table. And this is a lot of times how people will import data, especially when they're learning R and you're not using more complex sources. You would just get a CSV of the data, and then you'll pull it in. In fact, in this class, pretty much most of the stuff that I give to the students are going to be CSV files that make it easy to just import into R and start working on. They can be converted to a matrix by using data.matrix. So if you have a data frame where everything is the same class, it actually can easily be converted to a matrix because Just like before, with a matrix, we have number of rows, number of columns. A data frame also has number of rows, number of columns. And all you're doing is you're adding this extra restriction where they all have to be the same class. So let's look at an example. First thing is that we have X, which is going to be data.frame. And we're going to set column 1, so column 1, as the values 1, 2, 3, 4. Then column 2 is going to be the logical statements, true, true, false, false. So both of these we've given a name. When we set that call 1 and call 2, that is the label that we are giving it. Remember I told you they were giving it a name? So let's set that up, because I actually didn't set that up prior to this. So we have X, which is data.frame. And then first thing we have is we have call 1 equals 1 to 4. And then we have call 2, which is going to be equal to, we're going to concatenate the values, and it's going to be true, true, false, false. Now I'm going to run this. I'll put X so we can see it. And you will see that we get this data frame. So for the first column, we have 1, 2, 3, 4. For the second column, we have true, true, false, false. If we then were to look at the number of rows, so in row X, we will get that there are 4 rows. If we were to look at the number of columns, you will get that there are 2 columns. Just like before, if I want to just look at this in general, I could say, what are the dimensions of X? It is a 4 by 2. I'm going to say matrix, but it's not a matrix though, because if we look at the type of within this, so let's do, actually real quick, before we do that, let's do names X. And you'll see that we have 2 names for our columns, call 1 and call 2. Those are not arguments. Those are me setting the name as I'm setting up what they are. So if I were to do X money sign call 1, you will see that I get 1, 2, 3, 4. If I were to do X money sign call 2, you will see that I get true, true, false, false. So now what I'm going to do is I'm going to look at the fact that they are different. Type of X money sign call 1, you will see that we get that is an integer. Type of X money sign call 2, you will see that it is logical. So this data frame is made up of an integer vector and a logical vector. Notice that they have different classes. It did not coerce them to being the same. A reminder, your data frame, like a list, does not have to have the same class, but in fact, it's actually just a special case of list where it adds the number of row and number of column vectors, the dimension attribute. In a data frame, because columns are stored as elements of a list, operations that target these individual columns, that's to say are different variables, are optimized and highly efficient. Unlike matrices, a data frame can store completely different data classes, for example, character, numerical, logical, in each column, while enforcing a uniform length across all rows. So that way, all of your data will have that uniformity in the number of rows or number of columns, but you can have your different classes within each of those columns. In the modern data manipulation pipeline, though, standard data frames are upgraded, again, using something like Tibbles, which is part of Tidyverse. It will help you print cleaner console overviews and throw explicit immediate errors if you query a missing column name rather than silently dropping it into an undefined state. And these are some of the strengths of using things like Tibbles. One thing I want to do before we move on, though, I also wanted to do the structure of X. And you will see, just like before, it gives us the same output as when we had a list. It's a data.frame with 4 observations of 2 variables. Column 1, it's an integer, 1, 2, 3, 4. Column 2, it is a logical with true, true, false, false. What would happen if I were to change this to 1 to 5 and I tried to create my data frame? You'll see that error in data frame, call 1, 1 to 5, call 2, true, true, false, false. Argument implying different number of rows, 5 and 4. And so what happened is it didn't work, right? I already had X assigned, so it didn't end up reassigning it. If you didn't have X assigned already, it would have just said that it didn't exist. And then just to kind of expand on this a little bit, I decided to do the structure for MT cars, and you can see exactly here. It's a data.frame, so it is a data frame. It's got 32 observations of 11 variables. First one, miles per gallon, numeric, cylinders, numeric, displacement, numeric, all of these are numeric. So this means that other than having the row name, I could actually coerce this into being a matrix. Now, matrices don't generally have that row.name associated with them that data frames do. This is why this one is in fact a data frame. Even though these are all numeric columns and they're all the same length, we like we're using a data frame because it has those different row names which represent the different cars. Now we're going to look at another example. In this one, we're going to do call list, which is a list where we're going to have ID, which is equal to 1 to 3, and we're going to have treatment, A, B, and A. So this is the treatment that some people are getting based on ID 1, 2, and 3. Then we're going to have some sort of outcome, which is labeled passed, which will be true, true, false. So we're going to have a list with these 3 different things. So let's try it, see what we get. Okay, so now if I were to look at call list and run it, you'll see that it is a list with the first part being 1, 2, 3, second part treatment being A, B, A, and third part passed, which would be true, true, false. Now what I'm going to do is I'm going to turn this into a data frame because all 3 of these have 3 elements within them. So I'm going to do that by putting df from list, so df underscore from underscore list, which is we're going to use data.frame and then on that call underscore list. So when I run that, now my df from list is going to show up as a data frame with ID 1, 2, 3, treatment ABC or ABA, and passed true, true, false. If I were to do is this a list, I'm going to use is.list on my df from list. And you will see that is true because just like before, there is no matrix in R. There's just a vector with the added attribute of number of rows, number of columns, or the dimensions. There is no data frame in R. There's just a list with the extra attribute of number of rows and columns, and of course, row.names. So it is still a list, right? A list is not necessarily a data frame, but a data frame is a list. And just like before, we can actually assess the columns either using our atomic vectors, that money sign, or we can use the square brackets to select specific individual elements, columns, or rows. So for example, if we have df from list, money sign TRT, well, before we do that, let's do our names. Names, df from list, and you will see that we have ID, TRT for treatment, and passed. So what we're doing now is df from list, money sign TRT, and it's going to give us the outcomes from our treatment, A, B, A. Similarly, we could do df from list, use square brackets, and then we have the second square bracket saying choose the second column. And you'll see that we get the same thing, A, B, A. Now, one last thing I want to talk about before we're done with data frames for now, and we'll talk more about this later in the course as we're using it, but when we look at our dimensions of our df from list, you will see that it is 3 by 3. This means that if I want to grab a specific element, so I'm going to do df from list, I can use square bracket, and then I could say, let's say I want to choose the first row, second column. I could do 1, 2, and you will see that what it did is it went for the first row, and it chose the second column, and it gave me a specific element. And it gave me a specific element, which is A. Similarly, if I said first row, third column, we would get, so first row, third column, we get true. If I change the first item within my subsetting, let's say I did 2, 1, what this is going to do is it's going to say go to the second row, go to the first element. This gives us 2, which if we look at our original, we went to the second row, first element, and we got 2. So you can still subset within your data frame just like you would a matrix. You just tell it which row you want, which column you want, or which row and column you want. Because you can select an entire row, right? I could do something like this. Instead of picking the second row, I'm just going to say, I want the entire first column. And I get 1, 2, 3. Or I could say, I want the entire second column, ABA. Or I could get the entire third column, true, true, false. If I leave the second part blank, but before the comma, put a value, this will give me the first row. 1A and true. If I change this to 2, it will give me the second row, 2B and true. And you can actually use any sort of subsetting from this. So for example, if I want the second and third rows, so I could do C, 2 and 3, leave the column blank, which means grab everything from those rows, you'll see that we got the second and the third row. So your subsetting works within vectors, it works within lists, it works within matrices, and it works within data frames. And it works exactly the same thing, the same way. Just touching back a little bit, objects in R have names, which can be very useful for writing readable code, because a lot of times students, when they first start coding, want to put a bunch of comments everywhere. But if you can make your code understandable and readable without having to do that, that actually a lot of times is a lot stronger, because then you're not cluttering it up with a bunch of comments that aren't really adding anything to the code. So for example, let's say that we have X, which is 1 to 3. And what I want to do is I want to look at names of X. You'll see that there's nothing there. What I could do though, is I could do names of X, and then I could assign something to this. For example, I'm just going to do concatenate name 1, name 2, and name 3. Oops, I forgot my parentheses. And now if I were to do names X, I have name 1, name 2, name 3. Having names on stuff can be very useful, because as I showed you, you can go in to a data frame or a matrix and you can grab particular rows, grab particular columns. But oftentimes the way you're going to want to do it is you're going to grab things by their name. So looking at this, if we have X, you can see that we've now created this sort of named factor where it's named, oh, I don't know why I put parentheses on this one, but now you can see that we have name 1, there's 1, name 2, there's 2, name 3, there's 3. Like I said before, whenever you're subsetting, you're grabbing stuff. I'm going to go back to empty cars again. I've done it many times, but if we look at empty cars, you're going to see that we have a lot of data here. If I wanted to grab all the miles per gallon, right, I could look at this two different ways. I could do empty cars and grab it by its name, MPG, or what I could do is I could grab it by its column. So in this case, what I'm going to do is I'm going to do empty cars. I'm going to not grab any rows. I'm going to grab the first column. And you might wonder, why is it the first column? Because clearly I can see that there is this column on the left side here. Remember we talked about data frames. This is not actually part of the data. This is not a column. This is actually the name attribute, row.name. So the first row is named Mazda RX-4. The second row is named Mazda RX-4 wagon. The third one is Datsun 710. These are row names. So when I wanted to grab it explicitly using the particular column, I used square bracket, blank, comma, 1. This is a lot of times where the name can be more useful though, because if I wanted to grab something random like here at quarter second time, instead of going, okay, first row, second row, third row, fourth row, column, fifth, sixth, seventh column, I could just say empty cars, money sign, and then QSET. And you'll see that I can grab that data without having to try to figure out what row or column it is. Lists can also have names. So going back to our name part, let's now create our object X, and we're going to create a list where this is going to be A is equal to 1, B is equal to 2, and C is equal to 3. Now if we were to look at X, you'll see that we have 3 parts, 1, 2, and 3, and they have a name associated with them, A, B, and C. If I were to do names X, you'll see that we have the names A, B, and C. Also, matrices. If I wanted to give a name to a matrix, so this would be matrix. Oops. We have M, which is a matrix. And what I'm going to do is I'm just going to create a simple matrix where I have 1 through 4, and then I'm going to have the number of rows equals 2, number of columns equals 2. If we were to look at M, you'll see that right now it has no name. It's just going to tell us by row and column. So for rows, I've got 1, comma, nothing, 2, comma, nothing. For columns, I've got comma, 1, comma, 2. right? It's telling you which of those rows or columns it is. But if I wanted to add names, it's a little bit different. Instead of just doing names for a matrix or a data frame, we are going to use dim names, so dimension names. And so what we're going to do is we're going to say, what are we adding the dimension names to? In this case, it is our object M, and we are going to make a list where we're going to concatenate the values A and B. And then for our rows, we're going to concatenate C and D. So now if I were to run this, what is my M? Well, my M is now still the same matrix, right? So 1, 2, 3, 4, but now my rows are A and B, my columns are C and D. So I can use dimension names to name not only the rows, but also the columns, or not only the columns, but also the rows of a matrix and a data frame. Data frame works exactly the same way. So we finished up with data, coercion, entering data, different types of how data is stored, whether it be data frames, lists, vectors, or matrices. Last thing I want to briefly kind of talk about is how do you get your data actually into R? So there's a couple different ways you can read data into R. And I've got more on this again later, just like a lot of stuff. But the main ways we're going to do this are using read.table or read.csv. So this is the one that everybody starts with. And if you were to do $read.table, and to get our documentation, you're going to see there's a lot of different options that are available. But notice right underneath it, it has read.csv with it, and it has a lot less options. And it's because read.csv is a special case of read.table with this part right here. Separation, or sep equals, and then what separates your data. For a read.table function, you would have to specify this. It's got the argument here for you, sep equals something within quotes, and you would have to say, how is your data separated? Is it separated by commas, is it separated by dashes, separated by periods, which if it is periods, you do have to change your decimal, because some places they might have a comma for decimals and a period, something like that. But for CSV, notice that the default is sep equals, and then within the quotes, it has a comma. That's all it is. A read.csv is how you could read a CSV file, which basically looks like an Excel workbook. Whenever we look at it, if you click on one a lot of times, it'll pull it up in Excel. But it's not actually. What a CSV actually is it is just a basic text file with numbers and things separated by commas. So let me give you a quick example. For one of the projects I do for Intro to Stats, we use the old faithful dataset. So if you look at this, we have faithful.csv. If I open this, what's going to happen is Excel is going to open up and you're going to see some data for eruptions. This is how long an eruption is for Old Faithful at Yellowstone National Park, followed by the column waiting, which is how long you wait between eruptions. And like I said, if you just click on it, if you have Excel or something like that, it's going to look just like this. But let's actually look at what this underlying file actually looks like. So what I'm going to do is I'm going to do open with, and I'm going to open this with Notepad. This is what the data actually looks like. So each row is a different line in the Notepad, and each column is separated by a comma. So for the first one, it's 3.6 for the eruption time, it's 79 for the waiting time. For the second row, it is 1.8 for the eruption time, it is 54 for the waiting time. This is what a CSV actually is. It is basic data where it is line represents a different row, comma is how you separate data. That is why it is comma separated value whenever you use CSV. You can also use read lines. This is for reading lines of text time. So basically, if this is one, if you have a bunch of text coming in, you can do read lines. You can do source. This is for things like reading in our code files. This is the inverse of a dump. You could use dget. This is for reading in our code files. Again, it's the opposite or inverse of a dput. You can do load for reading of saved workspaces. So remember how I told you when you close RStudio, it's going to say, hey, do you want to save this? Even if you've saved your file, what it's doing is it's saving your workspace. It's saving all the variables you have. It's saving anything you have open and you're using. It's going to save that into a workspace. You can load that using load. Or you could use something like unserialized. This will be for reading single R objects in binary form. There are a lot more different ways that you can bring data into R. I have an entire slideshow devoted to different ways you can import data, and there's a lot of them. These are just some of the most basic ways, but the main one that students are going to use are going to be the first two, read.table or read.csv. As I mentioned before, a lot of times when you're learning about stuff like this originally, you're going to get things in this form. You're going to get a CSV, you're going to import it, you're going to do your analysis, you're going to do all this. That's sort of where the end of a class like this usually stops. And then you would need to go out further to figure out how to do things like import doing an API call or something like that, where you're pulling in a different method to get the data in, especially if you want to have live data where it's constantly updating, stuff like this. But for now, we're just going to focus on these main ones, things like read.table and read.csv, because we're focusing more on the programming aspects of it right now. We're focusing on the analysis, we're focusing on R, and we're going to focus on the statistical computation. Later, I may make videos and stuff like that going into more detail of these expanded topics.
Hello, everyone. In statistics, a lot of times a big part of it is that we need to disseminate our ideas. It's not just a matter of doing analysis for the sake of doing analysis. And the way we do this oftentimes is by displaying the data in either tables or graphs. So that's what we're going to dive into today. First, let's touch back on categorical data. So we often view categorical data with tables, and this will allow us to look at our data in a bit more of a graphical manner. Instead of just having all the data listed out in some long list, what it'll do is it will combine the data into groups, allowing us to get a better feel for what we're seeing. You can do this using the table command in R, which will allow us to turn this list of data into a table. Its simplest usage will look like something like table, and then whatever your X is will represent your data with your categorical variables. So let's jump straight into an example. Let's say you have a survey that asks people if they smoke or not. The data is yes, no, no, yes, yes. So we're going to create this data using X, and we're going to concatenate the values yes, no, no, yes, yes. And notice that each time we have it within quotes because this is just a category. Either you are in a yes answer or you were in the no answer group. And then we will take that data X and we will put it in a table. So let's jump over to R, and I've already got it set up here. So I'm going to do exactly this. X is yes, yeah, no, no, yes, yes. And then, of course, if I were to just look at my X, you will see that it is these character strings. And now what I'm going to do is I'm going to do table X. And you'll see that our display here is that for X, we have no, there are two categories, two outcomes. And for yes, there are three outcomes. Now, one thing I want to caution you about here, and you can actually see I've already set it up in the next line, is what if one of the outcomes was lowercase? So we have yes, no, no, yes, yes still, but what happens if I create a table is now it sees this as a third category. It has no, two answers, lowercase s, one answer or response, and uppercase yes, two responses. So this is something you always need to be careful about when you're dealing with categorical data, especially something that people type into a system, because you're sometimes going to have capitalization on some, not on others. You're going to have typos. And this is a lot of that part we talked about previously, where you're going to be needing to clean up your data. In fact, a lot of times whenever I'm doing anything with natural language processing, this is one of the first thing I do is I either get rid of capitalization. I also could sometimes use things called like stemming or lemmatization to try to break words down into the root part of the word, so that, for example, play, played, and playing would all just be categorized together for the word play versus being separate categories within the data. You can also use factors for this. So categorical data is often used to classify data into various levels or factors. For example, for our smoking data, this could be part of a broader survey on student health issues. And R has a special class for working with factors, which occasionally it can be important to know, as R will automatically adapt itself when it knows it has a factor. So to make a factor, just like we had talked about in our previous lesson, we can use the factor command. Or if you already have the data, you can use as.factor to treat it as a factor within some other function. So just like before, if we were to look at our code here, we have x. This would just output our responses. So I don't have that part put in here, so I'll just do it now. So if we do x, you'll see that it's yes, no, no, yes, yes. If I were to do as.factor x, what's going to happen now is it's going to put it and now as a factor. So notice it lost its quotes, everything like that. We've talked about this previously. Now this is still in the x where I had the lowercase yes, so it, just like before, treated that as its own category. So whenever you factor, it's actually going to tell you what the levels are, right? So you have your data, yes, no, no, yes, yes, but also the fact we have levels, capital no, lowercase yes, capital yes. And just like before, you can change the ordering of these values, these levels, by using the levels attribute. So now that we've actually created some tables using very simple examples, let's jump into some different types of graphs and charts we can do in base R. So first we're going to look at bar charts. So a bar chart will just draw a line with the height proportional to the count in the table. Now by default, your bar chart is going to be vertical. You can use attributes to make it horizontal if that's what you prefer. So the height could be given by the frequency, or it can be set as a proportion. It will look the same, but the scales will be different in this case. If you're using the pure count, or if you're using a proportion, it will look the same, but the y-axis will change. So suppose that a group of 25 people are surveyed about their favorite beer that they drink. Categories are 1, domestic can, 2, domestic bottle, 3, microbrew, and 4, import. And our raw data is as follows: 3, 4, 1, 1, 3, 4, 3, 3, and so on. So we're going to do something a little bit different here, though. We're going to use a new command that we haven't talked about before, which is called the scan command. So the way the scan command works is it allows you to directly input data, and it will scan it until you've gotten to a new line with no data, hit enter, and then it will stop inputting data. So we're going to make our bar plot with both frequencies and proportions. So let's do that. First things first, we're going to start with our command beer scan. And when I run this, notice what happens in my console window. It says 1, and it's asking me to type stuff in. So this is where I would actually put the numbers in. So if I wanted to just follow along with what it did here, 3, 4, 1, 1, 3, 4, 3, 3, 1, 3, 2, 1, 2, 1, 2, 3, 2, 3, 1, 1, 1, 1, 4, 3, 1. And when I hit enter, it's going to go to a new line. It's going to say 26. That means that I have 25 data points so far that it has scanned. If I just hit enter on this line with no data in it, this will end the scan. So it's read 25 items. So now if I would put in beer and run this, what's going to happen? It's going to give me those 25 data points. So this is what the scan function allows you to do. So if you have a bunch of data coming in, you want to type it in quickly on numpad like I did, you can do exactly that instead of having to copy it in. Now, for the code, for the future times we do this, I actually did copy this in so I could just copy it in and not have to type it every single time. So now that we have our beer data scanned in, which remember, 1 represents a domestic can, 2 represents domestic bottles, 3 represents microbrews, and 4 represents imports. What we're going to do is we're going to create a bar plot. So if I use the bar plot function, you'll see that we get this graph. Now, this is an accurate bar plot, but it's not very good. It's pretty ugly, and it has a lot of problems. So what this bar plot actually did is, for the first bar, this represents the number for the first data. That means that it has a value of 3. The second bar is 4. The third bar is 1, and then 1. So what it's doing is it's actually doing a bar for every individual outcome. But generally, when we have a bar plot, that's not what we're actually trying to figure out. We're trying to figure out, we want to see some graph of how many people like domestic can, domestic bottle, microbrews, or imports. So what we can do in this case is we can use that table. So remember when we looked at table, so if I do table beer, what we have is that we have 10 people who prefer domestic can. We have 4 people who prefer domestic bottles. We have 8 people who prefer microbrews, and we have 3 people who prefer imports. So what we can do is we can actually put that within our bar plot command, or function, and now we get a bar plot based on the groupings. So now we see the bars as a proportion with their total frequency on the y-axis of what the preference is. So you can see that the most common preference is domestic can, followed by microbrews, followed by domestic bottles, and then last we have imports. What if you instead wanted to do this as a proportion? We don't want to know that 10 people selected domestic cans. We want to know what percentage did. Well, we can create a percentage by taking the individual raw data from our table, which again, if you remember, is 10, 4, 8, 3, and we can divide it by length of beer. Length of beer is going to give us the amount of data we have. And we had 25 data points, so this will be 25. As I mentioned previously, a lot of times if we cannot hard code in a number like 25, it's better because that way, let's say that you have a program like this and you get more data. Next thing you know, you go out and do a survey and you survey 100 people what their beer preference is. Well, now instead of having to go and change everywhere you referenced how many data points you have, instead you can let R find it for you. You can say, okay, well, I have X is 100 data points, take length of X, it's equal to 100, and then I can just find my proportion by taking the individual values, which is really just a relative frequency, 10 domestic can preference over 25 total, 4 domestic bottle over 25 total, 8 microbrew over 25 total, and 3 import over 25 total. So I'm going to run this, and you will see now that we have the relative frequency for each of these, which represents the proportion. So we have 40% or 0.4 prefer domestic can. 16% of our people we surveyed prefer domestic bottles. 32% of our people, or 0.32, prefer microbrews, and 12% or 0.12 prefer imports. So now what we can actually take this data and we can put it directly in our bar plot, because remember, R is immutable. So if I were to go and look at beer, it is still the raw data. But I can take this exact function that I've created here, this command I've created here, table beer divided by length of beer, put that within my bar plot, and now what we're going to get the exact same graph. As I said, it's going to look exactly the same, except for what's going to change is my y-axis is now going to be representing proportion, or the relative frequency of the preferred beer of these people we surveyed. So in this example, though, we use the scan function to read in our data. This command can be very useful in reading data from a file or by typing, right? So for example, if somebody gives you a long list of data and it doesn't have commas in it, you could copy it in to R, but then if you wanted to do like concatenate, you have to go and put a comma between every single data point. Or what you could do, just like before, is, like I said, I copied these right here. You could literally run beer.scan and then paste in this long list of data where there's no commas put in, and guess what? Now I have the data loaded in. So this is one of those places where scan can actually be very useful. Now, looking back at our graph though, you can see that the color scheme is pretty ugly, right? There's no labels on this graph. Really, this would not be a good bar plot, or bar chart, and I would not recommend anyone do something like this. Like for example, when I'm teaching my intro to stats class, we specifically tell them that you need to always label your x-axis, label your y-axis, put a title, things like that. Well, let's look at that. So you can see here that we have 3 different bar plots that we want to plot. The first one, right, we're going to take bar plot and we're going to plot beer, but we're now using the attribute main. This is the attribute that allows us to give the chart a title, right? So in this case, I just put, oops, I want 4 categories, not 25. That's just saying sort of like the first one we did and adding a title to it. And again, this one wasn't the correct graph. The second one, what we're doing is we're again taking a bar plot of table beer. So this time we're doing a proportion, and now it's going to give us the groupings, and then we change our title. Main is 4 categories bar plot. And notice the next part, I have YLab. That is how we label our y-axis. So we're going to label that as frequencies. And then I'm going to change the color a little bit. I'm going to do call for color, and this is going to be color 90, which will be a different, gray 90, which will be a different color of gray than the one that was defaulted to. And then the last graph we're going to do, we have bar plot. We're going to take our table beer divided by length of beer. That's going to give us our proportional data. We change our title for 4 categories beer plot. And we're going to change our Y label in this case to proportion. But now what we're going to do is we're going to use color 3, and that's going to change our color in this case to a green color. So let's try that out. Going to R, we have our 3 bar plots. So the first one is going to go back to the original bar plot, but now it has a title. So oops, I want 4 categories, not 25. Great. And anything, this is why your titles are in quotes, because notice I have a period in there. You can have other special characters. But remember, going back to the original lessons, sometimes you're going to have special characters you can't directly put into the quotes. For example, if I want to put a quote within a quote, it's going to cause issues. So in this case, that's where you would need those stop commands. So next graph, let's graph it, see what it looks like. Okay, so now we've grouped it, and notice that the color has changed. It went from that dark gray to a lighter gray, and we've added this Y label, frequencies. So comparing it, you see no Y label, and we had this darker gray. Going to our new one, we have a lighter gray, now we have this Y axis label. And now for our last graph, again, we're doing a proportion in this case, table beer divided by length of beer. We've got our title, we've got our Y-axis, but now we're going to have color equals 3, which will change it to green. So when you are doing graphs like this, a lot of times you're going to want to select different colors. And you'll see an example, you can probably see in the code below, I have an example where I type in different colors, but you actually have a lot of different options. You can use different numbers to represent colors. So for example, let's try a few out, right? I always say, whenever you're not sure about something, try it out. So color 1, we get black. It's sort of, yeah, it's black color. Color 2, you can see it's sort of a light red color. Color 4, you can see it's a blue color. Color 5, and there's a bunch of different colors you can reference by number. You can also type in color names. For example, let's say I wanted to do red. Well, in this case, because it's a character string, I'm going to put quote, I'm going to put red. And notice that RStudio will automatically put a color if it knows what this is. Just a way to help with, again, making the code readable and stuff like that. So if I were to do this, now I have a red graph. Before we move on to more examples and expanding on all this, I actually wanted to briefly jump aside to talk about some of the colors in R. So I pulled this site up, as you can find on bookdown.org, and it's got this chart. You can see a bunch of different colors. We could do Alice blue, antique white, aquamarine. You've got blue 3, blue 4, blue violet. So it's not just a matter of your primary colors, you know, your red, green, blue, or even your Roy G. Biv. There are lots of different colors that you can do. You can do light green, you can do maroon 2, you can do medium orchid, you can do red 4, sea green 2. This is there's a lot of options for colors in R. In fact, there's actually more, because any color that you can think of can actually be represented using hexadecimal code. And these also will work in R. So for example, let's say that I wanted to do, let's pick a color we haven't done before. Let's do a light pink. So I'm going to pick # FFDCF5. So I'm going to copy that in. I'm going to put that within my quotes. And you'll see that it colored it pink in the actual code. And now when I run it, I have this color. So as I said, you can do hexadecimal colors for your graphs. And there's also some other fun ones you can do. Before we move on to a new type of chart or graph, what I want to do is, as always, I want to do * bar plot. And when I run this, you're going to see all the different options you can have for this. For example, you got bar plot. It's got height, and then there are a lot of different arguments, right? Your default is width of 1, space equals null. You got names, horizontal equals false. This is where you would change it to a horizontal bar plot. So if you wanted to, I could go into, I'm going to do my first one just because it doesn't have a lot of stuff in it, and I'm going to put horiz equals true, and you will now see that it is a horizontal bar plot. You've got main, which is where you label your title of your graph. You have X limit. This will affect the sort of the width of the graph. So if you wanted to go out further, or you wanted to cut off near the end, maybe you have a really far outlier out there and you just wanted to focus on the center of the data, you could affect your X limit. Y limit, same thing, put in your Y axis. Maybe you want to zoom out a little bit, you can change your Y limit. X lab, this would be your label for your X axis. Y lab, this would be the label for your x-axis. So there's a lot you can do with this on top of what we've done, right? I'm only showing you the basics of how to do graphs, especially because most people will do graphs like this for a quick analysis for themselves. But if you really want to make great graphs for display, you're going to do what we're going to look at later in the section, which is going to be using ggplot to create much better graphics and charts. The next type of graph we're going to look at are pie charts. So the same data can be studied with pie charts using the pie function. So here's some simple examples to illustrate its usage, similar to how you can do like box plot, but with some added features. So first things first, we are going to have a new variable we're going to set up called beer.counts, and this is just going to be the table of our beer. So we don't have to type table beer every single time. And then we can create our original pie chart using pie beer.counts. So let's do that. So we have beer.counts, which is going to be our table. So if we look at that, you can see, 1, 10, 2, 4, 3, 8, and 4, 3, which remember, 1 is domestic can, 2 is domestic bottle, 3 is microbrew, and 4 is import. So now what I'm going to do is I'm going to do pie beer.counts. And you can see that, bam, it instantly makes a pie chart. But this isn't really that great of a pie chart because, yeah, we have 1, 2, 3, and 4. But part of the problem with pie charts is it's not very helpful because I don't know what these proportions are. And most people are not great at determining like what the actual proportion is. I can tell that 1 is bigger than 3, which is bigger than 2, which is bigger than 4. But otherwise, I don't have any sort of easy way to directly compare them. But first things first, let's actually update this a little bit to make it so it's labeled. Because right now, 1, 2, 3, 4 is kind of confusing. Every time I do it, I have to go, okay, 1 is domestic can, 2 is domestic bottle, so on and so forth. So what we're going to do now is we're going to add labels to this by giving names to our beer.counts. So if we look at this, you have names, beer.counts, and we're going to apply our concatenated values of domestic \n can, domestic \n bottle, microbrew, and import. So if you remember, the \n, what this is going to do is this is going to create a new line. So if I were to run this, let's see what our names look like. So it shows exactly what I wrote here, right? So not great, but this is what I was kind of talking about before, is that it depends on what you're actually doing with it. Because I just looked at it, I didn't tell it to print or anything like that. But if I were to do my pie chart now, look what happens. Notice that where that \n is, it cuts to a new line. So domestic can becomes domestic, and then it's followed by can. Domestic bottle becomes domestic bottle. This will make the graph look a bit cleaner because if we, for example, if we didn't have this, this is what our graph would look like. So I'm going to get rid of those. And in this case, it looks fine, but sometimes it's going to look very cluttered and you're going to want to have that sort of control over spacing, separation, lines, stuff like that. Next thing I'm going to do is I'm going to add some individual colors. So in this case, I'm going to do pie beer.counts, but in my color, instead of just picking one single color, I'm going to use my C command in order to give 4 different colors. So it's going to be purple, green 2, cyan, and white. Notice again that RStudio will show me what those colors look like. So if I run this, now I can actually control the individual colors of the different parts of the graph if I want. You could do the same thing in bar plot. If I wanted to, I could have had each bar be a specific color that I selected. Or I could do some sort of gradient, stuff like that. There's all sorts of options you can do. Now, in our effort of always trying new things, what would happen if I didn't have enough colors? Let's say I only put 3. Let's find out. So if I were to run this now, notice what's going to happen is that it's going to recycle. It's going to go purple, green 2, cyan, purple, green 2, cyan, purple, green 2, cyan. It's going to cycle just like it did whenever we were working with data in different matrices, data frames, things like that. So that's really kind of it for our pie charts. Just kind of recap for our first one, it was kind of boring, so we added names to it. We did that with the names command, which allows us to specify the different names of our categories instead of using 1, 2, 3, 4. Resulting pie chart showed how the names can be used, and then we added some color to our pie chart. So setting the color is done with the attribute call. We can set this equal to a vector of color names with the length, which is equal to our data we have, the categories of our data, not the actual data itself. Or we can actually use, like I said before, hexadecimal colors. There's a lot of different colors available. Whenever you want to know more about something, what do? We always put question mark and then the function. So if we do that real quick, let's do question mark pie. And then you can look at the individual attributes of this. And there's always going to be some that are specific to whatever you're looking at. For example, we have clockwise equals false. So this is not something we would have with like bar plots. In this case, what it's saying is that it's actually going to fill in counterclockwise. If you want it to fill in clockwise, you would do it with clockwise equals true, but the default is false. You can also set the initial angle. Init.angle is if clockwise, 90 degrees, else 0. You got density, angle, all sorts of stuff like this that you can play with to create the graphs that you're trying to show whatever it is you're trying to display for whoever you're doing it for. So those are the two of the most common types of graphs we'll use whenever we have categorical data. Now let's look at some graphs whenever we have numerical data. So to describe a distribution, we often want to know where it's centered and what its spread is. And these are typically measured with certain things like mean or variance, or of course standard deviation, which is just the square root of variance. Or oftentimes we'll use median, or specifically we might want to use a 5-number summary. So there's commands for this, for all of these in R. For example, we have mean, we have var for variance, we have SD for standard deviation, we have median for median, we have 5num for 5-number summary, and we have summary for a different type of 5-number summary using quantiles instead of medians. We're going to jump into a new example now. Suppose that we have CEO yearly salaries or compensation has been sampled, and we have the following that were found in millions. So we're going to use our scan command, and we're going to have 12.452 58,314.25. And then we're going to find the mean, the variance, the standard deviation, the median, the 5-number summary, and the summary. So let's do just that. Just like before, I said that we can do cells equals scan. And then I'm just going to copy this data so I don't have to actually type it all in. So I've read in 10 data points. These are the different salaries or compensation of these CEOs in millions. So if I were to use the mean function, what it's going to do is it's going to take those 10 values, it's going to add all of them up, it's going to divide by 10, and it's going to give me the mean of the data. So we get 8.565. So of these 10 CEOs, their average compensation is $8.565 million a year. Now let's look at the variant. If we do question var, looking at our variance documentation, I kind of wanted to look at this first because oftentimes, if you studied statistics, you know that we might divide by n if we have population data, or we might divide by n-1 if we have sample data. These are the kind of things you need to think about when you are using a computer program to do stuff like this for you, because you need to figure out what is it, or the defaults that it's using, and do you need to do anything to change that. So if we scroll down a little bit here, you'll see this part right here. Var is, nope. The denominator n-1 is used, which gives an unbiased estimator for the covariance for IID observations. This means that when we do variance, we are treating this as sample data. So if you wanted to do a population variance, then you would need to put an argument in to actually adjust this. You also can change the method that it uses for variance. So for example, you could use Pearson, which is the default, you could use Kindle, or you could use the Spearman variance. If we want to find standard deviation, we can do SD, and it's going to have similar kind of arguments. So our standard deviation is going to be 15.01714, meaning that the standard deviation of the compensation of these CEOs is a little over $15 million a year. If we look at the median amount that they make, it's 3.5 million. If you remember, the median is just the middle value. So if you have an odd number of values, it will be the exact middle one. If you have an even number of values, it will be the average of the middle two numbers. That means that half of the CEOs get less than $3.5 million in compensation. But the average amount of compensation is $8.565 million, meaning that based on this data, we have some pretty big outliers in the positive direction. You have one or two CEOs making a lot of money, which means that it's going to pull the average up because it's heavily affected by outliers, where the median will give us a good idea of where the actual middle is, for half of them make less than this, half of them make more. Now let's look at our 5num function. You can see in the code here, originally I was missing an E. No big deal, I've just fixed it. So if we do 5num, what this is going to give us is, the way you find a 5-number summary is first you find the median. That is going to be your Q3. You have your minimum value, you have your maximum value, and then you find the median between your Q1 and Q3. That will be your Q2. You're going to find the median between Q3 and Q2 and Q4. That will give you your Q3. So what this is telling us is the first value is going to be our lowest value. The last value is going to be our highest value. The middle value, this 3.5, is the median. That is the point where half the data is below, half the data is above. This value, this 1, is the first quantile, meaning that, or quartile, meaning that 25% of the data is below this, 75% is above. And then this fourth number is our third quartile, which is going to be the point where it's our 75th percentile, which is where 75% of the values are below it and 25% are above it. So what you're doing is you're splitting the data into 5 numbers, right? You got the middle of the bottom half, you got the middle of the top half, and then you've got your 2 extreme values. This will come up later whenever we do box and whisker plots, because we're going to be using 5-number summary data, but it does one thing a little bit differently, which is it will automatically, instead of using the minimum maximum, which is how we used to just teach it in Intro to Stats, it actually will use the interquartile range to figure out what the boundary is, where anything outside of it would be an outlier. So something to think about whenever we do box and whisker plots. But notice this is going to differ a little bit from when we do a summary. So when we do summary, you are still going to get 5 numbers. Actually, technically you're going to get 6 because it's going to give you the mean and the median. But what's different is we're going to have our minimum value, just like before. We're going to have our maximum value, just like before. We do have our median, and of course, this also gives us our mean. But notice that our first quantile is 1.25, which differs from our 5-number summary of 1. And our third quantile, 7.250, differs from our third quartile of 8. And that is because instead of using the value where half the data is above or below for each part, so the lower half, Q1, what it's doing is it's using quantiles and it's finding the exact value where the actual number, the percentage, is above or below. Now, one thing that's nice about summary, and this is something I actually do quite a bit, is I love that when I do a summary, it gives me both the median and the mean right here next to each other without having to go through and do it all individually. You can, but the reason is because when I see something like this, a median of 3.50 and a mean of 8.5, this shows me that this is very skewed data. Because remember, if you have a bell-shaped symmetric distribution where it's very normal, then you would expect that the mean equals median equals mode. Well, this clearly does not have that, meaning that we have pretty skewed data. Rather than just relying on summary, we could also use the quantile function to figure out what the actual quantiles are specifically. So first we're going to start by setting up some data, which is going to be 10, 17, 18, 25, 28, 28. So if I were to do a summary of this, right, we have a minimum of 10, we have a first quantile of 17.25, a median of 21.5, a mean of 21, a third quantile of 27.25, and a maximum value of 28. If I were to use the quantile function, so quantile, we're going to take our data, that's where we're pulling from, and we're going to use 0.25. That means we're going to take the 25th percent, where 25% of the data will be below it. You will see that we get the same thing as our first quantile, which is 17.25. If we did quantile 0.75, this would give us the value where 75% of the data is below. And here's the nice thing about doing quantile, though, instead of summaries. What if I wanted to know what value had 66% of the data below it? So I could do quantile data, comma, 0.66, and you will see that I get a value of 25.9. So 25.9 is the point where 66% of the data would be below it. You can also concatenate if you want to have more than one quantile. So we use quantile, data, comma, and then we're going to concatenate 0.25 and 0.75, and this will give us 2 values, which you will see match with our 25th percentile, right, our first quantile, 17.25, and our 75th percentile, which matches our third quantile of 27.25. So the next thing we're going to look at is you can also sort your data. We can use the sort command, and if we do that, it will put it in order Because a lot of times when you have a lot of data, it can be kind of hard to see what the data looks like. It's just a bunch of numbers bouncing all around, stuff like that. So a lot of times you're going to want to sort it. For example, let's say that I wanted to find the median of the data, but I wanted to do it by hand. Well, what's the first step you do when you're finding median? You put it in order. You can either do ascending or descending order, and then you're going to figure out how many data points you have, right? And if it's odd, it's the middle value. So you divide by n, or whatever number it is. If it goes like, let's say it's 7.5, it would be the 8th number. If it's an even number, that means it's going to, let's say you divide by n, you get 6. You go to the 6th value, it's the average between the 6th and the 7th. R can automatically sort it using our sort function. And by the way, there is a lot more in depth about sorting. And you can see, for example, here that by default, it is going to have decreasing equals false. If you wanted to sort decreasing values, you could do that, set it to true. But the reason I want to bring up that there's a lot more to sorting is because if you're interested in getting into more the software developer side, but a lot of data science positions, a lot of interviews are going to involve algorithm type interview questions. And these will be things like sorting questions. How do you do tree sort? How do you do, they might ask you something obscure like what's bubble sort? There's a lot to sorting. For example, if you just look up sorting algorithms, you will see that there are many. Let's look right now and let's just type sorting algorithms. And you're going to see that there are many different ones, right? If we just go to like Wikipedia, you can see all sorts of, these are just, classification type ones, the things to look at. And here you go. Here's a bunch of different sorting algorithms. You got heap sort, intro sort, merge sort, in-place merge sort, tournament sort, tree sort, block sort. There's so many different types of sorting algorithms. Generally, though, when you're programming, you just let the program do it using something simple like sort. But if you need to have a specific type of sort where you want to have more control over it, this would be something that you might want to look more into. It's actually very useful to look into algorithms, sorting algorithms, stuff like that. Okay, so next thing we're going to do is, again, we're going to do a 5-number summary of our data. So I'm actually going to change this from sols to data. And then we are also going to do a summary of our data. And if we run both of these, again, you can see that the minimum and maximum are both the same, but there's a difference between our first our Q1 value and our first quantile, and our Q3 value and our third quantile. When you're looking at the center and spread of data, the most common measurement of center that we use in statistics is mean. Now, I often tell my students that for generally just looking at data, I think that median oftentimes is a much more informative central tendency. But there's a lot of reasons why we tend to use mean over median. So one of the things we can do if you have data that might be heavily affected by outliers like mean is you could use something like a trimmed mean. So the most used measure of center and spread are the mean and standard deviation due to the relationship with the normal distribution. But they suffer when the data has long tails or things like that. It means if you have a lot of outliers or very far out outliers, it can heavily affect or skew your data. Well, one way you can deal with this is you can do what's called a trimmed mean. So the way you can do this is within the mean function, you can use the trim attribute. So looking back at our sales data, we had this. We had 12.4, 0.52, stuff like that. So before we actually do this, let's remind ourselves what our mean was. So mean of our sales was 8.565. Now what we're going to do is we are going to trim 10% of our data. So what this means when you do a trimmed mean is that it is going to take that percentage, it's going to figure out how many values it is, and you're going to cut that much off the lower end, you're going to cut that much off the upper end. So when you do a 10% trim mean, you're actually cutting 20% of the data. You're cutting the lower 10% and the upper 10%, which oftentimes is a good way to get rid of outliers, or if you want to focus on, in this case, the middle 80%. So now if we do this, what do we get? We will get 4.425. So just by cutting off the most extreme upper and lower values, now we have a mean that is much more focused on the center data and makes more sense based on our data. What about if we did a 20% mean? So 2 over 10, this would give us a mean of 3.8333 repeating. Now, of course, I have these as fractions. You can put these as decimals. For example, we could have done this as 0.2, and that would work just as fine. So a lot of times this can be a really simple way to reframe a problem to help with outliers, right? So whenever we're teaching stuff like this, let's say that you have the example that
a bunch of people are on a bus, and let's say you took the average wealth of those people, and it was something like, I don't know, $110,000, right? People have houses, stuff like that. And then somebody rich like Bill Gates or Elon Musk or somebody jumps on the bus. Well, guess what? Now the average income of everyone on that bus is over $1 billion. Obviously, no one else's income is increased, but it gives this false sense that these people on this bus happen to all be very rich when there's just one extremely rich outlier who's pulling the entire mean up. So what we might do is we can reframe the problem. We might say, I want to know what the average person is, dealing with based on income, something like that. So you might decide to do the middle 50%. You cut off the bottom 25%, which is the lowest earners. You cut off the upper 25%, which is the highest earners, and you focus on the middle 50%. So now you didn't just cut outliers because they're outliers. You use the fact that you want to focus on the middle 50%. So the last part we're going to focus on for this video is going to be stem and leaf plots. So if your data is relatively small, then you can use a stem and leaf diagram, which might be useful to help you see the shape of the distribution and the value. The number on the left of the bar will be your stem. The number to the right of the bar, you will only ever want to have one single digit. So that stem represents whatever is there. So for example, if you have the number 11, you would have 1 and 1. Or let's say you were doing it in hundreds, right? 110, 111, 112. It would be 11, 0, 11, 1, 11, 2. It would based on these stem and leaves. And then you can use the size of the leaves, because you put them equidistant from each other, to get an idea of what the shape of the graph looks like. The number on the right of the bar is the leaf, which is a single digit. You combine them to find your observations. So suppose that you have the score of basketball games and you want to find the following points per game for players on both teams. So first thing we're going to do is we are going to scan scores. Let me just copy my scores. Okay, so we have 20 scores in total from these different basketball games. Now let's say that you wanted to look up some function, but you don't know what the actual function is. You just have an idea of like what it sounds like. You want to do a stem and leaf plot, but you don't remember how to do it. You can actually use this function, the apropos function, which will actually look up within R what are all of the things that you can call on that have stem in them, right? So you can, for example, see system file, system32. A lot of them are going to be system, but you'll see this right here, stem. That's our function for our stem and leaf plot. So we're going to do stem for scores, and you're going to see right here, this is our stem and leaf plot. So the way that you would read this, right, our stems are 0, 1, 2, 3. So you combine them, 0 and 0 means we have a value of 0. 0, 0. So 0, 0, 0, 2 means we have a value of 2, 2, 2, 3, 4, 4, 5, 6, 8. For the second row, these are going to be, you're going to combine these numbers. 1 and 2 gives us 12. 1 and 3 gives us 13. 14, 14, 16. For the third one, we have 2, so 2, 3, 23 points, 28 points. And the last one we have 31 points. And this will give us an idea because you can kind of think of this, if you were to rotate this, it would give you an idea of what the distribution is. So this is definitely a right skewed graph because most of the data is on the left and we have a longer tail off to the right, which I guess for you all would be that way. So last thing we're going to do, just as always, we are going to do question stem and we are going to look up because you'll notice we have certain things here. This one is going to focus more on things like spacing, width 80, because like I said, the way you kind of keep track of the shape of the graph is by making sure that everything is perfectly lined up. That way, whenever you have 8 numbers in one and 7 numbers in the other, it won't be the fact that they look about the same because you won't have different spacing, which is one thing when you're doing this by hand, you kind of take that into account. So that's going to be it for these first graphs and some stuff like that around graphs that we've looked at so far today. One thing I want to point out, though, is I started with a lot of the graphs that people use, and they are useful for showing things, but they're not the graphs that we use most often. We're going to focus more on things like histograms going forward, stuff like that, things that you are more likely to see, especially in, statistical or scientific computation. And then after we've done all this basic R plotting, we will then move on to ggplot2. But I do still want to show this because this is one of the strengths of R, is that I can pull up a fresh copy of R that I just downloaded 5 minutes ago, and I can start plotting data. Would they be ones that I want to put into a research paper or on some presentation for a boss? No, but if I need to just get a quick feel for the data, I can do that very quickly. I can just do something like, hist, and I don't know, let's say I'll do my scores. And I can get a histogram within seconds. Now I have an idea of what the data looks like, and I can still make decent looking graphs based on the stuff we've looked at. Right? I can change the colors, I can change the titles, and it's good enough for something quick. Now, again, I wouldn't use this for like production-ready pictures, but this is a lot of power that you have at your fingertips very quickly, right? So just something to keep in mind as we move forward. Hello, everyone. In our last lesson, we left off with doing some sort of graphs using mostly categorical data. Specifically, we looked at bar plots and pie charts, stem and leaf for numeric data. Now we're going to jump into some of the most commonly used types of graphs, which are histograms. So we're going to start by focusing on the way that you can take numeric data and turn it into categorical data. So categorical variables can come from numeric variables by aggregating those values together. For example, previously we looked at CEO salaries, which ranged in various numbers from about 0.1 million up to, I think it was 50 million. So now what we're going to do, instead of looking at the individual salaries of each of the CEOs surveyed, we're going to break them into groups of $0 to $1 million, $1 to $5 million, and anything over $5 million. So to do this, we can actually use the cut function within R and the table function. So suppose that our salaries are, right, we have 12, 0.4, 5, 2, 50, 8, 3, 1, 4, and 0.25 for the amount that these CEOs are paid, or their compensation, in millions of dollars. And we want to break this down into groups of 0 to 1 million, would that be inclusive for both of those, 1 to 5 million, where 1 is not included but 5 million is, and then 5 to 50 million, where 5 million is not included in this group, but anything up to 50 million is. So what we're going to do is we are going to use the cut function in R, and we're going to specifically set the cuts to 0, 1, 5, and 50, which we can actually do with equals max of whatever the data is called. In this case, SALS or SALS for sales. And the reason we wanted to do this is because if we were to go and get more CEO salaries and someone happened to be above $50 million, then instead of being cut off at 50 where they're no longer included, what we could do instead is by setting the maximum based on the data, it would automatically adapt to that. So let's do that. So to begin with, we're going to reload our data. So we're going to use sales and we're going to concatenate 12.45 and all the other data. So we're entering our data first. Then we're going to set our categories. So that's what the cats object is. And we're going to cut our sales data and we're going to break it into those groups we said, 0, 1, 5, and maximum of our sales. Then we're going to view those groups. We're going to set a table. So we'll put all the data into the factored groups that we talked about. And then we will set the levels as rich, richer, and super rich based on those three categories. And then we'll look at our table again. So let's do that. First things first, I'm going to load my sales data and set my cut values. So if we look at our cuts, you will see that we have those groups we talked about, 0 to 1, 1 to 5, 5 to 50. Now what we're going to do is we're going to create a table in that, and you can see that there are 3 CEOs that make between 0 and 1 million, 4 CEOs that make between 1 and 5 million, and 3 CEOs that make over 5 million. But again, this isn't really that descriptive, so what we're going to do instead is we're going to set our levels for rich, richer, or super rich, and now we're going to create our table again, and you will see that we have 3 of these CEOs fall into the rich category, 4 of our CEOs fall into the richer category, and 3 of those CEOs fall into the super rich category. You might wonder, why did we start by setting up this example of taking our numeric data and turning it into categorical data? Well, because whenever you make a histogram, that's exactly what you're doing. Generally, when we teach about histograms, we teach about first by looking at a frequency table, which is you're going to have some groupings, which are your categories, and then you go through your individual data, you put it into the frequency category, and you figure out how many fall into each group. That's exactly what we're doing here, except for instead of doing it manually by going through all the data and putting check marks or tick marks and then writing out what the number is afterwards,
the computer does it automatically. But instead of just doing it where it's equal groups, like we normally would do for an actual histogram, we can specify the groups that we specifically want. Now, I will caution you on this because when you're making a histogram, you do generally want the groups to be the same width. You want to have the same width for each category. And that's because if you have different group sizes, like we're talking about here, this can lead to misleading conclusions. For example, in our category of rich, richer, and super rich, it looks like generally there's some, average number around 3 to 5 that fall into each category. But if we were to break it into equal groups, let's say 5, so 0 to 5, 6 to 10, 11 to 15, so on and so forth, you might find that there's large chunks in there where there are no CEOs. Most of the CEOs fall into these ranges, and then suddenly you have 1 or 2 that are way up on the upper end. So this is why generally we want the categories to be the same size, except sometimes we will specifically make the first or last one bigger just as a catch-all, right? Over $50 million or under 0.5, we might say something like that. An example being if you're doing ages, you might do every 10 ages, but once you get to like 60, 65, you might just say 65 and up. And this is usually just to kind of aggregate it so you don't have, a bunch of groups with very little actual data in them. So if there's too much data or your audience doesn't know how to read a stem and leaf plot, you might want to try other types of summaries. So one of the most common methods to use to summarize our data is to do a histogram, which is similar to a bar plot, except for there are no gaps within it. In fact, when I get data, when I'm doing research, I'm working with a group, something like that, and they send me data, one of the first things I do is I run a summary or a 5-number summary just to get a feel for like what the data looks like numerically, and then I will create a histogram. And this will give me an idea not only of how the data is grouped, but also gives me an idea of the shape of the graph, right? So this will tell me a good idea, give me a good idea of what the distribution of the data is. So the histogram defines a sequence of breaks and then counts the number of observations in the bins formed by the breaks. This is identical to the features of the cut function. So histograms actually already have this built into it. So the cut function we did was external. I showed how we could actually create our own cuts, but histograms already have this feature built in and you can actually integrate it. If you don't specifically tell it what the cuts are, it's going to pick equal cuts based on your data, or you can specifically manually enter them within the function. Then the histogram will plot these bars similar to a bar chart, except for all of the bars will be touching. That being said, you can have groups that have no data in them. So you might have a gap, but that gap would represent a group with nothing in it, not a separation like you would with a bar chart. Because a bar chart, you're using categorical data. Group A, Group B, Group C. They're separate. In this one, it's a continuum of data where it's saying from here to here, this is how many are in it. From here to here, this is how many are in it. From here to here, and it's creating a continuum of data. So the height can be either in frequencies or it can be in terms of proportions. In the later case, when we have it set in terms of proportions, the sum of all of the bars must add up to 1, right? Because if you think of the proportions, which are a relative frequency, you could also equate these to a probability. And we know that probabilities have to be a value between 0 and 1. And if I sum up all of the discrete probabilities, they have to add up to 1. So let's do an example. Now what we're going to do is we're going to add some new data to this. So we're going to use X for this example. So we're going to use our scan function again. And then just like before, I'm going to scan a whole bunch of numbers. And then I have more numbers this time. So I split it so we can see it easily on the line, but you could do this all as one line. And then once I'm done with my data, I'm going to go into the console. I'm going to hit enter one more time. And now we have 26 items in our X. So if we were to pull up our X and look at it, this is what it would look like. Actually, I want to show you one quick thing before we move on. Instead of always selecting X and then running it to see what it looks like, you could also use the print command. So if we use print X, this is just going to print it out for us. And you can see that we have our 26 numbers here. So if I were to just use the hist function to create a histogram, this is what the frequency histogram would look like that based on the cuts that it makes automatically. So notice what it did is it took the data and it split it by cuts of 5. So 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, and 25 to 30. And there is a gap in 20 to 25 where there are no CEO salaries, or whatever this values actually represent. We got off the CEO salary. So our data here is very skewed, right? Most of our data falls between 0 to 5, whatever this is. And if we look at our frequency, that's our y-axis, this group, by looking at the bar, we can go to look at the height, and we see that we have a frequency of 20. Going on to 5 to 10, it looks like we have a frequency of 1 or 2, probably 1. From 10 to 15, looks like we have a frequency of 2. 15 to 20, it looks like we have a frequency of 1 again. And again, this is, if I got data sent to me by some group, I could just do histogram with no information about it, and automatically I get a good idea of what the data looks like. In this case, it's very skewed. Most of the data is to the left, giving us a right skew because the tail is off to the right. If I want to create a relative frequency histogram, which is to say, instead of using the actual frequencies for the height, we're going to do the proportion or the relative frequency, I can use the freq equals false, because the default for a histogram is frequency equals true, meaning that it will use frequency. If we set freq equal to false, we will get the exact same graph, but now instead of being the frequencies, it'll be the relative frequency. And again, if I were to sum all these up, they would add up to 1. As always, let's look at the documentation for our function. So we're going to do hist, and if I were to run this, we can see that we have hist, we have x, this is our actual data, breaks equal, and then this is where we could put in information about our breaks, include lowest equals true, that's the default, right equals true, default, density equals null, color, the default for it is light gray, but we talked previously in our graphs that we could change this with all sorts of different color options, including hexadecimal code or different color names. We have main, this is where we title our histogram. X limit, this is where we can affect the limit of our x-axis, meaning we could, zoom it in, zoom it out, stuff like that. We have our xlab, which is the label for the x-axis. Similarly, a ylab for the label of the y-axis. So there's a lot of different things we can do to customize the look of our histograms. So let's go back to our example histogram. And now what we're going to do is we're going to use the argument probability equals true. So if I run this, what you're going to see is that it looks exactly the same as when we did the frequency equals false. So this is another way that you could tell it that you want this to be a probability histogram or a relative frequency histogram by setting the probability equals true. So now what we're going to do is we're going to add one more part to it, which if we add the rug command, let me actually show you before I do the jitter. If we do rug x, this will put underneath the graph where the actual values are. And you can see where most of these values are. But this can be kind of misleading. And this is why I wanted to add the jitter to it. Because what jitter does is when you're graphing something like this, and I put this line for where the data is, if I have multiple things that are all in the same point, all you're going to see is a single line. So even if there's 1,000 things at that one point, you're going to see one single line. So it might look like 1,000 values at one part that have the same value are 1, and one value over here, and you're going to see them equal. So what we're doing with jitter is we're just telling the program, the computer, to have a little bit of jitter to it, and it'll thicken the lines where there's more data. So let's start again by recreating our histogram without the rug, and now we're going to do it with the jitter. And now you can see these lower values down here are way thicker. There's a lot of values here versus when we did it without this. See, it looked like there were 3 or 4 down here, but actually there are quite a bit. It's just that they were overlapping with each other. Now what we're going to do is we're going to make our histogram again with this X data, but now I'm going to add breaks to it. So I've actually changed what's showed here a little bit because when I do breaks 10, it actually looks exactly like the prior graph did because the data kind of fit that way. So what I did is I upped it to 15. And you can see that if I run this histogram with breaks of 15, it will actually change the look of the graph because now we're doing breaks based on the data with every 15. So we're grouping them together. So now instead of having this amount of data here, this amount of data here, what it's doing is all the data within this one will be combined together. And then from, next group, and it'll basically combine them into bigger groups. Or we can look at our next example where we have our histogram, where we're going to do specific breaks. 0, 1, 2, 3, 4, 5, 10, 20, and the max of our X. So by doing this, you're going to see that we actually have different groups that we specified. So our first group is from 0 to 1. Then we have a break from 1 to 2. Then we have a break from 2 to 3, where there's no data. 3 to 4, where there's some amount of data. 4 to 5, where there's no data. Then we make the jump from 5 to 10. So notice this is a bigger grouping. Then we did 10 to 20, so we have an even bigger grouping. And then we did from 20 up to max, which is like 29, something like that. So this is what I was kind of talking about previously about the fact that when we did those manual cuts, you can do this directly in histogram. And the way you do this is you just use these breaks and you can set the exact cutoffs you want for each group. Generally, we want these to be equal size, but sometimes because of the type of research you're doing, type of analysis, you may know that there are certain groups you want to use. And it might even be something arbitrary. Let's say, for example, that you're doing some research on different generations. You might do the breaks based on however the generations are defined, right? So you have, Gen X is between here and here, Gen Y or millennials are between here and here, Gen Z or Zoomers are between here and here. And again, the numbers are kind of arbitrary. They're just sort of selected roughly about 15, 20-year intervals. But because you want to do this analysis on generational divide, something like that, you would use the grouping size that was already set so that it makes sense for the type of analysis you're doing. Next, we're going to talk about box plots. These are another useful plot to get an idea about the information's distribution. Things like skew, where the middle 50% of the data is, are there any outliers, things like that. So a box plot is used to summarize data succinctly, quickly displaying if the data is symmetric or has suspected outliers. What it does is it uses a 5-number summary, and then you have your middle box here, which is your Q1 to Q3. In the middle, that is your median or your Q2. So right there, if you have an equal size box with the medians in the middle, this shows you have fairly good distribution in the middle 50%. If that Q2, the median, is shifted towards one side or the other, it shows you that middle 50% is skewed. And looking to the right here, looking at this graph, you can see that 25% of the data is right here, and 25% of the data is here, showing that there's definitely some skew in that middle 50%. Then we have our minimum and our maximum. Now, if you were to just put a box plot into R, what it's going to do is it's actually going to use the interquartile range, which is the distance from Q1 to Q3. It's going to figure out what that range is. It's going to multiply it by 1.5. You're going to subtract it from Q1 to get your lower boundary. You're going to add that value to Q3 to get your upper boundary, and that would give you where your whiskers are, right? Because it's a box and whisker plot. Anything that falls outside of those whiskers would be considered an outlier. Now, when we teach this a lot of times in Intro to Stats, we just teach the students to go to the minimum, maximum instead of doing we calculate interquartile range and figure out what the outlier boundary is, but we still draw it to minimum, maximum. You can do this in R. You just have to change one of the settings. By default, it will use that interquartile range to give you your whiskers. So in this example, we're actually going to use a file that we're going to pull up the CSV for movie data. And I have it written right now as read.csv file equals, and then within the quotes, this is where you put the file. I have it set to file path CSV, and then header equals true. So header equals true means that at the top of your data, there is a header, which means you have labels for what each column is. If you only have data in the CSV, but no label for the columns, then you would put header equals false. Now, the reason I put file path.csv is because I wanted to actually kind of show how you can find these file paths. So let's jump to where my actual data is stored, and I have my data right here. So if we look for movies.csv, now of course, if you're using a Mac or Linux, you'll do this a little bit different, but for Windows, I'm gonna right click this, and I am gonna go into properties. And then if I go right here, I can see exactly where my data is located. So I'm gonna copy this, and I'm gonna go back to R, and in my file path, I'm gonna paste this in, and then I'm going to add the file name. But one thing you need to do before you do that, the file system in R is different than Windows. Windows, for the file paths, uses backslashes, but R uses 4/, meaning we actually need to change all of these slashes to 4/ in order for R to work. But that way you don't have to go and try to type out your entire file path. So slash, and then last thing I'm gonna do is slash, and let me just double check if it's capitalized. It's not, okay, so movies.csv, header equals true, and now we've loaded our data. So let's look at what this movies data looks like. So it looks like I have 77 data points. I've got 3 columns where the first one is profitability. Then I have Rotten Tomatoes score. Then I have, 4 columns. Then I have worldwide gross, which is how much money it made. And then I have the year that the movie came out. So if we were to, just like anything else, if I wanted to look at the dimensions of this, so dimensions of movies I'm going to see that it's 77 by 8. Oh, because there's more. Sorry. I forgot. I skipped over some. Profitability, Rotten Tomatoes, worldwide gross. Above that, sorry, there's the first few columns. I forgot to split. You've got the film. For example, you got What Happens in Vegas. You got Water for Elephants, Wall-E, Waitress. You've got the genre. You've got the lead studio. You've got the audience score. Then you've got your other columns that we first looked at, right? And anytime, like I said, if you have a lot of data, you're not 100% sure, just do names, movies, and you can see all of the different column names. We've got film, genre, lead studio, audience score, profitability, Rotten Tomatoes, worldwide gross, and year. So what we're going to do now is we are going to specifically look at the worldwide gross, which is how much money the film made. So we can do this by selecting our data, movies, using the money sign, and then from within that, we can pick any of our different named entities. So, right, for example, if I did movies, do money sign, notice that RStudio is automatically going to populate the possible options. So I've got film, genre, lead studio. I said I wanted worldwide gross, so I can click it, or you can type it in. And you will see here's all the data for how each of these movies grossed worldwide. So what I'm going to do is I'm going to create a box plot based on those worldwide gross of how much money they made, the revenue. I'm going to set it to horizontal equals true because by default the bar plots will be vertical. I'm going to set the range to 0. This is what's going to make the whiskers go all the way out to the max and min. And then I'm going to set my X label as gross sales in millions. And my title of this graph is going to be worldwide movie gross sales. So let's see our graph. And you can see here that we have our box and whisker plot. So looking at this, this means that from 0 to whatever the value this is, that's 25% of the movie's sales. So 25% of the movies made this much in sales. 25%, so 25 to 50th percentile, made this much in sales. The 50th percent to 75% made this much in sales. So notice it's kind of starting to spread. And then the upper 25% had this much in sales. So you can kind of get an idea here that this is very right skewed. Half of the movies made less than like $90 million, but then the other half made over 90 million, with the top 25 percentile making well over that amount. Now, one thing I want to change real quick, I want to get rid of this range. I just want to show you that what this would look like without having this. So we did this. Now you can see what happened is the bottom whisker didn't change, and that's because it will stop at the interquartile range times 1.5 subtracted from Q1 or the minimum value, right? So whichever one it hits, it will stop there. For the top part, it's taking 1.5 times the interquartile range, it's adding it to Q3, and it's stopping either there or at the max, whichever one comes first. Well, that means that it stopped at, so we took our interquartile range, multiplied it by 1.5, added it to this point, and it gets to here. That means anything that is beyond this is an outlier, which means we have 4 outliers from our data, right? So all I did, if I wanted to go all the way to the maxes, I just do range equals 0. If I wanted to have the interquartile range setting the limit of my whiskers, I can just not put that range and it will automatically do the interquartile range for me. I have another example, this one using one of the, within our data sets, just like MT cars, this one is for links. So I'm going to first grab that links data. I'm going to get a summary for it. And looking at my mean and median, right, I have a median of 771.0 and a mean of 1,538.0, meaning I can already tell from this that I'm going to have skewed data. But let me see what the data actually looks like. So I'm going to create a box plot. Again, it's horizontal with a range of 0. And you can see that this will give me a box plot. Again, if I get rid of this range, we will see if we have any outliers. It looks like we do have 4 outliers. Similarly, if I get rid of horizontal equals true, we will get a vertical box plot or box and whisker plot. And then I just want to go one step further. Let's see what our histogram looks like for this data. So we're going to do hist and we'll do links. And let's see what we get. And there you go. So you can see, like I said, that it's right skewed. I could tell that just by looking at the mean and median, but now I can visualize how right skewed it is. And you'll notice that, again, just like before, most of the data falls between 0 to 1,000, and then you have some data between 1,000, 2,000, 3,000, 4,000, and then it gets less and less but you are having some data out there that is pulling that data up. You have those 4 outliers we saw in the box and whisker plot. And sometimes you're going to want to overlay the lines over the graph to get an idea of how the graph is changing, right? So sort of like think about a line chart over a histogram. So we can do this by using the lines function. So first thing we're gonna do, we're gonna start by creating a new X object, which we're gonna concatenate some values, 0.314, 0.289, 0.282, so on and so forth. We're then going to use temp to create a histogram. And then we're going to use the lines function, where we're going to start with the minimum of our whatever this histogram's breaks are. We are then going to use the midpoints, and we are going to use max. So what this is telling the lines is I want you to put the line at the minimum of my data. Then I want you to put a point at each of the midpoints. So one here, one here, one here, one here, and then put a point at the maximum, which is here, and then connect them with a line. And so we're going to do, and real quick, also this type L, this is for a line. So if we were to do this, let's see what we get. So here's our histogram, and now we're going to overlay lines on top of it. So as I mentioned, the L represents that we want a line. There are other things we could put here. For example, I could put P for a point. So if I were to do this instead, what's going to happen is instead of putting a line, it would put a point, but it's overlaying it on top. So let's go back, create a fresh histogram, and now if we run this, notice what it did is it put a point at the minimum, the midpoint of each break, and the maximum. And I pulled up this website here called rcharts.com, and you can see some of the different options you can do here. So P if you want points, L if you want line, B if you want lines and points, C if you want lines without part of the points, O if you want lines and points overplotted, H if you want histogram-like, S if you want stairs, capital S if you want stairs, but the first line is vertical versus horizontal, and N if you want no plotting. And you can kind of see to the right the different examples of what these would look like. So again, there's lots of options for how you could overlay this. A lot of times you may want to do something like this where you have a histogram, but you want to overlay something like this. Or if you did like a cumulative frequency histogram, maybe you want to put the line of the ogive chart or something like that on top of your histogram, your cumulative frequency histogram. We can also do density plots. So the point of doing the frequency polygon is to tie the histogram in with the probability density of the parent population. So more sophisticated density functions are available and are much less work to use if you just use, for example, some built-in functions. The built-in data set faithful tracks the time between eruptions of Old Faithful and how long the eruptions occur. So what we're going to do is we're going to use the R command for density that can be used to give more sophisticated attempts to view the data with a curve as the frequency polygon does. So density versus lines will do something similar. We'll overlay this curve, but it will be based on the actual density curve. So the density function has the means to automatically select the bandwidth. You can see help for this. And we call lines function to include this into our histogram. So let's actually look at an example of what this looks like. So first things first, we're going to grab our Old Faithful data. So we're going to use data of faithful, and we're going to attach that to make our data visible. You can actually directly call on faithful, but I'm just going to attach it anyway. So if we make a histogram based on our eruptions, by the way, if you didn't attach it, you would have to actually call on empty cars. So if you didn't attach it, this would have to be hist and then empty cars, money sign eruptions, data equals empty cars. So the reason we attach is we just don't have to do that anymore. So we create our histogram. This is the histogram of our eruptions for Old Faithful at Yellowstone National Park. If we were to use the command lines and then density for eruptions, you'll see that we get this sort of smoothed out function giving us a density plot overlay. Now, if we wanted to, we could change the bandwidth. So we could do lines, density, eruptions, but now we're going to change our bandwidth to SJ, and we're going to set the color to red so we can see what this looks like. So this one you can see has higher peaks, seems to follow the data a little bit more smoothly. It does follow the data a little bit better. Because what this is doing is it's using the data to create a density function and then try to estimate where the data should be based on this. But there's different methods you can use to do this. And then as before, what I did is I just created another one where I changed it to blue and I changed it to point. So you can kind of see what it would look like if you did something like that. Because you can do more of these at one time.
So just like before, I actually pulled up a website so we could see some of the information about this. So with this SJ bandwidth, this is actually the Sheether and Jones bandwidth of a Gaussian kernel density estimator. As always, I would highly recommend you all go and search out what other bandwidths are available and maybe look at why choose one over another, right? Why was the default the normal Gaussian sort of bandwidth versus something like this, where you saw this one did seem to fit our data a bit better? There's times where you might want one versus the other. So these are things that, like I said, you should always play around. See what other bandwidths they are, see what they look like, see how they fit different types of data, determine when one is better, pros and cons, all that kind of stuff. So this concludes our graphing with base R part of the course. Going on from here, we're going to be looking at ggplot2, which will allow us to create a lot more professional and clean graphs, allowing us to build on what's called the language of graphics, where we can actually build up piece by piece into these really good looking graphs. Hello everyone, it's finally time to jump into ggplot2 so we can make really good professional looking graphs by building them piece by piece. So first, let me introduce what ggplot2 is. ggplot2 is a data visualization package for R programming language. It was developed by Hadley Wickham, and it's based on the principles of the Grammar of Graphics by Leland Wilkinson. This grammar concept allows for systematic construction of visualizations by combining different components. So the philosophy is, the core philosophy behind ggplot2 is that data visualizations can be decomposed into systematic components. You've got the data. This is your raw data that you want to visualize. You've got the aesthetics. These are mappings from the data to visual properties like position, color, and size. You've got geoms, which are geometric objects that represent data, such as points, lines, and bars. You've got stats, which are statistical transformations that are applied to your data, things like binning and smoothing. You've got coordinates. These are coordinate systems like Cartesian or polar. You've got facets, which are ways to split the data into subsets and display each subset in its own panel. And then you've got theme, which is the overall appearance, controlling things like fonts, colors, and grid lines. So ggplot2 uses a layered approach. This will allow visualizations in ggplot2 to be built layer by layer. You start with a base layer, specifying the data and the aesthetic mappings that you want. Then you can add the other layers like geoms, stats, and other components. And this will allow you to have a lot of flexibility and customization within your actual graphs. In fact, you can actually create very basic graphs just like we did previously with base R using ggplot2 and then build from there. It's actually one of the nice things about it. You make your basic graph and then you add a little bit more to it. Then you add a little bit more to it to get that real feel that you want from your graph. Aesthetics are a central concept for ggplot2. They define how variables in the data are mapped to visual properties. So the common aesthetics will include X and Y, color, fill, shape, and line type. Geoms are the visual representations of those data points. So different types of geoms can represent different types of data visualizations. For example, geom point will create a scatter plot, geom line will create line plots, geom bar will create bar charts. Then we have our data transformations. So ggplot2 allows for on-the-fly data transformations. So instead of having to do all the transformations beforehand, you can do it within the graphs themselves. This will make it easier to visualize summaries or transformations of the raw data without having to create a new data set, for example, some new object, or to have to change your original data set. Remember, transformation is a big part of what we do when we're preparing data for doing statistical analysis. Scales will control how data values are translated to visual values. For instance, a scale might determine how values in a numeric variable are mapped to things like colors or even sometimes shapes, things like if you want triangles versus squares versus circles. These are all things you can affect in scales. Finally, one of the parts that I really like are the themes. So themes in ggplot2 control the non-data ink in the plot. This is everything from the grid in the background, the color of the background, the font, everything about the graph. And you can actually create your own themes. And then anytime you make a graph, you can call on that theme and automatically make all your graphs follow the same theme. So this includes things like background color, grid lines, axis labels, legend appearance, and more. ggplot2 does provide several built-in themes. So a lot of times if I'm just doing basic graphs, I will just focus on using the minimal theme. But you can, like I said, you can create your own, which is where it's really cool. And I'll actually show all of this in this lesson. There are other advantages to ggplot as well. For example, the core of ggplot2 is that you can extend it, right? It's extensible, meaning that I can actually take whatever base functionality ggplot2 has, and I can add other extensions to expand what it can do even on top of that. So the many packages have been developed to extend its capabilities. These can add new geoms, new themes, new scales, and a lot more. It also is integrated with tidyverse. So it's part of the tidyverse collection of R packages that are designed for data science. We talked a little bit about this previously, but most actual people who use R regularly, especially for production level code, will be using tidyverse. And ggplot2 is a built-in part of those packages. So all tidyverse packages use a common data structure and philosophy, making it easy to use them together seamlessly. And then the last part is that it's extremely popular. Because it's one of R's most popular packages for data visualization, this means that it has a large and active community, which means that there's a ton of tutorials, there's a lot of online resources, there's a lot of extensions. It has just a lot of variety of things that you can find about it because it's used so extensively by R users. So the first step we're going to take is we're going to install and load ggplot2 onto our RStudio, or specifically onto R, but using RStudio. Now this is a fresh install of R, so I don't currently have ggplot2 installed. So we can use the install.packages, and then you put whatever package it is in quotes. Now this is case sensitive. So ggplot2 is lowercase. Some packages will have different parts that are capitalized. If you wanted to use the graphical interface for this, you could go to packages, and you will see that I do not have ggplot2 installed. So if I wanted to, I could go to install here and just do a quick search, ggplot, and you will see that ggplot2 is right here, and I could hit install, and it has this checkbox for install dependencies. So as I mentioned previously, I actually prefer to use the command line. That way, if I send this to somebody, they would see that I have ggplot2 and all this kind of stuff. So I'm actually going to add something to this to be just like the graphical part, which is I'm going to use dep equals true. This means when it is installing ggplot2, it is actually going to install any dependencies that ggplot2 also calls upon within it. So that way I don't have to worry about trying to do something and be like, oh, well, you don't have this other part installed from something else. So if we run this, it's going to take a little bit because this is a fairly extensive package. You'll see all these files loading, all this kind of stuff. Now, while this loads, generally what I'm going to do is I will go back up in my code to where install.packages is, and I will add a comment. So now if I were to run all my code, it would not run this install again. But the command for installing it is there. So if I give this code to somebody and they don't have it installed, they can literally just get rid of that comment, or they can just highlight the part and run it. So you can see that ggplot2 loaded up quite a bit of stuff, not just ggplot, but also things that it relies on. Going over to the right now in my packages, you can see that I now have I now have ggplot2 installed. I could check on this checkbox right here, and this would cause it to load up library. You see here that it loaded it up, and if I uncheck it, it will detach this package. Or I'm going to use the command for it. So library, and then in parentheses, you put the package name you want, in this case, ggplot2. Now you don't need quotes here for this one. So I'm going to load it up, and now we have ggplot loaded up. This means that anytime I call in a function that is in ggplot2, it will automatically go to ggplot2 to grab that. As always, we're going to start with basic plots, and we're going to build from there. So the main function to create plots in ggplot2 is to use the ggplot function. So ggplot and then parentheses, and this is where you can put your basic data information. So the basic idea is to map variables in your data to aesthetic properties of the plot, such as the axis, scales, and colors. So our first thing we're going to do, we're going to create a scatter plot. We're going to use the mtcars data, and we're going to call on that. So if we look at what I have here, I have data mtcars, so I'm going to load that up, and then I'm going to use ggplot mtcars. So I'm going to call on this data from mtcars, and then within these parentheses, I'm going to use AES for the aesthetics. I'm going to set X to miles per gallon in mtcars, and I'm going to set Y to horsepower. So just to remind everybody, actually, let's do it this way. If I were to remind everybody, if we do names, mtcars,
you will see that we have miles per gallon, cylinders, displacement, horsepower, so on and so forth. So what we're doing now is we're using the aesthetics to assign miles per gallon to the X values and horsepower to the Y values. And then we're going to use geom point, and this is what will tell it to make a scatter plot. Now, one thing I want to point out before we actually make this, though, is in a lot of the examples, you're going to see I have multi-line graphs. And the nice thing about RStudio is, if I were to hit enter after this plus, watch what's going to happen. It's going to automatically indent the code because it knows that when I add this plus, I'm saying do ggplot for this plus this part of it. So by going to the next line, it auto indents it for me. So when I run this, what's going to happen is it's going to run this line plus the next line. So run that, and you'll see that we get this scatter plot here, right? So we have miles per gallon in the x-axis, we have horsepower in the y-axis. It automatically labeled it for us because we set what these variables were with our aesthetic. Now we could change the names just like a regular plot, anything like that, but it will automatically do some of this functionality for me. You can probably already see that this looks a lot better than our original graphs did in base R, and we haven't even done any of its actual good functionality. This is just a basic scatter plot. But this geom here is how we can actually determine what kind of graph it is. So in this graph, AES defines the aesthetic mappings. So mappings like MPG to x-axis and HP to y-axis, and then geom point is what adds the layer for our scatter plot. For example, if I were to go back and just do ggplot but not have the aesthetic part, what would happen? Nothing, right? It's just going to give me a blank graph where miles per gallon are mapped to my X, horsepower are mapped to my Y, but I haven't told it what kind of graph to do. So then from there, this is where I told you build on. You say, okay, well, X is mapped to this, Y is mapped to this. Here's your basic plot. Now, what am I doing with it? Okay, well, I'm going to create a scatter plot by using geom point, and you overlay this on this, right? Because remember, the whole point of ggplot2 is that, or ggplot, is that it creates these layer by layer graphs. And then we can customize our plot further. So in this example, what we're going to do is we're going to add coloring based on cylinders variable. So the cylinders, type of car, 4-cylinder, 6-cylinder, and 8-cylinder, we are going to color code this. Then we are going to add text labels for each point using geom text. We are going to have custom axis labels and title with labs. And then finally, we're going to switch it to a minimum theme. So going back to our graph, you can see it all here together. And I set it one line per part so we can easily distinguish what it is. So we have ggplot. Again, we're using MT cars data. We're using our aesthetic where we have X is miles per gallon, Y is horsepower, and in color. Now I did change this up a little bit because if you look at my original code, I had color as cylinders, but I changed it to as.factor. And this is because cylinders, even though it's meant to be this sort of factored data, 6-cylinder, 4-cylinder, 6-cylinder, and 8-cylinder cars, it would see it as a spectrum or a continuum. So what I did is as.factor to make it actually be a distinct factor. 4-cylinder cars are one. It makes it this discrete data set, so it'll be color. Instead of being a spectrum of color, it'll just be jumps in color. Then we have label equals row name MT cars. So what this is going to do is it's going to add the car names to each of our data points. We're going to, again, create a scatter plot using geom point. And then for geom text, we're going to add an aesthetic to this where we're going to have label equals row names of MT cars. And then we're going to have a vertical adjustment of 2 and a horizontal adjustment of 0.5. Next, we're going to add labels. So for labs, we have the title is MPG versus HP, so miles per gallon versus horsepower. For our x-axis, we're going to have miles per gallon, and for y, we're going to have horsepower. And then last thing, we're going to use a minimum theme, which will then get rid of like the gray background and stuff like that. So let's put all this together, run it, and look what it looks like. And now you can see the changes that we've made. First and foremost, let's talk about the labels because that's the easy part. So, and the theme. So the theme is, notice it got rid of the gray background. It made it a lot simpler. It's just a grid, no problem. We have miles per gallon and horsepower for our axes, and we also have miles per gallon versus horsepower for our label. It's added a legend to the graph for 4-cylinder, 6-cylinder, and 8-cylinder cars. That is what these colors represent. So for example, the blue represent 8-cylinder cars, the greens represent 6-cylinder cars, and the kind of peachy color is for 4-cylinder cars. We also added the labels so that each one of the cars would be listed by their dot. Now, of course, it's kind of crowded because these are long names and we're putting them in the graph, all that kind of stuff. The vertical and horizontal adjustment, this is what will shift those labels. So for example, if I put this to like 0, 0, let's see what's going to happen to our graph. So notice what it did is it shifted all the things closer to the actual dots. It no longer has that horizontal and vertical adjustment off of the dot, making it look even more crowded versus our prior graph where we added just a little bit more spacing between the names. See, we shifted the names by telling it to take this and offset it. So let's specifically look at that Lotus Europa. You can see that it starts where the first letter starts touching the dot, and then by offsetting it, now it shifts it over and down. Of course, it did to all of them, so anything where it's like overlapping the text, it's still overlapping the text on those as well. And there are ways, by the way, you can make it so that it will try to shift and not have things overlap. Now, I just want to show you this graph on my slides really quick, because this is what it would look like if we didn't have it as dot factor. So remember when I told you that we did cylinders as dot factor and it did those three distinct colors, the blue, the green, and the reddish color? Well, this is what it would look like if we didn't include the as dot factor. It has a spectrum of from 4 to 8 cylinders, but there are no 5-cylinder cars. There are no 7-cylinder cars, but it's still treating it as a continuum of values from 4 to 8. We just only happen to have 4, 6, and 8. So it's just a way to clean it up a little bit so that the legend makes more sense. So instead of having this spectrum here, we instead have these distinct 4, 6, 8 colorations. Next, we're going to talk about all the different types of plots you can make. So ggplot2 offers a variety of geoms, or geometric objects, to create different types of plots. For example, we could do a box plot, just like we did previously, and you would do this with geom_boxplot. So looking at our example here, again, we have MT cars data. For our aesthetics, we have X, and we're going to do this as dot factor of cylinders. Again, just like it's going to be 4-cylinder, 6-cylinder, 8-cylinder. We're going to have Y be miles per gallon. And then we're going to create a box plot of this data with the labels for the title being MPG distribution by cylinder. For X, we've got number of cylinders. For Y, we've got miles per gallon. And then last thing, we're going to use a new theme, which is the light theme. So let's run this. Notice that the theme changed a little bit. It added these outer grid line. So no longer it's just the grid lines within, but it also added this sort of outer boxing of it. It also changed the line widths and stuff like that just a smidge. So now what it's done, when we did this box plot and we set X as dot factor, it is treating it as 3 different factors. We've got the 4-cylinder cars, we've got the 6-cylinder cars, we've got the 8-cylinder cars. And then it's created a box plot for each of those within our graph. But sometimes you're not going to want everything crammed all into one graph. This is where you might want to use what's called faceting. So faceting is a way to create multiple plots based on a factor or factors of your data set. So in this example, we're going to do something similar, except for now we're going to use histograms, and we're going to split it into 3 histograms based on the cylinders of the car. So looking at our plot, again, we have ggplot, we're using MT cars data. Our aesthetic is that our X is going to be miles per gallon for this one. So we're doing a histogram of miles per gallon. We're going to geom histogram to create histograms with bin width of 2, right? So remember, our bin width is just going to tell how we're going to break up our groups for that histogram. Then we're going to do facet wrap, and we're going to use cylinders. This means that it is going to create individual graphs based on our cylinders. We have a 4-cylinder graph, a 6-cylinder graph, and an 8-cylinder graph. Again, we have our labels, and then this one we're going to do theme BW. Okay, so let's do it. And look what happened here. So in this case, it's split it up. So we've got our 4-cylinder cars are the graph on the left, our 6-cylinder cars, the graph in the middle, and our 8-cylinder cars are the graph on the right. So we faceted it to create multiple graphs instead of putting them all together or all next to each other. You actually create this facet, this sort of windowed mode for each one of these. And we're doing it by the factor of cylinders in the cars. So as a quick recap, whenever we're looking at grammar of graphics, when we're doing our ggplots, you always want to be thinking about your data. These are the data sets you're working with. The aesthetics, these are the mappings of the variables in the data to your visual properties. You've got your geoms, these are geometric objects that represent the data, things like points, lines, bars. You've got your stats, which are statistical transformations, things like binning and smoothing. You've got coordinates. These would be, again, if you want to change from coordinate systems, so from Cartesian to polar or something like that. You've got your facets, which we just looked at, which is faceting to create multiple plots. And you've got your theme, which is your overall appearance, things like background color, grid lines, things like that. This is the nice thing about ggplot2 is that because you can do this layered approach, you can start by building the base graph and then you can customize it to look the way that you want, giving you that more professional and clean and polished look. Aesthetics are our central concept of our ggplot. They have to be a part of every single one. They define how the data is represented on our plot, and the most common aesthetics are going to be, of course, your X and Y position, which is what we've been looking at. You've got color and fill. So this would be how are we going to color those geoms? Are we going to color them by some other thing? Like, for example, we did as.factor. Are we going to have some sort of continuum where maybe, gradient from this to this as it changes, things like that. You got size, which could be the size of your geoms. So if you wanted them to be bigger for your graph or smaller, you can change that in size. Shape would be the shape of those points. Again, you can do dots, you can do squares, you can do triangles, things like that, circles. And then also line type. If you have lines in your graph, what kind of line type? Is it a dotted line? Is it dotted and dashed line? Is it a dashed line? Is it a solid line? These are all things that are part of our aesthetics. Now, one key note I kind of want to point out while we're talking about aesthetics is the global versus local mapping trap. So the aesthetic function, the AES, has one strict mathematical responsibility, and that is to map structural variables, so that's our data frame columns, to visual dimensions. That'd be our axes, our color channels, and our shape indices. If you pass a literal static constant, things like blue or hex code inside AES, the grammar engine is going to interpret this as a string as a brand new categorical data vector containing the word blue, and it's going to repeat this for every single row. So R will create a generic discrete legend called and labeled blue, but it'll paint the actual points using its default first color. In this case, it would be like a salmon pink color. So to hard code a static visual style property across the entire layer uniformly, what you want to do is you want to pass the regular argument directly into the geom underscore whatever it is that you're doing. Okay, so this would be outside of the AES. So I just want to show you a quick example of what I'm talking about. So it does, obviously, like I mentioned, that AES does have certain properties like shape, color, things like that. But oftentimes you're not going to want to put your color and stuff like that directly in AES. Here's an example. We have ggplot2. Our data is, again, MT cars. We're going to map using AES. X is the weight of the car. Y is the miles per gallon. And we have color blue. And we're going to do a scatter plot, so geom point. If I were to run this, what's going to happen is notice it didn't do the color blue. What it did is it did it in its default color, and it gave us the legend that it's blue. So the color of this is blue. If I were to then change this, put this into my geom point instead, take it out of the AS, put it in geom point, now it will actually change the color to blue, not creating another variable within my data called blue where that's what it's saying, okay, these dots represent whatever blue is, something like that. So it's just something to be careful about when you're learning how to do this. As you're learning, I will admit there's sometimes some learning curve to it, and it's useful sometimes to look up, things on Stack Overflow, play around with it. Like I said, this is why it's kind of sometimes nice to build your base model first. Don't worry about the colors, don't worry about the shape, just first get that scatter plot. Once you have the scatter plot, figure out what changes you want to make. Change them one by one. Okay, now that I've got my scatter plot, I want to make it blue. Great. Now that it's blue, maybe I want to have a minimal theme. So add the theme. Once I've got my minimal theme, okay, I want to change my labels. Add your labels. Now that I've got my labels, my minimum theme, and my color, I actually wanted this to be a faceted graph. Add the build it piece by piece. That's why it's sort of a layered approach, which is one of the strengths of it, because when you're building out these layers, you can focus on what's most important first and then figure out how to add the next layers from that. There are many different built-in geoms that we can use when using ggplot2. So this is actually what makes the graph that you see. This is the type of graph it is. So geom point, which we already looked at, would be a scatter plot. Geom line will give us a line plot. Geom bar would give us a bar plot or bar chart. Geom histogram would, of course, give us a histogram. Geom box plot would give us box plots. And geom smooth would give us smooth lines. Instead of having like jagged lines with edges, it smooths it out for you. In this example, we're going to again grab our MT cars data. We're going to, for the aesthetics, set X equal to miles per gallon. Y is going to be our horsepower. And we're going to create a geom line. So we're going to create a line graph where our aesthetic for this one is our group is going to be equal to 1. And our color is going to be equal to blue. Then we're going to add geom point, and we're going to do color equals red and size equals 3. So basically what this is going to do is we're going to have a scatter plot of our data, basically. We are going to connect it with lines that are blue, and then we're going to put a point at each point, which is red with a size of 3. So let's run that and see what we get. So you'll see here that we have exactly that, right? We have this, every one of the points, it's connecting them with a blue line and a red dot. If we change the line, let's say we thought these dots were a little big, maybe I want to change it to 2, and I'm going to rerun this, and you'll see it's the same thing, but now I've changed the dot. We can also do statistical transformation. So many geoms have an associated statistical transformation. For instance, for geom histogram, this can use stat bin. This would determine how big the bins are. For example, in our prior example, we did a bin of size of 2. You could do set bin equal to 5 or 10 or 7, whatever size you want. For geom smooth, we can use the stat smooth. This would be how are we smoothing this graph. So let's do an example of exactly that. So looking at this next ggplot, we have ggplot. Again, we're using mtcars data. Our aesthetic is x is miles per gallon, y is horsepower. We're going to use geom smooth, and our method we're going to use is linear model. So basically what we're going to do is we're going to take the data of miles per gallon versus horsepower, and with all the data, you think of it like a scatter plot, we're going to do a best fit line. So that's what our smoothing function is. We're going to treat it as a best fit line. And you'll see that we get this best fit line representing that data. Normally what I would like to do in this case is I actually like to overlay the scatter plot with the best fit line. So this line, you have some reference of like, what is it graphing? It gives you a better idea of how well does it fit the data, right? Because the problem with something like a linear model is this might be the best fit line, but without extra information like seeing the data or correlation coefficient, we have no idea how well it's actually fitting the data. We just know that it appears that there is a negative linear relationship between them, right? As x increases, y decreases, but I usually like to have a little bit more to substantiate this linear model. But this is, a smoothing method. We have taken the dot, think of the dots, we have smoothed it into a linear model. You could do something else though, quadratic, something like that. Transformations can also be applied directly within scales. So for example, if we had scale x log 10, this will apply a log 10 transformation to our x-axis. If we did scale y square root or SQRT, this would apply a square root transformation to our y-axis. So let's do that. So what we're going to do is we've got our ggplot, mtcars, aesthetic, x is horsepower, y is miles per gallon. We're going to do geom point, which is a scatter plot, and we are going to scale it to a log 10. So we're going to scale our x values to log 10. Let's say that we got rid of this. What's going to happen is that we're going to get the same graph, but our x-axis is no longer scaled. So when we did our logarithmic scale, it's going to compress down our x-axis values. What about if we did the scale y by square root? If we look what's going to happen, now what's going to happen is it's going to take whatever our y values were, and it's going to take the square root of those, and it's going to compress them down as well. And this is another point I kind of wanted to point out where some people run into issues. So I want to talk about geom bar versus geom call. So under the hood, every geometric object in ggplot2 will rely on a default statistical transformation layer, that is our stat, to pre-process the coordinates before rendering them. When you use geom bar, its default stat is equal to count. So it expects an unaggregated raw vector of individual observations, things like categorical or discrete numeric string. Behind the scenes, the statistical engine computes the summary table, that is your frequency, so count y equals count, and it will require only the x aesthetic. If you were using geom call, its default stat is identity, meaning that it expects data that's already been summarized or pre-aggregated. That is to say, a data frame containing explicit group names and explicit frequency counts. So this leaves data exactly as it is without transformation, meaning it requires both x and y. This is something to kind of keep in mind whenever you're doing a geom bar versus geom call. And I have an example to kind of show you what I'm talking about. Let's say that we have this raw data, which going back to one of our prior example where 5 people were asked, do they smoke, yes or no? So we have this data frame where they have smoke equals yes, no, no, yes, yes. So if we look at our raw data, you can see right here, right? We have 5 entries, smoke, yes, no, no, yes, yes. If we were to do ggplot, raw data, where our aesthetic is x is smoke, and we have geom bar, you'll see that this gives us our bar plot. If we wanted to use geom call, right? So in this case, we're going to create a new object called table summary table. This is going to be a data frame based on the same thing. So there's two groups, smoke, no, or yes, and the counts are 2, 3. So now if we look at this table, you will see that we have this data frame, which represents our outcomes. Do they smoke? Yes or no? And the count of it. No, there's 2 of them. Yes, there's 3 of them. So with the next ggplot, we have ggplot2. ggplot, we're going to use our summary table. Oops. We're going to use our summary table. Our aesthetic, X is the smoke, yes or no. Y is the count, how many said yes or no. And then we're going to do geom call. And if you look, it looks basically exactly the same. The difference is not what the output looks like. The difference is what your input looks like. If you have the data in its raw form, you would want to use geom bar. If you already have aggregated it into a table form in a data frame, you would want to use geom call. So this is just something I kind of want to point out, because this is some of the early learning stuff whenever you're learning how to do these graphs, where you're trying to get stuck on, right? You'll have one type of graph, you're trying to make a column and it's not working. You're trying to make a bar chart and it's not working for some reason. And it might be because you have it in a data frame, you have the X and the Y, and it's trying to bin it differently than you have and do a transformation that you don't want it to do, stuff like that. ggplot2 will use a Cartesian coordinate system by default, but you can change this. You could do chord flip. This is going to flip your X and Y axis. You could do chord polar if you want to use polar coordinates, or you could use coord fix if you want to have equal scaling of X and Y. So again, we're going to do another example, but first things first, let's just do the original graph. So this is what our ggplot would look like with empty cars. X is assigned to horsepower, Y is assigned to miles per gallon, and we did a scatter plot. If we were to add the coord flip, what's going to happen is it's going to flip my horsepower to my y-axis and my miles per gallon to my x-axis. In this case, we used our coordinate to flip your x and y-axis coordinates. I already did an example with faceting, but faceting is a powerful tool to split data visualization into multiple panels based on a factor. So you could do factor wrap. This will wrap a 1D panel. You could do facet grid, which will create a 2D layout of grids. So basically what this means is this. Let's say that we did the first one, you have 3 facets. You could do 1, 2, 3, it lines them all up, just like we did with our box plots. Or you could do a grid view, which is you might have 2 by 2. So you're gonna have 2 graphs, and underneath you're gonna have 2 graphs. And you could do any number you want. You could have like a 3 by 3, 4 by 4, 5 by 5, whatever it is that you want to do. So let's actually look at a 2D faceting example. So again, we're grabbing our empty cars data, X is miles per gallon, Y is horsepower. We're going to do a scatter plot geom point, and we're going to facet grid gear by cylinder. So this means what it's going to do is it's going to have 4 cylinder by how many gears? It's going to have 4 cylinder by some other number of gears, 4 cylinder by some other number of gears. Then it's going to have 6 cylinder by gears, and it's going to do each of the cylinders by each of the different gears. So if we do this, notice that we get a 3 by 3 facet of grids, which is to say we have our cylinders. These are our 4-cylinder graphs. These are our 6-cylinder graphs. These are our 8-cylinder graphs. And then we've got the horsepower within each of these based on our gears. So these are, these top ones are cars with 3 gears. This middle one is cars with 4 gears. And the bottom ones are cars with 5 gears. So we created a facet of all the different combinations of gears and cylinders of the cars, then graphed a scatter plot of the miles per gallon. Themes allow us to control the display of non-data components of our plot. Some of the common themes you'll see are theme gray, which is your default theme. You got theme BW, which is black and white theme. You got theme minimal, which is my favorite, which is a minimalistic theme. You've got theme classic, which is a classic theme without our grid lines. I also like this one because a lot of times I don't like the grid lines. But you can also customize individual themes or any elements you want within a theme. So let's look at exactly that. We're going to create our own little theme here. So again, empty cars, X is miles per gallon, Y is horsepower. We're doing geom point, so this is a scatter plot. We are going to do a minimal theme, but then what we're going to do is we are going to alter this theme by using theme. We're going to get axis title for X. We're going to element text. We're going to change it to blue, and we're going to change the size to 14. Then we're going to do axis.title Y. We're going to set this color to red, and we're going to also make this size 14. So first things first, let's do our graph without these added theme components. We're just going to do a minimal theme to begin with. So this is our scatter plot with a minimal theme. Now, if we were to run this with this extra theme, watch what's going to happen with our X and Y labels. They're going to go to size 14. The X-axis will be blue and the Y-axis will be red. So see, we've added these themed elements to it, and you could actually create your own theme where every time you call on it, call it like theme Houston, and every time I call on it's going to call on all the same aesthetics or for the theme that I want. Not aesthetics in the sense of ggplot, aesthetics in the sense of how it looks, to a human. Scales control the mapping of the data to the aesthetic. They take things like selecting a reasonable set of tick marks, creating a legend. Some common scales that you might see are scale X continuous and scale Y continuous if you have continuous data. You have scale X discrete and scale Y discrete if you have discrete data. You could do scale color gradient if you want to have a color, or you want to have a gradient color scale. Or you can do scale fill manual for manually specifying fill colors. Let's do an example here where what we're going to do, again, empty cars, aesthetic is X is miles per gallon, Y is horsepower. This one, we're going to do color by cylinders of the car. We're going to do geom point for a scatter plot, and then we're going to scale color gradient for low cylinder values are blue, high cylinder values are red. And then what it's going to do is it's going to create a gradient as we go from low or 4 cylinders up to higher cylinder cars of reds. You can see this gradient scale as the cylinders gets higher, right? As we go from the blues, kind of becomes this purpley color, and then it turns to red as we get to higher cylinder cars. You can add custom labels, titles, and annotations to enhance the readability of your plot. We already looked at this a little bit, but labs will allow us to modify the axis labels, plot title, and the legend titles. We can also use annotate to add static annotations. So let's actually look at an example of adding those annotations. So same sort of ggplot, X, empty cars, X is miles per gallon, Y is horsepower. We're going to do geom points. This is a scatter plot. We got our labels, miles per gallon versus horsepower. X is miles per gallon, Y is horsepower. That's not anything new. But now what we're going to do is we're going to annotate the text. We're going to make at X 15 and Y 300, and we're going to add a label high horsepower, and we're going to put that in red. So what this is doing is this is the labeling position. We're telling it X 15, Y 300, and we're going to have this label high horsepower in red. So let's see what happens. And then you can kind of see this sort of adds like this annotation where anything above this would be considered a high horsepower car, something like that. ggplot has tons of extensions that can expand what it's capable of doing. So some of the most common ones you might want to use would be things like ggAnimate, which will allow you to create animated plots, ggRidges, which can help create ridge plots, which I'm a big fan of, ggRepel, which prevent text labels from overlapping. Remember I mentioned this earlier when we did that graph with all the text and it overlapped? You can use ggRepel to actually work with that. Now, it's not always going to be perfect based on how much labeling there is and stuff like that, but it makes a huge difference. ggMap can be used for integrating maps. So first thing we need to do is we need to install these packages just like we did for ggplot too. So I'm going to first install my ggRepel package. Okay, so it's going to load up, and then I'm going to load it into R using library ggRepel. So in this case, we're going to do our ggplot, empty cars data, X is miles per gallon, Y is horsepower. We're going to do our labels based on the row names, which are the different car names. We're going to do geom points, so it's a scatter plot, and now we're going to add this geom text repel. And when we actually run our graph, you're going to see that it creates this graph now where in the different labels, it's going to try to repel them from each other so they're not overlapping. And some of them, where it does get a little crowded, you're going to see that it adds a line to show you. Like this one here, the Merc 450 SL, it's going to be associated with that point. The Merc 450 SLC is going to be associated with this point. And because this one here, right, the Merc 450 SE is this one, you can see that it's kind of overlapping with these. So to kind of spread it out, it's putting a line so you know where they go. Once you've created a plot, you actually might want to save it. Now, we talked previously that whenever you have a plot, you could come up to here, export, save as image, save as PDF, or save to clipboard. Generally, I would suggest not doing the clipboard because it does seem to kind of copy weird. But let's say you do save as image. You can pick what kind of format you want. You want a PNG, JPEG, TIFF, bitmap, meta file, SVG, or EPS. For example, if I'm doing academic graphs, I usually will use a TIFF, so I can actually set it to be a 300 DPI image and all that kind of stuff. You can actually change the width and the height. If you are changing it, if you click a minimum aspect ratio or maintain aspect ratio, as you change one, it'll change the other. So if I wanted to change my x-axis, it would actually change the y ratio with it. And then you can update the preview from here, stuff like that. Once you've saved your plot, you just hit save and it'll save it. It'll bring up your save window, stuff like that. Or what you could do is you could actually use the inline, which is what I actually usually do, using the ggsave function. So this will save the last plot to the file. That's the one you most recently graphed. This is actually really nice because when I'm creating graphs, I specifically upscale them to 300 DPI. Then I save it inline. So it's the graph that I specifically just made with the settings that I want. So it'd be something like this, gg save, and then within that, you're gonna put what the save file is. So you put something like myplot.png, and then you can also change the width and the height here. Before we move on, this is something I briefly wanted to show you. If you are working in R and you wanna know where it's gonna save, you could put the entire file path, just like when we did that read CSV, you could read the entire file path up to your file. You can also save the same way. You could do, say, your file could be c:/whatever, or you could save it to whatever file you're currently working in. So if you want to know what working directory you're in, you can use the getwd function within R, and this will give you your working directory. So right now you can see that it's my users, documents. I can set my working directory by doing setwd and then parentheses, and within that you put whatever your working directory is that you want to save to. So for example, I usually would do something like, I think I have like R stuff or something like that in here. So I would do something like c:/R stuff, I think it is. Okay, well that one's not a working directory I have on this computer. That's my other computer. But either way, this is how you can actually change your working directory. So if you ever want to check your working directory, if you don't put a file path, this is where it's automatically going to save. Meaning if I were to save this image I have in front of me right now, it would save it into my documents because that's the current working directory that I have R working in. Anything I save, it will automatically go there unless I tell it otherwise. Another useful package you might want to use is Grid Extra or Patchwork to combine multiple ggplot2 plots into a single visual. So let's do exactly that. We're going to use Patchwork, and first thing, just like before, again, fresh install of RStudio and R. So what I'm going to do is I'm actually going to install the package Patchwork. Okay, so it's going to load up, and now I'm going to load this package into R. Okay, so Patchwork is now built in. So I'm going to build two different ggplots. The first one I'm going to call P1, and this is going to be a scatter plot, which is using MT_cars, X is miles per gallon, Y is horsepower. I'm going to create a second plot called P2, again, MT_cars. This one is a static of X equals miles per gallon, and this is going to be a histogram. And then I can combine these two together by doing P1 plus P2. And what's going to happen is it's going to combine these into one graph. So if I wanted to add this to like a paper or something, but I wanted to have the different graphs together, I can use this Patchwork to make one cohesive graph, where then I could just copy this one graph into the paper, and I'm not trying to have to mess with, you know, maneuvering and sizing and all that kind of stuff with my different graphs. You can also do position adjustments. These are used to adjust the position of geoms. Some common adjustments are, you might do position dodge. This will dodge overlapping objects like bars in a bar chart. You could do position jitter. This will add a small amount of random noise, which will prevent overplotting, and also will give you like thickness pretty much wherever you have a lot of data. You could use position stack. This will stack bars in a bar chart. So let's do an example. Just like before, we're going to add jitter to this. So MT_cars data, X is cylinders, Y is miles per gallon. Geom point, so it's a scatter plot. But in this case, what we're going to do is we're going to do position is equal to position jitter with a width of 0.2, meaning that it's going to add a random amount of jitter to it within this 0.2 distance. And let's see what it looks like. So you can kind of see now that it spread out the data a little bit by adding that jitter around it by our x-axis, which is cylinders, and our miles per gallon. So so we know for a fact that all of the cars are 4-cylinder, 6-cylinder, or 8-cylinder. So they should all be perfectly lined up. There's no difference to them. But what we did is we added jitter to kind of spread that data out a little bit
in order to give it a little bit more depth to our graph so it doesn't just look like 3 lines next to each other. You can also add legends to your graphs and customize them. So legends can be customized using the guides function. So the guide legend will customize the legend for discrete scales, and guide color bar will customize a color bar for continuous scales. So in this example, what we're doing is, again, we have empty cars, and we have our aesthetic of miles per gallon. Our Y is going to be horsepower. Our color is as.factor cylinder. So again, 4, 6, and 8 cylinder cars. Shape is going to be as.factor based on gear. So that means we're going to change the color of our whatever we're putting based on our cylinders. We're going to change the shape of it based on gears. We're going to do geom point, which means that it is a scatter plot. Our labels are going to be color are going to be cylinders, shape are going to be gears. And then our guides is color equals guide underscore legend, order equals 1, shape equals guide underscore legend, order equals 2. So if we were to run this graph, you will now see that we have this legend added where we added our cylinders will be different color. So we got this sort of red, green, and blue. And based on our gears, we have different shape. We have sort of a circle, a triangle, and a square. So then looking at this, you can get the combo of any one of these cars to see what their gear and cylinders are. So if I pick a random one, this one, it's a green square, which means that it is a 6-cylinder car that has 5 gears. You can zoom in on specific areas of your plot using the coord Cartesian. Just an example of this would be something like we have our scatter plot, geom point, coords Cartesian, x limit. What we're doing is we're going to say focus in for x values between 15 and 25, and for y values, y lim, we're going to do from 50 to 150. So running this graph, you'll see it's the same basic graph, but we zoomed in on a particular part of the x and y axes to zoom in on that part of the graph. You can create custom themes, like I've mentioned in this section, by using the theme function. So in this case, what I'm doing is I'm creating a theme where I'm going to add the panel.background. It's going to be element rect. It's going to be rectangle where it's going to fill with light blue. So I'm filling in the background grid with light blue. It's going to have axis line where each element is going to have a blue for the axis lines. It's going to have red for the color of the text. So if I were to run this, notice it's not going to actually do a graph because we haven't done a graph. Now what we're going to do is we're going to create a graph. So we're just going to do another scatter plot, but this time notice the theme is my underscore theme. So what's going to happen now is it's going to use the theme that I put on there. And I didn't say this was a good theme. I just did this as an example to show you. And I made it kind of drastic. So you can see that my labels or the numbers for the axes are now red. The background is blue, and there is a blue border around the graph. You can also make interactive plots. Now, I will admit this is not one that I use very often because generally when I'm making plots, they're for a research paper or a slide for a class, stuff like that. But these are really fun to play with, and they're really cool if you want to see like how things are changing, stuff like that. So what we're going to do is we're going to use the Plotly package to make our ggplots interactive. So as before, first thing we're going to do, we are going to install Plotly. So install Plotly, all lowercase. It's going to install that. And then once this is finished installing, we are going to load it using library. So library Plotly. And now what we're going to do is we're going to create a graph. This is P, it's ggplot empty cars. Aesthetic is X is miles per gallon, Y is horsepower, and we're going to create a scatter plot. So this is our regular ggplot. But what we're going to do now is we're going to do ggplotly on this, and you will see that it's going to take a little bit longer, but it's going to create this interactive graph. Notice that when I highlight things, it's going to show me the miles per gallon and the horsepower of our X and Y. And there's other things you can do with these interactive graphs. You could have ones with sliders where as you change them, the graph changes, all sorts of cool stuff like this. This one, all I did was add the interactivity of when you highlight, it will tell you what each of these dots represents, what its horsepower is and what its miles per gallon are. You also might want to look at extensions for enhanced features for special plots. Some examples of this would be GG histogram. This can be used to create enhanced histograms with a lot more functionality to it. You have GG mosaic. This will allow you to do mosaic plots. GG turn. These will be ternary diagrams. And GG force is a collection of additional geoms. There's many more.
A lot of times, which ones you're going to use are going to be based on what kind of plots you're making. It's going to be based on what kind of research or analysis you're doing. For this next slide, this one, it doesn't really serve much of any purpose other than the fact that I wanted to show how you could build out these really complex graphs by adding more and more and more stuff. I'm not going to walk through everything on this, but you can see we got ggplot, we got MT cars, we got our aesthetic, X is weight, Y is miles per gallon, color is as.factor cylinder, shape is as.factor gear, size is based on horsepower, alpha is based on quarter second time, environment, we got show legend equals true, we've got our labels for our title, we got a subtitle for it, we got a caption, we got our X value, our Y value, we got our colors, we've got our theme all set up here, and then I've got it to where it's going to print this plot. So again, this is more just to show like how you can build and build and build onto this really complex graph. I'm not saying it's a good looking graph. So if we run this, you can see what happens. Now I want to point out, I did get an error. So when I originally made this, there might have been an update where maybe they've changed it from show legend equals true to something else, like instead of show.legend, maybe it's some other way. But either way, it still allowed me to run the graph. The only thing is it did not include my legend like it did previously, but it's not a big deal. You can see how like this graph is kind of over the top. We've got sizing, we've got coloring, we've got shapes, all this stuff based on the different aspects we put in. I've got a title and a subtitle. I've got Y and X axes. Oh, I do have my my legend at the bottom here. So the legend is a little bit wrong, but that's fine. It sometimes things like when you make these slides like years ago, it updates, it changes just a little bit. But overall, the example still holds. You can just add all these layers. You can see how much went into this graph. Again, I didn't say it was a good graph. I'm just kind of showing you that you can build layer by layer. You can start with nothing but ggplot, your aesthetic, and what kind of graph it is. You can add a theme, you can add colors, you can add gradients, you can add shapes, all that kind of stuff. You can just build and build and build into the graph that you're looking to do. It adds so much customization versus the base graphing in R. One of the things that comes with all this customization though, is you're going to run into problems. Like I said, there is a bit of a learning curve when you're doing ggplot too. So let's talk about debugging and troubleshooting. If you encounter errors or unexpected results, one, check your data. Ensure there are no missing values or incorrect data types, right? Always start at the most base level issue. Is your data okay? And this is where you use the stuff we talked about previously. Look for is.na, check is.nan. Make sure that your dimensions work for whatever type of data you're doing. Make sure it's the right data type. Remember we talked about geom call versus geom bar. Then you want to check your mappings. Ensure that aesthetics are mapped correctly. Make sure you are actually mapping what you want to which part you want. If that you're still running issues, consult the documentation, right? ggplot2 documentation is comprehensive and it does provide a lot of examples. If you're still running issues, this is where I would look at going to something like Stack Overflow, right? You could go and look, add it to an AI system and it could probably fix the problem for you right away. But the problem is if you're doing that, you're not learning, right? The whole point of this is you want to learn how you can do it because this tells you what you're able to do, helps you get the graph you want, not just trying to explain it to an AI system. It works, but you don't know why it does. The last thing I want to talk about is the data pipeline interface. So I mentioned that ggplot is part of a more comprehensive package of packages called tidyverse. So historically, modeling workflows required generating endless temporary file data frames in the workspace environment. This would be things like df filter, df summarize, df final, where you're creating all these different parts of your data, and then you want to feed these all into just one single plot. Well, because ggplot2 belongs to a broader tidy ecosystem, you can seamlessly string, I've never know how to pronounce this. I call it Doppler, but it's like probably diply R. Data transformation pipes. So these pipes are a vertical line followed by the less than or greater than symbol directly into initialization of your graphics. This native piping operator automatically passes the modified data set forwards. That's what it represents. That pipe represents moving from whatever's here into the next phase. The first implicit parameter or data in your ggplot. You connect data manipulation steps using these pipes, but the second you cross the boundary into the ggplot engine, you must switch to the addition operator. So this is ggplot is part of tidyverse. You can use this to feed into ggplot, but once you're within ggplot, you do have to use those plus operators in order to add to your plot. So let's do an example to kind of show you what I'm talking about. So first things first, I don't currently have these installed, so I'm going to install them. So install.packages And then the first one we're going to do is this dplyr. Run that. Oh, actually, it looks like I do have that one installed already. Perfect. Next one, I already have ggplot2 installed, so that's good. Okay, so I'm going to load both of these up. Okay, now they're both loaded. Now when you notice I've got empty cars. I'm using the pipe operator to pipe this into, we're going to filter miles per gallon greater than 15. Then we're going to take this data, we're going to pipe it into, we're going to mutate cylinder factor as.factor for cylinders. We're going to change those cylinders into factors. Then we're going to pipe this into a geom plot. Aesthetic x equals weight, y equals miles per gallon, and color is cylinders factor. So that's going to be the thing we just did up here. Then we're going to create a scatter plot, geom point, and then we're going to use a theme of minimal. Notice though that once we put it into ggplot, we switched from pipe operators to plus. Okay, so when we run this, what's going to happen is we're going to get this graph where we basically use the pipe operator to start with our MT cars data, feed it in to a filter to filter above miles per gallon of 15. We're going to feed that into a mutate function, and then we're going to feed that into ggplot. Once it's in ggplot, then we have to use the plus to add on our different parts, like the fact that we want to use a scatter plot and the fact that we want to use a minimal theme. And this is kind of, like I said, this is the beginning, foundational, hopeful part for you, where you're going to start learning these skills, putting it together to really build out your ability to do computational statistics and data science using R. And these are the tools that people actually use. This isn't just something you learn in school and then you move on and you never think about again. This is the kind of stuff that will help you when you move on to doing actual data work. Hello everyone. In this lesson, we're going to deviate a little bit away from talking specifically about R and programming in R to talk about a concept that's kind of universal between all programming languages, and that is variable naming and clean code. So when writing code in R, it's important to use variable names that make the code easy to read and understand. Good variable names should be descriptive and meaningful and should follow a consistent naming convention. So in this lesson, what we're going to do is we're going to discuss some of the guidelines for good variable naming in R. And the reason we want to do this is because you want your code to be as readable as possible. That way you're not having to add tons of comments and things like that so people can follow along. You want your code to be able to be read directly, and any input that you're putting in the form of contents should be related to things that are outside of just what the code is actually doing. For example, a lot of times when we're teaching things in statistics, we'll use variables like x, y, and z. And that's fine for very quick explanations about what the data is doing, confidence intervals, hypothesis testing, whatever it is that we're doing. But with code, you want it to be kind of self-encapsulated so that if you were to go back to it 2 years later or share this with someone, they don't have to then go through the code and try to figure out what X was and what it represented. You just want it to be something where they could look at the variable and see, okay, I know exactly what this is. And that way, when it comes up later in the code, you don't have to constantly go back to reference what it referred to. So let's start with some general guidelines. The first is you want to use descriptive variable names. So the variable names should be descriptive and they should be meaningful. Avoid using abbreviations and acronyms that may not be understood by others who are going to read your code, or by yourself years later when you're trying to figure out what it is you did when you originally made this code. For example, you might use the variable age instead of A, or number of children with underscores instead of NOC to represent number of children. There are two cases that we generally use when we're doing these naming conventions. The first is camel case, and the second is snake case. So when naming variables in R, again, these are the two that are most oftentimes used. And anytime I'm talking about doing this in R, I mean basically with any programming language. If you're doing variable naming in Python or C, you likely will want to follow the same sort of advice. So in camel case, the first letter of each word is capitalized except the first word. So notice on the slide, the word camel case, camel is not capitalized, but case is. And this is so that way if you have longer variable names that are more descriptive, it's easy to tell where each word is. It makes it a little bit easier for the person who's looking at it to read. Now, the one that I generally am going to use is going to be snake case. So snake case is where each individual word is left lowercase, but you have an underscore between them. This helps you differentiate the words that are part of your variable name, but also make it very easy to read. Another advantage of using these underscores is it makes referring to these variables much easier later on. If I have something like number of children, and I want to refer to this in a function later on. Instead of having to write number space a space children, where it's going to see those spaces as, okay, this is something new. So you'd see number and then space would be a separate entity. What you could do is you could use quotes within R to tell it that this is all one character string, but it's easier to just have it be number underscore of underscore children. So whether you decide to use camel case or snake case, the big thing with this is to keep it consistent. A lot of times when people and students are learning how to code, they will kind of jump around between them based on whatever feels right at the moment, but you want to kind of keep it consistent. That way it just makes your code a little bit easier to read. Some other guidelines are things like you should always use lowercase. So variable names should always be in lowercase. You want to avoid using uppercase letters in variable names, as this can lead to confusion with other R functions and objects that use uppercase letters. Oftentimes, R is case sensitive, and a lot of packages will use functions that rely on capital letters. So if you use lowercase letters for most of your variable naming, it actually can make it a lot easier to tell whether something is a function name from a package or it's an object that you labeled yourself. The exception to this being if you're using camel case, like I mentioned, you would capitalize each word within it, but it does start with lowercase. And that's the reason we generally start it with a lowercase instead of capital letter. Next, you want to avoid using special characters. So variable names should not contain any special characters such as space, dash, or dots. Instead, we use an underscore to separate our words or concatenate words together. Finally, we want to avoid using reserved words. So variable names should not use reserved words in your programming language. So in R specifically, this would be things like if, else, for, while, function, and many things like this. C is another big one, and we'll talk about, I have an example about that for later on. If you need to use a reserved word in a variable name, add an underscore to it or something before or after the word to make it clear that this is a variable and not masking that specific function or action within R. So diving a little bit more into naming, there's a massive structural difference in R between syntactic reserved keywords and global baseline utility functions. So words like if, for, else, and function are hard-coded into R's parser. This means that if you were to attempt to assign some object to those specific things, for example, if, and you draw an arrow operator 5, the interpreter is going to throw an error and it's not going to assign that object that you're trying to name. Global baseline utility functions, though, things like C for concatenate, mean, df, t, or data, are not protected keywords. So R will allow you to overwrite them in your global environment without a warning, and this can lead to issues later on. This is actually what's called name masking. In fact, I updated some of the codes. You'll see some of the images that I snipped where I will have something like written as like data, and then I actually updated it in the newer code to specifically deal with this situation. For example, if you were to name an object C, you're going to mask the system's vector concatenation tool. So every subsequent array initialization script will fail with this cryptic object not found error, meaning that instead of being able to concatenate, it's going to be trying to use that object that you named C. So on this slide, you can kind of see an example. In this, we named the object if to 42. We haven't discussed if or else if statements or anything like that yet, but just know that if is one of those defined functions in R. This will result in not letting you do this, right? It'll give you an error. It'll say unexpected if in if. Another issue, though, where it will do it, even though it's going to cause problems later on, is if you tried to use C and then arrow operator, C, parentheses, 1.2, 3.5, 4.8. So this is assigning C as the vector 1.2, 3.5, 4.8. It's going to overwrite C, which in R is usually going to be used to concatenate, meaning that for now, in this case, because C is originally properly defined, it will concatenate those three numbers. But if you tried to do another value, let's say you did D, and then you concatenated some numbers, it's going to give you an error where it's going to say that you can't do this operation because it's trying to apply whatever this vector is to that vector you're trying to create. Or if we look at the example below, we try new underscore vector using our snake script, and we do C 10, 20, 30. But because we redefined what C is, now this no longer works. So now we've kind of talked about naming. Here's just a quick example of what some of the naming conventions might look like. So for the first one, for camel case, if you have my variable name, my is lowercase, then variable, the second word, is capital V, followed by name, the third word of the variable, which is capitalized. or age of person. Age is lowercase, of is capitalized, person is uppercased. For the same two variable names, if you're using snake script, it would be my underscore variable underscore name or number underscore of underscore children. So let's look at an example. If we look at the example here, we're assigning the values to variables with descriptive names, and then we're going to use them in calculations. So you see we have the variable age, and we assign the number 25. We have the variable first underscore name, which we assign the character script John. We have last underscore name, which we assign the character script Doe. And we have the variable is underscore married, and we assign the logical statement of false. Following this, we are going to create some more variables. Years of education is 12. Income is going to be years of education times 1,000. Tax rate is going to be assigned as 0.25, and taxes are going to be income times tax rate. And then from there, we're actually going to print out different statements based on this. So let's jump to it and do that. So looking at our code here, first thing, we're going to assign age, first name, last name, is married, years of education, income, which is going to calculate using years of education times 1,000, tax rate, which is going to be 0.25, and taxes, which will be income times tax rate. Then we're going to use the cat function, which is to concatenate and print, and we're going to use name. It's going to be first name, last name, so it's going to be name John Doe. Next, we'll have concatenate the character string age with the person's age, so age 25. Next, we have married, and it will take the outcome of is married. Finally, or next we have income. It'll output income, so income $12,000. And next we have taxes, and it will give the taxes based on the income and their tax rate. You can see here that in this case, this is just an example to kind of show you these variable naming conventions. Because now without putting any comments, I know what each of these variables represent. I can look at it and say first underscore name. Oh, that's obviously a first name. Last underscore name. That's their last name. Income. That's income. Tax underscore rate. That's going to be the tax rate. These are all things that make this code clearly readable without having to put any comment in order to understand what each of these variables represent. Clean code is important because it will make your code readable, understandable, and it also helps with making it maintainable. Clean code is easy to modify, debug, and to test, which makes it more efficient to work with. So what we're going to be focusing now are some guidelines for writing this clean code in R. Now, before we begin, I do want to point out that there are some conversations about clean code, because a lot of times if you're just doing quick and dirty analysis, it's not really necessary. So sometimes there is going to be the argument of speed versus something like this. If you're just writing a quick throwaway script in order to like a confidence interval, then you probably don't need to focus on this as much, because the idea is what's called throwaway code, where you're just doing it, getting your answer, and then moving on. The idea of clean code is that because it is clearly able to be read and understood, it makes it easier to expand, to reference later on, to debug, things like that. So beyond just the naming, here are some other guidelines that we want to follow. First, use descriptive function and variable names. Functions and variables should have names that are descriptive and meaningful. So for example, if I wanted to know the mean of subset 1, I might name it mean of subset 1. That way I'm not just using like sub 1 or sub mean. Make it something that if I looked at it, I would know what this function or whatever it is that I'm calculating is going to be doing. You want to again avoid using abbreviations and acronyms that may not be understood by others who read the code. Now, there are exceptions to this if there's some known thing that people use all the time. For example, in statistics, we use lowercase n to represent sample size. We use capital N to represent population size. In that case, because we're doing statistical work, it would make sense to use these variable names because they're commonly used in the field. So anyone who's doing this kind of analysis would understand that. For example, we want to use calculate underscore mean instead of calc mean, because again, this one is still probably fine because most people will be able to figure out what it means. Use number of children instead of NOC. You also want to write self-documenting code. So the code should be self-documenting, meaning that the code itself should provide clear information about what it does. You want to avoid writing comments that repeat what the code does. Instead, write comments that explain why the code is doing what it does, or to highlight important information that may not be immediately obvious from the code itself. Next, you want to use consistent formatting. So consistent formatting makes the code easier to read and understand, so you're not jumping between different coding conventions. And I'll talk more about this when we get to all these different parts. It's not just a matter of your naming. It could even be things like spacing. In fact, there's a huge debate in the programming community about using spaces versus tabs in code. For most people who are just starting out in code programming, this won't really make any difference, and you won't really understand why this is an issue, but it is. Go look up the debate between spaces versus tabs in programming, and you'll see that there are a lot of very heated discussions on this topic. Another thing is when we're creating functions, there are specific ways that we tend to write functions, and I'll talk about this later on in the course. In the end, the function will work regardless, but you want it to be something that is uniform so that every time you look, you can quickly read, assess, or debug that function. Use consistent indentation, spacing, and line breaks throughout your code. For example, 2 spaces for indentation, and then leave a blank line between functions or logical sections of your code. This again will make it be more readable. The next one is one that's a little bit more controversial, and that is to keep functions short and focused. So functions should be short and focused with clear purpose. Functions that are too long or try to do too many things at once can be difficult to understand and to debug. If a function does too much, consider breaking it down into smaller, more focused functions. Now, the reason I bring this up is because there's a lot of issues in programming with whether it's better to do a bigger function and does a bunch of things at once, or whether you do smaller, more precise functions. And this can lead to a lot of times the discussion of adding levels of abstraction. So abstraction in coding is a hotly debated topic because sometimes you need that level of abstraction away from the specific calculation, things like that you're doing. But at the same time, it's always like a balance, right? Depends on what you're doing. It depends on what your thoughts are on it. Now, a lot of times, if you are new to programming though, shorter functions are beneficial, and it's because they're easier to debug. If I have a short function that does one thing, calculate the mean, it's easy to figure out if it has a mistake, where it went wrong. Even if it's something, similar where it's a little bit longer, it's going to calculate the mean, the standard deviation, and then maybe write out the confidence interval based on that information. That's fine, right? Because it's kind of singular in focus of it's focusing on confidence interval, but it has some parts, intermediate steps in between. But if you have one that's like 3 pages of code with some complex function where it's referring back to itself and doing all this, if you run into a mistake or an error, it can be kind of hard to figure out where it's going wrong. Next, you want to use meaningful variable and function arguments. So similar to names, arguments should have meaningful names that describe its purpose. This makes it easier to understand the function or code block and to use it in other parts of a program. Later on, when we talk about functions, we will talk about creating arguments. In fact, you've already seen this when you're implementing functions. And we always do the question mark or the help operator to see what the different arguments are for it. So when I do something like rbind, I need to put n, the number of values that I'm trying to get. I need to put p, the probability of success. I need to put how many trials that I'm using for this binomial value. When you are making your own functions, you set those arguments. You set the defaults. So when you're creating those arguments, you oftentimes, much like with the naming conventions, want to make them as understandable and self-referencing as possible. And the last thing is writing reusable code. Reusable code is code that can be easily used in other parts of a program or other programs altogether. So to write reusable code, you want to use functions and modular programming techniques that allow you to separate code into logical units. Another part of this, and I kind of brought this up previously, is writing general case code. Instead of hard coding in values, use things that will reference whatever it is you're pulling in. So if I pull in data and I know that I'm going to have these 4 columns with these names, instead of going and saying column 1, column 2, column 3, column 4, I could actually reference the name, or I could reference whatever it is that I'm trying to pull. So that way, if I were to try to add this into some other program or use it later, I can literally just paste it in and it should be good to go. And this is actually how, when we make functions in R, we actually set it up to work. Because if I'm doing something like a generalized linear model, this needs to work whether I have a 10 by 100 data set or a 20 by 76 data set. So it's written in this general form that allows me to quickly reuse it regardless of what the actual data frame is that I pull in looks like. So next, let's look at an example where we're going to do just that. So in this example, we have 2 functions that are going to calculate the mean and standard deviation of a data set. We haven't talked about functions yet, but this is the general form they'll take. Function and then parentheses, and this will be where you name your arguments and if you have any defaults. So in the first one, we're using function of data. This is the data that we're putting in. And then within your curly brackets, that will actually define what the function is operating and doing. So our first function, calculate underscore mean, is a function based on whatever data we're putting in. That's the argument name. and it's going to take the mean of data. So it's going to, whatever data we put in, it's going to give us the mean. The second function, calculate underscore SD, is going to be a function also on data. And again, within curly brackets, it is going to use SD on that data. So it's going to give us our standard deviation. Following that, we're going to create some data, which I'm going to call my data, which is just going to be the concatenated vector of 1, 2, 3, 4, 5. Now, one thing I want to caution you on before we actually do this example, though, is that data, the name, is highly prominent built-in utility function within R. So it's going to work within this example, but it can cause problems later on because oftentimes we're going to refer to data. An example of this would be if I'm doing a linear model. One of the arguments in it is data equals, and this is where you put where this data is actually coming from, your data frame. Well, we've just labeled data as whatever this would be. This is actually why, for example, when I'm running this, when I'm actually assigning the specific data, I use my underscore data. And that's that way it's not replacing data. And a common issue that new programmers run into is they just will name things like data or df or data frame. And again, R will let you do this, but it can cause issues later on because these are highly referenced by other programs and packages in R. So, and some other options you might want to use are things like input underscore vector or my underscore data. So let's actually jump to our example and let's see what this looks like. So first things first, what we're going to do is we're going to run this function, calculate mean. Now you'll notice it didn't output anything because I didn't actually tell it to do anything. What I did is I created this function that I can now reference later on. So if I do calculate mean and I were to run this, it's going to tell me that it's a function of data where it's going to be the mean of data. Similarly, I'm going to create the function calculate underscore SD, which will take the standard deviation. Now I'm going to assign my data. So my underscore data was 1, 2, 3, 4, 5. Now when I do calculate underscore mean, in place of data, I'm going to put the data that I actually want it to run the function on, which is in this case, my data, or 1, 2, 3, 4, 5. So if I take the mean of 1, 2, 3, 4, 5, I get 3. If I take the standard deviation of 1, 2, 3, 4, 5, I get 1.581139. Notice though in all of this, I have names that make this code very readable. I understand that that first function is to calculate the mean because the name of it is calculate mean. I understand that the point of the second function is to calculate the standard deviation because it's calculate SD. If you wanted to be more precise, you could put calculate underscore standard underscore deviation. This would be even more understandable. But a lot of times when you're writing quick code, you're going to have this trade-off between something that is understandable, but also something that's easy to write because you don't want to have some variable name that's like 32 parts long. Sure, it works and it's going to be very descriptive, but now you have to type that out every time. Now, of course, you can use RStudio's built-in autocomplete to kind of help you with that, but just keep it kind of short, but also descriptive. But we also need to talk about lexical scoping and the global workspace. So lexical scoping rules are when a variable is invoked inside of a function, R is going to search for its definition sequentially from the inside out. That is to say, it's going to check your active local function in your environment first. If it does not find it there, then what it's going to do is it's going to go step outward to your parent environments, eventually until it hits your global workspace. And this is one reason why, and we'll talk about later, is we want to generally avoid global variables if at all possible, because you want things to kind of be localized as much as you can. So if a function utilizes an external variable from the global environment instead of an explicitly declared internal argument, it can create a hidden fragile dependency. So if a global variable's state shifts anywhere else in a long script, the function's behavior will then alter silently, bypassing isolated unit tests. Meaning that if I have some variable, a global variable that's named, and then in a function, I reference that global variable. Let's say later on, you change that variable, right? Because remember, R is mutable, but let's say you overwrite it with something else. You take more data, you add it to it, you change it. Well, next time you run that function, because it's referencing that global variable, it will automatically update to that, not whatever it is that you had in that isolated case. Meaning that when you were unit testing it, that is to say, testing your code to see if there's any errors, that it works properly, all that kind of stuff, you may actually be adding in things that you didn't take into account when you were doing those unit tests. So a lot of times when possible, we want to try to use as localized as possible variables instead of just global variables. Now, if you have something that is universal and you're going to be applying it to everything, then sure. An example of this might be if you're doing a bunch of analysis in R and you want to label what the sample size is, you could do that. Now, again, it'd be easier to use a generalized case. N is just going to be reference to the length of my data, something like that. So an example of this might be something like this. We have weight modifier, and we're going to have 2.2. Then we're going to have the function convert weights, which is going to be a function on kilogram vector, and this kg vector times weight modifier, which is going to then search locally based on whatever it is that weight modifier is. It's not going to find it, so then it is going to go to our weight modifier, which we labeled globally. But if later on, after many lines of code, we put weight modifier is 1, now you've actually changed what the output of that original function would be. And this is something you do have to be very careful with, because whenever you are using R, remember I told you that it will ask you, do you want to save this state when you close it? If you hit yes, when you start R back up, it is going to have those variables and objects already labeled and in your memory that you were using last time. And this can actually cause a lot of issues. I've had this happen to me before, where I'm writing up some new script, I don't clear out my variables, and I start doing stuff, and it starts referencing variables that I labeled in a completely different script because I had used global variable names. Next, let's talk about the DRY principle. So DRY stands for don't repeat yourself. So every piece of logical or mathematical knowledge must have a single unambiguous representation within your code base. So in statistical workflows, what this means is that analysts will routinely copy and paste calculations, things like min, max normalization, or log scales. And they'll use this across multiple data frames and columns. But when you're copying and pasting fragments, inevitably this is going to lead to structural replication bugs, aka you're going to make a mistake and you're going to cause problems but not notice it because you're working so fast using pasting. So this could be things such as transforming feature 3 but accidentally leaving it referencing feature 2 embedded inside of your calculation. Another part of don't repeat yourself is that anything that you can turn into a single or small function, or something that you can reference the actual data itself using generalized form, this would be better. So don't hard code end 25, use length of my data, and that way, anytime you don't have to constantly repeat yourself with what n is. You don't have to update it. You can just use it as is. So in this example, you can see a case where someone copied and pasted. They had df money sign x1 underscore scaled. So, you know, okay naming convention. And then they assigned it df money sign x1 minus minimum of df money sign x1 divided by max df x1 minus minimum df x1. They took this, they copied it, they pasted it, updated it to x2. They pasted it again, updated to x3. But then in all of this, they make a mistake on the last line and they forget to update the last one. So they have minimum df money sign x2 instead of x3. Well, this can be hard to see because this will give you an answer, but it's not going to be the correct answer because while copying and pasting it, you made a mistake. We all do this. Again, if you're doing quick and dirty code, I do this all the time. If I just have some some analysis I need to do and I'm going to do it 10 times, a lot of times it's easier than writing a function which iterates and all this other stuff. It's easier to just go copy, paste a bunch, change the variable name, but then you have to be very sure that you didn't make a mistake. And if you have enough of them, inevitably you will. So with the idea with don't repeat yourself is if you were going to have something that you were constantly repeating, you want to put it in a form where it's not going to lead to you having to do this over and over and over again. So an example of this might be you create this function min underscore max underscore scale, and it is going to be a function on some feature, and the function itself is going to be feature minus min of feature divided by max of feature minus min of feature. In this case, now all you have to do is when you update feature, whatever that feature is, it can automatically run this operation on it. You update feature again, it can run this operation on it. You update this feature again, it can run this operation on it. You didn't have to retype it every time you have some new feature. Now, what about clean code versus production? So code is not good simply because it computes the correct numerical result. It must be maintainable, auditable, and clear to another statistician. I will caveat this by saying when you are trying to do something that you are oftentimes giving to others. A lot of times, if you're just doing some quick code for yourself and doing basic analysis, if it runs, that's going to be good enough. In fact, a lot of STEM programs, that's exactly what we do. We are trying to get some analysis. We're using this throwaway code, meaning we're never touching this code again. We're going to run our analysis. We're going to get our output. We're going to put it into a paper or into something else. And then that code is going to go in the scrap pile and you're never going to touch it. The problem with this, though, is that this is where a lot of times you can run into mistakes, and also checking that you can audit the actual code. This has actually led to, in academia, a sort of newer movement where two things. One, before any sort of project is done, we actually will explain what statistical analysis and steps we're taking beforehand. This is to help limit people trying to game the system by when it doesn't work or doesn't get the results you want. They change it and then they say, this is what we were looking for. No, we've already said that we're going to do this kind of test and this is what we expect. And if we get the results, great, we publish them. If we don't, then we look at why didn't it work instead of saying, but if I had done this instead, it actually would have worked. No. But the other reason is because when you are doing these research papers, things like that, oftentimes people are going to ask to see your data. They're going to ask to see your methodology because there's going to be things that you might have messed up without even thinking about it. So what we do is we write this code in a clean, auditable way. We post it somewhere like Figshare, and then that way people can actually go and analyze our code. So that way, if we make a mistake, it's not we were trying to manipulate some journal to get this paper. It could just be something as, oh, we found a mistake here. If we correct it, does this still apply? Do we need to retract it, or can we update it? Can we fix it? An example of this would be something like, and we'll talk about this later on when we're talking about confidence intervals. When we teach confidence intervals in Introduction to Stats, we use what is called the Wald method, where we take the null hypothesis values for our proportions. But if we're doing a confidence interval on R, it's actually going to use a Wilson method with continuity correction, meaning that your confidence interval values for proportion will be different than if most students calculated it by hand. Doesn't mean that it's wrong, it just means that it would be different. And these are the kind of things you might not think of. You jump into R, you tell it to give you a confidence interval, it gives you an answer. You put that as part of your published results. But now by seeing your code, I can actually dive in and say, okay, they use this is the Wilson method, but when they explained it incorrectly. They were talking about the Wald method. Easy fix, no big deal. It's not that the analysis is wrong, but it allows us to audit it to determine if there might be a mistake, which could lead to a bad interpretation of the results. So this is why a lot of times when we're doing this kind of code, we want it to be clean, readable, and auditable, because it helps us kind of go back and check all the code and everything like that. Code that is functional but structurally brittle, poorly spaced, unreadable, these could be problems for this sort of thing, right? This could be something where your code does work, but if there's certain changes that are made, it could cause the code to break down, or it could just make it where someone who's trying to check your code is going to have a really hard time interpreting what it is it's doing and where you might have gone wrong. For example, cryptic single letter variables and condensed unspaced lines can save negligent keystrokes, but they can introduce significant lag during tracking, debugging, and review cycles, right? Because remember, R isn't space-based. I could put 100 spaces in my line of code and it will still run. The only thing that spaces do is they separate different parts of my code. But 1 or 1,000, it doesn't mean anything to R. Some programming languages it does. But if I have these sort of lazy steps that I take, it can cause a lot of issues as I'm trying to go back and read and understand my code and fix it. Just as sort of an example here, if we look at my first function, I have m, and notice that there's no spaces in this. So m is a function of d, where the function is sum of d divided by length of d. This will 100% work, but it's not very readable. There's not good spacing, there's not good indentation, different lines, anything like that. We have s, which is a function of d, where it's the square root of the sum of d minus md squared divided by the length of d minus 1. Third line, you've got v1, which is concatenated values of 1, 2, 3, 4, 5, and another line of code, which is residual 1 is going to be m v1, residual 2 is going to be s v1, and we're going to concatenate those together of res1 and res2. All of this code will work based on whatever it is that we're trying to input, but it's not readable. Now, looking below this is the same code, but in a readable format. So the first one, we have calculate underscore mean. Okay, that's a better function name. This is going to be a function of x, which is going to take the sum of our x divided by length of x. Then we've got calculate underscore SD. This is going to be a function of x, and then we're going to start our function, sample variance, blah, 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 blah. But notice in this case, when we do our function, oftentimes this is one of the formats that we'll use. This is what I generally am going to use, which is going to be you write your function, and then you put the open curly bracket. You then put a space. This is where you now put your function, and then the end curly bracket ends on its own line. It makes the function clearly defined so I can easily go through your code and I can find where you have functions. This first line of code, there's a good chance if I'm scrolling through quickly, I wouldn't even notice you put functions here. I would just think this is some operation you did. So in conclusion, good variable naming is an important aspect of writing clean and understandable code in R. And by following these guidelines, you can make your code more understandable and more maintainable. So writing clean code in R is going to be essential for making code readable, understandable, and maintainable. And again, auditable. So by following these guidelines, you can then make your code more efficient for you to work with and easier to modify, debug, and test. So my final thoughts on this are, if you were just doing a quick and dirty analysis for yourself, I know a lot of times we tend to not pay attention to any of this. And that's perfectly fine. But if you're going to be sharing your code with others, if you're going to be displaying it, if you're going to be posting it online for others to review or anything like that, I would highly recommend you kind of follow some of these guidelines, if not all of them, in order to maximize the ability to actually use your code. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.